friends, welcome back to our channel. So in today's session, we'll discuss about the introduction to operating systems. So usually this operating system we call as OS. So OS stands for operating system, right? So the definition of an operating system is OS is an interface between user and computer, right? So I'll explain about this individual word, that is interface, right? So we are saying that operating system will act as an interface between the user and a computer. So what is this interface? This interface is also, for better understanding, I'm writing this one. So interface can be treated as a mediator. So mediator, that means which is used for communication between the user and a computer. Okay, so and also the operating system is a software which manages the hardware. Right? So our computer will be having the hardware, right? So hardware means, so we'll get the memory, IO devices, okay, and etc. Everything will be comes under this hardware, right? So CPU, main thing, we have forgotten about this main thing. CPU, that means a processor, and etc. So everything we call it as an hardware, right? So in order to communicate with all these things, we require one software which is called this operating system. Best example, so consider a computer. So here we are having some sort of keys. So we are having some keys, right? So there will be some, okay, so if you press these keys, the key will be printed on the screen. If you press A, for example, we'll be having all the keys here. So for understanding, I'm writing only A, B and C, okay? So if you press A, the A will be displayed here, and immediately if you press B, a B will be displayed, and if you press C, the C will be displayed here, and etc. Right? So whatever the input we are giving from the keyboard, immediately the same thing will be appeared on the monitor itself. Right? So this happens with the help of a software called operating system. So that's why we are saying the operating system is a software which manages the hardware. Right? So here we are interacting with the computer, right? We are interacting with the system with the help of some sort of hardware, right? So here we are using some input devices. So input device like a keyboard or a mouse, right? And we are getting the output in the output device. So there must be one interface between these things. So what we are giving the instructions and what the system understands, everything will be done with the help of this operating system, right? So let me give you a diagram for this one for better understanding. And also the operating system is a system software. It's a system software. So we have seen in the previous sessions about the categories of softwares, that is a system software and application software. So system software means which manages the hardware is called the system software. Okay, the software which manages the hardware is called the system software. And another one is the application software. So which we call it as an application software. So here the example is operating system and also some sort of software drivers. So for every hardware there will be some sort of software. So unless you install the software, the hardware will not be get work, right? So some operating system will get these drivers inbuilt, okay, with the operating system. That's different, right? So every hardware will be having the drivers, and to work the hardware properly, we have to install the drivers, and these drivers are also known as the system software. And application software, these are the softwares which are meant for a specific task or functionality, some specific application. For example, some media player. So this software is used to play the media, that means either audio or a video, okay? And text editor. So this is a software which is used for writing the text, okay? So like Word, Excel, so all these are nothing but application software. So these are meant for a particular task. Okay, system software which manages the software, which manages the hardware is called the system software. We are having two types, that is the operating systems and the drivers. So without operating systems, we can't interact with the system. Okay, so we can interact, but we have to pass each and every instruction. So it would be very difficult for the user to interact with the computer without operating system. So to make the user easily accessible, this operating system will help. Okay, now let us have the structure of this operating system. So the importance of operating system. So the lower is hardware, So this is the hardware, and here we are having the operating system, because this operating system will manage the hardware, right? And this operating system, again, we are having applications, okay, and here we'll be having the users. Here we'll be having the users. Right? So user 1, user 2, user 3, and so on, user n. So number of users can be applied. So these users will use the applications, and these applications will be implemented or executed by the hardware with the help of operating system. Okay, so these are the applications, and in order to run the applications, we require the operating system. Right? So without the operating system, we can't run these applications. Example, let us take the C program. Let us take the C program. So the first step, we'll write the instructions, and we'll save the file with a .c. So that is a source code. So we'll prepare the source code for a C program. And the second step, we'll do the compilation process, or we'll save the file. Okay, we'll save the file. Save the file. Okay, and where it will be stored? It will be stored in hard disk. Hard disk. That means secondary memory. Secondary memory. So hard disk means secondary memory. And again, after that, we'll use the compilation process. Compile the program. Again, that will be in hard disk itself. And whenever you are using the run or execute. So after successful compilation, we'll execute the program in order to get the output. So once you run the program or execute the program, what happens? So the object file will be given to this particular hardware, right? The object file generated by the compilation process will be given to the hardware. Hardware here is nothing but CPU. So all the applications will be executed by the processor itself. So our system is having some processor. So that processor will execute the object code, and this CPU will access only the main memory. Main memory. So it will not execute the applications from the hard disk. It will execute the applications or processes from the main memory itself. So during the running or execution, the object file generated from the compilation process will be stored into the main memory, and it will be available for executing by the processor. And all this process will be done by the operating system. Right? So hope you understood. So once the compilation process is done, we'll get the object file. And see, remember, every process will be executed by the processor itself. Every process. So here, so we are saying that execution of a program is also a process. Right? Execution of program is also a process. And see, the CPU will access everything from the main memory. But the files are in secondary memory. So now, during the execution, the object file which is generated from the compilation will be stored into the main memory. That means it will locate, or it will load the object file to the main memory, because the CPU will execute the processes from only the main memory. So this process will be done by the operating system. So that's why operating system is an interface between the user and the hardware. If you want to execute any programs, so that programs will be done in the applications, and that will be executed by the CPU with respect to the operating system, with the help of operating system. Right? So whatever the programs we are writing, those programs or processes, whatever the process we want to execute. So if you want to, listen to a music, so everything will be loaded into the main memory, and it will be executed by the processor, and this process will be done with the help of operating system. Right? So that is the importance of operating system. So I think the point is very clear. So what exactly this interface? Interface is called as a mediator. It will act as a mediator, right? So in between the user and a computer. So user and the computer means the CPU or hardware. Input devices, output devices, whatever it may be, everything comes under the hardware. So in order to communicate the user with the hardware, there should be one application, there should be one system software called the operating system. Right? So in our further sessions, we'll go in deep about this operating system. So what are the functions, what are the services provided by these operating systems, and we'll see one by one in our further sessions. So hope you understood this basic introduction about the operating system, the definition and the importance of operating system. Services of operating system. So here these services are categorized into two types. One is user services. Another one is system services. But all these services are provided by the operating system. So coming to the first one, user services, the first one is program execution. Program execution. So coming to this program execution, so a program is executed from the main memory, and this program will be saved in the secondary memory. So our CPU, so every process or every program will be executed by the CPU, right, processor. So before executing that by the CPU, that particular program should be loaded into the main memory from the secondary memory. So this will be done by the operating system. So a program should be loaded to main memory for execution. So this process will be done by the operating system, right? So there's one service provided by the operating system. So all the program or all the processes will be executed by the operating system. That means by the processor with the help of this operating system. And the second service is user interface. So in order to communicate with the computer is somewhat difficult because the user have to communicate with the computer with the help of instructions. For everything, you have to use some instructions. And by using this interface, it makes the user very easy to communicate with the computer, right? So here the computer means the hardware. That means either processor or a memory or IO devices, etc., etc. So the user can use this interface to easily communicate with the system. And this interface is of two types. One is command line interface, CLI. It's a command line interface. So here, everything will be in terms of text-based commands, right? So the user have to give the text-based commands in order to do the process. And there is one more thing, that is a GUI. GUI stands for a graphical user interface. And this graphical user interface, interface will be used by the user. That means we are having some widgets, okay, folders, and some sort of visibility, right? So visibility will be more, and this makes a user very easy to communicate with the computer, right? So example, we can go with the DOS operating system, which is a command line. So for everything, even if you want to create a file, if you want to create a folder, we have to use these text-based commands in this particular operating system. And graphical user interface, we can go with the Windows, okay, Linux, so Mac, all these things comes under this graphical user interface, right? So we can create a folders, or we can work on the folders or files with a simple mouse moves and by using the widgets, folders, etc., etc. So this is one best feature provided by the operating system, right? So with this user interface, it makes the user very easy to interact with the computer, right? Next, so I'm discussing about this user services, then we'll go with the system services. So two, and the third one, IO operations. So coming to this third service, so we know the IO devices, input devices and output devices. So the user will use the input devices to give the input from to give the input to the system, and the system will give the output by using the output devices. For every IO device, there will be a controller, right? So for example, if you are using some keyboard to give the input, right, it is having some keyboard controller through which we can communicate, right? So next, if you are using some memory, there will be some memory controller. And if you are using any video, so we'll be having, so if you are displaying the output on the monitor, example, right? This is the best example. So we'll be having some video controller. Like this, for all the IO devices, we'll be having a different controllers, and through this through these device controller, we will commonly call them as a device controllers. Okay, device controller. So by using these device controllers, so the operations will be communicated, and all these controllers will be maintained by the operating system. Okay, so these IO operations will be executed smoothly with the help of these controllers, which are maintained by the operating system. So this is one service given by the operating system. And the next one, communication. So here the communication means, so in our system there will be a lot of processors executing, right? So if one process wants to communicate with another process which may reside in the same system or another system, so if we call it and the another system, we call it as a network, right? If two systems are in a network, so there should be some sort of communication, right? There's some sort of communication should be done between the processes, and that process will be maintained by this communication. And this is also a service provided by the operating system, and this we call it as IPC, is inter-process communication. So in order to communicate between different processes which are maintained in the same system or in different systems, so this will be used. I mean, the operating system will take care about this communication, right, between different processes. Then the next one, file system and manipulations. So coming to the file system, so we are going to write some data onto the files. We can read the data from the files, and we can store the files in the memory. So everything will be done, right? The data can be stored in a files, right? And data can be retrieved from files, and we can search the files. We can search the files, and we can delete the files, and also we can create the files. We can create the files. So file will be having the data, right? So the file will be having the data, and we are going to search the file. We can store the data into files, we can retrieve the data from the files, and we can search the files, we can delete the files, we can create the files. So everything will be done with the help of this file system and manipulations, which is the service provided by the operating system. So we can do these processes in this service, and this is a service provided by the operating system. So without operating system, it would be very difficult to search the files, or we can manipulate the files, or we can create the files, right? And the next one, error detection. Error detection. So while executing the program, some sort of errors may occur. So errors may occur in program or in hardware, right? So the operating system should know about all the errors that may occur, right? So the service provided by the operating system is these errors which are occurred from the program or the hardware should be reported to the users. So errors, so whatever the errors we are getting, those errors will be reported to users, so that the users can take a certain operation to debug those errors, right? So sometimes the OS itself debugs the errors. So if the errors occurs, so OS itself debugs the errors. Otherwise, the errors will be reported to the user, so that user can take appropriate action to resolve those errors. So this will be maintained by the operating system, and by using this one, the system can work consistently without any errors. Okay, the errors can be occurred from either program or any hardware. It seems like from the memory point of view, or some IO point of view, etc. So whatever it may be, everything should be known by the operating system. So all the errors that may occur must be known by the operating system, right? And those errors should be reported, or some sort of errors can be debugged itself. The operating system will take care about that one, right? So these are all called as a user services, right? And then coming to the system services. So there are a few services. System services. So the first one is resource allocation. So that means if a program or a process is being executed, so it may require a lot of resources. So similarly, our operating system can, more than one process can be executed at a time, and multiple resources should be allocated to different processes. And sometimes different process may require the same resource. Okay, all these ways, so the resource can be allocated to each and every process without any overlapping, right? So that process will be done by the operating system. So we can have a different processes, process 1, process 2. So if both are using the same resource, so without much waiting time, this resource will be allocated to process 1 as well as process 2 with a less waiting time. Because if the process 1 is using this resource, this process 2 has to wait until this resource is released by the process 1. So if there is another process, process 3, and if it is also using the same resource, so then this process 3 has to wait until the resource being released by process 1 and process 2. So this resource allocation with a less minimum, that means a minimum waiting time, the resource will be allocated by this operating system. And similarly, different processes can access different resources. So optimal utilization of resources can be done by the operating system. Okay, so this one is one service, and the next one is accounting. So accounting means operating system will provide different accounts for different users. Okay, so multiple users can have different accounts, so that each and every user will be having different operations, right? So all the log of particular user can be maintained by the administrator. So what actually is being done by individual users will be maintained by the user administrator, right? So different accounts can be created for multiple users. So every log, okay, the log of user means whatever the operations being done by the user will be maintained in a log, and all these logs will be keep on monitoring by the administrator, right? So this is one service provided by the operating system. And the next one is security and protection. It's also very important, security and protection. So we need to provide the security for the data. Okay, we need to provide the protection and security for the data. So in the previous service, that is accounting, we are providing, the operating system is providing different accounts for different users, so that one user can't access the data of another user. Okay, so we can prevent from unauthorized access to data and files. And also we'll use some firewalls okay, for the security purpose, okay, we'll use some firewalls and we'll use some unauthorized access, okay, we'll have the we'll protect the data from unauthorized access to the data and files, because accounts will be having permissions, okay, accounts will be having some permissions. So based upon the permissions, only the users can access the data who have the permissions, right? So without the permission, the data cannot be accessed by the unauthorized persons. So by this, the protection and security will be achieved, and this is also one service provided by the operating system. So all these are the different services provided by the operating system. So at a time I write all things and we'll close. So the first one, user interface, program execution, communication, file system and manipulations, IO operations, input output operations, error detection, resource allocation, accounting, protection and security. So all these are the services provided by the operating system, and all these comes under the user services, and last three comes under system services, right? So hope you understood about these services of operating system, right? So we'll see one by one. There are different types of operating systems. The first one is batch operating system. Batch operating system. So here the user will not be directly interacting with the computer, right? So the user will give a jobs, job 2 and job 3, and these will be placed in a punch card, okay? This will be placed in a punch card, okay? And these punch cards will be given to the operator. So this operator will collect these punch cards from different users, okay? So there will be user 1 and also user 2. So again, job 1, job 2, job 3, etc., etc. So again, this is one more punch card. So these punch cards will be collected by the operator, and this operator will make batches related to the particular jobs. So based upon the similarities, okay, based on similarities, this operator will create a batches, right? Batch 1. So batch 1 will be having different jobs with a related similarities. Similarly, batch 2, okay, it will be having a different jobs with a related similarities. So this is how the programs will be executed in this particular batch operating system. So user will not be communicated to the system directly. So the user will create the jobs and it will be placed in a punch cards, and these punch cards will be given to the operator. So operator will collect the different punch cards from different users, and based upon the similarities, the operator will group the jobs and we call them as a batches, and at a time one batch will be given to the CPU, right? And here the drawback is, until the batch 1 completes, this batch 2 will have to wait, okay, until the CPU completes the batch 1, okay, the batch 2 jobs should be in a waiting position. So even though, so here the main drawback is CPU utilization. So there will be, the CPU may be in an idle state, okay, CPU may be in an idle state. If any process is requiring the IO operations, then the CPU have to wait until it completes the IO operation, and after that only the CPU can execute the processes. So until the batch 1 completes, the batch 2, and again batch 2 completes, then only batch 3. So there might be a chance of idleness of a CPU, right? So this is about our batch operating system. So coming to the second one, in order to reduce the CPU idle time, okay, in order to reduce the CPU idle time, the second one is multi-programmed operating system. So here the name itself indicates multiple programs will be given at a time to a CPU. So if it is a CPU, then multiple programs, so job 1, job 2, job 3, right? So multiple processes will be given to the CPU, so CPU first executes the job 1, and if this job 1 requires any IO, immediately the CPU will start executing this job 2. So if the job 2 is also requires some IO operations, immediately the CPU will start executing the job 3. And still the job 3 requires any IO operations, immediately again CPU will be start resuming the job 1. So that means there will be no idle stage for the CPU. CPU will not be in an idle stage. So CPU will be switching between the processes based upon the IO operations. right? So CPU doesn't go to the idle position. So here you can see multiple programs are executing at a time by the CPU. So that's why we call it as a multi-programmed operating system. Multi-programmed operating system, right? Next, the next category is multi-processing operating system. Multi-processing operating system. So coming to this multi-processing operating system, so a memory will be there, and there will be a different processors. There will be a different processors accessing the memory. So at a time, multiple processes. Okay, job 1, job 2. Similarly, job 1, job 2. So here the multiple processors will be connected to the same computer. Multiple processors using the multiple processors. Okay, so here we are having two processors and the jobs are divided between two processors. Okay, so here the CPU will execute the job 1, job 2, and CPU will execute the job 1, job 2, but both the processors are connected to the same system. So connected to the same computer. So automatically, so the jobs will be shared, right? So easily and fast we can execute the jobs. So one more thing, if any one of the processor fails, automatically the jobs will be executed by the another processor. So this is the main advantage of using this multi-processing. So the name itself indicates multi-processing means multiple processors will be connecting to the same computer and the programs will be get executed, right? This is the next one. We'll move on to the next one. Next type of operating system, distributed operating system. Distributed operating system. So also we can call it as a network operating system. So there will be a lot of computers connected. Okay. So here the jobs will be distributed by the different processors. The jobs will be distributed to the different processors. So at a time we can execute the multiple processes. Okay, multiple processes. And see, if any one fails, automatically the remaining process will be executed. Okay, there will be no much impact on that. So the processors, the jobs will be distributed. The processes will be distributed, right, throughout the network. So there should be some connection between all the networks, and the jobs will be shared between all the systems of a network. So this type of operating system we call it as a distributed operating system. And the next one is multitasking. Multitasking operating system. So it is nothing but logical extension of multi-programmed operating system. So here also multiple tasks will be given to the same CPU. Okay, multiple tasks will be given to the same CPU, so it will be executing the multiple tasks. So here also there will be no CPU idle state. Okay, so that's why we call it as a logical extension of multi-programmed operating system. Right. Next, time sharing operating system. Time sharing operating system. So in this time sharing operating system, so the name itself indicates some time will be given for each and every process. Okay, so for example, CPU need to execute 3 processes, some P1, P2, and some P3. So it will allocate some time to this one. So let it be the P1 should execute, it requires some 5 milliseconds to execute, and it is 4 milliseconds to execute. It is some 3 milliseconds to execute. So CPU allocates some 3 milliseconds for each process. Okay, 3 milliseconds for each process. Right, equal distribution. So after 3 milliseconds, automatically the CPU will be given to the P2. So here the remaining is 2 milliseconds. Okay, and here whenever the P2 comes into the processor, it will execute 3 milliseconds and only 1 millisecond is required. And again, after 3 milliseconds, again the CPU will be given to the P3, the process. Okay, the CPU will be given to the P3 to be get executed. So P3 will be executed three times, so it will complete. And once again, it will come to the process 1 and it will execute this one. And again, after completion of P1, it moves to the P2. Right? So like this, some sort of time will be given for each process to get executed, right? So here there is a difference between the multi-programmed and the time sharing. So in the multi-program, the system will be divided. That means the system will be allocated to the processor based upon the IO operations. If P1 gets the IO operations, requires IO operations, so instead of maintaining the CPU idle, it will move to the P2. But here, after every given time, the CPU will be given to the next processors. Okay, so this is the time sharing operating system. And the next one is a real-time operating system. Real-time operating system. So in this real-time operating system, so we'll be having some time limit, and within the time limit only the process should be executed. Okay, so the process should be executed within the time limit. Process should be executed within the time limit. So if it exceeds, automatically we'll get some error. Okay, so this is a special type of operating system which gives a time limit for each process to be get executed. So usually it will be used for embedded systems. Okay, embedded systems. And here there are two types of real-time operating systems. One is hard real-time operating system, and soft real-time operating system. So here there is a slight difference between hard and soft. So in both the cases, the system will give some time limit, and within the time limit we have to complete the process. So if the time limit exceeds in this hard real time, automatically it leads to the failure, system failure or critical failures. Okay, critical failures, or a device or a system, whatever it may be, a critical failure leads to a critical failure. So when the process exceeds the time limit, okay, the execution of process exceeds the time limit, automatically it leads to the critical failure. So that's called a hard real time operating system. So within the perfect time limit, the process should be get executed. And coming to the soft real time, so it may accept a few delay. So if the process execution exceeds the time limit, so nothing happens here. Okay, that type of thing we call it as a soft real time operating systems, right? So these are all the different types of operating systems. So I'll write one by one, I will list out and I will wind up. So the first operating system is batch operating system. The next one, multi-programmed operating system, multi-processing operating system, distributed operating system, multitasking operating system, time sharing, real-time operating system, right? So these are the different types of operating system. So functions of operating system. So the first function, so first I'll list out all the functions and then we'll elaborate each and one, right? So the first one, memory management, processor management, device management, file management, security, job accounting, error detection, and coordination between other softwares and users. So these are the main functions provided by the operating system. So we'll see the first one, a memory management. We know that our memory is divided into two categories, that is a main memory and secondary memory. So actually, so whatever the files we are saving in our computer will be stored in this secondary memory. Now files or program, okay, simply we can say it is a program, files or process, whatever it may be. And if you want to execute this program, so which will execute the program? So obviously the CPU or a processor will execute this program. So before executing that, this program should be loaded into the main memory. Right? So then only this program will be get executed. So if you are loading the program into the main memory, some sort of memory should be allocated for this particular program or a process. So here, program or process or file, whatever it may be, right? So some sort of memory should be allocated. Should be allocated, right? So operating system will maintain this memory log. Okay, so OS maintains a memory log. So memory log means it keeps on tracking about this memory. That means which memory is available, and which memory is used. So this is very important, because so whenever the operating system wants to allocate a memory for a process or a program, first it have to know which memory is available, which memory is already allocated. So the operating system will allocate the memory whenever the program is loaded into the main memory for the execution. And whenever it requires any IO operations, or whenever the process execution is completed, or the memory will be deallocated by the operating system itself. So allocation of memory and the deallocation of memory will be done by the operating system, right? So hope you understood. So the programs or processes should be executed by loading it into the main memory. So some sort of memory should be allocated for that particular process, and that particular thing will be maintained by the operating system. Then that process we call it as memory management. So this will be done by the operating system. This is one functionality done by the operating system. So allocation of memory to the program to be get executed. Then next one, processor management. Processor management. So here the processor management means we will be having a lot of processors available in the queue to be get executed. So operating system will decide, so OS will decide which process should be executed first, and how much time it requires. So this will be done by this process, and this process we call it as a process scheduling. That means which process should be get executed, right? So execution of the process will be done by the CPU. So the process should be given to the CPU. So the OS will give the access of CPU to the process. Okay, allocates the processor to the process. So allocates processor to the process. So this sort of allocation. So after completion of the process, that means whether it can be terminated or it may be waiting for the IO operations, then it will be deallocating the processor. Because so whenever it works with the IO devices, automatically instead of making the CPU in idle, so CPU will be allocated to the other process. So that we have seen in the multi-programmed operating system. So that we call it as a multi-programmed, right? So whenever the process requires for the IO devices, so automatically the CPU, instead of keeping the CPU idle state, the CPU will be allocated to the other process, right? So the allocation of processor to the process will be done by the operating system. Also, the deallocation will also be done by the operating system. So the deallocation means it may be the processor completes its execution, or it may waiting for the IO operations. So anything, in any case, the deallocation of processor will also be done by the operating system. And this process we call it as a process scheduling. Right? So hope you understood this one. Processor management. So allocation of a processor to a process. Next one, device management. So during the execution of a program, so it may require some IO operations. So in that time, so all the devices, so OS maintains the status of all the devices connected to the system. So whenever the process wants the IO operations, so this particular operating system will allocate the device to the operating system. And also it will keep track on how long it requires the device, how long it maintains the device, right? So everything, that means allocation of device to the processor will be done by the operating system. So device to the process, okay, not the processor, device to the process. And also whenever after completion of the IO operations, automatically the deallocation of the device will also be done by the operating system itself. So whenever during the program execution, whenever it requires the IO operations, automatically the operating system will allocate the device. So it should maintain the status of all the devices connected to the system and how long the device is using by the process. Everything related to the device. So we can simply call it as a device log. Device log will also be maintained by the operating system in order to allocate and deallocate the devices to the process whenever it is required. Right? So this is called the device management. And the next one, file management. Coming to the file management, so actually the programs will be stored in directories. And inside the directories we can have files and directories also, right? Directories. So we need to keep track on each and every file. So OS will track all the file status, right? It will know about the information where the information is stored. Information is being stored. So this will be done by the operating system itself. So where the information is being stored, right? So the file system, the data is, the information will be stored in directories or files and where it was located, right? So whenever it is required, we can access the data from that particular file. So that complete log will be maintained by the file management, and that process we call it the file management. It is maintained by the operating system. It will be done by the operating system. And next one is the security. So OS provides the security. OS provides the passwords for different users so that the data can be protected from the unauthorized access, right? And also it maintains a log. Okay, it maintains a log of all the users, right? So by using these passwords and the security will be provided for the data. And coming to the job accounting, and OS will maintain a log for all the users. So here the log means it will keep track, it will track the time and resources, the time and resources used by the users. How much time and how many resources are being used by the users. So this log will be maintained by the operating system, and that is the job accounting, right? So we'll be having a more number of users. By giving a login, it will maintain a more number of users, so that the data which was created by one user cannot be accessed by another. So for that, it will keep tracks the time and resources used by the users. So how much time they are using the resources, and everything related to the user will be maintained in this job accounting. And the next one is error detection. Error detection. So this error detection means the OS keep on monitoring the errors occurred in OS or in hardware or anything, okay, in the system. Simply we can write it as system. That can be in the program, the errors may be occurred in the program, or in the hardware like IO devices, or as a processor, so memory, whatever it may be. So all the errors will be keep on monitoring. I mean, the operating system will be keep on monitoring the errors occurred in the system, so that whenever it is required, the debugging process will also be done by the OS, right, in order to avoid the malfunctioning of a computer, okay, to avoid the malfunctioning. So sometimes it will debug, and sometimes it will be sending the report of these errors to the user, so that the users can take a certain action towards that particular error and to rectify the errors. So that will be done by the operating system, and it is called the error detection. Error detection. And the last one, the coordination between the other softwares and the users. So the system will be used with by the different users and different softwares. So the OS will provide the OS provides all the language translators. Language translators. So we know that language translators. So these language translators are the compilers, interpreters, assemblers. So all these will come under the language translator. So it will provide all the language translators to the users and the softwares in order to function the program smoothly, right? It provides everything to the users, right? So these are all the functionalities of, the functions of operating system. So one is the memory management, processor management, device management, file management, security, job accounting, error detection, and the coordination between the softwares and the users, right? So hope you understood this one, and in our further concepts we will be discussing about all these things in detail. So there are a lot of questions arise in our mind, that is, what exactly is a kernel, and is kernel software or hardware, and is kernel and operating system both are same, and what are the functions of kernel? So like this, we are having a lot of questions in our mind. So this video will give the answer for all these questions, right? So let's start. Now, what is a kernel? So this kernel is a part of operating system. A part of operating system, right? So this is an operating system. And in this, there is one more layer that is called kernel. So the kernel is lowest layer of operating system, and also this kernel will act as interface between hardware and processes of a computer. So we can simply say the software applications, right? So whatever the applications we are executing in our computer, so the kernel will act as the interface between the hardware and the applications of a computer, right? See, let us assume this is an applications. All these are the applications, and this will be the kernel, and this is a hardware and the devices. So we'll be having a lot of devices connected to our computer. So the kernel will act as an interface between the application, software applications, and the hardware. So this is a hardware, right? And here the kernel loads first in memory after OS has been loaded, and remains in memory until operating system is shut down. So we know that. So once you switch on the system, the operating system will be loaded, and immediately the kernel will load first in the memory, and it will reside in the memory itself until the system gets shut down. So what are the functions provided by this kernel? What this kernel actually do? So the functions of a kernel are device management, allocating the devices, memory management, task management. So these are all the different functions provided by the kernel itself, right? So we have discussed about all these things in the previous sessions. What is the device management, what is the memory management, and what is the task management? Everything we have discussed in the previous sessions, right? So these are the functions provided by the kernel itself. And here the memory is divided into two types. One is a user space, and another one is a protected kernel space. Protected kernel space. So in the user space, all the applications will be get executed. So in the protected kernel space, so all these services will be done. That means the device management, okay, processor management or task management or memory management. So all things will be done in here itself. So these are not visible to the user. And here the name itself indicates the protected kernel space. So no other application can access this space. Okay, no other application can access this space because this is a protected kernel space, and kernel is a part of. And one more question: is a kernel is a hardware or a software? So kernel is a system software. It's a part of an operating system, right? So these are the functions provided by the kernel. So hope you understood the concept of kernel, a simple thing, and I think we got an answer for all the questions. The first one, so is a kernel software or hardware? It's a system software and a part of operating system. And if the both are equal, kernel and operating system are equal? No, exactly no. So kernel is the lowest layer included in the operating system, which gives the services for all other parts of an operating system. Okay, and this kernel provides services to all other parts of operating system. All other parts of operating system. So both are not equal. So both are different. So we'll see what is the system call and what are the need of this system call and how this system call works in operating system. Right. The first point, this system call will act as an interface between software applications or processes, okay, applications and kernel. So in the previous session we have discussed about the kernel. So kernel is an interface between applications and the operating system, but here the system call is an interface between the applications and the kernel. So if you observe, so these are the user applications. And this is the kernel, and this is the hardware, right? So this kernel will be acting as an interface between applications as well as the hardware. Right? Now this system call acts as an interface between applications and a kernel. Applications and a kernel, right? And this system call provides the services of operating system to the process via API. API means application process interface. So whatever the resources the process requires, that will be provided by this system call, right? So see, whenever the process is executed, when the process is being executed, and if it requires any resource, okay, so whenever the process is being executed, sometimes it may require some resources. So whenever it requires any resource, then the process will create a system call okay, a system call which is nothing but interrupt, right, and sends to the kernel, So here, whenever it requires any resource, then the process will create a system call, and by execution of this system call, the kernel will give the resource to the process. And in the previous session, we have already discussed about the memory, different types of memory, right? So the memory is divided into two categories. So one is user space, and another one is kernel space, right? So all the system calls will be get executed in the kernel space itself, and the system calls will be created in the user space, because the process execution will be in user space. The process execution will be in the user space. Whenever it requires any resource, immediately a system call will be generated, and immediately this system call will be sent to the kernel space, and here it executes the system call, and the system call will be executed in the kernel space itself, okay, and immediately after that, again the control will move back to so after completion of execution, automatically the control will move back to the user space, and automatically the execution of system call will be being executed, right? So whenever the process is being executed in a user space, whenever it requires any resource, immediately it will, so the resource will be provided by the kernel, right? The resource will be provided by the kernel. So it will create a system call or an interrupt. So we can also call it as an interrupt. So it will create a system call, and through system call it will enter into the kernel space, and here a system call table will be maintained. So in this table, it stores all the system calls which are generated by from the user space, which are entered into the kernel space through the user space, right? So here we are getting all the system calls here, and based on priority, each system call will be get executed, and immediately the control will go back to the user space. So this is the working of system call, right? So whenever the process is executed in the user space, if it requires any resource, immediately the system call will be generated, and through that it will enter into the kernel space, and in the kernel space a system call table will be maintained, and in the system call table the address of each and every system call will be maintained, and based upon the priority, one by one the system call will be retrieved from this table, and that system call will be executed, and the resource required will be given to the process, and the control will get back to the user space. So this is the working of any system call, right? So one point, that is, system calls are the only entry points to kernel space. So these are the only entry points. That means in the previous sessions we have discussed about the kernel and kernel services, right? So in that we have discussed about this one, the two modes. One is a user space, another one is a kernel space, and we call this kernel space as a protected kernel space, so that no other application will get access into this kernel space. So that's why only the system calls are the entry points to the kernel space. So no other application can enter into the kernel space, right? So these are the system calls. A system call is an interface between the application and the kernel. So kernel will provide the services, that means the resources. So that resources must be requested by the user space, that is called the system call. So user will give a request for accessing the resources. That request we call it as a system call. So in the previous session we have discussed about these system calls. What is the system calls, and how the system call works, right? So first let us recall the previous concept, that is a system call. A system call will act as an interface between the software applications and the kernel. So if any program is being executed, and if it requires any resource, so immediately it will interrupt. That means in the form of system call, it will interact with the kernel, so that the kernel will provide whatever the resource it requires from the operating system to the application programs. So this is a system call. So there are different types of system calls. So in this session we will discuss about different types of system calls. So first I will list out the categories. The first one is process control system calls. So these system calls are responsible for process management. Process management means for creating a process, terminating, right? So creating the process or terminating the process, everything will be having the system calls of process control. And the next one, file management. And these system calls are responsible for file manipulations. file manipulations. So we will be working on different files because the files will be having the data. So we'll be working on the files. So file creation, reading, writing, etc. So all these are the responsible system calls of file management. And the next one, device management. So these system calls are responsible for device manipulations. So like writing the data to the buffers, reading the data from the buffers, the input and output buffers, right? So for all these things, these system calls will be used. Device management. So first one, process control. Regarding the process management, file management system calls, these are responsible for all the file manipulations, and device management system calls are responsible for device manipulations. So if our program wants to write the data into a buffers or read the data from the buffers, then we'll use the system calls of this device management. And the next one, information maintenance. And this is responsible for all the information which is being passed from operating system to the software, right? So information being shared between processes or operating system, whatever it may be. So whatever the information we are exchanging, that information details will be maintained by that will be done with the help of the system calls of information maintenance system calls. And the next one, communication. And this is responsible for IPC. IPC means inter-process communication. So in order to communicate between different processes or establishing the connections between the processes from one system to another system, so whatever it may be, so the communication will be depending upon these system calls, will be achieved with the help of these system calls, communication system calls. So these are the 5 categories of system calls. So first one is a process control system calls, a file management system calls, device management system calls, information maintenance system calls, and a communication system calls. So different operating systems will be having different system calls. So I will show you the example of all these things by comparing with the Windows and the Linux. So I will write the system calls first. So process control, and then file management, device management, information maintenance, communication. So these are the 5 different system calls. So now we'll see the how the system call will be, and example for let us consider the Windows. In Windows, how the system calls will be represented, and in Linux, how the system calls will be represented, right? Windows and Linux. So coming to the process control, we have seen this is responsible for process creation. So here the system calls are create process. Here the system calls are similar to our methods or functions. So create process, exit process. Okay, and in Linux we'll be using this as a fork for creation. Okay, and wait, exit. So all these are the different different system calls used in Linux, and these are the system calls used in Windows operating system regarding this process control. Coming to the file management, so read file, write file. So in order to apply the read operations and write operations, we'll use a read file and write file for Windows, and simply we can use a read, write, open. So all these are the different system calls available in Linux. Coming to the device, this is a buffers, right? So read console, write console. These are the few system calls of device management, and here again we'll use a simply read, write. And the information maintenance, so this means the information is being exchanged between different processes, right? So get current process ID, So in order to get the current process ID, right? For every process there will be ID, right? So in the previous session we have seen all the system calls will be maintained in the system table. Similarly, the processes will also be having a different IDs, individual IDs. Okay, they will be maintained, and with the help of priority, based upon the priority, the process will be executed. So get current process ID, sleep. So these are the system calls of information maintenance. And here simply there is called a get PID, sleep, okay, and alarm. So these are the few system calls regarding this information maintenance. Okay, and coming to the communication, this is mainly used for communication purpose, establishing the connection and exchanging the information. So establishing the connection, it's a create pipe, is a one system call regarding this communication, and here we'll call it as a pipe, simply a pipe. So these are the very few system calls regarding all these things. Okay, regarding the process control, file management, device management, information maintenance, and communication. So these are the system calls represented in Windows as well as in Linux. Right. So we'll see a few system calls, what's the importance and how they were implemented. Right. So we'll see the fork, wait, exit. Okay. So let us see the very few system calls. So there will be a lot of system calls. Okay. See, coming to the fork. So this fork system call is used to create a process. If you want to create a process, then we need to use this fork system call. And so whatever the process it was created, that will be called as a child process. Child process. Okay. So if you want to create a process, the process from which it was created is called a parent process, and the created process is called the child process. Now here the parent process will be suspended until a child process completes its execution. Until the child process completes its execution. So whenever the child process is created, immediately the parent process will be get suspended, and it will wait until the child process completes its execution. So after executing child process, then control goes to its parent process. Right? So this fork system call is used to create a process. So once a process was created, that is called a child process. Okay. So whenever the child process is created, the parent process will be get suspended automatically until the child process completes its execution. And after completion of executing the child process, then immediately the control will go back to the parent process. And the next one is wait. So this is a related. So wait means, so immediately so just now we have seen, whenever the child process is created, the parent process will get suspended, and this process will be done with the help of wait system call, and the parent process will be suspended using this wait system call. So if the wait system call is executed, automatically the parent process will be suspended, right, until the child process completes its execution. And the next one, exit. So the name itself indicates exit means the process termination. Exit. So it was used by program to terminate the execution. In order to terminate the execution, this exit system call will be used. So whenever this exit system call is implemented, automatically the program or a process will be terminated from the execution. And similarly, there is one more system call which is called a kill. So it seems both are equal, but there is a difference between the kill and exit. So this was used by operating system to send termination signal to the process. So if the process, if the operating system wants to terminate the signal of a process, immediately the operating system will call this kill system call. Okay, there's a slight difference between exit and kill. So exit is used by a program and kill is used by operating system. So this program to terminate the execution, and this is used by operating system to send a termination signal to the process. Right? So these are very few system calls used in our operating system. Right? So hope you got an idea about the system calls and the different types of system calls. So process control system call, file management, device management, information maintenance, and communication system calls. Right? If any program is being executed in the user mode, if it wants any resources, immediately it will create an interrupt. Here the interrupt is also called as a system call. Right? The interrupt will be in the means of system call. So immediately an interrupt will be generated, that means a system call will be generated, and it will be sent to the kernel space. So the system call will be get executed in the protected kernel space. No other application will be accessing the kernel space. Okay, so this is the only way to enter into the kernel mode. So that is a system call. So once the system call is executed in the kernel mode, immediately it will get back to the user mode. Okay, so in the kernel mode, it will maintain some table of system calls, and based upon the priority, the system calls will be get executed. So the system calls are different types, so that we have seen in this session. So these system programs are somewhat different from application programs. So coming to the application program or application software, so this provides services for the user. Right? So these are the softwares which provides the services for the user. And the one more thing is system software. System software or system program, it provides services for another software. The best example for this system software is an operating system, because operating system will provide different services for different softwares. Right? So this is a slight difference between the application software and the system software. Now the system program provides the environment. It provides environment to develop and execute the program. So it provides an environment where we can develop and execute the programs. And this particular system program will lies in between the user interface and the system calls. So the users can't access the system calls, can't interact with the system calls directly. So with the help of these system programs, the user can interact with the system calls. So that's why this system program lies in between the user interface and the system calls. See, this is a user, and then it's a user interface. So in order to interact with the operating system or anything, the system needs an interface, right? So from here, so this will be the kernel. Inside the kernel, we are having the system calls. All these things we have discussed in the previous sessions, right? So in between the user interface and the kernel, the system programs will be appear. So this will be lies in between the user interface and system calls. And not only the system programs, also the application programs. So system programs as well as application programs. Anything can be there. Application programs. So it lies in between the interface and the system calls. And if you want to interact with the system calls, it will be done with the help of only the system programs. Right? Now, these system programs are classified into different types. So we'll see all those different types. What are the different types of system programs? Types of system programs. The first one, status information. So these type of programs will provide the information regarding the status. So example, regarding the system date, time, and also available memory. So how much memory is available? Available memory. And how many users have been logged into the system. So all the information, complete status information will be done here. So users logged in. All these informations will be given by these system programs. So that is a status information. And the second one is a communication. So here a virtual communication will be done among all the processors and the users. So virtual connections will be provided among processors and users, so that once the connection was established, the user can interact with another user. So simply we can say it as a remote logins. Remote login is an example, or email. So one user can send an email to another user. Similarly, web browsers. So web browser is also one category, so which builds the connection between the user and the network, right? So through the web browser, we are going to use the internet connectivity, right? We can interact with the other systems with in another network, right? So this is another category of our system program. Next, file management. So we know that whatever the data we are giving, everything will be stored in terms of files, and the multiple files will be stored in the directories. So the complete manipulations of files will be done here. Manipulations on files. So that means creating a file, deleting a file, locating and searching. So everything will be done by these softwares, file management softwares, right? So all the file manipulations will be done here. And coming to the fourth one, related to the files, that is a file modification. File modification. So a file modification means, the name itself indicates, the data on files will be modified, get modified. So the data can be modified, and this will be done with the help of a few text editors and the commands. So some editors will be there, and similarly commands, some special commands will be there in order to change the data, modify the data. So this comes under the file modification. These are the two other related, file management and the file modification. And the next one, program loaded and execution. Program loading and execution. So we all know that. So if one program is written, that program will be executed by the processor, and first the program should be loaded into the main memory. So that complete process will be done here. So program will be loaded into main memory. So all the execution will be done in the main memory itself. The processor will get the program from the main memory to execute. So the program will be loaded into the main memory, and the program will be executed. So all these things comes under this category. So program will be loaded into the main memory. So example, the linkers and loaders. So which will take care about all these things. So loading the program into the main memory, linking all the header files and object files to combine a single object file. So everything will be done, and these are the examples for this program loading and executing, linkers and loaders. And the next one, programming language support. So we know that we are having a more number of programming languages. So if you want to execute any program, so compulsory this should be done, and this will be achieved with the help of we know the translators like compiler, interpreter, assembler, debugger. So with the help of all these things, any programming language, any program can be executed by using this one. That means it provides additional features to the programming languages. Additional features will be provided. So that can be done with the help of these language translators, compiler, interpreter, assembler, debugger, etc., etc. Right? And the last one, the last category, just now we have discussed about that one, that is application programs. So this is somewhat different from our system software. So which provides the services for users. Right? So for example, if you want to write a document, we need some word processor. So the word processor is an example for this application program. Word processor or spreadsheets, right? Any video players, audio players, everything will comes under the application programs, because by using all those things, they provide the services for the users itself. So that will be the application programs, right? So these are the different types of system programs used in our operating system. So I will list out them and we'll close. The first category which we have seen is status information, and the second category, communication, and the third category, file management or manipulation, whatever it may be, no problem. Next, a file modification. The next one, program loading and execution. Programming language support. And the last one, application programs. So these are all the different types of system programs available in our operating system. Process state diagram. First of all, what is meant by a process? A process is defined as the program under execution. So whatever the program we are executing, that we call it as a process. So the process, the creation of process, from the creation of the process and the termination of the process will change its states. That means the process is executed in different states. So there are different states. One is new state. So if the process is about to create it, then that process will be in this new state. Process about to create. Then it is called a new state. So after this new state, that means after the process is created and then it's ready for execution. If the process is ready for execution, we call it as ready state. Then immediately the process will be moved to the ready state. So if the process is ready for execution, and right, so at a time in the ready state, a number of process can be residing. Right, depends upon the memory. Number of process can be in this ready state. That means more than one process can be in this ready state. So from this ready state, whenever the CPU is free, each process will be allocated to the CPU. So that we call it as running state. Running state. That means allocating the process to the CPU for execution. Right. So this is allocating process to CPU. That is a processor for execution. So after allocating the process to the CPU, so the CPU will execute the complete its execution, and once the execution of the process is completed, then that process will be in termination state, terminated. That means if the process execution is completed, then the process will be in terminated states. So after completion of process execution, right? These are the 4 states, major states. So without any interruption, if the process wants to be created and if the process wants to be executed successfully, minimum number of states required is 4. New state, if the process is about to be created, and after creation of the process should be moved to the ready state, and from that ready state, the process will be allocated to the CPU, and then after completion of the process will be in terminated state. Right? So here the execution will be done in 2 ways. One is preemption and non-preemption. That means if here from the ready to running state, if the process wants to move from ready to running state, so here in the running state we are allocating the process to CPU. Right? So if it is a preemption, if there are any high priority process is available in the ready state, automatically the executing process, the process which is going execution, will be interrupted and the high priority process will be allocated to the CPU. That is for preemption. So if there is a high priority process, then the already executing process will be interrupted. If there is high priority process. And in the non-preemption, it doesn't worry about the higher priority process. Once the process is allocated to the CPU, it will be executed only after executing the particular process. Next, only the second process will be allocated to the CPU. Whereas in the preemption, depends upon the priority of the process. If there is a high priority process available in the ready state, automatically the current process which is allocated to the CPU will be interrupted, and this high priority process will be allocated to the CPU. So switching of the process will be done. So that will be done. It is called preemption. And if one process is executed, if one process is in the running state, until it completes its execution, no other process will be entered into the running state. That is called non-preemption. No interruption. So no interruption. So here we can write interruption. If it is high priority process, the process with high priority, right? This is a non-preemption. And similarly, if the process is going to be executed, it requires 2 terms. So for every process, it requires 2 terms. One is CPU time, and another one is IO time. For every process, there will be CPU time and IO time. So what is the CPU time? So how much time it requires for the CPU to execute this process? That means this will be done by the CPU. All the CPU operations, the computations will be done by the CPU. That is called a CPU time. And IO time. IO time means if the process needs some IO request or IO operations, and so that is called IO time, and this is done by the IO devices. CPU time and IO time, right? So if the process is in IO time, the CPU will be in ID. If the process is in CPU time, the IO devices will be in ID. So if the process is in IO time, that means if the process requires some IO operations to be executed, then automatically there is one more state called block state or await state, and another process will be allocated to the CPU. That means one more process from the ready to run will be done. So the current process which requires these IO operations will be moved to the block state. if IO operations. If it requires some IO operations. These IO operations will be done by the IO devices, right? Okay, so these are the different states: new, ready, running, terminated, and a blocking bit. And this process execution will be done in preemption and non-preemption. That means from ready to running, it may be preemption and non-preemption. If it is interruption with interruption, that means based upon the priority of the process, automatically the current process will be suspended, and the new process with high priority will be allocated to the CPU. And if in the non-preemption, no interruption will be there. So until the completion of the current process, no other process will enter into the running state. Right? Now let us see the diagram so that you can clearly understand. See. First one, new state. That means the process is about to be created. So after creation of the process, then that process will be moved on to the ready state. The process will be in a ready state. From the ready state, if the process is ready to execute, this process will be moved on to the running state. That means in the running state, the CPU will be, the processor will be allocated to the particular process. So this is done. So in this ready state, number of processes can be decided. So it can allow more than one process in this ready state. So among those many processes, the scheduler will schedule each process to the CPU. So this is CPU. So here the scheduler will schedule each process to the CPU. This is also called as dispatcher. We can call anything dispatcher. And after successful completion of the process, it will be moving on to the terminated. So after completion of execution, it will be in the terminated state, right? So this is the process done without any interruption. That means non-preemption. And if there is a preemption, right? So as we have discussed earlier, the preemption means interruption. So the priority, based upon the priority of the process, the current process will be suspended, and the higher priority process will be assigned to the CPU. So if it is preemption, interruption will be there. When it will be? If we are getting the high priority process, that means a process with high priority, automatically the current process will be again moved to the ready state. And if the process requires IO operations, again the process will be moved to the wait state. See, IO request, right? If it requires some IO operations to be performed, those IO operations will be performed by the IO devices. So until that process completes, so that process will be moved to the wait state. And from after completion of these IO operations, again the process will be moved from wait state to ready state. So IO completion. Hope you understood this, right? So then here, this is the secondary memory. Right? The process creation, everything will be in secondary memory. And after completion of the process creation, the process will be moved to the ready state, which is in main memory. And this is also the main memory. And this is also the main memory. Right? If this main memory is full with the current process, and again the new process is coming to the wait state, some processes will be suspended, move to this state, suspended state, wait suspended state. So if this memory is full with the processes which are going on this IO request, that is IO operations, some of the processes will be moved to the wait suspended state. So again this is a secondary memory. So after completion of, after availability of main memory, again these processes will be moved on to this wait state, that is again main memory. This is called, this is suspended, this is resume. Some process, if the memory is full, some process will be moved to the wait suspended, and whenever the memory is available, again from the suspended state, the process will be moved on to the wait state. Similarly here also. Here, as we said, that ready is a state which can hold more than one process, right? So here also, if the main memory is full, automatically some process will be sent to the suspended, ready suspended. This is again secondary memory.
And after completion, after completion means here after availability of the main memory in the ready state, if the main memory is available, again this suspended will be resumed back to ready state. In some cases, from this wait suspended to ready suspended, the process will be moved from wait suspended to ready suspended. So once again, I am saying here it is a secondary memory. So moving this process from new state to ready state, that means the process moves from secondary memory to main memory. And here the main memory, ready state, there will be number of processes. Based upon the scheduling algorithms, there are different algorithms. So based upon the scheduling algorithms or dispatcher, we will pick up one process and it will be allocated to the CPU. And if there is any interruption, that means a preemption, if the algorithm is a preemption, that means we have to give the highest priority to some processes. So in such case, the process already in a running state will be again moved to the ready state. And it will be again waiting for the CPU. Right? So if the running process requires some IO operations to be performed, then it will be moved to the wait state. And after completion of the IO operations, again waits from the wait state, the process will be moved to the ready state and again waiting for the CPU. So here, this is the main memory. Wait state is a main memory. So if here this main memory is full, so there is no space to accept the process. So some of the process will be moved to the wait suspended state, which is in the secondary memory. And whenever the wait state, the main memory is available, this from the wait suspended, the process will be resumed to the wait state. Similarly, the ready state. Right? So this process, that means moving from secondary memory to main memory, this process we call it as long-term scheduler. That means this long-term scheduler work is to send this process from new state to ready state, from secondary state to it loads the process to the main memory. And from the main memory, we have to allocate the CPU to the processes. That work will be done by the short-term scheduler. Short-term scheduler, right? So this process from the ready state to running state, right? Again, with the high priority, again it will be ready state. So this scheduling the process, that means allocating the process to the CPU, that will be done by the short-term scheduler. And coming to this wait suspended and ready suspended. So some process will be in wait suspended, and after the main memory available, again this suspended, the process which is in wait suspended will be again moved to the wait. So this work will be done by the midterm scheduler. Right? So hope you understood this simple thing. There are three schedulers here. One is long-term scheduler, short-term scheduler, and the midterm scheduler. And the process can be executed in a preemption or non-preemption. And each process may require CPU time or IO time. So CPU time means the processor working, working by the processor, executing by the processor. And the IO time means the processor, if the process requires some IO operations. So that will be done by the IO devices. So these are the simple thing of process state diagram. So scheduling criteria, the first criteria is CPU utilization. So the name itself indicates CPU utilization. CPU is a processor, right? So every process will be executed by this CPU. So we have to allocate this CPU to each process to get execution. So CPU utilization means how long the CPU is being busy. So CPU is busy means some process are running by the CPU, right? So how long CPU is busy. So busy means some process is going on execution. The second criteria is throughput. Throughput. So as I said that number of processes will be in ready state, and at a time each process will be given to the CPU. So this throughput means the number of processes executed in unit time. In particular time period, the number of processes being executed by the CPU. That is called a throughput. Next, turnaround time. Turnaround time. So this turnaround time means, so how much time the process takes to complete its execution, right? So the completion of time minus the start time. So the difference of beginning of the process and ending of the process. So how much time it takes for execution. Time taken for execution. That means difference of end time minus arrival time or beginning time, right? Next, waiting time. So how much time the process waits for getting the CPU. So even the process is in ready state, so there will be, if one process is going on execution by the CPU, then the second process should wait until the executing process completes its execution, right? So how much time the process waits for allocation of this CPU. time waited by the process to get the CPU. Next, response time. See here, response time means after starting, that means after beginning of execution, the time taken to get the first response by the CPU, that is called the response time. After beginning of execution, time to get first response is called response time. So these are the different scheduling criteria. Scheduling criteria, right? CPU utilization, throughput, turnaround time, waiting time, and the response time. So for every process, we can calculate all these things. So except the CPU utilization, right? So the CPU utilization means how long the CPU is busy. Throughput means the number of processes executed in given time period at a unit time. Turnaround time is time taken for execution. That means the difference of completion time and arrival time. And the waiting time. Waiting time means time waited by the processor to get the CPU. Right? So response time, after beginning of execution, time to get the first response by the CPU. This is called the response time. So all these are the different scheduling criteria. So this will be taken care by the short-term scheduler. Right? So short-term scheduler main task is, so by using the scheduling algorithms, process will be moved from ready to running state. That means process will be allocated to the CPU or CPU is allocated to the process. So as we have discussed earlier, there is a ready state, so which contains a number of processes, and at a time only one process can be allocated to the CPU. So this selection of the process is done by the scheduler. Right? And this selection will be done by using some scheduling algorithms. So based upon these scheduling algorithms, we have to select one among those different there are different scheduling algorithms. So based upon the scheduling algorithm, the scheduler will schedule the process to the CPU. That means allocates this process to the processor for its execution. Right? Now let us see the scheduling algorithms one by one. So in today's class, let us see the one scheduling algorithm that is called the first scheduling algorithm, FCFS. That means first come, first serve. First come, first serve. So the name itself indicates whatever the process first arrived in the ready state, that process will be allocated to the CPU. So until that process is executed, no other process will be moved from the ready state to running state. So all the remaining process should be in a wait until the process gets executed. Right? Now, so there are two different modes while performing this scheduling. That is two modes. One is non-preemptive, another one is preemptive. So here non-preemptive means no interruption. So there will be no interruption to the execution until it completes its execution. Preemptive, there will be interruption. So if any high priority, if any process with a high priority is available, then automatically the process which is going to be executed in the CPU will be get back, and the high priority process will be sent to the CPU. So that will be done in preemptive mode. Right? So we can select any one in this non-preemptive or preemptive. Either if it is a non-preemptive, it's a no interruption. There will be no interruption. That means if one process is going to be executed by the CPU, then all the remaining process should be wait until it completes its execution by the CPU. So once it gets completed, then only the second process will be allocated to the CPU. Now, let us see the FCFS, the first come first serve. First come first serve. So here we are using the mode, say non-preemptive, right? And criteria is arrival time. So based upon the arrival time, we will schedule the process. So that's what we are saying. Which process gets first enter into the ready state, that process will be allocated to the CPU. That is called arrival time. Right? Right. Let us take an example so that your doubt will be clarified. Right? So if there are four processes, so four processes with the four IDs P1, P2, P3, and P4, and the arrival time is 0, 1, 2, 3. So 0, 1, 2, 3 is the arrival time. Let us take it as a relative time. Okay, it's not an absolute time, it's a relative time. So 0 means this process has been entered into ready state. 1 means next, this process has been entered into ready state. Let us take it as a milliseconds or seconds or hours, whatever it may be, right? So it's a time, arrival time. Next, burst time. So this is the arrival time. this is the burst time. So what is a burst time? Burst time means the time required to complete its execution. So process P1 has entered at 0 milliseconds into the ready state, and it requires 5 milliseconds to complete its execution. Next, P2 arrives at 1 millisecond, and it requires 3 milliseconds to complete its execution. Right? So generally in the problems, so we are supposed to find average waiting time and average turnaround time. Right? So these two questions will be frequently asked. That is, so they will give a processes, arrival time and the burst time, and we are supposed to calculate this average waiting time and average turnaround time. So before going to calculate this one, first we have to calculate this waiting time and the turnaround time. Right? See, for this, let us draw the Gantt chart. This is called Gantt chart. Gantt chart is the execution of the process step by step. See, I will show you. So always the process starts from the 0th milliseconds. So 0, at the time 0, process 1 enters into the ready state. So process 1 will be executed. P1 will be executed. So how much time it requires to complete its execution? 5 milliseconds. So until 5, P1 will be get executed. Now see, the time is 5 milliseconds. At the time of 5, all the remaining 3 processes are available. Right? So at the time 0, only one process is available in ready state. So automatically this process is allocated to the CPU, and CPU executes this process. So it takes 5 milliseconds to complete its execution. Right? So after executing this process, it requires 5 milliseconds. So now the time is 5 milliseconds. At the time of 5, there are 3 processes waiting for the CPU in the ready queue. Right? So P2 arrival time is 1, P3 arrival time is 2, and P4 arrival time is 3. So after completion of P1, 3 processes are available. So which process we have to consider? So based upon the arrival time, that means first come first serve. Which comes first into the ready queue, that process should be allocated to the CPU. So among these, arrival time is 1. So P2 comes after P1, right? So P2 will be given to the CPU, and it takes 3 milliseconds to complete its execution. So P2 starts from 5 and it requires 3, so it completes at 8 milliseconds. Now 2 more processes are there. So P3, so arrival time, we have to go for arrival time. So arrival time for P3 is 2, arrival time for P4 is 3. So P3 enters into the ready queue before P4, right? So P3 should be allocated to the CPU. So P3, right? So it enters in 8 milliseconds, it requires some 8 milliseconds. So at 16 milliseconds, P3 gets completed. Now P4. So P4 enters into the queue. So it requires 22 milliseconds to complete the P4. Hope you understood. So this is the queue. This is the CPU, allocation of the CPU. So first P1, arrival time 0. So at the 0, P1 enter into the ready queue. So P1 is allocated to the CPU, and CPU executes till 5 milliseconds. And the time of 5, there are 3 processes available in ready queue. So among these 3, we have to select only one. That is based upon the first come first serve. P2, among these 3, P2 comes first into the ready queue according to the arrival time. So P2 is allocated to the CPU. It takes 3 milliseconds. So 5 plus 3, 8. So again, next P3 is given to the CPU after completion of P2, and it takes 8 milliseconds. So 16, complete 16. And P4 is allocated to the CPU. It takes a total 6 milliseconds. Right? So one thing we can observe. So if you add all these burst time, that is equal to the total time required to complete all the processes, right? So this is 22, 5, 3, 8, 8 plus 8, 16, 16 plus 6, 22. Now let us write the completion time. So completion time for each process. So when the P1 is completed, so here P1 starting time is 0, completed at 5. So P1 completed at 5. P2, what about P2? Arrived at 1, but waited for some time. It arrived at 5 and completed at 8. So completion time of P2 is 8. Completion of P3, 16. Completion of P4, 22. This is the completion time. Now, turnaround time. What is the turnaround time for all the processes? See, turnaround time, as I have said in the previous one, in the scheduling criteria, turnaround time is the difference between end time and start time. So, completion time minus arrival time. Completion time minus arrival time. So, I will write above. Turnaround time. It's a completion time minus arrival time. So, end time minus starting time. So 5 minus 0, turnaround time is 5, 8 minus 1, it is 7, 16 minus 2, it's a 14, 22 minus 3, it's a 19. So turnaround time for each process is 5, 7, 14 and 19. Next, waiting time. So how much time it is waited? Waiting time. So waiting time means whenever the so how much time the process waits for to get the CPU, right? So how much time the process is waiting to get the CPU. So it arrived at 0, right? So it arrives at coming to this process P1, it arrived at 0, and the CPU is allocated at 0. So automatically, see, simply we can say turnaround time minus burst time. Minus burst time. Or I will explain you. So arrived at 0, CPU allocated at 0. So it is 0. So according to the formula, turnaround time minus burst time, 5 minus 5, 0. Second process, coming to the second process. It arrived at 1 and allocated to the CPU at 5, right? P2 is allocated at 5, it arrived at 1. So 5 minus 1. So that means 4. 4 milliseconds the P2 has waited. So according to the formula, 7 minus 3, it's 4. Next, P3. Arrived at 2 and CPU is allocated at 8. So 8 minus 2, 6. So here 14 minus 8, 6. Next, P4. Arrived at 3 and here CPU is allocated at 16. So 16 minus 3, 30. So hope you understood. So P1 is arrived at 0. Here the CPU is allocated at 0. So automatically there is no waiting time. Next, P2 is arrived at 1 and CPU is allocated at 5. So 5 minus 1, 4. P3 is arrived at 2 and allocated at 8. 8 minus 2, 6. P4 is arrived at 3, allocated at 16. 16 minus 3, so 13. Right? Hope you understood this simple thing. So for getting this average turnaround time, average all these things, so total turnaround time is 5 plus 7, 12, 12 plus 14, 26, 26 plus 19 is 45. Divided by, okay. So average turnaround time is equal to total turnaround time divided by number of processes. That is 4. 11.2 something. Right? Next, coming to the waiting time. So total waiting time. 0 plus 4. 0 plus 4, 4, 4 plus 6, 10, 10 plus 13, 23. Similarly, average waiting time is equal to total waiting time divided by number of processes. So 5.7 milliseconds around. So hope you understood this is a simple example how to calculate or how to schedule the process by using first come first serve. So this is the mode where we have calculated is non-preemptive, and one more thing, this is based upon the arrival time, right? So mode non-preemptive and arrival time, based upon the arrival time, will send one process at a time to the CPU. So there will be no interruption at all. So until the process gets executed by the CPU, the next process should be in a ready state itself. Right. So let us take one more example. So here also there are 4 processes, P1, P2, P3, P4, and arrival time 1, 2, 3, 4, and the burst time, that is the time to be executed for this process, 10, 5, 7, and 6. Now let us see for this example. Again, we have to prepare the Gantt chart, right? Gantt chart, the CPU allocation. So as I have said, the CPU starts always from 0. So the first process arrived at 1 milliseconds. So from 0 to 1, the CPU will be in idle state. Right? So the CPU will be idle state from 0 to 1. So at the time of 1, P1 will be allocated to the CPU. So it takes 10 milliseconds to complete its execution. So it takes some 10 milliseconds. So 1 plus 10, it will be 11. Right? So next, so after completion of P2 and P1, P2 is arrived at 2. So at the time of 11, all these 3 processes are available in the ready queue. So based upon the arrival time, P2 is first. So P2 will be executed next. So what's the time of P2? 5. So 11 plus 5, it takes 16. That means the completion time of P2 is 16. So next P3 will be get executed. So it requires 7. So 23. And P4, it requires 6. It requires 29. Right? So from 0 to 1, the CPU will be in idle state. CPU will be in idle state because the process enter into the ready queue from 1 millisecond itself. Right? So here now the completion time. What's the completion time? The completion of P1 is 11. Completion of P2 is 16. The completion of P3 is 23. The completion of P4 is 29. Right? Next, turnaround time. The completion time minus arrival time. So 11 minus 1 is 10. 16 minus 2 is 14. 23 minus 3 is 20. 29 minus 4 is 25. So this is the turnaround time and the waiting time. So coming to the waiting time, it arrived at 1. The CPU is allocated at 1. So obviously it will be 0. So turnaround time minus burst time. Arrived at 2. Here started at 11. Right? 11 minus 2, it's 9. So 14 minus 5, it's 9. Next, arrived at 3 and started at 16. 16 minus 3 is 13. So 20 minus 7 is 13. Next, P4, arrived at 4 started at 23. So CPU is allocated at 23. 23 minus 4 is 19. Right? So this is a simple thing. Now find out the total turnaround time. So total turnaround time is 10 plus 14, 24, 44 and 69. 24, 44 and 69, right? Average total time, so that is 69 by 4. Similarly, total waiting time, 0 plus 9, 9, 9 plus 13, 22, 22 plus 19, it's a 41. Similarly, average waiting time is 41 by 4. Right? This is one more example for first come first serve. So here, it's not a mandatory that every process is arrived at 0 milliseconds, right? So based upon the arrival time, we have to prepare the Gantt chart. So for that purpose, I have given this example. Now let us take one more example with a different case, right? So I am explaining with the different cases so that you can solve any type of problem regarding this FCFS, first come first serve scheduling algorithm, right? So now let us see the third case. Again, consider the four processes P1, P2, P3 and P4. So arrival time is 0, 3, 5 and 7. Now the completion time is, the execution time for each process required by each process is 2, 1, 2, 3. Now prepare the Gantt chart. See, again here the P1 starts from 0. So automatically at the 0 milliseconds P1 is executed, right? So it takes 2 milliseconds. So till 2 it get executed. And the second process is arrived at 3. Now CPU is still in waiting state. So CPU is waiting for process, right? So here process is not waiting for CPU, CPU is waiting for the process. Now from the 2 to 3, the CPU will be in idle state. CPU is in idle state. At the time 3, P2 arrived. So P2 is given to the CPU. So it requires only 1 millisecond. So at the time of 4, it completes its execution. P3 again arrived at 5. So from 4 to 5, again the CPU is in idle state. So in this example, the CPU is waiting for processes. So in the previous 2 examples, the processors are waiting for CPU. Right? Next, so from 4 to 5, the CPU is in idle. At the time of 5, P3 arrived. So P3 will be executed. So it takes 2. So 7. At the time of 7, P4 arrived. So immediately P4 will be given to the CPU. So total, it takes some 10 milliseconds to complete the process P4. Right? Hope you understood this one. So it arrived at 0, it takes 2 milliseconds. So 0, from 0 to 2, P1 is executed, by the CPU, and the P2 is arrived at the 3rd millisecond. So from 2 to 3, the CPU will be in idle state, and at the 3, P2 arrived. So it takes only 1 milliseconds to execute this process. So P2 is executed from 3 to 4, and again P3 arrived at 5. So from 4 to 5, again the CPU is in idle state. So no process is ready for execution. So from at the 5, P3 is allotted to the CPU, and CPU executes this P3 till 7 milliseconds. So at the time of 7, P4 is arrived, so P4 executes till 10. So now completion time. So what is the completion time of P1? 2. At the time of 2, P1 completed. P2, 4. At the time of 4, P2 completed. P3, 7. At the time of 7, P3 completed. P4, at the time of 10, P4 completed. Right? So next, turnaround time. So completion time minus arrival time. 2, 4 minus 3, 1, 7 minus 5, 2, 10 minus 7, 3. Waiting time. See, P1 arrived at 0. CPU is allocated at 0. 0. So 2 minus 2. Next, P2 arrived at 3. CPU is allotted at 3. Again it's 0. So 1 minus 1. Next P3. So arrived at 5. CPU is allocated at 5. Okay. P3 starting time is 5. Arrived at 5. So 0. P4 arrived at 7. Starting time of P4 is 7. So 7, 0. See, if you see this formula, turnaround time minus burst time, 2 minus 2, 0, 1 minus 1, 0, 2 minus 2, 0, 3 minus 3, 0. Okay, so in this example, the CPU is waiting for the processes, no process is waiting for the CPU. Right? This is another case. Now calculate the turnaround time. This is the turnaround time, 2 plus 2, 4, 5, 8. So 8, so 8 by 2. Here waiting time is 0. No process wait in a waiting state to get the CPU. So this is one more example for the first come first serve. So hope you understood these different cases. So based upon the arrival time, we have to prepare the Gantt chart, and from the Gantt chart, we have to write the completion time, turnaround time and waiting time. Turnaround time, I am writing the formula, turnaround time. As we said that, it's a time between starting and ending. So completion time minus arrival time. Completion time minus arrival time. Similarly, waiting time. So by seeing this Gantt chart, we can write the waiting time, or directly we can use the formula turnaround time minus completion time. Sorry, burst time. Turnaround time minus burst time. So by using this formula, you can calculate the turnaround time and waiting time, so that we can calculate the average waiting time and average turnaround time. So once again I am saying this is a non-preemptive mode, so no interruption will be there. Even though there is a process with highest priority, it should wait till the process completes execution by the CPU. Right? So only the scheduler will schedule the processes based upon the arrival time. The process will be get allocated to the CPU. Shortest job first. That means the process which is having the less execution time, which requires the less execution time, that we call it as a shortest job. So in the previous session we have discussed the scheduling criteria, that is the CPU utilization, throughput, turnaround time, and waiting time and response time. So in then we have seen one of the scheduling algorithm, that is FCFS, first come first serve. That means which arrives first into the ready queue, so that process will be allocated to the memory. So after completion of the process, based upon the arrival time, the second process will be allocated to the processor, CPU. So that happens in the first come first serve. So coming to this shortest job first, based upon the execution time, we will schedule the process to the CPU. So here this can be implemented in two modes. One is preemption and non-preemption. So we have discussed in the previous session, that is if it is a non-preemption, there will be no interruption. If one process is allocated to the CPU, so until the process being executed completes its execution, no other process will be allocated to the CPU. So that is called non-preemptive mode. And coming to the preemptive mode, if any process with highest priority is there, automatically the already executing process will be sent back to the ready state, and this highest priority process will be allocated to the CPU. So that is a preemption. Now let us look on the first case, that is non-preemption, SJF. So here we are applying mode is non-preemptive. So non-preemptive means no interruption. And the criteria is burst time, right? The criteria is burst time. So in the FCFS, the criteria is arrival time. Now let us see an example. So here also the frequent asked question is to calculate the average turnaround time and average waiting time, right, by using SJF with non-preemption mode. Now let us take the process. So here I have taken total 5 processes. The arrival time 0, 1, 2, 3, 4. So again this arrival time is a relative. It's not an absolute. It's a relative. That means lower the number, it comes the processor. The processor enters into the ready queue. Right. The order of a process enters into the ready queue. Next, this is the burst time. This is the arrival time. Right. So for this we have to prepare the Gantt chart. So let us prepare the Gantt chart. So always starts from the 0. So at the time 0, P1 arrived. So here among all these 5 processes, which process is having a very lower time to execute itself is P2. But P2 arrives at 1 millisecond, right? At 0, P1 arrived. That means at the time 0 in the ready queue, only one process is available. So automatically that process will be allocated to the CPU. So P1. So this will execute it until 8 milliseconds. So when the time is 8, all the remaining processes are ready in the ready queue, entered into the ready queue. So among all these processes, so P2, P3, P4, P5, which one is having the lowest burst time? 4. That means P2 is having the lowest burst time. So P2 will be given to the CPU. So 4, so 12. So again, this completed, this completed. Now there are 3 processes available in the ready state. Among them, P4 is having the lowest burst time. So the next process is P4 is allocated to the CPU. So P4 with 5, so it's a 17. P4. Next, 2 processes are in the ready queue. Among these 2 processes, P5 is having the shortest burst time. So P5 is allocated to CPU. So it will be executed till 23, right? So P5. Next, only one process is available in the ready queue. Automatically P3 will be allocated to the CPU, and P3 will be allocated till 32. Now count this one: 12, 21, 26, 32, right? 32. Total completion of for all, total time required to complete all these processes is 8 plus 4, 12, 12 plus 9, 21, 21 plus 5, 26 plus 6, 32. So 32 milliseconds is required to complete all the processes, right? Now, what is the completion time? The time required for completion. So P1 is completed at 8, P2 is completed at 12, P3 is completed at 32, P4 is completed at 17, P5 is completed at 23. Next, turnaround time. What is the turnaround time? So as we know that turnaround time is completion time minus arrival time. So turnaround time is equal to completion time minus arrival time. See, completion time minus arrival time, 8, 12 minus 1, 11, 32 minus 2, 30, 17 minus 3, 14, 23 minus 4, 19. Right? Now, some waiting time. What is the waiting time? How much time the process is waited for the CPU, right? So the waiting time is equal to turnaround time minus burst time. The formula is turnaround time minus burst time, or you can simply use this Gantt chart for completion. So P1 arrived at 0, arrival time 0, so automatically 0. Next, P2, the CPU is allocated at 8 and it arrived at 1, so 8 minus 1, 7. So if you apply the formula, you will get the same thing, 8 minus 8, 0, 11 minus 4, 7. Next, P3, so allocated the CPU at 23 and arrived at 2, so 23 minus 2, 21. So if you apply the formula, 30 minus 9, 21. Next, P4, allocated the CPU at 12, arrived at 3, 12 minus 3, it's 9. 14 minus 5, it's 9. P5, allocated the memory at 17, arrived at 4, so 17 minus 4, it's 13. It's 13. Hope you understood this, right? After getting this, we can calculate the average turnaround time. So total turnaround time is equal to, so 8 plus 11, 19, 19 plus 30, 49, 49 plus 14, 63, 63 plus 19, 82, right? Next, similarly, average turnaround time is equal to 82 divided by how many processes? 5 processes divided by 5. Similarly, total waiting time is equal to 0 plus 7, 7, 7 plus 21, 28, 28 plus 9, 37, 37 plus 13, 50. So 50, so average waiting time is equal to 50 by 5. So this is a simple thing. So here, the process is allocated to the CPU based upon the burst time. So initially at the time 0, no other process entered into the ready. So even though the burst time is higher for the process P1, P1 is allocated to the CPU. So after completion of P1, as it is a non-preemption, so once the process is allocated to the CPU, we should not disturb it until it gets execution. So it completes its execution. Now at the time 8, all the 4 processes are available in the ready queue. So among the 4, so select the shortest job. That means the shortest burst time. So among those, we are having P2 having the shortest job. So P2 get executed. So at the time 12, remaining 3 are available. So among these 3 processes, P5 is having the lower burst time. So P4 is allocated to the CPU, and then P5 is allocated, and then P3 is allocated, and the remaining process is same. So as it is a non-preemption, we should not disturb the processes until it gets executed. So if it's a preemption, then based upon the highest priority, we will just shift back the process to the ready state, and we will assign the CPU to the highest priority process, right? So as it is a non-preemption, we should not disturb these processes, the execution of the processes. So hope you understood. Now let us see one more example and we will wind up this concept, right? So second one, we will consider the 4 processes. The times are arrival timer is 1, 2, 3 and 4, and the burst times are 1, 3, 6 and 2. Right? So yes, this is the second example. Let us trace this one, or let us calculate this one. Let us take so 21. Okay. So prepare the Gantt chart. So this is the Gantt chart. Gantt chart. So at the time 0, not even a single process is available in the ready queue. So the CPU should be in idle state till 1. So CPU is in idle state till 1. So at the time 1, we are having only one process enters into the ready queue, that is P1. So P1 is allocated here. So total the time executed by the P1 is 21. So 22. As we have started at the 1 millisecond, so at the 22nd millisecond, P1 is completed. So at this time, 3 processes are available in the ready queue. So among these 3, P4 is having the shortest job. So P4 is allocated to the CPU. So P4 is allocated, so 24. Right? 24. Now, at the time 24, 2 processes are available in the CPU. So among these 2 processes, P2 is having the lowest burst time. So P2 will be allocated here. So time is 3, so it takes 27. Till 27, the P2 will be executed. So after that, only one process is remaining in the ready queue, that is P3. Now P3 is available. So P3 will be allocated and will be completed till 33. So total time required to complete all these processes is 33. Now calculate this one. So you can get that 21 plus 3, 24, 30, 32, and 1 is idle. So total 33. Right? Now let us write the completion time. So P1 is completed at 22, P2 is completed at 27, P3 is completed at 33, P4 is completed at 24. Turnaround time. So turnaround time is equal to completion time minus arrival time. So 22 minus 1, 21, 27 minus 2, 25, 33 minus 3, 30, 24 minus 4, 20. Now waiting time. So how much time the process waits for the CPU. So waiting time is equal to turnaround time minus burst time. Right? Turnaround time minus burst time. 21 minus 21, 0. So here let us see that. So P1 enters into at 1. Right? P1 enters, that means P1 allocated the CPU at 1 millisecond, it arrived at 1, so there is no waiting time. And coming to the P2. P2 allocated to the CPU at 24 and arrived at 2. So 22. 24 minus 3, 22. Next, P3. P3, the CPU is allocated at time 27 and arrived at 3. 27 minus 3, so 24. So 30 minus 6, 24. So I am saying the two ways, right? So based upon the formula, we can write this waiting time, or by using this Gantt chart also we can find out the waiting time, right? Next, P4. So P4 enters into the CPU, assigned to the CPU at 22 and arrived at 4. 22 minus 4, 18. So 20 minus 2, 18. So this is the waiting time for all these processes. So now total turnaround time, 21 plus 25, it's a 46. 46 plus 30, 76. 76 plus 20, 96. The average turnaround time is 96 divided by 4. Waiting time, 22, 46, 46 and 64. Waiting time, average waiting time is 64 by 4, as we have taken only 4 processes. So hope you understood this simple shortest job first. So here we have applied this in a non-preemption mode, that is no interruption while executing the process, and the criteria is burst time. So based upon the burst time, we have calculated, or we have prepared this Gantt chart. We have scheduled the process to the CPU. So hope you understood this shortest job first. AF, that is shortest job first. So whatever the process having with a short execution time, that is a burst time, that process should be allocated to the CPU. So here in the previous session we have seen in a mode a non-preemption, that is there will be no interruption during the execution of a process. So if one process is allocated to the CPU, until the process being executed, no other process should enter into the running state, right? So there will be no interruption. Now here in today's session we will see the preemption mode. Mode is a preemptive mode and the criteria is a burst time. So here there will be an interruption. So if one process is being executed by the CPU, so at the same time if any other process with lower burst time appears, automatically the executing process will be sent back to the ready state, and again this high priority process will be given to the CPU. So that is called preemption, right? So let us take an example so that you can clearly understand this one. So I will take an example. So let us take 5 processes: P1, P2, P3, P4, P5. The arrival time is 0, 1, 2, 3, 4, right? And the burst time is 8, 1, 3, 2, 6. So this is the burst time, this is the arrival time, right? First we have to prepare the Gantt chart. The procedure is same, right? The procedure is same. So we have to prepare Gantt chart. So the Gantt chart always starts from the time 0. So as I have said that the arrival time here is completely relative, it's not an absolute, right? So at the 0 time, here there are 5 processes, and P1 it requires 8 milliseconds to execute its process, P2 requires only 1 millisecond, P3 requires 3, P4 requires 2, and P5 requires 6. So our main problem is here mode is preemptive and criteria is burst time. So whatever the process which is having with a low burst time should be executed first. So by observing this, P2 is having the lowest burst time among all these 5. So actually P2 should be allocated to the CPU, but P2 is arrived at 1. So at the time 0, only P1 is available in ready state. So P1 should be allocated. So as it is a preemptive, whenever the highest priority process arrives into a ready state, automatically the present process must be sent back to the ready, and the highest priority should be executed. So after 1 second, so P2 has arrived into ready state, which is having low priority. So here 1 second has been executed. So now the P1 burst time is 7. Now the P1 burst time is 7, right? So after 1 millisecond, P2 arrived into the ready state. So there are two processes now in ready state, P1 and P2. Among that, which one is having the lowest burst time? P1 having the 7, P2 having 1. So P2 should be allocated to the CPU. So after that, it becomes 0. That means executed. Now the CPU time, the time is 2. So P3 arrived into the ready state. P3 having 3, P1 is having 7. So which one among these two, which one is having the lowest? P3. So P3 is allocated to CPU. Right. Now, so after 1 second, 3, here, so this has been completed 1 second. Okay, P3 has executed in 1 second. So now P3 requires only 2 seconds to execute. So at the time 3, P4 arrived into the ready queue. So now P1 is available, P3 is available, and P4 is available. So P1 requires 7, P3 requires 2, P4 requires 2. Right? So here, if any two processes having the same burst time, then select the process which is having the lowest ID, right? Lowest ID. So here P3 and P4 are having the lowest burst time. That means equal burst time, 2 and 2. So P3, P4, which is having the lowest ID, P3. So continue P3 till it executes the process. So 5. So until 5, it will be executed. So P3 completed. Now at the time 5, P4 is available in ready queue because it arrived at 3. P5 is available in ready queue because it arrived at 4. P1 is also available because it requires still 7 seconds to complete its execution. Now, among these three, which one is having the lowest burst time? P4. So P4 is allocated to the CPU. So how much time? 2 seconds, so 7. P4 completed. Now, P5 and P1 both are available in ready queue. So among these, P5 is having the lowest burst time. So P5 is allocated. So 13. Now only one is in ready queue, that is P1, which requires total 20. See, 8 plus 1, 9, 9 plus 3, 12, 14, 20. So the time required to complete execution of all the processes is 20. Okay, so hope you understood this one. Simple thing, don't get confused. So once again I will repeat the procedure. So first, at the arrival time 0, only one process is available in ready queue. So automatically P1 is allocated to CPU. So whenever the time changes to 1, at arrival time 1, P2 also available in CPU. As it is a preemption, wherever we receive the priority with lowest burst time, that process should be allocated to the CPU. So here P2 is arrived at 1 with a burst time 1. So 1 is less than 7. Here 7 because already 1 second completed here. 1 second of execution is completed by the process P1. So 8 becomes 7, right? So P1 still requires 7 seconds to complete its execution. So P2 will be having only 1 burst time. So P2 is allocated to CPU and it becomes 0. Now at the time of 2, P3 is available and P1 is available. Only P3 and P1 is available, right? So among these two, P3 is having the lowest burst time, that is 3, right? So P3 is given to the CPU. So after again completion of 1 second, then P3 requires 2 seconds to complete its execution, and at the arrival time 3, P4 is also available in ready queue, which requires the same 2 seconds to complete its execution. So here there are two processes which requires to execute the process is only 2 seconds. So if you get this case, select the process such that which is having the lowest process ID. So here P3, P4, P3 is having the lowest ID. So here I have given P3 is allocated to CPU and CPU completes the process P3. At the time of 5, now P5 is available, P4 is available, P1 is available. So among these three, here 7 requires, P4 requires 2, P5 requires 6. P4 is having the lowest burst time, P4 is allocated to the CPU. Next, P5 is allocated to the CPU and then P1 is allocated to the CPU. Hope you understood. So to avoid the confusion, you can write two terms. See, 2 to 3, that is P3. So in this here, P3 and P4 is having only the same burst times. So I have selected only P3, right? Now your confusion gets clear, right? Now let us write the completion time. Completion time. So P1 requires 20 seconds to complete. P2 requires 2 seconds to complete. So I will arrange all these things. Right. P3 requires 5 seconds to complete. P4 requires 7 seconds to complete. P5 requires 13 seconds to complete. Next, turnaround time. So turnaround time is completion time minus arrival time, right? 20 minus 0, 20. 2 minus 1, it's 1. 5 minus 2, it's 3. 7 minus 3, it's 4. 13 minus 4, it's 9. Right? Now, calculate the waiting time. Waiting time, that is turnaround time minus burst time. Right? see 20 minus 8 is 12. Next 1 minus 1 is 0, 3 minus 3 is 0, 4 minus 2 is 2, 9 minus 6 is 3. Right? So that's the waiting time. In order to get the average turnaround time, so add all these things, so you will get the total. So 21, so 24, 28, 37. So total 37 divided by 5 process. This is the average waiting time. Sorry, average turnaround time. Average turnaround time. Now average waiting time. So 12 plus 2, 4. I mean 14. 14 plus 3, 17 divided by 5. This is the average waiting time. Hope you understood this thing, right? Okay. So the same procedure you have to apply, but whenever the process with the lowest burst time arrived in the ready queue, immediately that process will be given to the CPU. So let us take one more example so that your doubt will be clarified. Let us take 4 processes now. 0, 2, 4 and 5. 7, 4, 1 and 4. Right? Now prepare the Gantt chart. So at the time of 0, so among all the 4 processes, this is the process which is having the lowest burst time, and these 2 processes are having the equal burst time, that is 4, and at last P1 is having the 7 milliseconds to complete its execution. Now, so at the time 0, only P1 is available in ready queue, so P1 will be allocated to the CPU. So until 2, the P1 is executed. So until 2, the P1 gets executed. So at the time of 2, P2 is available in, so here 7 becomes 5 because already 2 seconds have been completed by the P1. Here in P2 arrives into ready queue at the time 2. So at the time 2 with the lowest burst time. So at the time 2, P1 and P2 are available in ready queue. So P1 requires 5 seconds, P2 requires 4 seconds. So this one is the lowest among these 2. So P2 will be get executed, right? So until arrival time 4. So at the time 4, P3, so here again 2, it reduces to 2 because P2 also executed 2 seconds. So at the time of 4, P3 is arrived in ready queue, which is having the lowest burst time 1. So now at the time of 4, P1 is available in ready queue, P2 is available in ready queue, and P3 is also available in ready queue. So P1 requires 5 milliseconds, P2 requires 2 milliseconds, P3 requires only 1 millisecond. So P3 is allocated to CPU and it finished its execution. So this finished its execution. This one completed. Now at the time of 5, P4 also available in ready queue. So P1, P2, P4, 3 processes are available in ready queue. So P1 requires 5, P2 requires 2, P4 requires 4. So among these, P2 requires 2. This is the lowest burst time. So now P2 is available. That means assigned to the CPU. This completed. P2 is completed. Now P1 and P4. P4 requires 4. P1 requires 5. So among these two, P4 is having the lowest burst time. So P4 is allocated to CPU, and then P1 is allocated to CPU. Right? So total 16 milliseconds requires to complete all the processes to be get executed. Now let us take this one. 7 plus 4, 11. 11 plus 1, 12. 12 plus 4, 16. Total 16. So this Gantt chart is correct. I will erase all these things. Right? Now completion. The completion time. So P1 is completed at 16. P2 is completed at 7. P3 is completed at 5. P4 is completed at 11. So turnaround time is completion time minus arrival time. 16 minus 0 is 16. 7 minus 2 is 5. 5 minus 4 is 1. 11 minus 5 is 6. So waiting time. So waiting time is turnaround time minus burst time. So I will write here so that you can clearly get that. Turnaround time is equal to completion time minus arrival time. Similarly, waiting time is equal to turnaround time minus burst time. So this is a simple formula to fill the table, right? So turnaround time minus burst time. 16 minus 7, 9 seconds. 5 minus 4, 1 second. 1 plus 1 minus 1, 0. Right? So 6 minus 5, sorry, 6 minus 4, 2. Hope you understood this one, right? So the waiting time can be calculated by using this Gantt chart also, right? So everything is right. In the next session, we will move on to the another scheduling algorithm. So before closing that, so I am just repeating the same thing. So here we are using the preemptive mode. That is, if any process is with the lowest burst time appears in the ready queue, automatically that particular process will be allocated to the CPU. So already the executing process will be sent back to the ready state. Right? So from this we have to prepare the Gantt chart. From this Gantt chart we have to fill this completion time, turnaround time, and waiting time. Now calculate the average turnaround time and average waiting time. 16 plus 5, 21, 22, 28 divided by 4. So this is the average turnaround time. Here 9 plus 1, 10, 10 plus 2, 12, 12 by 4. 12 by 4 is the average waiting time. Hope you understood this thing. Priority scheduling algorithm. So for every process which is in a ready queue will be given some priority. So based upon that priority, we have to allocate the process to CPU. So coming to this first come first serve, based upon the arrival time, so which process arrived first into the ready queue, that process will be get executed by the CPU. And then in the shortest job first, which process is having the least burst time, so that process will be allocated to the CPU. And now in this priority scheduling, so some priorities will be given to the processes. So based upon that priority, the process will be allocated to the CPU. So here the priorities will be from 0 to 7 or some 0 to 4093, right? So that is some numbering. So numerical numbers will be given as a priority to the processes, right? See, let us see an example so that you will know the procedure. So priority for the processes, process ID, arrival time, burst time, completion time, turnaround time, waiting time. So we need to calculate all these things. So now let us take the process IDs. So that is from, I will take 5 processes, P1, P2, P3, P4 and P5. So total 5 processes, and the arrival time for this process are 0, 1, 2, 3 and 4. So arrival time, as I said, that arrival time is a relative time, right? Now what about the burst time? 9, 4, 5, 7 and 3. This is the burst time. Now we have to give some priority to the processes. So the priorities will be given by the CPU itself. So 5, 3, 1, 2, 4 priorities, right? 5 for P1, 3 for P2, 1 is for P3, 2 is for P4, 4 is for P5. Here I am taking 1 as or low in number is having high priority. Low in number in high priority. And also the mode is non-preemptive mode. Non-preemptive. So as I said, that non-preemptive means we should not disturb the process which is going on execution by the CPU, right? So until it completes its execution, no other process should enter into the running state. Now let us prepare the Gantt chart so that we can find out all these times. So this is the Gantt chart. Gantt chart. So always this starts from 0. At the 0 arrival time, only one process is in ready queue. So even though the priorities, see here the priorities, so 5, 3, 1, 2, 4. So here the highest priority is given to the process 3. But process 3 is arrived at 2, arrival time 2. So initially only one process is available in ready state. So this process will be allocated to the CPU. Right? So it will be allocated till 9, and then so after arrival 9, all these processes are available in ready queue. So because P2 arrived in 1, P3 arrived in 2, P4 arrived at 3, P5 arrived at 4. So here it is already 9. So all these processes will be available in ready queue. So among all these processes, which one is having the highest priority? That is low in number, P3. So now P3 is allocated to the CPU and it will be executed till 5. So 14. Now P1 is completed, P3 is completed. Now what about the remaining? At the time 14, now 3 processes are available in ready queue, P2, P4, P5. So among these 3 processes, so which one is having the high priority? This one, P4 with the 2, right? Low in number, high priority, 2. So P4 will be given to the CPU and it will be executed till 21 because it requires 7 milliseconds to complete its execution. Right? This one completed. Now at the time 21, 2 processes are available in ready queue, P2 and P5. So among these 2, P2 is having highest priority because 3. Here P5 is having 4. So lowest number is high priority. So P2 is having high priority. P2 will be given to the CPU. It will be executed till 25. Right? Next, automatically P5, 4. So P5 is given to the CPU and it will be executed till 28. Hope you understood. So at the time of 0, only one process is available, so we need not check for the priority. So automatically P1 is allocated to the CPU. So it is not a non-preemptive. This implementation is a non-preemptive algorithm. So it is a non-preemptive means we should not interrupt the process during its execution. So we have to let it finish its execution. So after completion of this execution, the next process with the higher priority should be allocated to the CPU. So at the time 9, there are 4 processes available: P2, P3, P4, P5. So among these 4 processes, P3 is having the lower priority because low in number, high priority. So low number, so it is having the highest priority. So P3 is allocated, and then after completion of P3, 3 processes are available. Among these 3, P4 is having the highest priority with number 2. So P4 is executed, then P2 and P5. So if you sum all these things, we should get the 28. So 9 plus 4, it's 13, 18, 25 and 28. So this Gantt chart is correct, right? Because the total time required to complete all these processes is 28. Completion time. So P1 completed at 9, P2 completed at 25, P3 completed at 14, P4 completed at 21, P5 completed at 28. Right? Now turnaround time, as I said, that turnaround time is a completion time minus arrival time. So 9 minus 0 is 9, 25 minus 1 is 24, 14 minus 2 is 12, 21 minus 3 is 18, 28 minus 4 is 24. Right? So this turnaround time is completion time minus arrival time. Similarly, waiting time is equal to turnaround time minus burst time. Right? Now, waiting time, so P1 arrived at 0, here, P1 is allocated to CPU at 0, arrived at 0, so 0 minus 0, 0. Next, P2 is allocated to CPU at 21 and arrived at 1. So 21 minus 1, it's 20. So based upon the formula also you can check 24 minus 4, it's 20. Next, P3 is allocated to CPU at 9, P3 is allotted at arrival time is 2. So 9 minus 2 is a 7, 12 minus 5 is 7. Next, P4 allocates the, P4 is allocated to the CPU at 14, arrived at 3. So 14 minus 3, it's 11. So 18 minus 7, it's 11. Next, P5 is allocated to the CPU at time 25 and arrived at 4. So 25 minus 4 is 21. Right, 21. So 24 minus 3 is 21. Hope you understood this one. So calculate the average, total all these things. So you will get the total turnaround time. So, see 9 plus 24, 33, 33 plus 12, 45, 45 plus 18, 63, 63 plus 24, 87. So, average turnaround time is equal to 87 divided by, how many processes are there? 5 processes are there. This is the average turnaround time. Now, waiting time, 20 plus 7, 27, 38, 59. So, here the average waiting time is equal to 59 by 5. This is the average waiting time. Okay, so hope you understood. Here, some priorities will be given to the process. When based upon those priorities, we have to allocate the process to the CPU. So, as it is a non-preemptive mode, so we should not disturb the process which is going on executing by the CPU. So, once completion of that process, the next process with the highest priority will be allocated to the CPU. Right? Hope you understood this one. So, let us take one more example so that your doubts will be clarified. See, now let us take the 4 processes: P1, P2, P3, P4. So with arrival times 0, 3, 4, 9. With the burst times 60, 30, 40, 10. What's the priority? 3, 2, 1 and 4. Right? So P1 is having 3, P2 is having 2, P3 is having 1, P4 is having 4. So now among these processes, which one is having highest priority? P3. So P3, then the second highest priority, P2, next third priority, P1, fourth priority, P4. But here, at the time of 0, only one process is available in ready queue, that is P1. So, which is having the third priority. Even though only one process is available in CPU, first P1 will be get executed by the CPU. Right? Let us prepare the Gantt chart. So 0, first P1 will be allocated to the CPU, so until 60. So at the time of 60, all the processes are available in ready queue. Among these 3 processes, which one is having the highest priority? This one, P3, because it is having 1. That means lower number will be highest priority. So P3 is having the highest priority. No, P3 will be allocated to the CPU and it will be executed until 40. So it's a 100. Next, 2 processes are available in ready queue. At the time of 100, 2 processes are available in ready queue. So P2 is having with the 2 priority, P4 is having with the 4 priority. So as P2 is having the highest priority, P2 should be allocated to the CPU. So now P2 is allocated to the CPU it runs until 130. Right? After that, only one process is remaining, that is P4. It is allocated, and now till 140 it will be available. So let us find out the total. 60 plus 30, 90, 90 plus 40, 130, and 140. So here also 140. Now this Gantt chart is correct, because so the total time required to complete executing all the processes is 140. So here also it's 140. Now completion time. So P1 is completed at 60, P2 is completed at 130, P3 is completed at 100, P4 completed at 140. Turnaround time. Turnaround time is completion time minus arrival time. So 60 minus 0, it's 60. 130 minus 3, 127. 100 minus 4, it's 96. 140 minus 9, it's 131. Right? Now waiting time. So waiting time is turnaround time minus BT. So turnaround time minus BT. 0. 127 minus 30. 97. 96 minus 40. 56. 131 minus 10. 121. So we can observe here also by using the Gantt chart also we can find out the waiting time. So P1 allocates to the CPU at 0, arrived at 0, so 0. Next P2 is allocated to the CPU at 100, arrived at 3, so 100 minus 3 is 97, so 97. P3 is allocated to the CPU at 60 and arrived at 4, 60 minus 4, 56. P4 is allocated to the CPU at 130 and arrived at 9, so 130 minus 9, 121. So this is the correct one. Now we can find out the average waiting time and average turnaround time. So that by adding all these things divided by 4. So total turnaround time divided by 4. So average turnaround time. Similarly, average waiting time is equal to total waiting time by 4. So hope you understood this simple thing. So this is a priority scheduling algorithm. The name itself indicates we have to give some priority to all the processes, and based upon the priority, the process will be allocated to the CPU. So here the low in number is having the highest priority. So in some examples we can say high in number is having the highest priority. So based upon that situation, based upon that case, based upon the given node, so we have to solve the problem. And also this is a non-preemptive. If one process is going to be executed by the CPU, so until it completes its execution, no other process should be entered into the running state. So that means no interruption. There must be no interruption. Right? So hope you understood this simple algorithm. That is a priority scheduling algorithm in non-preemptive mode. Non-preemptive mode. Criteria is priority. Criteria is priority. So for the FCFS, the criteria is arrival time, and for SJF, the criteria is burst time. For priority scheduling algorithm, the criteria is priority. So priority scheduling algorithm. So here mode is preemptive. So there will be an interruption. And low in number is having highest priority. Right? So let us see the procedure by taking one example. So let us consider here the priority, process ID, arrival time, burst time, so time taken to complete its execution, completion time, turn around time, and waiting time. Right? So we have to consider the processes, arrival time, burst time, as well as the priority, and based upon this we have to prepare the Gantt chart, and from the Gantt chart we have to find the completion time of each process, turnaround time of each process, as well as the waiting time of each process. Now let us take an example. 4 processes, P1, P2, P3 and P4. So the arrival time is 0, 2, 3 and 5, and the burst time is 10, 5, 2, 20. The burst time is 10, 5, 2, 20. Now the priority is 2, 1, 0, 3. So here 4 processes, we have taken the 4 processes, their arrival time and burst time and their priority. So in this example we can say that P3 is having the highest priority, then P2 is having the highest priority, then P1 is having the highest priority, then P4 is having the highest priority. So among the 4 processes, P3, P2, P1, P4, based upon the priority, right? Now let us prepare the Gantt chart. Gantt chart. See, at the time 0, at the arrival time 0, only one process is available in ready queue. So P1 is allocated to CPU. So at time 1, no other process had entered into CPU. At time 2, P2 entered into CPU, which is having the highest priority than P1. Okay, don't get confused. So until the time 2, no other process is available in ready queue. Only one process is available. So P1 is allocated to CPU. So it completes its time in 2. So it will be 8 now. So at the time 2, P2 is available in ready queue. So P2 is having highest priority 1 than P1. So P2 is allocated to CPU. Now at the time 3, one more process is available in ready queue. So now what are the processes are available in ready queue? P3 and P1, right? So P3 is having highest priority than P1, and also P3 is having highest priority than P2. So P2 will be again moved back to the ready state. So how much time? So here 1 second is completed. Now P3 is allocated to CPU. At the time of 5, okay, it executes till 5, and at the time of 5, one more process is available, P4, which is having the low priority than P3. Okay, here P4 is having the low priority than P3. So P3 continues its execution until it completes the execution. So P3 means 2, that means 5. At the time of 5, it's completed, right? P3 completes. Now at the time of 5, what are the available processes? P4, P2, P1. Okay, P3 already completed, so P4, P2, P1. Among these, which one is having the highest priority? P2 is having the highest priority. So P1 is having 2, P2 is having 1, P4 is having 3. So here low in number is having high priority. So 1 is the highest priority. So P2 is having highest priority. Now P2 is allocated to the CPU. So P2 completes its execution. So 4, so 9. So it becomes 0. Now at the time of 9, so P2 completes. At the time of 9, P1 is available and P4 is available. So among these two, which one is having the highest priority? P1 is having the priority 2, P4 is having the priority 3. So low in number is having the highest priority. So P2 is having highest priority. So P1 will be allocated to the CPU and it completes its execution. Total 8. That is 17. Right? At the time of 17, only one process is available. That is P4. Now P4 is allocated to the CPU and it completes its execution till 37. So it becomes 0. So it becomes 0 in the earlier. Now it becomes 0. Right? So hope you understood this one. So I will erase all these things. Only burst time I will be displaying. So for better understanding, I am writing all these things. So erase these things. Right. Now completion time for this one is P1 completed at 17, P2 completes at 9, P3 completes at 5, P4 completes at 37. Right? 17, 9, 5 and 37. Now turnaround time. So as we know that turnaround time is the completion time minus arrival time. Similarly, waiting time is turnaround time minus burst time. So we have to remember these formulas. So CT minus arrival time. So 17, 9 minus 2 is a 7, 5 minus 3 is a 2, 37 minus 5 is a 32. 17, 7, 2, 32. Now waiting time. So waiting time can be calculated by using this formula or by using this Gantt chart also we can find out the waiting time. So first let us write this formula. Based upon the formula you will write down and I will explain. 17 minus 10, 7, 7 minus 5 is 2, 2 minus 2 is 0, 32 minus 20 is 12. Now let us check with the Gantt chart. So P1. So P1 allocates the CPU at 9 and previously it completes 2. So 9 minus 2, 7. So 7 and arrived at 0. So 7 minus 0, 7. Next coming to the P2. P2 is allocated to CPU at 5 and earlier 1 second is completed. So 5 minus 1, 4 and arrival time is 2. 4 minus 2, 2. Next P3. P3 allocated to the CPU at 3 and arrived at 3. So 3 minus 3, 0. There is no waiting time. Next P4. So P4 entered into the CPU at 17 and arrived at 5. So 17 minus 5 is 12. So by calculating this average, so 17 plus 7, 24, 26, 58 divided by 4. So as there are 4 processes, so this is average turnaround time. And here also 7 plus 2, 9, 9 plus 12, 21 divided by 4. This is average waiting time. So average waiting time. So hope you understood this one. So here, so first process is allocated to the CPU and based upon the arrival time and the priority, the process will be again shifted to the ready state and the highest priority process is allocated to the CPU. Right? So there is an interruption here. So that's why we call it as a preemptive priority scheduling algorithm. And here low in number is having the highest priority. So if you count this burst time, 20 plus 2, 22, 22 plus 5, 27, 37. So the time required to complete executing all these processes, 37. So in the Gantt chart also, we got 37. Right? So hope you understood this one. Let us solve one more example so that you can get a more idea about this priority scheduling algorithm in a preemptive mode. Now let us take one more example. So my main concentration is for the slow learners. So if I solve more examples, automatically their doubts will be get clarified and they will be easily understood, right? So don't think otherwise. Now coming to the second one, let us take a 5 processes. P1, P2, P3, P4, P5, and the arrival time is 0, 1, 2, 3, 4, and the burst time is 9, 4, 5, 7, 3, and the priority is 5, 3, 1, 2, 4, right? So P1 is having 5, P2 is having 3, P3 is having 1, P4 is having 2, P5 is having 4. Now before going to the arrival time and burst time, first let us see which process is having the highest priority. So as we know that low number highest priority. So first P3 is having the highest priority, then P4 is having the highest priority, then P2 is having the highest priority, then P5 is having the highest priority, and at last P1 is having the highest priority. So this is the highest priority to lowest priority, high to low, right? So that other than arrival time and burst time and all these things, just we are writing according to the priorities, right? Now let us draw the Gantt chart so that we can find all those things. Gantt chart. So always starts from 0. So at the arrival time 0, only one process is available. So P1 is allocated. So at the arrival time 1, another process is available, P2, which is having the highest priority than P1. So P1 is having 5, P2 is having 3. So P2 is having the highest priority than P1. So P1 sent back to the ready state and P2 will be allocated to the CPU. Right? So after at the time 2, again, so here 8, here 3. So because 1 second completed, here also 1 second completed. Now at the time 2, P3 is in ready state, which is having the priority 1. That means highest priority than P2 and P1. So P3 is allocated to the CPU, right? So at the time 3, again it checks for P4, which is having the low priority than P3. Low priority than P3. So P3 executes, and now at the time 4, P5 is already in ready queue, so which is having the again low priority than P3. So P3 continues its execution until it completes its execution. So 7. So it becomes 0. Right? Now at the time 7, 4 processes are available in ready queue. P1, P2, P4 and P5. So among these 4, which one is having the highest priority? P4 with the 2, that is low in number, high priority. So P4 is having a low number, that is highest priority. So P4 is allocated to CPU and it completes its execution 14. Next, so this becomes 0, so P4 completed. Now at time 14, P5 is available, P2 is available, P1 is available. Among these 3, P2 is having highest priority because P1 is having 5, P2 is having 3, P5 is having 4. So among these low number is for P2, low number is high priority. So P2 will be allocated to the CPU and it completes its execution. So P2 is having still 3 seconds to complete its execution. So it completes its execution. Next, at time 17, again we had 2 processes in ready queue, 5 and 4. Among these 2, 4 is having the highest priority. So P5 is allocated to the CPU and it completes its execution. So 3, so 20. Right? Next, at time 20, only one process is available in ready queue, that is P1. Now P1 is allocated to CPU and it completes its execution, that is 28. This becomes 0. P1 completes. So hope you understood, right? At the time 0, only one process is available, so directly the process is allocated to the CPU. So it executes until 1 second, so until the arrival time becomes 2, and the arrival time becomes 2, there is a at the arrival time becomes 1, another process is available which is having the highest priority than P1. So P1 is removed from the CPU and P2 is allocated to CPU. And again P2 is executed at the time arrival time 2, another process is available in ready queue which is having the highest priority than P2. Now P3 is removed from the CPU and P3 is allocated to the CPU. And at the time 3, P4 is available in ready queue which is having the low priority than P3. So P3 continues its execution. At the time 4, P5 is available in ready queue which is having again low priority than P3. So P3 still continues its execution until it completes its execution. So after that, at time 7, we are having 4 processes, 4 processes available in ready queue, P1, P2, P4, P5. Among those 4, P4 is having the highest priority, P4 is allocated to the CPU and it gets executed till it completes its execution. And after the 14, 3 processes are available, among those P2 is having the highest priority, so P2 is allocated to the CPU and it completes its execution. And at the time 17, 2 processes are available in ready queue, among these 2, P5 is having the highest priority, P5 is allocated to the CPU and it continues its execution. And finally, P1 is having the highest priority, only one process is remaining, so P1 is allocated to the CPU and it completes its execution. Hope you understood this Gantt chart. So if you are able to write this Gantt chart correctly, automatically we can find all these things, right? So I will erase all these things except the burst time. See, What is the total time required? 9 plus 4, 13, 18, 28. See, here also, it requires total 28 milliseconds to complete all the processes to get executed. Now completion time, let us write the completion time. So P1 is completed at 28, P2 is completed at 17, P3 is completed at 7, P4 completes its execution at 14, P5 completes its execution at 20. Right? This is the completion time for each process. Now turnaround time. So as we have said, the turnaround time is equal to completion time minus arrival time. Waiting time is equal to turnaround time minus burst time. So this is the formula. So turnaround time, completion time minus arrival time. 28 minus 0, 28, 17 minus 1, 16, 7 minus 2 is 5, 14 minus 3 is 11, 20 minus 4 is 16. Next, waiting time. So waiting time, turnaround time minus burst time. 28 minus 9 is 19, 16 minus 4 is 12, 5 minus 5 is 0, 11 minus 7 is 4, 16 minus 3 is 13. Now let us check with the Gantt chart. So coming to the P1, so P1 enters the CPU at 20 and already completes its execution for 1 second. So 20 minus 1, 19, arrived into the ready queue at 0, so 19 minus 0, 19. Next, P2. P2 allocated to the CPU at 14, so in the earlier only 1 second is completed, so 14 minus 1, 13, 13 minus, it arrived into ready queue at 1, so 13 minus 1, 12. Next, P3. P3 is allocated to the CPU at time 2 and P3 is arrival time is 2, so 2 minus 2, 0. Next, P4. P4 allocated to the CPU at time 7 and it is arrived at 3, so 7 minus 3 is a 4. P5. P5 is allocated to the CPU at 17 and it is arrived at 4, 17 minus 4, it's a 13. So average turnaround time is equal to 28, 16. So 44, 49, 60, 76. 76 by how many processes? 5 processes. 76 by 5. Now average waiting time. So 19 plus 12 is 31, 35 plus 48. 48 by 5. Average waiting time. Right? Hope you understood. Here, this is the process for preemption. Preemptive priority scheduling algorithm. Right? So preemption means there will be interruption. So whatever the process is in running state, so if any other process is available with the highest priority than the running process, automatically the running process will be sent back to the ready state and the new process, that is which is having the highest priority process, will be allocated to the CPU. Right? So this is the process of preemptive priority scheduling algorithm. So far we have seen three scheduling algorithms. One is FCFS, first come first serve, SJF in both the preemption and non-preemption, and priority scheduling algorithm both in preemption and non-preemption. So these are the very simple concepts. So if you are able to draw this Gantt chart, automatically you can find out all these things easily. Round robin scheduling algorithm. So here we have to consider some time quantum, and based upon the time quantum, the CPU will be allocated to the processes. Right? So every process will be allocated to the particular time quantum itself. And after completion of the time quantum, the process will be removed from the CPU and it will be again sent to the ready queue, and that process should wait until it gets its turn to complete its execution. So every process will be having the equal time quantum. That means every process will spend equal time with the CPU to complete its execution. So let us see an example. So here there are two nodes. One is considering the arrival time and without considering the arrival time. Now let us look with the time quantum and arrival time. Let us see an example. So time quantum plus arrival time. So we are considering both time quantum and arrival time. We are considering both here. So let us take this process, arrival time, burst time, completion time, turn around time, waiting time. So we have to find out all those things. So let us take an example. So let us take complete 4 processes, and the arrival time for this process 0, 1, 2, 4. The burst time 5, 4, 2, and 1. So let us find out this completion time, turnaround time, and waiting time. So for this we have to prepare 2 boxes. That is, one is for ready queue and another one is for this Gantt chart. Now, so let us take the time quantum is equal to 2 milliseconds. Here the time quantum is 2 milliseconds. Now let us take the ready queue. So this is the ready queue, and we have to follow this ready queue, right? To allocate the process to the CPU, we have to follow this ready queue. So this is the ready queue, and this is the Gantt chart. This is the Gantt chart, right? So as you know, at the time of arrival time, at the time of 0, P1 is in the ready queue, right? P1 is available in the ready queue. So at the time, so only P1 is available, so P1 will be removed from the ready queue and it will be allocated to the CPU and it will be get executed. here the time quantum is 2. So P1 spends only 2 milliseconds with the CPU. So 2, right? So the remaining is 3. So here P1 still requires 3 milliseconds to complete its execution. Now after completion of 2, that means after completion of time quantum, P1 is removed from this ready queue, and P1 is removed from the CPU and it will be sent to the ready queue. Before that, at the time of 2, there are 2 processes available in ready queue, that is P2 and P3. See, at the time of 2, there are two processes in the ready queue, P2 and P3. And after completion of these 2 milliseconds, P1 will be removed from the CPU and is allocated to the, it will be moved to the ready queue. So P1, right? So understood. So first, at the time 0, only P1 is available in the ready queue. It will be removed from the ready queue and it will be allocated to the CPU. So after completion of execution to 2 milliseconds, at the time of 2, 2 more processes are available in the ready queue. So after completion of this time quantum, P1 will be removed from the CPU and it will be sent to the ready queue. Now we have to allocate the CPU according to the order of processes available in ready queue. Now P2 is removed from the ready queue and allocated to the CPU. Again, all the processes will be executed only with an equal time quantum, that is only 2. So P2 will also execute only 2 milliseconds. So still P2 requires 2 milliseconds to complete its execution. Right. So at the time of P4 and at the time of 4, P4 is also available in ready queue. Right? P4 is also available in ready queue. Now after completion of time quantum, P2 still requires 2 milliseconds. So P2 is removed from the CPU and it will be moved to the ready queue. So here P2. Right? Next, P3 will be removed from the ready queue. P3 is allocated, right, to the CPU and it will be executed 2 milliseconds. So P3 completes its execution. So it completed its execution. So P3 doesn't require the CPU once again. Right? So within the given time quantum, P3 completes its execution. Next, P1. So P1, again the time quantum is 2, so 8. So it requires 1 milliseconds to complete its execution. So P1 will be removed from the CPU. So at the time of 8, no other processes are available in ready queue. So P1 will be removed from the CPU and it will be added in the ready queue. So P1. Now P4. So P4 is allocated to the CPU and it executes only 1 second. So even though the time quantum is 2, it requires only 1 second to complete its execution. So it will be 0. Right? Now P2. P2 is allocated. That is also for 2 milliseconds. 0. So P2 completes its execution and then P1 completes its execution with only 1 second, that is 12. Right? So this is the order, or this is the procedure to be followed for executing the round robin scheduling algorithm. So first, at the time of 0, P1 is allocated to the CPU and it will be executed for 2 milliseconds. And at the time of 2, 2 more processes are available in ready queue, P2 and P3. And still P1 requires 3 milliseconds to complete its execution. So P1 is removed from the CPU and P1 will be allocated to the, P1 will be moved to the ready queue. And P2, in the order of ready queue, P2 is available. So P2 will be allocated to the CPU and it will again execute 2 milliseconds, so 2 to 4. And it still requires 2 milliseconds at the time of 4. P4 is also available in ready queue, so P4. And it still requires 2 milliseconds, so P2 will be removed from the CPU and added to the ready queue. And in the order, again, next P3 will be executed for 2 milliseconds, and within this time quantum itself, it completes its execution. So P3 will not be added to the ready queue because it completes its execution. Next, after that, in the ready queue, P1 is available. So P1 is removed from the ready queue and it will be allocated to the CPU and it will be executed for 2 milliseconds, and still it requires 1 milliseconds. So P1 will be again added to the CPU, ready queue. Next, in the order, P4 is available in the ready queue. So P4 will be removed from the ready queue and it will be allocated to the CPU, and it again, the P4 requires only 1 millisecond to be executed. So P4 is executed till 1 millisecond and completes its execution. So it doesn't require any other time to complete its execution. So P4 will not be added to the ready queue. So now in the order, P2 is available in the ready queue. So P2 will be removed from the ready queue and allocated to the CPU. So P2 requires 2 milliseconds, and here the time quantum also 2 milliseconds. So it completes its execution at this level. And then in the order, P1 is added in the ready queue. So P1 will be allocated to the CPU and it executes 1 millisecond and it completes its execution. So this is the Gantt chart and this is the ready queue. So hope you understood this thing, right? So 5, 4, 2, 1. Now completion time. See here the completion time. So completion time of P1 is 12. Completion of time of P2 is 11. Completion time of P3 is 6. The completion time of P4 is 9. Turnaround time is completion time minus arrival time. 12 minus 0. 12, 11 minus 1 is 10. 6 minus 2 is 4. 9 minus 4 is 5. Waiting time, that is turnaround time minus burst time. 12 minus 5 is 7. 10 minus 4 is 6, 4 minus 2 is 2, 5 minus 1 is 4. So you can also check with the waiting time with this Gantt chart. So P1, here 11, 11 minus 2, 9, 9 minus 2, 7. Right. Next P2, coming to the P2, it's 9, 9 minus 2, 7, and it arrived at 1, so 7 minus 1, 6. Next P3, 4, it arrives at 2, so 4 minus 2, it's 2. Next P4, 8, it arrives at 4, 8 minus 4, it's 4. Right? So find out this one, so 19, so average waiting time is 19 divided by 4. So like this way, we can use this, I mean we can implement this round robin scheduling algorithm. So here the main thing is time quantum. And another one is based upon the arrival time. So if the arrival time is not given, so we can consider the arrival time for all the processes 0. Let us see one more example for this round robin algorithm. So here I have considered 5 cases, I mean 5 processes, and with the arrival times 0, 1, 2, 3, 4, and the burst time, so 8 milliseconds to complete the execution of P1, 1 for P2, 3 for P3, 2 for P4, and 6 for P5. And here let us consider the time quantum as 3 milliseconds. The time quantum as 3 milliseconds. Now let us draw the ready queue and Gantt chart. See, this is the ready queue. This is the Gantt chart, right? So at the time of 0, only P1 is available in the ready queue. So P1 is available in the ready queue. So this P1 will be removed from here and it will be allocated to the CPU and it will be executed till 3 milliseconds. So P1 still requires 5 milliseconds to complete its execution. So at the time of 3, right? At the time of 3, P2, P3, P4 is also available in ready queue. So P2, P3, P4 is also available in ready queue at the time of 3. Now, after completion of this time quantum, P1 still requires 5 milliseconds to get executed. So P1 will be removed from the CPU and it will be allocated, I mean added in the ready queue. Right? Now, in the order, now P2 will be removed from the ready queue and it will be allocated to the CPU. Now P2 executes its execution till only 1 millisecond because so only 1 second is required to complete its execution. So P2. Next, at the time of 4, P5 is also available in ready queue. So P5 is available in ready queue. Right? So next in the order, P3 is removed from the ready queue and it will be allocated to the CPU. And again, P3, it requires 3, so 3 milliseconds it will be executed. Right? So P3 doesn't require any more allocation of CPU. Right? So P3 will not be added again to the ready queue because it completes its execution. Now in the order P4, the P4 is removed from the ready queue. It will be added to the CPU, allocated to the CPU, and it executes 2 milliseconds. 0 because here it is a time quantum is 3, only 2 milliseconds are required to complete its execution. Right? Now, next after completion of P4, P1 is executed, so it will be removed from the ready queue, it will be allocated to the CPU, and again 3 milliseconds, it will execute 3 milliseconds. Now, again it requires 2 milliseconds to complete its execution, so P1 will be removed from the CPU and it will be added to the ready queue. Now P5, in the order P5. Remove the P5 from the ready queue and it will be allocated to the CPU, and now P5 is also executes to 3 milliseconds, so 3 milliseconds. So again P5 requires 3 milliseconds to get executed, so P5 is removed from the CPU and it will be moved to the ready queue. Now, in the order P1, P1 removes from the ready queue, P1 is allocated to the CPU, so P1 again still, it will be executed till 2 milliseconds, so after 2 milliseconds, P1 completes its execution. Now, in the ready queue, P5 is there, so P5 is removed from the ready queue, P5 is allocated to the CPU and it executes 3 milliseconds, so it is also completed its execution. So, all the processes have completed its execution. Right? So this is the ready queue and this is the Gantt chart. So at the time of 0, P1 is available in the ready queue, so P1 will be allocated to the CPU, and here the time quantum is 3, so P1 is executes only 3 milliseconds. At the time of 3, these 3 processes are available in the ready queue, so P2, P3, P4 is added in the ready queue. So after completion of this time quantum, P1 still requires 5 milliseconds to get its execution, so P1 will be added in the ready queue. So now in the order, P2 will be removed from the ready queue and it will be executed only 1 millisecond, so it requires only 1 millisecond to complete its execution, so it completes its execution till from 3 to 4. Now, in the order, P3 will be there, so P3 will be removed from the ready queue and it will be allocated to the CPU and it executes 3 milliseconds to complete its execution, so it executes from 4 to 7 as the time quantum is also equal to 3. So P3 completes its execution. Now in the order, P4 is available in the ready queue, so P4 will be available, removed from the ready queue and it will be allocated to the CPU and it executes 2 milliseconds to complete its execution, so from 7 to 9 it will complete its execution. Next, in the order, P1 will be there in the ready queue, so P1 will be removed from the ready queue and it will be added to the CPU, and again P1 will execute till 3 milliseconds because time quantum is 3. So again still P1 requires 2 more milliseconds to complete its execution, so P1 will be removed from the CPU and it will be added in the ready queue. So in the order, P5 is there, so P5 will be removed from the ready queue and it will be executed, allocated to the CPU and it executes for 3 milliseconds as the time quantum is 3. So it still requires 3 milliseconds to complete its execution, so P5 again it will be removed from the CPU and it will be added in the ready queue. So in the order P1 is there, so P1 is removed from the ready queue and it will be allocated to the CPU, and it executes 2 milliseconds to complete its execution. So it executes from 15 to 17 and it completes its execution. So in the order P5 will be there, so P5 will be removed from the ready queue and it will be allocated to the CPU, and it executes 3 milliseconds, which completes its execution. So from 17 to 20, it will be this P5 will be executed. So this is the process. The scheduler will scheduling these processes according to the time quantum and arrival time. Now, see, add all these things. 8 plus 4 9, 9 plus 3 12, 12 plus 2 14, 14 plus 6 20. So Gantt chart is also 20. So 20 milliseconds are required to complete the execution of all the processes. Right? Now completion time. P1 completes at 17, P2 completes at 4, P3 completes at 7, P4 completes at 9, P5 completes at 20. Next, turnaround time. It's a completion time minus arrival time. 17 minus 0 is a 17, 4 minus 1 is a 3, 7 minus 2 is a 5, 9 minus 3 is a 6, 20 minus 4 is a 16. Now waiting time. Turnaround time minus burst time. 17 minus 8 is 9, 3 minus 1 is 2, 5 minus 3 is 2, 6 minus 2 is 4, 16 minus 6 is 10. So let us check this waiting time with the Gantt chart. So P1, so here P1 is a 15, here 3, P1 15 minus 3 is a 12, 12 minus 3 is a 9, 9 and arrived at 0, so 9 minus 0 is 9. Next, P2, P2 3, arrived at 1, so 3 minus 1 is 2. Next, P3 is 4, 4 minus arrived time it arrived at 2, so 4 minus 2, 2. Next, P4, so P4 is allocated to the CPU at time 7, it arrived at 3, so 7 minus 3, 4 milliseconds it has been waited. Next, P5, so the CPU allocated to the CPU, P5 is 17, and previously 3 milliseconds completed, so 17 minus 3 is a 14. So 14 and arrived at 4, so 14 minus 4 is 10. Hope you understood this one. So find out the total turnaround time and waiting time. From that we can get the average turnaround time and average waiting time. So we know the process, right? So it is a task under execution. Task under execution, we call it as a process. And thread is a lightweight process. And it is a part of a process. It's a part of process, or we can simply call it as a segment of process. That means each process may have a multiple threads. Okay, so each process may have multiple threads. So what's the reason behind creating these threads? Means it improves the CPU utilization. So by using these threads, improves CPU utilization. Similarly, it will increase the performance of application. So it will also increase the performance of application. See, I'll tell you the example of a process and a thread so that you will be understanding clearly. So process means, so opening web browser is a process. So we know web browser which will connect us to the internet. So that is called a process. And thread, for this process, opening tabs, multiple tabs in a browser. So in a browser we can open a multiple tabs, right? So that we call it as a thread, right? Similarly, you can also say one more example. So ATM machine, consider ATM machine as one process, and the services, whatever the services provided by ATM can be considered as a threads. That means, so withdrawal service and mini statement, and even deposit, if you are going with the deposit machines, deposit, right? Pin change, okay, mini statement, all these can be considered as a thread. That means a part of a process. So a process can be divided into a multiple threads. Okay, depends upon the application. So it may have a multiple threads or a single thread, right? And these threads are classified into two categories. So one is user level threads, and another one is kernel level threads. So user level threads will be created by the users, and the kernel level threads will be created by using the operating system, right? So which will be done by operating system, which will be done by users, right? So that's why we call it as a process is a task under the execution, and a thread is a lightweight process, okay, and it's a part of a process or a segment of a process, and each process may have a multiple threads. So execution of multiple threads, running of multiple threads is called as a multi-thread. Right? So each process will be having multiple threads, and running these multiple threads concurrently is called multi-threading. And running a different process simultaneously or continuously is called as a multitasking. Okay, multitasking and multi-threading. Multitasking means executing more than one task at a time, and multi-threading means executing more than one thread at a time. Right? See, I'll write here, and we'll go with a diagrammatic representation. So if you have any doubts, definitely those doubts will be get clarified once you see the image. Okay, once you see the image, it will be clarified. So running of multiple threads concurrently is called multi-threading. Multi-threading. So running multiple threads at a time. And running of a multiple task. A task is nothing but a process, right? Running of multiple tasks at a time is called multitasking. It's called a multitasking, right? See, so one type of thread is a user level thread, and created by user and not recognized. It is not recognized by the operating system. It will be recognized only by the user itself. And these are the kernel level threads. The second part is a kernel level threads created by OS, and these are recognized by operating system. Right? So these are the two categories of threads. Now we'll see what exactly the proper process looks and how exactly the thread looks. See. So let it be, this is a process. This is a process, and you can see example, let us take this is the threads. So a combination of threads is known as a process. Okay, process can be divided into multiple threads to run concurrently and to improve the performance and the synchronization. And see, if the process is having only one thread, this is known as single threaded process. So it is not mandatory that every process will be having a multiple threads, right? So depends upon the application. So the process may have a single thread or multiple threads, right? So if the process is having only one thread, that is called a single threaded process. Single threaded process. That means only one thread will be there. And if the process is having a multiple threads, thread 1, thread 2. So let it be. And this is the process. So if the process is having a multiple threads, so this is known as multi-threaded process. Multi-threaded process. The name itself indicates the process will be having multiple threads. And there are two more categories. So multiple processes. This is process 1 and this is process 2. And here we are having thread 1 and here also we are having thread 1. So multiple process having single thread in each process, right? So this is multiple process having single thread for each process. So there are multiple processes, and among these individual processes again we are having only one thread, right? So this is the third one. And the next one, having a multiple process, and in each process we are having a multiple threads. Let us take this one. So this is a process 1 and this is process 2, and this is thread 1 and this is thread 2. So thread 1, thread 2, right? So you can see here this is multiple process having multiple threads per each process having multiple threads. So 4 categories. So there are different categories, okay, different categories. And so by creating a multiple threads for a single process, so these threads will share the common memory and the data. of that particular process. Right? See, I'll write down here. One important point. So if a process is having a multiple threads, process having multiple threads, right? So what we are telling this one, this is called a multi-threaded process. Just now we have discussed it, right? So multi-threaded process. So if the process is having a multiple threads, so these threads shares same memory, because so all the threads belongs to the same process, so the memory will be shared among all the different threads, right? Same memory, and also data can be shared, and also the data will be shared. Okay, for example, in previous, just now we have seen the example that ATM machine is a process, so all the services will be comes under the threads, right? So all the services will be related to the single bank account. Okay, so that bank account, the account holder itself is a one process. So if two persons are having, if two persons are there, so one person is having one account and another person is having one more account. So these two accounts, we can consider them as a multiple process. And each process, for each account, we can generate the PIN, we can generate the mini statement, we can avail the service of withdrawal, we can avail the service of deposit. And also we can use all the services of these ATM for another account also. So such means all the threads of the same process will be sharing the same memory and same data. Right? And also switching between one thread to another thread is also very simple. Okay, so execution of one thread to another thread is also very simple, right? So that we call it as a context switching. Context switching. So execution or navigating from one thread to another thread, right? Context switching is very simple because both are having in the same memory. Both are available in the same memory, right? So it's very simple. Context switching is very simple. And also creation is also simple. So creating a thread is also very simple. Creating it is also very simple, and also inter-process threading is simple. So communication between one thread and another thread is also simple because all comes under the same process. So when compared to the process, inter-process threading, that means the communication between one thread and another thread is also very simple, right? So communication between threads is simple. Communication is simple, right? And also, once the work is completed, the termination of threads is also simple when compared to the process. So, termination is also simple, okay, when compared to the process. So, in order to improve the utilization and the resource allocation, so the process can be divided into multiple threads, and each thread can be executed concurrently, right? So, so that's why we call it as a thread as a lightweight process. Lightweight process. It's a part of the process. Process and thread. So the first one, the process definition is a task under execution by CPU is called a process. So that means all the processes will be executed by the processor itself. So here the processor means the CPU. And here the first one, a thread it's a lightweight process. That means it's also called as a part of a process. Okay, part of a process. So process itself is an alone, and here group of threads makes a process, or we can simply say that process will be divided into different threads. Next, so creation of process takes more time. This is only a comparison, right? So when compared to the thread, the creation of a process will consume more amount of time. And when compared to process, creation of a thread is simple. Creation of a thread is simple and it will take a less amount of time. Okay, it will take a less amount of time. And the fourth one, similar to the creation, termination is also somewhat complex in the process when compared to the thread. So once the process is completed, so termination of process also takes more time. When compared to the thread, right? When compared to the thread. Now, compared to process, termination of thread is simple. Termination of thread is simple and also it takes less amount of time. Right? Within a short time, So a thread can be terminated because it's a lightweight process. So in order to terminate the process, first the threads should be terminated, then only the process will be terminated. So that's why it takes more amount of time, and termination of a thread is very simple. Communication between threads, this is a process. Between the processes also takes more time. The communication, that means inter-process communication. If one process wants to communicate with other, so that inter-process communication it will take some more time, right? But here, communication between threads, right? Communication between threads takes less time. So the reason means, so process doesn't share the same memory. So one process will be in one memory, another process will be in another memory. So in order to retrieve the data from one memory to another memory, the time taken, right? But whereas thread, the same memory will be shared among different threads. So all the threads will be residing in the same memory. So automatically the communication between the threads will be very simple and very short time, because all the threads will be available in the same memory itself, right? So the next one, doesn't share memory. So among different processes, it doesn't share the memory. And here, memory is shared. So if memory is shared, automatically the data which is available in the memory will also be shared. Right? So doesn't share data among the processes, and data is shared among different threads. Right? Next, context switching. Coming to the context switching. Context switching means switching from one process to another process. So just now we have discussed that a process will be get executed by the CPU, and during that execution, if any other process arrives with a high priority, so automatically the CPU should handle that high priority process first. So in such case, so the switching will be done. Okay, one process will be moved to one state and the other process will be moved to another state, right? So switching between process to process is called a context switching, and here the context switching also somewhat complex. That means it also takes some time. Okay, so context switching. Context switching will take more time, and here context switching is simple. So this is also the main reason for this context switching becoming simple is the same memory is shared among different threads, right? So context switching. Then errors on process doesn't affect on other, but whereas here errors on threads affects on other. So here, so if one process gets an error, that means if it is in a blocking state, right? If it is blocked for some other reason, so it doesn't affect on other process. So immediately another process will comes into the CPU and it will start executing that particular process. But whereas in the threads, if one thread is in a blocking state, automatically all the remaining threads will also goes to that particular blocking state, because all the threads belongs to the same process. So if one process gets the error, that effect will be on the other processes. That means the impact will be on other processes, right? I mean other threads. And here that doesn't happen. So process are alone, right? Here we have seen process itself is an alone. Right? So if one process is affected, if one process is getting an heavy error, so that will not affect on other processes, right? So these are the major differences between the process and thread, right? So one more time I'm telling the example for you. So process means, so we can consider a browser, opening a browser in the system as a process, and opening the multiple tabs in the same browser will comes to the thread, right? So every process can have multiple threads, and concurrently executing the multiple threads is called multi-threading concept. So here the threads are classified into two categories. So one is user level threads and another one is a kernel level threads. So the major difference among these two is, so this is managed by user. It is managed by user. So that means the creation and everything will be done by the user. And here the kernel level, these threads are managed by operating system. And
So there is no support of OS. There will be no support of OS, and here, so there will be a support of OS in creation. But one thing you have to remember, so everything will be executed by the operating system, that means the kernel itself. So there should be a mapping. There should be a mapping of user level threads to kernel level threads. Kernel level threads in order to execute these user level threads. So as there is no support of OS, so there should be some sort of mapping between user level threads and kernel level threads. So there are different types of mapping, one-to-one, many-to-one, one-to-many, etc. So that we'll see in our next session. Now we'll see what exactly the differences between the user level threads and kernel level threads. See, so let us divide into two parts. So one is a user level, another one is a kernel level. So user level, and this side I'll write kernel level. Right? So the first difference, just now we have discussed that implemented by user. So these user level threads are implemented by the user itself. So the name itself indicates, right? So this is a thread, okay, and here also I write thread. Right? So here the kernel level threads were implemented by kernel, which is the heart of operating system, right? Next, context switching is easy and context switching is difficult. So this is just comparison, right? So when compared to the user level threads, so context switching will be different. So now what is meant by context switching? Already we have discussed about this context switching in our previous session while discussing about process and threads. So once again I will recall it. So context switching means, so if one process is being executed, either it may be a process or a thread, right? If one process or one thread is being executed, at the same time, if there is another process or thread which is having the highest priority, so then there should be a switching between one process to another process, right? So that type of transformation or switching, we call it as a context switching. So here, everything will be done by the user and there is no support of operating system. So that's the main reason why the context switching is easy in this user level threads. And here it will be somewhat difficult because it needs some operating system, that is a kernel system calls like that, right? Then multi-threading. So if it is a user level thread, multi-threading is not compatible. It's not compatible, right? So multi-threading is not compatible. So everything will be implemented like a single threaded process, right? And here multi-threading is compatible. So multi-threading means running multiple threads concurrently. Multi-threading is compatible. And next, implementation is easy and takes less time. Similarly, here comparison, the implementation is difficult or complicated only when comparison, right? And takes more time just with the comparison, right? So when compared to the user level threads, the implementation of kernel level threads is somewhat, it takes more time, right? Blocking operation means, so if one thread is in blocking state, all the remaining will be in blocking state, right? So blocking state means it will be waiting for some resources for IO operations, right? If the thread is waiting for IO operations or any resources, automatically the thread will be in the blocking operation. And coming to here, if any thread is in blocking state, then other threads will not be in blocking state. So alternate, it will move on to the another kernel and it will keep on executing, right? So there will be no stop for this kernel level threads because the threads will be executed by the operating system itself. So even though the user level threads, so these user level threads should be mapped with kernel level threads and there it will be executed. So if if one thread of this user level is blocked, that all the threads related to the same process will be in a blocking state.
Okay, so here we are saying that a complete process is divided into multiple threads. So among all those threads, if any one of the thread is in a blocking state, automatically all the remaining threads will become in a blocking state. The complete process will be in a blocking state. So that there doesn't happen in this kernel level mode, right? So in this kernel level thread, if one thread is in a blocking state, immediately the kernel will execute another thread. Okay, then. So these threads are recognized. These threads are recognized. Sorry, doesn't recognized by OS. That means OS doesn't recognize these user level threads. Okay, so these threads doesn't recognized by operating system. But here, these threads recognized by operating system because the kernel itself creates these threads and the kernel itself implements these threads. Right? So it doesn't recognize, and this is recognized by operating system. Next. The next difference, thread management is easy. So thread management is easy, and here thread management is difficult because so here there will be a thread library, and in this library there will be a code available for thread creation, destroy, data transfer, etc. So for all these things, the code will be available in this thread library. So obviously, if immediately the creation, destroy, and data transfer, everything will be maintained in this thread library of user level. So it will be very easy to create or to destroy or data transfer. But here, so here also the code will be shared. Okay, here also the code will be available, but there will be involvement of OS. So in order to create a thread, there will be some system calls. System calls will be there for creation, everything. Okay, for creation and everything, there will be some sort of system calls. So calling the system call, executing the system call. So involvement of OS will be there. So that's why the thread management is somewhat difficult. Thread management is creation of thread, destroying and data transfer, etc. Everything related to the thread, right? So here for everything there should be a system calls. Next. So hardware support is not required. Hardware support is not necessary or not required. But here, so we are these kernel level threads are executed by the kernel, so there should be the hardware support. So hardware support is required. Okay, then. So here runs on any operating system. So these threads, these user level threads will be running on any operating system because so everything will be available in the thread library. Okay, if you are having the thread library, so we can run these kernel level threads. User level threads. So that's why. So it runs on any operating system. But here, so kernel level threads will be created and running on kernel. That means related to the operating system. So this is operating system specific. So these are the operating system specific. So for every operating system, there will be a different kernel level threads, right? So operating system specific is the kernel level threads, right? So these are the major differences between the kernel level threads and user level threads, right? So only one thing. So these user level threads were created by the user. So that will also right. So created by the user in user space. So there will be different spaces which we have discussed in the earlier sessions, right? So kernel space and the user space. So these user level threads were created by the user in the user space, and here created by kernel in kernel space. So how they are created? So these user level threads are created with the help of code available in the thread library. But here, how these kernel level threads are created? These are created with the help of system calls available in the kernel, right? So that's why the thread management will be easy here, difficult there. Okay, so these are the major differences of user level threads and kernel level threads. So whatever it may be, so the operating system will execute the thread. So that's why the user threads should be mapped to the kernel level threads, and those threads should be being executed by the operating system. So for that, there will be a mapping, and there are different types of mapping, and that we'll discuss in our next session, the mapping of user level threads to kernel level threads. So in our previous sessions, we have discussed about threads, what is meant by a thread, what is meant by a process, and also we have seen the difference between a process and thread. And in our previous session, we have discussed about two different types of threads, that is a user level and a kernel level threads. Now we have to go through about these thread models. So here two questions: what is a thread model, and what's the reason behind to go to these thread models, right? So what is this thread models means? Mapping of user level threads to kernel level threads is called thread models. That means, so by using these thread models, we are going to map the user level threads to kernel level threads. So here the second question is, so what is the reason why we are mapping the user level threads to the kernel level threads? Because, so as we discussed in our previous session, the user level threads were created by user and not recognized by operating system, right? Whereas the kernel level threads created by operating system and recognized, okay, and recognized because they are created, right? Recognized. So whatever it may be, either process or a thread, it should be get executed by the process itself, right? So without recognizing these user level threads, how these threads will be executed by the CPU? So that's why we are going to map these user level threads to the kernel level threads in order to get executed by the CPU. So here the CPU is a processor, right? So everything should be executed by the processor. So only the processor can recognize the kernel level threads. They can't recognize the user level threads. So that's why we have to map the user level threads to the kernel level threads in order to execute these user level threads, right? And this mapping process is called the thread models. Okay, and these kernels, the kernels which are mapped to user level are known as virtual processors. Right? Actually, these kernels are being created by the operating system, and we are mapping the user level threads to these kernels. So these kernels, we call it as a virtual processors. Right? So these user level threads are being executed by the virtual processors. Now there are three different thread models to map user level threads to kernel level threads, or to execute the user level threads by the processor. The first model, many to one, and one to one, and many to many. So simply we can call it as m to 1, and this is 1 to 1, and this is m to n. So these are the three different models which are used to map the user level threads to kernel level threads. So we'll see one by one. Coming to the many to one. So in this many to one, so there are different threads, right? So thread 1, thread 2, thread 3, right? So this is a user space, and this one will be the kernel space. Let it be some K1. So these threads are being mapped to a single kernel. All these threads will be mapped to the single kernel. So this type of model, we call it as a many to one. That means many user level threads will be mapped to the single kernel. So everything is fine, but there is a disadvantage of using this model. What is the disadvantage? If any one of the thread is waiting for any IO operation, and if it is moving towards the blocking state, immediately the complete process will be in the blocking state. So no other thread will be executed by the kernel, because all the three threads are being mapped to the kernel. So if any one is in a blocking state, so the remaining threads have to wait until the the thread which is being blocked should be being executed until it completes its execution. Right? That's the main drawback, because all the threads mapping towards the same kernel itself. So in order to overcome this one, we are moving on with 1 to 1. So in this model, one thread will be associated with a one kernel, right? So here we are having a multiple virtual processors. So hope you understood the disadvantage of using the first model, that is many to one. So if any one, mapping all the threads to the single kernel. So only if any one of the thread is in blocking state, so all the remaining threads have to be in waiting state until it completes its execution, because all have mapped to the same kernel. And now see the next one, 1 to 1. That means in order to overcome that one, so we are mapping each and every thread are mapped to each and every kernel. Right? So every thread will be map it to each and every kernel. So the problem has been solved. If T1 is in a blocking state for waiting for any IO operation, immediately T2 can't wait. It need not to wait, right? So T2 will be executed by another virtual processor. So K2, right? Kernel. And similarly T3 will be executed with one more kernel, right? So it overcomes the disadvantage of first model, that is many to one. But here in this model, again we are having some disadvantage. What is the disadvantage? So the number of threads are being increased, automatically the number of kernels are also being created, right? So we have to create a more number of kernels. So if a process is having some 10 threads, so there should be 10 kernels, because one thread will be associated with only one kernel. So that is the main drawback, because so creating more number of kernels automatically reduces the performance of processor. So the kernel will be created by the CPU by using some system calls, right? So creating more kernels automatically reduces the performance of the processor. So that is the main drawback. So it overcomes the drawback of first model, that means the waiting state, right? But here there is one more drawback, that is we have to create a more number of virtual processors. So in order to overcome the second disadvantage, that's a disadvantage of second model, we are moving with the third one, which is an efficient one. Here the mapping is between many to many. So m number of threads will be associated with n number of kernels. So there will be a pool of kernels. For example, there are 10 threads. So we can create a 5 kernels and 10 threads will be mapped to the 5 kernels. Right? So we need not create a 10 kernels each for one thread, right? So here, if 10 threads are there, we can create some less than n kernels, right? So if there are m threads, then automatically we can create less than m kernels. So automatically that avoids the disadvantage of the first one. That means if any one of the process is in a waiting state, automatically the next process can continue its execution with, associating with the another kernel. And the second one, so it is not necessary to create a more number of kernels. Some sort of kernels can be used and we can assign all the threads to those kernels itself. Right? So these two disadvantages of both the models can be overcome in this third model. So this will be the efficient one. So here, let it be. So K1, K2. Okay. So like this we can assign the kernels. Okay, we can map the threads to the kernels. So it is not necessary to map every thread to every kernel. Right? So this is how the kernel, user level threads are being executed by the operating system. First they have to be mapped to the kernel threads, and then the operating system will execute the kernel threads, because the operating system will not recognize the user level threads. So operating system will only recognize the kernel level threads. So that's why we are mapping user level threads to the kernel level threads. And this process of mapping is called model. So we are having the three models, many to one, one to one, and many to many. Process synchronization. So today we'll see the introduction to this process synchronization and what's the reason why we are moving on to this process synchronization. And in our next session we'll see different examples so that may require these process synchronizations, right? So in our previous sessions we have discussed about the process and the threads, and a process can have multiple threads and there are different types of threads, kernel threads and user threads. So at a time multiple threads can be implemented concurrently, that we call it as a multi-threading, right? So here if two processes, here there are two types of process mainly. So one is independent process, and the second one is cooperative process. So coming to the independent process, the name itself indicates, so if one process is being executed, so that all the resources required by that process will be bind towards that process only. So that means the execution of one process doesn't affect the execution of another process. So once the process completes its execution, then only the resources will be released and those resources will be associated with another process. So that's why we call it as an independent process. So if one process execution doesn't affect the execution of another process, then we call it as an independent process. And here, no shared memory, right? So once it was executed, then only it will move on to the next process. The execution of the next process will be started. But that doesn't happen in the cooperative process. So in this cooperative process, one process execution affects the execution of another process, because here in this cooperative process, the memory will be shared memory. So one memory will be shared among different processes, right? So the first point, one process
execution, one process execution affects the execution of another process, and here there will be a shared memory. Okay, the memory will be shared memory. So here in this particular cooperative process, so multiple processes will share the common memory. So if multiple processes shares the common memory, then the problem occurs with the data. So there might be a chance of getting inconsistent data. So in order to avoid that inconsistent data and to maintain the data consistent, we have to follow this process synchronization. And here we are not using any shared memory, so here the process synchronization doesn't require, right? But in the cooperative process, the process synchronization must be there, right? So our problem with cooperative processes, right? So here multiple processes shares a common memory, So let me tell you one simple example. See, common memory. So let it be, this is a memory, so which is having some value, some variable, a common variable, some a is equal to some 10. So it is associated with the different processes. So let it be P1, P2, P3. So all the three processes want to share the same memory, common memory. And P1 wants to update A with 1, P2 wants to update A with 2, P3 wants to update A with -3. Okay, so A plus 1, A plus 2, A minus 3. If all the three processes share the same memory, if all the three are doing the same operation at a time, what happens here? So if P1 is started executing, P1 will be having, for example, here I will go with the 1. So P1 will be having, what is the value of this one? After executing P1, 11, 12, 9, right? So all the three processes are sharing the common memory, and all the three processes are doing the same job at a time, at once, right? So according to the process for P1, A value is 11, according to P2, A value is 12, according to P3, A value is 9, right? So which one is the correct result? Which one will be the correct result? Because A is the common variable which is being shared among all the different processes. So here P1 tells that, so P1 itself is a correct value. P2 says that P2 itself is the correct value. P3 says that P3 itself is the correct value. So some sort of race is going on, telling that the process is having the correct result. So such a situation is called as race condition. So if there is in particular this cooperative process, so there is an inconsistency of data. So according to one process, the value of A is changed, right? So this is called inconsistent data. So that should not happen, right? That should not happen. So we have to make this one as a consistent data. So same value should be available for all the three processes. So that for that consistent data, making of this one to consistent, we are moving with process synchronization. So where some locking system will be there, if one process is executing the shared memory, so automatically the remaining process have to wait until the process completes its execution. So then the common variable will be having the consistent data. The shared memory the memory is shared among different processes, so with a consistent data, right? So in such situations, we are moving with this process synchronization. So the main problem with this type of process, cooperative process. Okay, so let us stop here. Hope you understood this race condition because of inconsistent data. And in our next session, we'll see about a few problems so that may require this process synchronization. Producer, consumer problem. So actually in our previous session, we are discussing about the process synchronization. So we have seen different types of processes, and in that, particularly if you are using the cooperative process, then it requires the process synchronization, because in cooperative process, the memory will be shared among different processes so that the data will be inconsistent. So that's why we require some process synchronization in cooperative processes. So one such problem which requires the process synchronization is the producer-consumer problem. So here we are having two processes. So let me explain this one. We are having two processes. One is called a producer. So produces a product
and place it in a buffer. We call it as a memory, right? We call it as a memory. So the work of a producer is always produces the products and place those products in a buffer. That we call it as a memory. And the second process is a consumer. So the name itself indicates the consumer consumes the product which was placed in a buffer. We call it as a memory by the producer. So actually, the consumer work is to consume the products from the buffer. So it takes the product from the buffer and consumes it, right? So here both the processes are working with the buffer. So this is a shared memory, right? So both are working with the buffers. So let us consider this one. This is a buffer, or we can call it as a memory. So here, see, these are all products produced by the producer, and these are all products consumed by consumer. Products placed by producer, right? So producer will keep on placing the products in the buffer, and from the same buffer products will be consumed by the consumer. So this is the shared memory. So both are using the same memory, right? So here there are two conditions that the producer and the consumer need to satisfy before placing the products into the buffer or consuming the products from the buffer, right? So what is the condition that should be satisfied by the producer? I write the condition here. So two conditions, one for producer and another should be followed by the consumer. So condition at producer side. So what's the condition? So before placing the product into the buffer, producer have to check whether the buffer is full or not. So if buffer is full, the producer can't place the products into the buffer. So there should be some space in the buffer to place the product into the memory. So before placing a product into a buffer, producer have to check buffer is not full. If buffer is full, the producer can't place the product into the buffer, right? So here it is a memory, so there will be some sort of memory allocated for this particular buffer. So if buffer is full, that means the memory is full, so we can't place the products into the buffer. So producer have to wait until some sort of memory is released. That means some sort of products should be consumed by the consumer. So similarly, so this is a condition at the producer side, right? Next, condition need to check at consumer side. So obviously, so before consuming the product, before requesting the product from the memory, so this consumer have to check whether buffer is not empty. So if buffer is empty, that implies there is no product in the buffer. So how the consumer can consume the product from the buffer? So during the consumption, the consumer have to check whether the buffer is not empty. So if it is empty, the consumer can't consume the products, right? So before consuming product from buffer, consumer have to check buffer is not empty. So if buffer is empty, the consumer can't get the product from the buffer, right? So in order to access this products from the buffer, so one count will be maintained here. So count is nothing but shared variable, right? So count is nothing but shared variable. So in order to check whether buffer is empty or buffer is full, so for that purpose, this count variable will be used. And in this producer side, whenever the producer places the product, the count will be incremented. At the consumer side, whenever one product is consumed from the buffer, the count will be decremented. right? So this count is nothing but a shared variable in order to check the size of the buffer, whether the buffer is full or empty, whether the products are available in the buffer to consume or whether the buffer is not, not able to place the products into the buffer. For that purpose, we are using this count. Count is nothing but a normal integer variable, so which is nothing but a shared variable that will be shared among both the product producer and the consumer. So whenever the producer places the product into the buffer, immediately the count will be incremented by 1 by the producer. So whenever the consumer consumes the product from the buffer, immediately the count will be decremented by the consumer. Right? See, for example, you can observe here. Let it be, this is a memory. This is a memory. Okay, so this is a producer side and this is a consumer side. What happens? Initially the count is 0. Initially the count is 0 because that means the buffer memory is empty. Right? So the count represents the number of products available in the buffer. Number of products available in the buffer. So the producer first check with the count. So whether count is not equal to buffer size. Buffer size. Whether count not equal to buffer size. If it is not equal to buffer size, then place the product into the buffer. Okay, so place the product into buffer. Place the product into buffer. And immediately increment the count value. So the count will be incremented. Count will be incremented. Right? So you can observe here, so these steps will be continuously executed. Right? These steps are continuously executed because that is a never-ending process. That's a never-ending process. So producer always produces the product. Okay, and consumer always consumes the product by the from the memory, right? So this happens at the producer side. If it satisfies all the things, one product will be updated here. And again, if this condition is true, again another product will be included. Next, if again condition, another product. Like that, the products will be sent to the buffer. And here, whenever, so first condition we have to check at the consumer side whether the buffer size is empty. That means whether the count not equal to 0. If the count is not equal to 0, okay, if count is not equal to 0, if count is 0, that implies that there is no products in the memory. So count means number of products, right? So I write here. So I write here. See, count. Count means number of products in buffer. Number of products in buffer. So if count is not equal to 0, that implies there are some products available in the buffer. So then immediately, see, the products will be consumed. The products will be consumed. So consume the product will be consumed, and immediately the count value will be decremented by 1. The count value will be decremented by 1, right? So whenever there is a not equal to 0, one product will be consumed. Similarly, the same process will be continued. So this is also a never-ending process. This is also a never-ending process. So always the producer produces the product and always the consumer consumes the product, right? So hope you understood. So now we'll see the same concept. So this is a normal logic. Okay, we'll see the same logic implementing by the processor. So because in the processor everything will be executed with help of registers, right? So we'll write the same thing. We'll write the same thing in the register format. Okay, in the registers format. See, producer. In the producer side, I write instruction 1. What is the instruction 1? So R1 will be initialized to count. So whatever the count, that means the number of products which are available in the memory will be initialized to register 1. And immediately, whenever the producer produces a product, that means applies a product in the this one, that means a memory, R1 will be incremented. So R1 is equal to R1 plus 1. So 1, it will be incremented to 1. Immediately, we have to update that, right? So the count should be updated to R1. The count should be updated to R1, right? Next, let us take about the consumer. Let us take about the consumer. So let us take the instruction 4. Instruction 4, here, the same memory, so register 2. The count will be initialized to register 2, and I5, immediately whenever one product is consumed, the R2 must be decremented with 1, and I6, we have to update the count, right? So the count is now R2. After decrementing, count will be R2, right? Now, for example, if processor executes the instructions, right? If processor executes the instructions, I'll erase this one. See, if the processor executes the instruction, so I'll write here instruction execution, right? So let us assume the count of buffer is some 4. That means there are some 4 products available in the memory. Okay, four products are available in the memory. So first, let us write out instruction 1. So what is instruction 1? R1 is equal to count, which is initialized with 4. So R1 is having 4. So immediately after placing the product, a new product produced by the producer into the memory, the instruction 2, if let us suppose instruction 2, so R1, right? So R1 is updated with 1, that implies R1 now will be 5. R1 now will be 5. Next, after updation, let us assume I4 is being executed. So another process. So because at the same time, two processors are sharing the same memory, two processes are sharing the same shared variables, right? So that's why let us assume I4 is executed. Okay, in priority, I4 is executed. So I4 is executed. So R2 is equal to count. So what is the count value here? The count value is 4 because not yet updated by I2. After I2, count is not updated. So count value is 4. So R2, the value will be 4. And then immediately I5 is executed. So R2 is equal to R2 minus 1. So which is nothing but R2 is equal to 3. Next, I6 is executed, which is nothing but count is equal to R2. So now the count value is 3. Then I3 is executed. So count is equal to R1. So where the count will be 5. Count will be 5. So actually what happens here? So whenever the count is 4, whenever producer produces a product, then count will be 5. And whenever consumer consumes the product, the count will be 4. Right? So whenever the product is producer places the product into the buffer, the count will be 5. Consumer consumes the product, count will be 4. So initially let us take some 4 products are available in the memory. So after one production and one consumption, the count will be remains 4. Right? But what happens in this case? So two processes are sharing the same memory and executing parallelly. Right? So here we are having the two values for a count. Count is equal to 3 and count is equal to 5. So there are two different values. So this is called data inconsistent. Data inconsistent. Right? Now, according to producer, the count value is 5. According to the consumer, the count value is 3. So there is a dilemma. So which one is the correct one? So this type of condition is called a race condition. This type of condition we call it as a race condition. So both the processors are in a race to justify the correct value. The count is 3 according to consumer, count is 5 according to the producer. So this is called a race condition, and in this process we are having the data inconsistent. So such a type of process will require the process synchronization. Process synchronization. So this is one major problem, one among different problems. There are different problems. So this is one among different problems where we require this process synchronization. Right? So hope you understood this is a producer-consumer problem. Right? So two processes, there is a producer and a consumer. So after calculating or after executing the different instructions from the producer and the consumer, so we are having a different values. That means the data inconsistent. Right? So to avoid this one, so we will have to use this process synchronization. Critical section problem. So in our previous session, we have discussed about the process synchronization and why we require the process synchronization. So if there are cooperative processes, so they must be executed concurrently and they have to share the common resources, the common variable, right? So in such cases, there might be a chance of getting a race condition. So the data will be inconsistent. So that's why we require the process synchronization. So in order to avoid the race condition, such race condition, one solution or one problem is this critical section problem. So here, a critical section is a code segment. It is a code segment. So which allows only one process to execute. Right? So if two processes want to execute, if one process is being executed, the another process have to wait until the first process completes its execution. Right? So this is a shared memory. Right? This is a shared memory. So if one process, see, if there are two processes, if one process is executing and the another process P2 have to wait until P1 completes its execution. That means the P1, after completion of its execution, the P1 deallocates all the resources bounded with that process, and then only the P2 will be taking over the control of processor. So this type of thing, we call it as a critical section problem, right? So here, see, this is a code segment, as I have said, that critical section, and this particular section is having the three things. One is the entry section, and this is a critical section,
and this is an exit section. Right? Critical entry section, critical section, and exit section. So if one process is in a critical section, no other process will be allowed to execute. Right? So the entry section will be acting as a gate, right, to enter the process. So if one process enters into this critical section, the entry will be stopped for another process. Right? If there are any other process wants to get executed, so that those process will be halted or waited by this entry section. And whenever a process completes its execution, immediately the exit section will release or deallocate resources bounded with that particular process. Then only the entry section will will allow the another process to enter into the critical section. For example, let us take P1 and P2. So P1 and P2 are the two, and P3. There are three processes. Okay, three processes, they need to get executed. So here the shared memory. In this shared memory, we can have variables, functions, and any other resources. Right? Any other resources. So if the process wants to get executed, all the processes can access the shared memory. Either they can access the variables, functions, or other resources, and all these are common to all the processes. So if P1 enters into this critical section, the P2 and P3 will be in a waiting section. So once it was completed, so whenever the P1 get to the exit, then P2 will enter into the critical section. So entry section is used to stop other processes to enter into the critical section until this critical section becomes free. So whenever the processes get executed in the critical section, and whenever the process completes its execution, so the process will come to the exit section where all the resources and the shared memory will be released for that particular process. Then only the another process will be allowed to enter into this critical section. So this is how the processes will be get executed. The best example for this problem is our ATM. So we all know about this ATM, right? So anytime we can go to the ATM machines and we can get the amount, right? So at a time only one person can enter into the ATM, and once if one person is availing the services, the another person have to wait until he or she completes its execution, right? So once the person inside the ATM have completed the services, so when he comes out, then only the second person will be allowed to use the services in the ATM machine, right? So that is one example. Another example, availing the printer service in a network. So if there is a network, we are having a lot of systems available in the network, and we are having only one printer, which is shared among all the different computers. So at a time, only one print can be done by the printer, right? So if system 1 gives a print, and at the same time, if system 2 also gives a print, system 2 will be in the waiting state until the system 1 prints, whatever the job given by the system 1 completes its execution. So once the task given by the system 1 has been completed, then system 2 process will be get executed. So this is the example. That means at a time only one process can complete its execution, and until it completes its execution, all the remaining processes will be in the waiting state. Right? Now the solution is the process should satisfy the three conditions in order to get in this critical section problem. So what are the three conditions? So first condition is a mutual exclusion. Mutual exclusion. So every process should satisfy the three concepts. So whenever these three conditions are being satisfied, that means there is a synchronization. So there will be no race condition. So in our previous example, we have seen the two processes are sharing the same memory. So the data will be inconsistent. So we have seen some 3 instructions for producer and 3 instructions for consumer. So executing the instructions may give the inconsistent data, right? So that is why we are getting some race conditions, right? So here, if the process obeys this mutual exclusion, and the remaining two processes, that means the remaining two conditions like progress and bounded wait, so automatically there is a overcome of race condition. There will be no question of race condition. The data will be always consistent. So what is a mutual exclusion? So mutual exclusion means, so at a time, only one process is being executed in critical section. Right? So if one process is in the critical section, the other process have to wait. That is called a mutual exclusion. And the second condition, progress. So progress means if any one of the process doesn't want to execute in the critical section, it have to allow other process to enter the critical section, and other process need to execute the process. Right? So that is called a progress. So if one process doesn't require critical section, that process should not stop the other process to get executed. So if one process doesn't need the critical section, it should not stop the other process to take the control of this critical section, right? So we have to allow other process to complete its execution, right? And that's the second one. And the third one, bounded wait. Bounded wait. So actually this bounded wait means, so every process should have some boundary of waiting time, right? So there must be some prediction, there should be some prediction how much time the process needs to be get completed its execution, right? So bounded waiting. So every process have to complete its execution before its predicted waiting time. So every process requires some sort of amount, some sort of time to complete its execution, right? So we have to predict that time, waiting time, right? So every process should complete its execution before its predicted waiting time, right? So this mainly, this condition, if any process fails this condition, automatically there will be becoming a starvation problem. That means the other process which is waiting for the critical section will be keep on waiting for its execution. So whatever the process which is available in the critical section doesn't complete its execution, and still the remaining processes will be in a waiting state. So that should not happen. So after some amount of time, so the process should give the control to the another process to complete its execution. So there should be some limitation on waiting time. So the process which is availing the critical section should complete its execution before that particular boundary of waiting time. So if any process satisfies all these three conditions, then there is no question of race condition. So automatically the process synchronization will be possible, right? And the data will also be consistent. And which process, for example, we have said that there are three processes, and this is a critical section, and one process is being executed, and P2 and P3 are being waiting for the critical section. So which process will be get executed? That will be taken care by the scheduling algorithms. So process scheduling algorithm will take care about which process is having the priority and which process should be executed in the critical section, right? So this also will taken by the scheduling algorithms, right? So the name itself indicates the scheduling means which process should be executed first and which process should be executed next. The order of executing the processes based upon the priority and other requirements, right? So if any process satisfies these three conditions, we can say there will be no race condition. Automatically the data will also be in a consistent. So this is called the critical section problem. So only one point at a time, only one process should use this critical section. So one process can share the memory, we can access the shared memory. So other process should be wait until the process completes its execution. So what is this semaphore? So the semaphore is mainly used as an integer variable to prevent the race condition, right? So semaphore, it is an integer variable which can be used as a shared variable. So which can be used as a shared variable to prevent race condition. So actually in our previous session we have discussed about the thread concept, a process concept, and we have seen the process synchronization, right? So there we have seen the critical section problem. So only one process should be entered into the critical section so that other process need to wait for its execution until the critical section is available, right? So that we have seen in our previous session, and that in order to solve the critical section, so the three conditions should be satisfied. That one is a mutual exclusion. So mutual exclusion means at a time only one process should complete its execution, right? So for that purpose, we'll use a semaphore as a solution to prevent the race condition. So race condition means if two processes are executing concurrently, there might be a chance of getting the inconsistency on data. So that we call it as a race condition. Both the process will be having a different results, and both the process will be treating that their own result will be the correct one, right? So such type of thing we call it as a race condition. So in order to prevent that race condition, we'll use a semaphore as an integer variable which can be used as a shared variable. So actually, if you are using the process synchronization, if you are using some multiple processes which are being executed continuously, some shared resources will be some sort of resources will be shared between both the process, right? So those resources may be the variables or functions or any other resources, right? So this integer variable will be acting as a shared variable among the different processes in order to prevent the race condition. And see here, this semaphore is implemented with the help of two procedures. So see, semaphore is implemented using two procedures. So first one is a wait procedure and the second one is a signal procedure. So this will tell the process whether it is able to enter into the critical section or it has to wait for some time. So for that purpose we are going to use this wait and signal in order to implement the semaphore. And see, both are atomic procedures. So here the term atomic procedures means until it completes its execution, it should not be interrupted by any other process. Right? So if the wait procedure is being executed by the process, so until the process completes its wait procedure, no other process should interrupt this one. So after successful completion of all the instructions available in the wait, then only the next process will be being executed. So that's why we call it as an atomic procedure. So no process will interrupt, right? So let us take the wait procedure. So in this wait procedure, it mainly tells that whether the process is able to use the critical section or not. So it gives the status for the process to enter into critical section, right? And if the semaphore value is greater than or equal to 1, then it indicates process can evade the critical section. So the process can enter into the critical section. That means, so as we said that the semaphore is an integer variable, right? So integer variable. If that integer variable is a greater than or equal to 1, that implies the critical section is available for the process. So a process can enter into the critical section. So whenever the process enters into the critical section, the semaphore value will be decremented. So immediately what happens? So semaphore value will be decremented. So just for understanding, let us assume that semaphore value is nothing but the number of resources. Okay, so just for understanding, semaphore value is a number of resources. So if there are any resources available, that means if the semaphore value is 1, that implies 1 resource is available. So automatically the process can utilize that particular resource, right? So in such a way, if the semaphore value is greater than or equal to 1, that implies some sort of resources are available and that can be utilized by some other process. So a process can avail the resources which are available by entering into the critical section. Immediately after entering into the critical section, immediately the semaphore value should be decremented. So if the semaphore value is not decremented, that implies there are still the resource is available, right? It indicates that still the resource is available, but the resource is allocated to the process, so we have to decrement the value, right? So the thing, and the next point, if it is 0, if the semaphore value is 0, then it indicates some process is in critical section. So no other process should be allowed. No other process should be allowed into critical section. Right? So if the semaphore value is 0, that implies, so just now we have seen the semaphore value is equal to number of resources. If the number of resources are 0, that implies all the resources have been availed by other processes. So the current process should wait until it gets the resources. Right? So if you write the same procedure with the code, so the code will be wait of semaphore and write down the loop while s less than or equal to 0. See, while s less than or equal to 0, semicolon. That means it will be inside this particular loop until s is greater than 1. I mean greater than 0. Right? So if it is s is less than 0, it will wait in this particular loop itself. Immediately the s value will be decremented. So that means if s is greater than 0, that means if s is equal to 1, so automatically it will be decremented. It will be allocated by allocated to other process, and that will be decremented.
right? So this is the wait. This is a wait procedure. Then signal. The second procedure is a signal procedure. Second procedure is a signal procedure. So it's a very simple. So whenever a process completes its execution in the critical section, whenever it comes out of the critical section, immediately the semaphore value will be incremented, right? So after completion of the process, in critical section, immediately the semaphore value will be incremented. Semaphore value will be incremented. Value will be incremented. So immediately signal of yes, that's a semaphore, yes plus plus. Immediately after completion of the process execution, immediately the semaphore value will be incremented, so it becomes greater than 0. That means some sort of resources are deallocated from the process and they are available for the another process. So immediately yes is shared among different process. Okay, so in the wait signal we are using the S, and in the signal we are using the semaphore. Here we are using the decrement, and here we are using the increment. So whenever it is a less than or equal to 0, it will wait until the resource is available, and here automatically S plus plus. Once the process have been completed its execution, immediately S will be incremented automatically. If S is implemented, automatically S will be greater than 0. If S is greater than 0, the resource is available, so some other process can avail the resource. Immediately it will be allocated for another process, and S will be decremented. So this is how the critical section problem will be solved with the help of wait and signal procedures. And both the procedures are the atomic procedures. That means after completion, successful completion of one procedure, then only the second procedure should be executed. So no process should interrupt this one. Right? Now we'll see the types of procedures. Types of semaphores. What are the different types of semaphores? Types of semaphores. So there are mainly two types of semaphores. One is binary semaphore. So where the value is either 0 or 1, and if value is 1 implies process can avail critical section, and if value is 0 implies process have to wait to execute. That means some other process is being executed, so it has to wait. Right? And the second category of semaphore is a counting semaphore. So here it will be a non-negative value, non-negative integer, and will have more numbers, and this type of semaphores are mainly used for using the pool of resources. There are multiple resources, right? So it is used for efficient use of multiple resources. If there are more than one resource, then we can use this counting semaphore. So these two are different types of semaphores: binary semaphore as well as the counting semaphore. So hope you understood this one. So let's see the advantages of semaphore. So first advantage, we have discussed it just now. We are using the semaphore to prevent the race condition. In order to prevent the race condition. So to prevent race condition. And the second one, to prevent the deadlocks. That means if one resource is allocated to one process and another process is also waiting for the same resource, so that's a never-ending process. That we call it as a deadlock. So in our further sessions, we will discuss about the deadlocks, right? So in order to prevent the deadlocks, also we use this semaphore, and to implement mutual exclusion, which is one condition need to be satisfied for critical section problem. So to implement mutual exclusion, and another one, efficient use of resources. Just now we have discussed it. Efficient use of resources. For all these reasons, we are going with the semaphores, which is an integer value. Now, what are the disadvantages? So obviously, some sort of disadvantages will be there. So the first main disadvantage is we need to use this semaphore perfectly. So if you are unable to use this semaphore perfectly, automatically there might be a chance of getting a deadlock situation.
So improper usage of semaphore may lead to deadlock situation. In our further sessions, we'll see about the deadlock. What exactly the deadlock, and also more number of semaphores. If you are using more number of semaphores, may lead to high maintenance and confusion. Right? More number of semaphores, that may lead to high maintenance and difficult to debug if any synchronization occurs. So mainly we are using these semaphores for a critical section problem, and why we are using the critical section to overcome the process synchronization problem, so which we have seen for the concurrent processes, right? So in order difficult to debug if any synchronization problem occurs, right? So these are a few advantages and disadvantages of using semaphores, right? Deadlocks. So in our previous session we have seen the process synchronization, right? So for the concurrent process, in order to use the shared memory, in order to maintain the data consistency, so we are moving towards the process synchronization, and then we have seen the semaphores, right? So next we'll see the deadlocks. So before going to the deadlocks, let us discuss a few points that if any process wants to get executed, it may require some resources, right? So the process will utilize those resources to execute itself. So who will allocate the resources? The operating system will allocate the resources to the processes based upon their availability. So if the resource is not available, then the process have to wait until it gets the resource. So without the resource, the process will not get executed, right? So once the work done by the process, automatically the resources which are being allocated to that process will be released. So these is the steps we need to remember while executing any process, right? So first one, so process may require resources to complete its execution. That's the first one, right? Next, operating system will allocate resources to the processes. If resources are not available, then the process have to wait until it gets the required resources. So without the resources, the process will not get executed. If it requires any resource, so it have to wait until it gets the resources, and all those resources will be allocated by the operating system itself. And the next one, once the process completes its execution, resources allocated to that process should be released. That means whatever the resources which are allocated for that particular process should be released, deallocated, so that those resources may be used by another process. So the operating system immediately, the operating system will find out the resources which are available, and the operating system will allocate those resources to the corresponding processes which are requiring these resources, right? So this is the steps going on, right? Now, what is a deadlock? So a deadlock is a situation. So it is a situation where one or more processes are being executed and waiting for the resources which are being allocated for another process, right? See, I'll explain. So this is a situation, a deadlock. It is a situation where one or more processes are waiting for the resources which are allocated to some other processes, right? So example, let us explain you with an example so that you can understand what exactly the deadlock. So let us consider two processes, P1, P2. There are two processes and there are two resources. there are two resources, we call it as R1, R2. Okay, two processes and two resources. So if P1 requires, R1 is allocated to P1. So I write here, R1 is allocated to P1, right? So R1, which is being allocated to P1. Similarly, R2 is allocated to P2. So let us take here R2, which is being allocated to P2, right? So two processes and two resources. So if R1 is allocated to P1, that means the resource 1 is allocated to process 1 to complete its execution. Similarly, R2, resource 2 is allocated to process 2 to complete its execution. So in order to complete the execution of P1, if it requires R2, right? See, I'll write here. If P1 requires R2 for its completion, which is allocated to P2. That means P1 is requesting for R2 to complete its execution. That means P1 requires, already R1 is allocated to P1, but in order to complete its execution, P1 requesting the resource R2. But here what happens? R2 is allocated to P2. So P1 will be in a waiting state. Okay, so which is allocated to P2. And similarly, the second point, if P2 requires R1 for its execution, which is allocated to P1. So P2 requires R1 in order to complete its execution. P2 requires R1 to complete its execution, which is allocated to P1. So P2 will be also in the waiting state. So because in order to complete the execution of P1, it requires R2. R2 is already allocated for P2. So P1 has to wait until P2 releases the R2. So P2 will release the resource 2 whenever it completes its execution. But here, if the situation is like this, that means if P2 requires R1 to complete its execution, which is allocated to P1. So P2 will be in the waiting state until it receives the R1, which has to be released by P1. So here you can observe the situation. P1 will release R1 only after its execution. P2 will release R2 only after its completion of execution. But P2 requires R1, P1 requires R2. So unless the P1 gets the R2, P1 will not complete its execution. Until P2 gets R1, P2 doesn't complete its execution. So this chain process, so here in this situation, P1 and P2 will be in the block state. So both will be in the waiting state. So this is a never ending process. So such a situation, we call it as a deadlock. Such a situation, we call it as a deadlock situation. Right? So it's a situation where one or more processes are waiting for the resources. So here P2 is waiting for R1, P1 is waiting for R2, which are allocated to some other process. So R1 is allocated to P1, R2 is allocated to P2. So this type of situation, we call it as a deadlock situation. Deadlock situation. So for, just for understanding, I will give one example. So traffic, right? See, let us take, this is a so there is a center, okay, where this is a center, right? So if car from this side wants to move here, see, okay, and car moves here, and car gets here, and car gets here. So you can imagine this situation. So this car wants to move this side. So when it will move, whenever this car will move towards the front, it will move. So this is stuck. This car is stuck. This car is stuck. So such a type of situation is called as a deadlock situation. Such type of situation, we call it as a deadlock situation. So here, what happens? All the cars will be in the waiting state. This is a never-ending process. Okay. So such a situation, we call it as a deadlocks. Such situation, we call it as a deadlocks. And now we'll see what are the necessary conditions that to be satisfied if the situation is a deadlock. That gives the deadlock situation, that makes the deadlock situation, right? So conditions for a deadlock. What are the conditions for deadlock? So there are mainly 4 conditions for a deadlock situation. So conditions for deadlocks. So first one is a mutual exclusion. Mutual exclusion. So this already we have discussed in our previous sessions. Mutual exclusion means, so if one or more process wants to share the resources
at a time only one process should share it, right? So if one process is allocated, I mean one resource is allocated to one process, so other process have to wait until completes its execution. That we call it as a mutual exclusion. So only one process can be executed or utilize the resources. So only one process should utilize the resources. So another process have to wait, right? So this is one reason why we are getting the deadlock, because if one process, so for example, R1 is allocated to P1, in our previous example, R1 is allocated to P1 and P2 have to wait until the P1 releases the R1. So that we call it as a mutual exclusion. The next one, hold and wait. This hold and wait means one process can hold multiple resources and again it can wait for any other resources, right? So one process can be availing multiple resources. So a process can hold multiple resources and still it can wait for another resource. So if the process want to release the resource, it should get another resource and then only it can complete the process and it can release the resources. So this is the second condition why we are getting these deadlock situations. And the third one, no preemption. So here no preemption means, so no interruption. So the process have to release the resources only after the completion. So the user or the operating system can't release the process by force. I mean can't release the resources from the process by force, right? So the resources allocated to the process can't be released by force. Process itself have to release the resources. Only the process can deallocate the resources. Okay, and the fourth condition, circular wait. So here the processes will be in a waiting state in a circular fashion to allocate, I mean to utilize the resources. So processes will be waiting in a circular manner to utilize the resources. For example, let us take this one, process P1 and resource R1 and resource R2 and process P2. So already R1 is allocated to P and R2 is allocated to P2, and so you can observe P1 is requesting for R2 and P2 is requesting for R1. So you can see the last process is allocated, the last process is requesting the resource which is allocated for the first process. So this is called a cyclic manner. Okay, cyclic manner. So you can observe this is the last process, right? So this is the last process. So last process is requesting the resource which is allocated to the first process. So that doesn't happen. That never happens, right? So because process 1 is already waiting for R2, which is allocated for P2. So these are the four conditions: the mutual exclusion, hold and wait, non-preemption, and circular wait. So these are the four conditions. So that may give the deadlock situation. Deadlock detection. So in order to detect the deadlock, whether the process leading to the deadlock situation, so we need to draw some graph called resource allocation graph. So because mainly just waiting for the resources which are held by the another process, we are getting the deadlock situation, right? So if any process is waiting for one resource which is already held by the another process, right, that we call it as a deadlock. So that's why, so we need to draw the resource allocation graph, and by using that resource allocation graph, we can say that whether the situation may lead to the deadlock or not, right? So our concept is a resource allocation graph. So here the name itself indicates, so this resource allocation graph will be having the complete details about the resources. So it contains details of resources. So what are the details here? So resources which have been allocated, which are available. That means, so we are having some resources will be allocated to some process to execution for its execution, and some process will be in the available. That means any other process can avail the resources, free resources. Right? So in order to get the details of these resources which are being allocated and which are available, so we are going with this resource allocation graph. So before drawing the graph, so we have to see a few points. So whenever you saw this graph, the two things we'll get in the mind, that is vertices and edges. Vertices and edges. Right? So in this resource allocation graph, we are having the vertices of two categories. One is for process. So one vertex represents the process, another vertex represents the resources. And process is represented using circle. So process is represented using circle, and similarly the resources will be represented using rectangle. So P1, this is a process, and R1, this is a resource, and both are the vertex, right? Both are the vertex. So process and resource. Now again, the resources may have a single instance or a multiple instances, right? So the instance of resource represented using dot. So if there is a single instance, so we'll be having only single dot, and if the resources are having a double instance, multiple instance, so we'll use a multiple dots. For example, so see, I write here. So this is a R1, and I give one dot. That implies R1 is having only one instance. And see, this is the second one. I go with the R2. I give a two dots. That means R2 is having two instances, right? So I write P and R, right? So this is single instance, multiple. That means here two instances. That means two processes will be there. Two instances will be there. So two instances will be allocated to different processes. Right? So this is a basic thing. So that means vertex. So we are talking about the resource allocation graph. So if we are talking about the graph, so the pictorial representation of all the resources which are available and allocated will be represented in terms of vertices and edges. And here we are having the two types of vertices, process and resource. And process is represented with a circle, resource is represented with a rectangle. And if coming to the resource, there might be a chance of having a single resource and multiple instances. Okay, single instance and multiple instances. So coming to the single instance, we will represent with a single dot inside the rectangle. And if we are having a multiple instances, so we will count the instances and we will represent each instance with a dot symbol. So in this, we are representing R2 with the two dots. That implies resource 2 is having a two instances that can be allocated for two processes. Right? Now coming to the edges. So here the edges is also having a two categories. One is assigned edge, another one is requested edge. See, this is all about vertices. I'll erase this one. See, I'll write here. Okay. Edge is also two categories. One is assigned edge, requested edge. So that means assigned edge means the resource is already allocated to the process, and requested means if the process is requesting for the resources. Right? For example, coming to the assigned, I'll erase this one. Hope you understood this one. So I'll erase this one and I'll show you what exactly how we can represent the assigned edge and requested edge. So let it be P is a process and R is a resource. And here the edge is a directional, unidirectional, and C, if there is a unidirection from R to P, that we call it as a assigned edge. That implies R is allocated, that means a resource R is allocated to process P, that means already allocated. And similarly, P and R, and if the edge is from process to resource, this is called requested edge. So these are the two categories of edges, right? So one is an assigned edge, another one is a requested edge. So if it is an assigned edge, the arrow mark should be from the resource towards the process. And if it is a requested edge, the arrow mark is from process towards the resource. Right? So this is all about vertices and edges. So now we are having the vertices, that means the number of processes, resources, and also we are having some edges. Now we'll see one example. So we'll draw the resource allocation graph, right? So So first we'll draw the resource allocation graph for the resources with a single instance. So there might be a chance that resources can have the multiple instances. Now we'll see. So P1, P2. R1, R2. Right? Now, see, R1 is allocated to P1, R2 is allocated to P2. Right? So, P1 is requesting R2 and P2 is requesting R1. Okay, so this is a small graph, right? So P1 holds the resource R1, similarly P2 holds the resource R2, and P1 requesting R2 to finish its execution, and P2 requesting R1 to finish its execution, and here R1 and R2 both are the single instances. I'll write here. So single instance. Resource with a single instance, this example. And here, if a cycle forms in the graph, if the cycle forms in the graph, so you can see P1, P2, and again P1. So this is a cycle, right? So P1, R2, P2, R1, P1. So this is one cycle, right? So if such a cycle forms a graph, that implies it will lead to deadlock. Definitely that will lead to the deadlock. That means, see, 2 points we have to remember. If the resource allocation graph is drawn for the example, that means each resource is having only single instance. So then, if the resource allocation graph forms any cycle, that implies it will lead to the deadlock. Otherwise, that means if resource allocation graph doesn't forms a cycle, that means there is no deadlock. There is no deadlock. 100%, right? So this is only applicable for resources with a single instance. Resources with a single instance, right? So for example, consider the same resource allocation graph with the 2 instances. Okay, with the 2 instances. So obviously, if P1 needs R2, there is just another instance. So this one, okay, so this one will be this one, and automatically this instance will be allocated to P1. That means if it is a multiple instance, that means if the resource allocation graph is drawn for the resources with the multiple instance, and again, if a cycle forms in the graph, I'll get no confusion, right? So multiple instances, then it is not sure that it may lead to deadlock. It may lead to deadlock. That means that's not a confirm. That's not 100%, right? So it may lead to the deadlock or it may not lead to the deadlock. For example, you can see the same thing. So it forms a cycle, right? Again, it forms a cycle, but here there is a multiple instances. One instance is available. So P1 can avail the instance of resource R2. So that doesn't forms the deadlocks, right? That may not lead to the deadlock. So if the resources are having the multiple instances, and if you draw the resource allocation graph, and in that if a cycle forms in the graph, considering the multiple instances, automatically it may lead to the deadlock. It's not confirmed that it may lead to the deadlock. And coming to if it doesn't form, if the cycle doesn't form, obviously there will be no deadlock. That doesn't lead to the deadlock. So that we have to remember. So we can say that 100% the situation is having the deadlock only when a cycle forms in the single instance resources. Right? So this is about our resource allocation graph. So I will summarize the points. So this resource allocation graph can be drawn for 2 categories. One is resources with single instance. So still, if you are having any doubts, so that will be clarified, right? See, resources with multiple instances. So in these 2 categories we can draw the graph. So one is the resources with a single instance, another one is resources with a multiple instance. So in both the cases, see, one is RAG forms cycle. RAG forms cycle. So RAG means resource allocation graph. So if RAG forms a cycle in this single instance, deadlock is detected. And here
may or may not deadlock. So only one by watching or by getting this cycle, we can't decide that there will be a deadlock. And no cycle in RAG, no deadlock. And here also the same thing. No cycle in RAG, no deadlock. Right? So these are the points for single instance, and these are the points for multiple instances. Right? Hope you understood this one right now. Right? So I think all your queries have been covered. Okay. So how to detect this deadlock situation if the resources with the multiple instances? So we are having another approach for this one. So if the resource is having a single instance, this is the approach, and we can draw the resource allocation graph, and we have to check for the cycle, and we can decide whether the deadlock is available or not. I mean, it leads to deadlock or not. And but here we are having the another approach. So as of now, we'll stop the session, and in our next session, we'll discuss about the process. So for these particular resources with the multiple instances. Peterson solution, and this particular solution, this particular Peterson solution will be suitable only if there are two processes. So if there are more than two processes, this solution is not possible. So very important point, which is suitable for only two processes. Right? So let us write the structure of a critical section problem. So there will be entry section. So where in this section itself, we have to check whether process is already in any critical section. If any process is in critical section, if the process is in critical section, then the other process have to wait in this particular entry section itself. Then critical section. If there is no process in this critical section, then one process can be entered into this critical section. After that, exit section. This is a small structure. Okay, small structure. So based upon this structure, we will define the Peterson solution for two processes. Okay, so before going to that, this Peterson solution will be using two variables. One is turn, which implies the process is already in a critical section. The process is in critical section. So for example, here two processes are Pi and Pj. Two processes, because here you just see this Peterson solution will be suitable only for two processes. So let it be Py, Pj. So turn is equal to I, means process I is in critical section. Okay. Similarly, turn is equal to J, implies process J is in critical section. So this is a one variable. Okay, so you can also use it as integer, and you can represent 0 and 1. Okay, 0 and 1. So 0 means first process, 1 means second process. So this is a one variable. Another variable is a flag of 2. So which means array. So if it is an array, we can say flag of 0, flag of 1 means, okay, let it be I is 0 and j is 1. Flag of 0 means, see, initially it is a false and it is also a false. So this is a Boolean variable. Boolean variable means only true and false. Initially both the cases we are having a false. What is this one? So flag of 0 is equal to true means process I. So because I am indicating I as 0 and j as 1. Process I was interested to enter into critical section. Similarly, flag of 1, if the flag of 1 is true, then process J was interested to enter into critical section. Okay, so these are the few things we have to know before writing the solution for this critical section. So this is for only two processes, let it be Pi and Pj or P0 and P1, so or you can indicate anything. Okay, now two variables will be used for this solution. One is a turn. So if turn is equal to I, that implies turn variable means already in a critical section. So if turn is equal to I, that implies process I is in critical section. So process J have to wait until process I completes its execution. Similarly, if turn is equal to J, that implies
process J is in critical section and process I have to wait until it completes its execution. And the second variable is a flag array. So with index 0 and 1, initially this will be, this is a boolean data type. Initially the value of this flag will be false, and if flag 0 is equal to true, process I was interested to enter into critical section, and flag 1 is equal to true, process J was interested to enter into the critical section. So these are the basic things. Now we'll write the simple logic. Okay, right. So hope you understood so far. Let us take it. So actually this is a never-ending process. Okay, so every time some of the process will be keep on executing. So simply we will write the code in a iterative infinite loop. Okay, infinite loop. So do, and here let it be first flag of I is equal to true. Flag I is equal to true. Here I is 0, so don't get confused. I is equal to 0 to 1. Okay, process I, process J, process 0 and process 1. Okay, P0 is equal to Pi, P1 is equal to Pj. Okay, now let it be flag I is equal to 0. That implies flag means was interested, showing interest to enter into the critical section. So this one wants to enter into the critical section. So if the critical section is empty, automatically the process I will be entering into the critical section. But here imagine already process J is in critical section. Imagine. So for that what we have to do? Turn. Imagine, just imagine, turn is equal to J. That implies process J is already in critical section. Now process I wants to enter into critical section. What we have to do? So process I have to wait until process J completes its execution. So process I have to be in the waiting state. For that, so we will write while, okay, flag of J is equal to true and turn is equal to J. See, this is the simple loop we are writing. We are not writing any body. Okay, so when this loop will be get executed and terminated, whenever any one of these two conditions are false. Okay, any one of the these two conditions are false. One is flag J is equal to true. Flag J is equal to true means J is interested. Turn is equal to J means J is already in critical section. So if any one of these two conditions are false, then immediately the control will come out from the loop. So nothing will be executed. So this is nothing but entry section. Entry section. So already we have said that already process J, turn is equal to J. That means already process J is in critical section. So process I have to wait in this loop until this loop get terminated. That means when it is terminated, immediately whenever if the flag of J is false or turn is equal to J is false. If any one of the conditions is false, automatically this loop will be terminated. That's how it will enter into this critical section. Okay, whenever the loop is terminated, it will enter into the critical section, and once it was the termination was, I mean, the complete resources was completed, then immediately the flag of I becomes false. Flag of I becomes false. So this is called exit section. Exit section and close, and this is a infinite loop. While we can write it as true. So this is a simple logic for Peterson solution. It's a very simple logic for Peterson solution. Okay, so once again I'm saying flag I is equal to true means flag process I wants to enter into the critical section. So before process I wants to enter into the critical section, it have to check whether any other process is available in the critical section or not. So for that, so the second statement, turn is equal to J means process J is already in critical section. So in the entry section itself, the process I will be waiting until this condition becomes false. Whenever this condition becomes false, immediately the process I will enter into the critical section. And once the process or execution completes, the flag of I will be initialized to false. So this is called as an exit section. Okay, yes. Now I will write both the process and I will compare. Okay. See, now let us see, this is a process I and this is a process J. That implies, so here process I wants to enter into the critical section and here process J wants to enter into the critical section. For example, this is happening. So do flag I is equal to true. So that means process I showing interest to enter into the critical section. Immediately turn J. That means if suppose already process J is in critical section. Now if the process I have to wait until the process J completes its execution. So when it will be completed, immediately whenever the turn not equal to J or flag J not equal to true. Flag J is equal to false means the process J doesn't wants to enter into the critical section. So that is one reason. Or if turn not equal to J, that implies process J is not in critical section. So if any one of the, if both the things are true, okay, both the things, I mean, if any one of the thing is false, automatically it will come out from the loop. That means process J completed its execution. Immediately the process I will be entering into the critical section. Okay, then flag I is equal to false. After completion of execution of process I, flag I is equal to false. Meanwhile, so if the process I is in this critical section, now here flag J wants to enter into the critical section. Okay, see for example, now the control is here itself. This was not executed. Okay, so flag J is equal to true means if flag process J wants to enter into the critical section, then automatically in the critical section I is there. Okay, in the critical section I is there. Okay, so forget about this false. This one. Okay, now process I is in critical section. So term is equal to I. Term is equal to I. Now process J have to wait until the flag of I becomes false or term not equal to I. When the term not equal to I, whenever the process I come out from the critical section, then term will be not equal to I. Right? So it have to wait here. The process J will be waiting in this place. So whenever the process completes its execution, then the flag I becomes false. So whenever flag I is not equal to true, that means false, immediately the control comes here and process J will be entering into the critical section. And similarly, after completion of that, process J will be initialized to false and the rest of the things will be continued. Okay, so this is how the Peterson solution will be executed, and once again, this solution will be suitable only if there are only two processes. And three conditions to be satisfied for a critical section problem. One is mutual exclusion. Let us check. Mutual exclusion means at a time only one process should be in the critical section. Obviously, if process I is in critical section, process J will be in the waiting state at the entry section. If process J is in critical section, process I have to be in the waiting state. So at a time only one process is there in the critical section. So this condition is satisfied. And the next one is a progress. Progress. So if any one process doesn't want to enter into the critical section, let other process have to be encouraged to enter into the critical section. So that's what we are using this flag. So if the flag of I is equal to false, that implies the process I doesn't want to enter into the critical section. So it will allow process J to enter into the critical section. Similarly, if flag of J is equal to false, then process J doesn't want to enter into the critical section. So it will allow process I to enter into the critical section. So this is also done. And the next one, bounded wait. Bounded wait. So how much time it takes to complete its execution. So it doesn't want to be in infinity way. So it have to give a chance for both the processes. So here also immediately after completing the execution in the critical section, this flag we are changing it to the false. So that implies it will allow another process to enter into the critical section. So at a particular time it will be executed and it will be completed and it will give the chance to the other process. So this is also done. So if these three conditions are satisfied, then we can say it is a critical section. So the process can be in a critical section problem. So this is one solution, Peterson solution. Okay, Peterson solution, and this will be only suitable for if the it is having two processes wants to share the common resource. Mutex locks. So here the name itself indicates mutex means a mutual exclusion locks. So it is a mutual exclusion locks. So we know that the mutual exclusion means only one process is allowed to access the shared resource. If one process is sharing the resource, utilizing this resource, then other process have to wait until the process gets finished its execution. So this mutation locks, there will be a one lock. So where if one process enters into the critical section, then a lock will be required, and until the lock is released, no other process is allowed to enter into the critical section problem. So the same code which we have seen in the Peterson's solution, the same code will be used. So before that, this mutex locks will be used three components. So what are these three components used in this mutex locks? So the first one is mutex variable. So the name itself indicates this is a variable which holds the state of the lock. State of lock. That means whether the lock is available or unavailable. Okay. So state means available or unavailable. So this mutex variable holds that state. And the second one is lock acquisition. So lock acquisition means every process will be requesting for the lock. Okay. So in order to utilize the shared resource. So every process, so you can also call it as a process or a thread. Okay, every process or a thread will be requesting for a lock because to utilize the shared resource. So if the lock is available, then the lock will be granted. If the lock is unavailable, so the process or a thread should be in a waiting state. So if lock is available, then it will be granted. Then it will be granted to the process. If the lock is not available, process or thread will be in wait state until the lock is released. Okay, so what it means, if lock is not available means the lock is already granted to some process. So whatever the process which is requesting for a lock, that should be in a waiting state until the lock has been released. And the third component, lock release. So whenever the process completed utilizing the shared resource, then the lock will be released. So after completion of utilizing shared resource, then lock will be released. So until it completes the utilizing of shared resource, the lock will be in a granted. Lock will not be released. So these are the major components of Mutex locks. Mutex variable which holds the state, lock acquisition, requesting of lock, and lock release. Now let us see the code of these Mutex locks. So one is a common thing, so which we have seen in our Peterson solution. So this will be the infinite loop. Okay, first one, entry state. Okay, entry section, which we are calling it as acquire the lock. So here instead of giving a normal variable, we are passing the reference. So ampersand lock. So that means the address of that lock will be given. Okay, then waiting state. So this is an entry. Okay, while lock is equal to or not equal to 0. So until the lock becomes released, then the process will be in this particular while loop. Okay, so when the process comes out of this while loop, whenever the lock value will be 0. Okay, whenever the lock value is 0. Lock value 0 means lock is available. Okay, now critical section. The process will be entering into the critical section. Okay, then release lock. So this is a continuous loop. Okay, so if one process enters into here, it will request for the acquiring of lock. So acquiring of lock, we have to write it here. Acquire of star lock. So here we are passing the address. So the value should be here. If star lock not equal to 1, then star lock equal to 1. Okay. Close. And release of star lock. What is this release? Star lock is equal to 0. So this is what happens here, right? So I think a little bit, okay, sorry. So this is not written here, acquire lock and then critical section, then release lock. And here we need to write it. So while lock not equal to 0, then, so whenever the lock not equal to, yes, so it comes into out of the loop, and here we need to initialize lock as 1. So lock as 1 means that lock has been given to the process. I mean that the data or the common resource will be in a lock. So whenever the process completes its transaction, then it will use the release lock. So where again the lock value will becomes 0. Okay, hope you understood. So once again I'm repeating. So acquire lock means requesting for a lock. So it will implement this particular code. So here this particular process, while star lock not equal to 0 means it will wait until the lock not equal to 0, until it becomes a lock equal to 0. Then it will be initialized to 1. That means lock will be granted, right? Then the process will enter into the critical section. So once the process enters into the critical section, it will access the shared memory, it will access the resources, and after completion of that, then release of lock. So the release of lock means again this code will be executed. Now the lock value will becomes 0. Okay, so hope you understood this code. So this is called as a Mutex locks, right? So with this Mutex locks also the mutual exclusion will be implemented. That means at a time only one process can enter into the critical section. The other process have to be in a waiting state until the process completes the utilizing the shared resources in the critical section. Let's start. So before finding the solution, first let us see what exactly the problem means, and then we'll see the solution for this kind of problem. So now what is the problem? Okay, so consider a round table, dining table. Okay, as our problem defines the dining philosophers problem, let it be, it's a dining table, it's a round table, and here we'll be having 5 philosophers 5 philosophers. We'll call them as P1, P2, P3, P4, P5. Let it be philosophers. That's humans. Okay, humans. And every person, in front of every philosopher, there is a foot, a plate with foot. Okay, in front of every philosopher, there is a plate of food. And in between the philosophers, there is a chopsticks. There is a chopsticks. In between every philosopher, okay. So these are the chopsticks. We can call it as a C1, C2, C3, C4, C5. Okay, so I'm writing here philosophers P1, P2, P3, P4 and P5, and chopsticks. So we can call it as a chopsticks or spoons, whatever it may be. So every philosopher have to eat the food by using these chopsticks. Chopsticks with a numbering C1, C2, C3, C4 and C5. So if you relate this one, okay, if you relate this one to our subject, consider these philosophers as a processes and this chopstick as a resources. Okay, so hope you understood till now. Now what is the problem? So till now what we have seen, a round table is there and there 5 philosophers have been settled down, and in front of every philosopher there is a plate with a foot, and in between the philosophers there is a one chopstick. So here one condition is, so here the philosophers will be in thinking state and eating state. Thinking state and eating state. So when the philosophers in a thinking state, not able to eat, so they are not able to eat the food. When the philosophers are in eating state, have to eat food with 2 chopsticks. See, this is most important. So 2 phases, one is a thinking phase and another one is a eating phase. Whenever the philosophers are in thinking, they will not communicate with any other philosophers. They are not able to eat the food. And when they are in the eating state, they have to eat food with the 2 chopsticks. Okay, they have to, sorry, here they will not be, if the philosophers are in the eating state, they are not able to communicate with any other philosophers, and they have to eat the food with the 2 chopsticks. When they are in the thinking phase, they are not able to eat anything. Okay, they are not ready to eat. Okay, if they want to eat, they require 2 chopsticks. But see, how many philosophers are there? 5 philosophers are there. How many chopsticks are there? Only 5 chopsticks. You can see C1, C2, C3, C4, C5. Only 5 chopsticks. So 5 philosophers. And according to the condition, if they want to eat, if all philosophers wants to eat, so how many chopsticks required? How many chopsticks required? So how many they are required? Obviously, each philosopher need 2 chopsticks. So 5 into 2, 10 chopsticks are required. 10 chopsticks are required. But how many chopsticks are available? Only 5 chopsticks are available. So that means this is the case where the limitation of resources, limitation of resources. That means only a very few resources are available, so that can be used by the processes. So how the allocation or how the utilization will be done. So this is one kind of process synchronization problem. So here see, one condition, if all philosophers pick up the right chopstick and waiting for left chopstick to eat. See, imagine a condition, if all the philosophers picked up the right chopstick and every philosopher is waiting for the left chopstick, because if the philosopher wants to take the food, he or she should require 2 chopsticks. So every philosopher picked up his or her right chopstick, okay, and waiting for the left chopstick. So what happens? All the 5 philosophers were holding one chopstick and they are waiting for another chopstick which was held by another person. Yes. So where it cannot be done. So this kind of condition, we call it as a deadlock situation. Okay, deadlock situation. So the one thing, if all the philosophers wants to take the food at a single time, that is not possible, because that leads to the deadlock situation.
So how can we solve this one? By using the semaphores. So this is the actual problem. Okay, this is the actual problem. How can we solve the problem using a semaphore? So in our previous session, we have seen what about the semaphores. So a semaphore is an integer variable and it mainly operates two functionalities. One is a wait and a signal. Wait and signal. So wait means if one process holds the resources, that will be in the waiting state. So no other process should enter into the critical section. Right? So the same thing applied here also. I'm erasing this one. So in order to avoid the deadlock and how to utilize the resources efficiently, the limitation of resources efficiently, you can see if one philosopher wants to eat the food, the adjacent philosopher should also be in the waiting state. So for example, if P1 wants to eat the food, eat food. So what happens? The C1 should be wait. Okay, C1 should be picked up. Okay, picked up, as well as C5 should also be picked up. Okay, C5 also should be picked up. Okay, so that means whenever the philosopher wants to eat a food, then Ci plus 1 mod 5 should also in the waiting state. Okay, should also be in the waiting state. Right? Now, see what we'll be doing here. Do what we have to do. Wait signal, wait of chopstick of I. Let it be an array of chopsticks. Should be in the waiting state, as well as wait chopstick of I plus 1 mod 5 should also be in waiting state. Okay, should also be in waiting state. So this wait signal implies the philosopher wants to eat food. So adjacent chopsticks should also be in waiting state. So if philosopher, for example, P5 wants to eat, then P5 will hold C1 as well as C1 and C2. So this will be I and this will be I plus 1. Okay, and as it is in a round table, so we should apply this mod 5. We should apply this mod 5. For example, if C5, okay, if C5 should be taken, then 5 and 5 plus 1 mod 5. So that implies C1. So C1 and C5. With C1 and C5, P1 can eat the food. Okay, as it is in the round table, so we need to apply this mod operator. And now you can see after that, so the philosopher will be in the eating state. So what it means? Wait means the philosopher wants to eat the food. So no other philosopher, that means adjacent philosopher should not be in the eating state. So they will be in the waiting state. If still they are hungry, they doesn't have the resources to do the process, to execute the process. So here executing the process means just eating the food. So if they want to execute the process, they have to utilize the resources. Here the resources are the chopsticks. Here the resources are availed by another process. So whoever the process wants to utilize the resources, they have to wait until this process releases the thing. So releasing means the thing called a signal command. So signal of chopstick I and signal of chopstick I plus 1 mod 5. So whatever the resources in a lock state, that will be released here. So after that, again, the philosopher will be in the thinking. So they are not able to eat. So this is a simple code which can be used to solve the dining philosopher's problem. Hope you understood. Okay, so here what we are doing, so wait, we are just holding the current chopstick and the next chopstick. So if P5 wants to eat the food, P5 should pick up the left hand side chopstick and the right hand side chopstick. So C1 and C2. If P4 wants to eat, P4 wants to eat with C2 and C3. If P3 wants to eat the food, P3 have to hold C3 and C4. If P2 wants to eat the food, P2 should hold C4 and C5. And P1 have to hold C1 and C5. So here the adjacent philosophers should also be in the waiting state. So no adjacent philosophers will be start eating at a time in this case. Okay. So one more solution for this one is considering only 4 philosophers. So instead of 5 philosophers, you can consider only 4 philosophers. For example, if you consider only 4 philosophers, you can consider only 4 philosophers and 5 chopsticks. Then, for example, P1 holds C1 and C5, chopsticks C1 and C5. P2 holds, so there is no C5, so C4 or CC. For example, so in the previously we have seen the deadlock situation. If all the philosophers wants to eat the food, so then if they pick up the right hand side chopstick and waiting for the left hand side. So if P1 picks the right hand side chopstick, that means C1, then P2 will pick up C5, P3 will pick up C4, P4 will pick up C2, and see here again C4, C3, C2 is available here. So P4 will pick up C2 also. So P3 will be waiting until P4 releases, okay, C3. Once P4 completed, P3 will be assigned, I mean C3 will be assigned to P4, P3, and once it was completed, so it will be releasing C4. So it will be allotting C4 to P2, then C5 to P1. So there will be no problem. Okay, all the remaining philosophers will be in the waiting state until one philosopher completes its execution. So one solution is you have to consider only 4 philosophers. 4 philosophers at a time, 4 philosophers with 5 chopsticks. Okay, so this is the dining philosophers problem. So hope you understood this one. We need to know the exact problem, and then with using the semaphores and also by using this weight signal and weight state or weight function and a signal function, this kind of dynamic philosopher problem can be solved. So this is a process synchronization. Once again, I'm repeating here, the philosophers means the processes, concurrent processes which are being executed continuously, and chopsticks are nothing but resources, available resources. So here we are having only limited resources, and all the processes have to utilize the limited resources without inconsistency. So for that kind of problem, we are using the semaphores concept. So this is a semaphores. So the solution for the dining philosophers problem will be using semaphores. So, readers, writers, problem. So first we'll see what exactly the problem means, and then we'll see the solution. What is the solution using the semaphores? So here also we'll be going to use the semaphores for solving this readers, writers problem. Yes, so all these are examples or problems of process synchronization. So when we are having the process synchronization problem, means when there are some limited resources. So for example, a database is having a file, and there are many processes accessing the same file. So for example, this is a process 1, this is a process 2, this is a process 3, this is a process 4, and process 5. So at a time 5 processes were exactly want to utilize the same database, a common or a shared database. And here accessing means there are 2 operations can be done by the process. One is a read operation, another one is a write operation. That means one process wants to read the file and one process wants to write, that means want to update that file. So for example, this process wants to read, and this wants to write, and this wants to read, this wants to write, and this wants to write. So then there, in such case, that means whenever a multiple processes wants to perform multiple operations, that means either read or write concurrently on the same shared file, then there is a problem of synchronization or inconsistency of data. For example, this process P1 was reading a file. For example, here let it be some x equal to 10. So P1 reading the file, so x is equal to 10. At the same time, P2 updates the file as x equal to 20. At the same time, P3 reads that x is equal to 30, because all are accessing the same file. So you can observe the x value is different in P1 as well as P3. So that is called as an inconsistency. So here in the process synchronization, that means if multiple processes are sharing the common files, then how to avoid the conflicts or how to avoid the inconsistency, data inconsistency. So that we'll see. See, the things we have to remember here is the first one, multiple processes can read a file at a time. So if it is only reading the file, okay, if it is only reading the file, multiple processes can read the file. For example, see, if this is a process, 2 processes wants to read this file, then write operation should not be done here. Multiple reads can be available or multiple reads can be done, but write operation should not be performed. So if this is happening, P3, which is a write, if another process wants to write operate, then have to wait. Okay, if multiple, multiple read operations can be done, and write should be wait until it completes the read. So both read and write should not be done, right? So read at a time file. While one process reads a file, no other process should be allowed to write. So while one process or a multiple processes reads a file, no other process should be allowed to write. So write process, the process which wants to write this file should be in a waiting state. Similarly, while one process writes the data, no other process should be allowed to read or write. To read or write. So if one process is writing the data onto the file, no other process should be allowed either to read the data or to write the data. So if both are writing, if both the processes are updating the file, then also there will be a conflict. So here, see, if this is a database and if one process P1 writes the data, then if P2 wants to read the data, have to wait. If P3 wants to write the data, have to wait. Okay, hope you understood this one, right? So operations can be performed. Operations can be performed is read, 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 and so on. Only reads can be done. Okay, and then see the second one, read operation followed by write operation should not be done. So this is happens. And similarly, write operation, if one process is writing the data, the read operation should not also be done. And the third, fourth one is if one process is writing the data, another process wants to write, then also this is not possible. So simply read and read is possible, read and write is not possible, write and read is not possible, write and write is also not possible. So these are the operations that can be performed on this readers writers problem. Okay, so in all these three cases, if it happens, then what happens? There will be inconsistency on data. Now such kind of things can be solved by using semaphores. By using semaphores, we know that semaphores concept, it will be using two signals, that is wait and signal. So by using these two semaphores, okay, so we can solve the problem of readers writers, that if one process is reading, no other process will be with writing, and if one process is writing, no other process is allowed to read or write the file of the common data, on the common data, right? So now let me write a small code which will give the solution for readers writers problem by using these wait and signal semaphores. Okay, see, by using this simple code for writing operation and reading operation, so we can have the solution of this readers writers problem. So here we are using the two binary semaphores. One is called a mutex, which gives the status of mutual exclusion, which gives the status of critical section. Okay, so mutex, which will be initialized to 1, and another one is WRT, which is a write operation. Okay, write operation. So whether the process can be able to use the critical section to write the operation. So that is also initialized to 1. And one more thing is an integer variable, normal integer variable, read underscore count, which is initialized to 0. So that will be used to count the number of processes that are in the, that are applying the reading operation, that are doing the reading operation. So because in our problem we have seen multiple processes can read the data simultaneously or concurrently, but no write operation should be performed and no read and write operation should be performed. For that purpose we are using this one, right? Yes. And this is a write operation. This is a write operation. So we'll see the 4 cases. One is a read, read, write, read, and write. Okay, so first let us see that read and read operations. That means if two processes wants to read the data. For here mutex equal to 1, so we know that wait will be decrementing. So the wait means decrement by 1, and signal means increment by 1. Okay, increment by 1 as well as a decrement by 1. Now you can see the first operation is read. That means if multiple process wants to apply the read operation. So what happens? Reading operation. This is a code should be executed. So while true, this is a infinite loop. And here wait mutex. What's the value of mutex? Initially 1, write 1, and read count 0. Now wait mutex. Wait mutex means, so the mutex value will be decremented, so it becomes 0. Initially it is 1, it is now 0. Now read count plus plus. So the read count will be initially 0, now it becomes 1. And if read count not equal to 0, that means here read count is 1, so the condition is true. Wait WRT. So wait WRT means the WRT semaphore will be become 0. Okay, WRT semaphore will be 0. And signal mutex. Again, we are using the mutex value, incrementing the mutex value 1, because we have said that multiple processes can apply the read operation. So if one process is reading, definitely if another process wants to apply the read, and it can be allowed into the critical section. So here, see, now mutex is 0, that means mutex means which represents the critical section. Here the critical section is available, so reading operation is performed. So R1 is performing, that means process 1 is performing the read operation. Then again, if another read operation is going to be done, wait of mutex. So wait of mutex, again a mutex will be 0. Now what is the mutex value? 1. So again the mutex value becomes 0. Read count plus plus. Previously it is 1. So it becomes, read count becomes 2 because plus plus. If read count not equal to 0, obviously read count not equal to 0 because it is 2. Then wait of WRT. So the wait of WRT means already it is 0. It will be in the waiting state, right? Signal mutex. So again increment the mutex value with 1, and now read operation. So here R2 is also doing the read operation. So you can observe in this case 2 read operations are being done. Okay, if for example, if one process completes its reading operation, then see wait mutex. What's the mutex value? 1. So now the mutex value becomes 0. Read count minus minus. Read count minus minus means now the read count becomes 1. Previously it is 2, now it is 1. If read count is equal to 0, so it is false. So WRT should not be incremented by 1. Still the WRT value will be in 0 and it will be in waiting state, because already one process completes its execution here. Okay, and there is still another process is applying the read operation. So if one process is in read, write should not be done. So until the read count is equal to 0, that means until all the read operations has completed their execution, then only the signal of WRT, then only the WRT semaphore will be incremented to 1 and it will be available for write operation. So here again, so this is false, directly signal mutex, again mutex will become 1. So why we are using this mutex multiple times means allowing the multiple users to read, multiple process to read. Okay, so this we can call it as an entry section, and this is a critical section. And this is the exit section. Okay, so this will be the entry section, that means entering the read process, and this is the exit section, leaving the process. So in this case you can see multiple reads can be performed on the thing. Now one read and one write. In this read operation, so the mutex will become 0 because initially it is 1 1 0. Read count, so let it be, take it as RC is equal to 1, initially it is 0. If read count not equal to 0, wait WRT. So WRT is decremented with a 0 and signal mutex, so mutex becomes 1. And now read operation, so read is going on. Okay, this is a process and read is going on. Then write operation, if go with this one, see wait of WRT. So here WRT is 0. So whenever it is 0, say it can't be decremented. The value cannot be decremented with a -1 because it is a binary semaphore. The value of WRT will be either 0 or 1. So wait means decrementing. See, wait means decrementing. It is already decremented by 1 because it is 0. So it doesn't allows the process to do the write operation here. So when if for example if it is write operation is 1, then this can be applied. Okay. Hope you understood. So wait and signal are, this mutex, the WRT is a binary semaphore. It holds the value either 0 or 1. So wait means decrementing and signal means incrementing. So here already WRT value is 0. Now whenever a process wants to do the write operation, we are applying wait of WRT, which will be decrementing. So already the value is 0. We can't decrement it. So how to wait? That implies the process is not able to apply the write operation. And the process doesn't allow, it doesn't allow the process to enter into the critical section. So write operation cannot be performed. So this is not possible. And for example, if you go with a write and read. For example, write operation, first write operation. So the wait of WRT means WRT becomes 0. So write operation is going on. here. And then then immediately we are applying for read operation. Read operation, weight of mutex. So now the mutex value will be 0, and read count RC value becomes 1. And if our read count not equal to 0, here not equal to 0, weight of WRT, you can see weight of WRT means we have to decrement the WRT value. It's already 0, so it is not possible. So if it is not possible, the reading operation cannot be done. Okay, if this is not possible, this is not possible, because here the condition is true, read count not equal to 0, because read count value is 1. So the control should execute this wait process, but already WRT is equal to 0. That means wait is in, I mean write operation is going to be done, so none other process can't enter into the critical section. So read operation cannot be performed. For example, the third next case, write and write. So if you apply the write operation, WRT becomes 0. So immediately write operation is going on. Write operation is going on, and until this write operation completes its execution, then only the signal operation, the signal will be executed. So write operation will be incremented, right? So here what happens? Whenever another write operation done, again the same code will be executed. Weight of WRT, again the write should be decremented by 1, which cannot be possible. So write operation cannot be performed. Okay, so just remember these points so that this code will be very easy to understand. So here we are using a 2 semaphores, that is a binary semaphores. So mutex, which gives the status of critical section, so whether a process should be allowed or not allowed, and WRT represents the write operation, whether the process can be allowed for write operation or not, and one integer variable for read count, because multiple processes can apply the read operation. So read count to know the number of processes that are in the critical section. Okay, so wait and signal semaphores, I mean wait and signal functions are the semaphore functions. Here wait means which will be decremented by 1, and signal means which will be incremented by 1. And here we are checking read, write, write, and write operations, where RR can be possible, where all other cases are not possible. So finally we can say that if one process is in critical section applying the read operation, so only a reading operation can be done by another processes. So if any process wants to do the write operation, it have to wait until the read operation completes its execution, right? So this is the readers writers problem, which can also be called as a classical problems of synchronization. These are the process synchronizations in order to maintain the consistency. Okay, utilizing the shared resources or common resources without going with the inconsistency, right? So here we also seen the solution by using the semaphores. So monitor, it is a package. Okay, the first monitor, it is a package. So this package will be having the variables, functions, or procedures, and initialization of variables. Okay, so this monitor is a package in operating system. It's a special package in operating system. So where we have learned this package, usually these kind of terms we are using in programming languages, right? So absolutely correct. So these monitors are the language specific. So these monitors will be implemented in the programming languages, using the programming languages. So the programming languages like C++, Java, etc. were using monitors. So whereas we have seen the semaphores, which gives the process synchronization, they are operating system dependent. That means they will be defined by the operating system, but these monitors will be defined in the programming languages. So that's why these monitors are special packages in operating system, which will be having the variables, functions, procedures, or initial variables. So here, these variables cannot be accessed by the programs which are being executed outside the monitors, right? So where the programs running outside the monitor cannot access variables declared in monitor. So outside the programs cannot be accessed these particular variables which are declared in a monitor, but they can access procedures or functions of monitors. So inside the package, we are also having the variables and procedures. So whatever the programs that are being executed outside the monitors cannot be accessed these variables, but they can access these functions and procedures. And these variables will be initialized here itself. So this monitor will be in terms of a code, a simple code. Okay. So Similar to our semaphores, only one program can be executed in the monitors. Okay, only one program. So in semaphores, we are saying that a critical section. Okay, we are using the term as a critical section where one process can be entered into the critical section, and until the process completes its execution, no other process will be allowed to the critical section. Similarly, monitors also same. So at a time, only one program can be executed in the monitor. So other programs have to wait until this program completes its execution. So we'll see some code. Okay, the main syntax of monitors. What is the syntax of monitors? So syntax, as I said, that is a package. So package will be having the names. So a monitor will be used with the keyword monitor. So it will start with the monitor name. So whatever the monitor we are using, that monitor name should be given here. Okay. Monitor name. Then the variable declaration, similar to our programming languages, variable declaration. So whatever the variables we are using, that variable should be declared here. And apart from these variable declarations, we are also using the conditional variables. Conditional variables followed by the procedures. So procedure, some P1 followed by parameters. Okay, and this one. And similarly, procedure P2, and if it requires a different parameters, then and so on. Procedure Pn, parameters, and code. And finally, initialization code. And close the monitor. So this is a simple syntax for the monitor. So variables are there, and all these are the functions or procedures, and this is the initialization of variables. So this initialization code will be executed only once. So where these variable declarations, where these variables will be initialized with the values. And what about the conditional variables? So any conditional variable inside the monitor can perform two operations. We know those operations. One is wait operation, another one is signal operation. So which we have used in the semaphores. Similar to that, here also the conditional variables will be using the two operations, wait and signal. So we know that wait means whatever the process, the process will be in the waiting state until it gets its turn to enter into the monitor or anything. And signal means, so it is ready to enter into the monitor. So here one entry queue will be there. So inside the monitor, there will be entry queue. So in this entry queue, the processes or threads, we can also call it as a process or a thread, right? So a thread is a lightweight process, a part of a process. So either a thread or a process which wants to use these monitors, which wants to execute in the monitor, that will be stored in this particular queues. So if one process or thread is utilizing this monitor, that means utilizing these variables, then immediately another process have to wait. So that process will be in this particular queue. Okay, for example, P1 is there, here P2, P3, P4. So P1 is in the monitor, so P2 have to wait until P1 completes its execution. So once P1 completed, then immediately signal will be executed. Signal means this P2 is ready, the monitor is ready to access or execute the P2. So the P2 will be given to the monitor. So it will be getting executed in the monitor. Right? So this is called as an entry queue. Okay, so these are all different components, we can say, or characteristics, we can say, of these monitors. And simply I'm saying that monitors are the alternate solution similar to the semaphores for the process synchronization. So ultimate goal is the process synchronization, maintaining the consistency of data whenever we are using the shared data. So the advantage. What are the advantage means? Simple to execute than semaphores. Very simple to execute than the semaphores, and inbuilt mutual exclusion. That means, so at a time only one program or one process can be executed, right? And the third one is efficient process synchronization. So these are a lot of advantages over semaphores. Right? So another important point, once again I'm repeating, it is a special package in operating system. So package means this will be implemented in programming languages. Okay, so simply we can say the semaphores are the OS specific, right? OS specific means OS will be taking care of the semaphores, but programming languages will be taking care of these monitors. So mainly, in order to handle the deadlock situation, there are 4 methods. So the first one, deadlock prevention, deadlock avoidance, deadlock detection, and recovery, and finally deadlock ignorance. Okay, so these are the 4 methods that can handle the deadlock situation. So we'll see one by one. So in this session, I'll give a brief introduction about all these 3, and in further we'll go in depth, right? So coming to this first 2 categories, these 2 methods can be applied before deadlock occurs. So these are the methods which can be used before deadlock occurs, and these 2 are the methods after deadlock excuse me, occurs. Okay, so before the deadlock occurs and after the deadlock occurs. So here, the first thing, the name itself indicates deadlock prevention. Deadlock prevention means, so before getting the deadlock situation, so we have to make sure that the deadlock is not possible. That means the scenarios or the processes which we are using, and all the things we need to take care such that there should not be the deadlock. So we know the conditions that may cause the deadlock. So those are 4 conditions. So one is a mutual exclusion, and another one is hold and wait, no preemption, and finally circular wait. So all these are related to the resources, how the resources are allocated to the processes. Okay, so mutual exclusion means we know that one process can be utilizing the shared resources, and hold and wait, all the resources should be allocated to the processes simultaneously. Okay, and non-preemption, if any one of the process denied the resource, it have to release all the resources which are bind up to that particular process. And circular wait, so that exactly causes the deadlock, right? Circular allocation of resources. Okay, so if any one of these condition is satisfied, then obviously, I mean, if any one of these conditions was not satisfied, obviously we can say that leads to the deadlock. So we have to take care that, so while writing the code itself, we need to implement any one of these conditions or all the 4 conditions. So then we can say there is no deadlock situation if any one of the thing is processed. Okay, then that is called a deadlock prevention. Before getting the deadlock itself, we are taking care that that a deadlock situation will not comes, right? And coming to the second one, deadlock avoidance. So coming to the deadlock avoidance, so we have to collect all the resources that are related to the processes. I mean, if one process wants to be get executed, first we need to get all the resources that are required by that process in order to complete its execution. And then we have to take care about allocation of all those resources such that there will not be a deadlock. So one algorithm we'll be using for this deadlock avoidance, that is called as a banker's algorithm. Banker's algorithm. So we are collecting all the resources that are being used for one process, and we will be deciding how we can allocate the resources to the processes. And the next one, so these 2 are before deadlock occurs. We have to take care before the deadlock occurs. And coming to the next one, that is a deadlock detection and recovery. So once the deadlock occurs, then the deadlock should be detected, and then how we have to avoid the deadlock. That means once the deadlock occurs, then we'll be using this deadlock detection and recovery. Okay, so if any one of this fails, then automatically we say that deadlock will be occurs, right? So we have to wait until the deadlock comes, and then we decide what to do in order to change it. So simply one solution for this recovery means killing the processes. For example, we have said that, so for example, if this is a P1 and this is a R resource R1, and if this resource is given to P1 and P2, and there is one more resource R2, and this is given to this one, and if P1 requires the resource R2 to complete its execution, so it was requesting for R2, and which holds by P2, and P2 needs a resource R1 to complete its execution, so it gives a request here. So this is a deadlock actually we have known, right? So once it happens, for example, if the deadlock appears because P1 completes its execution if it has the resource R1 and R2, but R2 is already allocated to P2. P2 completes only if R1 is available, but R1 is allocated to P1. So this is a circular wait, okay, circular wait, and this should not be done. And here, if the deadlock occurs, what we are saying, the recovery. Recovery means one possible recovery is killing out the processes, killing the process. So if you kill this process, automatically whatever the resource it was allocated, everything will be done. Okay, then R1 will be available, so R1 will be allocated to P1, so P1 will be completing its execution. So killing of process is one solution for this detection and recovery. And the final thing is deadlock ignorance. So that means just ignore. If deadlock appears, just ignore. So this is the process, or this is the method being followed in our operating systems like Windows or Linux. Okay, so here if any deadlock occurs automatically, so the programmer point of view means the deadlock will never occur, and if the deadlock occurs, that may happens in once in a many years. So that's why, so they will be ignoring the deadlock. Okay, they'll be ignoring the deadlock. So this is a common method which are being used in our operating systems like Windows and Linux operating systems. Okay, so this is a method. So these are the different methods that are being used to handle the deadlock situation. So in our next session, we'll go in depth with the one by one. So already we have discussed about the deadlock prevention. So that these are the conditions which we have discussed in our previous session. And next we'll go with this Banker's algorithm, which gives the deadlock avoidance. So before the deadlock occurs, while allocating the resources itself, we need to take care, and we have to allocate the resources such that the result does not lead to the deadlock situation. So here the main concept of Banker's algorithm is allocating the resources to the processes without having the deadlock. So here we'll be having processes and resources. So process will be represented with P of I. Okay, P of I means the number of resources. So like P0, P1, P2, P3 and so on. So let us represent it with Pi. Okay, and this is Ri, which is nothing but resources, R0, R1, R2. So for example, to understand the resources means, so one resource is a printer. Okay, so printer can be shareable, right? So printers or scanners or any infrastructure, anything we can call them as a resources. So we need to allocate these resources to the processes, okay, such that it should not yield with the deadlock situation. So for this, there will be a resource count, and resource count will be for R0, R1, R2 and so on, right? And similarly, allocated resources. So how many resources have been allocated to the processes, and maximum resources. So this maximum resources means the maximum number of resources that process required to complete its execution. Okay, so this is completely different. Resource count is different, maximum resource is different. Resource count is number of resources that are available. Okay, number of resources that are available, and among that, some of the resources will be allocated to the processes. And this maximum resource means if one process wants to complete its execution, how many number of resources it should require. And from this, we have to find out, okay, needed resources. So we know the allocated resources, we know the maximum resources that a process requires. So the needed resources will be maximum resources minus allocated resources. So we'll be getting the needed resources. So that means some of the resources are already allocated to the process, and it requires these many resources to complete its execution. And so among this resource count, some of the resources are already allocated. So there will be one more term called available resources. Available resources. So there will be available resources also. Okay, so after allocating the resources, what are the how many available resources are there? From these available resources, we need to allocate the resources, needed resources, so that the process will be complete its execution. Okay, so a small thing I'll write here so that we'll see an example how we can proceed with this Banker's algorithm. So as we said it here, so need resources, the need resources are less than or equal to available resources. See, if need resources are less than available resources, so some resources are already available, and every process will be calculating the need resources to complete its execution. So if the need resource is less than or equal to available, what happens? That resources can be allocated to the process to complete its execution, so that, so we can write process can complete its execution. So before that, we can write resources can be allocated. So if the available resources are greater than the need, that means the need resources are less than available. So one thing, resources can be allocated, next process can complete its execution. After that, what we have to do? So release allocated resources and update available resources. See, simple. For example, process P0 requires the need resources are 4 and the available resources are 6. Okay, so P0 need 4 resources to complete its execution and available resources are 6. So you can see 4 is less than 6, so we need 4, but we are having 6, so we can complete it. So what happens? These 4 resources will be allocated. The 4 resources will be allocated, and see, P0 completes its execution, right? And what happens? Release all the allocated resources. Whatever the resources are allocated, that will be released. Okay, see, for example, one more thing I have just to. So already allocated, for example, already allocated are 2, right? So what happens? So 4 has been given to this to complete its execution, and we have to update the available. So available will be previously 6 plus 2 are deallocated, right? Already allocated, so it completes its execution, so you can release it. So 6 plus 2, which will be 8. So we have to update the available resources. That's also most important. So only one condition. So if need is less than or equal to available, then we have to allocate the resources, we have to complete its process and release all the allocated resources and update the available resources, right? And the same step will be repeated for all the processes, those who have not completed so far. And finally, check whether all the processes have been completed its execution. If so, we can say that the situation doesn't lead to a deadlock. It's a safe state. Okay, so the state is a safe state. So this is also called as a safety algorithm. Safety algorithm. So we are checking whether after allocating the resources, whether the situation becomes safe or not. Right? So hope you understood this one. Simple step, only this one. Just remember. And the same thing should be repeated for all the processes. So now we'll take one example and I'll solve that by using this simple thing. Right? Now let us see this example problem. Right? So here we are having a 5 processes. Let us consider this problem, 5 processes, and total number of resources that are available, 3 resources are there, and each resource R0 available resources are 10, and R1 5 resources, and R2 7 resources. So we have to share all these resources to the processes, 5 processes, such that it doesn't lead to the deadlock situation. So here the table was given. Yes, see, P0, P1, P2, P3, and P4. Let it be some 5 processes. So P0 requires a maximum of 7 R0 resources, 5 R1 resources, and 3 R2 resources to complete its execution. Similarly, P1 requires 3, 2, 2. That means 3 resources with the numbers 3, 2, 2 to complete its execution. So that is the maximum resources required to complete its execution. So till now, allocated resources are P0, R0, 0 resources have been allocated, 1 R1 and 0 R2. P1, 3 R0 resources, 0 R1 resources, and 2 R2 resources have allocated, right? So these are the allocated resources, and these are the maximum resources to complete its execution. So these are the need, how many required to complete its execution, and what are the available. So you can see R0 total 10 quantity are available, right? So resource R0 10 quantity are available. Among the 10, how many have allocated? So 3 plus 3 plus 2. So 6 plus 2, 8 resources have already allocated. So what is the available R0? Only 2 resources. Hope you understood. So these are the maximum resources available. Okay, available. And we need to share all these resources to all the 5 processes. So some of the resources have already allocated. So coming to the R0, total number of R0 resources are 10. Among the 10, 3 have been allocated for P1, 3 have been allocated for P2, and 2 have been allocated for P3. So how many resources are remaining? That means available means, so 3 plus 3, 6 plus 2, 8. So 10 minus 8, 2 resources are available. Similarly, R1. Total R1 resources are 5 and 2 resources are allocated, 1 for P0 and 1 for P3. So available resources are 3. And similarly, R2, total resources are 7 and 2 allocated for P1, 2 allocated for P2 and 1 allocated for P3 and 2 allocated for P4. So total 2 plus 1, 3 plus 2, 5 plus 2, 7. So all the 7 resources have been allocated for a different process. So available are 0. Available are 0. Now, what we have to do? So we require needed. How many resources are required to complete the execution? So coming to the P0, if P0 wants to get executed, completes its execution, how many resources are required? So R0 maximum 7, 0 are allocated, so need 7 more resources. So R1 5 resources, it requires 5 resources to complete its execution. 1 is allocated, so 4 it need. And R2, no resource have been allocated, maximum 3, so it requires 3. Similarly, if you want to complete a P1, process P1, how many resources? R0 3, maximum 3, so 0. R1 0, R1 2, so it will be 2. So that means simply we can say maximum minus allocated will be the needed. So 2, it will be 0. So that means if P1 wants to get executed, it requires 0 R0 resources, 2 R1 resources and 0 R2 resources. Similarly here also 9 minus 3, 6, 0 minus 0 is 0 requirement, 2 minus 2 it is again 0. And here 2 minus 2 is 0, 2 minus 1 is 1, 2 minus 1 is 1. And here also 4 required R0, 3 required R1 and 1 required R2. So these are the need resources. So we have seen the formula that need resources are less than available. So consider P0. What are the need resources? P0 need resources are 7, 4, 3. What are the available resources? 2, 3, 0. See here the condition, if need is less than or equal to available, then update available. Okay, so 7 need less than availability. So 7 less than 2, false. 4 less than 3, false. 3 less than 0, false. So P0 can't complete its execution with the available resources. Hope you understood. So P0 requires 7 R0 resources where we are having only 2. P0 requires 4 R1 resources where it requires 3. P0 requires 3 R2 resources where it is required to only 0. So here P0 can't be executed as of now. Now move to the P1. What are the need resources? P1 0, 2, 0. What are the available resources? You can see 2, 3, 0. See 0 less than 2, true. 2 less than 3, true. 0 less than 0, true. So remember, all should be true. If any one of the resources is not available, we should not start executing the process. We should not allocate the process. So here it is possible, right? So need resources are very less than available resources. What we have to do, we can allocate the resources to P1 and we can complete its execution so that we can update. So update the availability. So update the availability means availability is equal to availability plus allocated. So updated availability plus allocated means what happens? Availability is equal to 2, 3, 0. What are the allocated resources for this one? 3, 0, 2. Just add these two things. 5, 3, 2. So P1 completes its execution. So after completion of this execution, what happens? So this available resources, so this will be released. 0, 0. This will be released and this will be added to the available resources. So what happens here? It becomes, now available resources are 5, 3, 2 because P1 completes its execution. Okay, hope you understood. While executing the P1, need resources are less than available. So whatever the available resources, that will be allocated to P1 and it will be get completed. So once it was completed, we need to deallocate the resources which are already allocated. So 3, 2. So that becomes zeros. So that will be added to the available. Now coming to this P2. What's the P2? Need resources. What are the P2 need resources in order to execute it? So 600. So it requires 6 processes. Okay, 6 resources. Availability, what is that? 5, 3, 2. Now you can see 6. It is false. This is true. This is true. So if any one of these false, this cannot be continued. So P2 can't be continued right now. Move to the next one. P3. Need resources. What are the need resources for P3? 0, 1, 1. What are the available resources for P3? 5, 3, 2. So this is true. This is true. This is true because need resources are less than available resources. Okay, now what we have to do? Available, we have to allocate this one to the P3 and let it be completed. So available will be 5, 3, 2 plus allocated resources 2, 1, 1. So which becomes 7, 4, 3. So now it becomes 7, 4, 3 and this becomes 0, 0, 0. Because P3 has been completed its execution. Now just move with the P4. What's the need? The need resources for P4 is 4, 3, 1. And avail resources are 7, 4, 3. So 2, true, true. So 4 is less than 7, 3 is less than 4, 1 is less than 3. Now what happens here? Avail should be updated. So avail is equal to what are the available resources? 7, 4, 3 plus allocated resources 0, 0, 2. So that becomes 7, 4, 5. So this becomes 7, 4, 5 after completion of this P4 and this becomes 0. So resources will be deallocated. Now again start the same thing, repeat the same thing from starting onwards. Okay, so coming to the P0 because P0 not completed, right? So it need how many? What are the need resources? 7, 4, 3. These are the need resources for P0. What are the available resources? Available resources are 745. So what happens? This is true, and this is true. Now we need to update the available resources. Available resources will be 745 plus whatever the resources allocated, 701. Sorry, 010. Okay, 010. This becomes 755. 755, right? So this becomes 755, and this is completed, and this becomes 0. Okay, yes. Now what we have to do? One more process is available, so that is P2. Need R, P2 need R 600. Available R 755. So automatically true. So then we have to add available resources with 755, and allocated resources for P2 it is 302. So which becomes 10, 5 and 7. So this becomes 10, 5, 7. So now we completed P2, this becomes 0 and this becomes 0. Now you can observe all the processes have been completed its execution. After completion of this execution, what are the available resources? You can see R0 7, R1 5, R2 7, which are the available resources here, right? So if we get the same thing, we can simply say that it is in a safe state. The situation is in a safe state, so deadlock will not be occurred. So here the order of completion will be first what is completed? P1 completed, then P3 completed, then P4 completed, P4 completed, then P0 completed, then P2 completed. So this is the order of completion of the processes. That means allocating the resources to the processes such that there will be no deadlock. So this is called a banker's algorithm, which can also be called as safety algorithm. Right? So hope you understood. Simple thing. So some resources are already allocated to the processes and maximum resources will be given. So these are the maximum resources the process required to complete its execution. From that we have to calculate the need resources. How many resources are still needed to complete the process, and we have to find out the available resources, and only one condition we have to check, that is if need resources are less than available, simply allocate the resources to that particular process and let the process complete its execution, and then release all the allocated processes that are already, all the resources that are already allocated to the processes, and update the available resources, and repeat the same step for all the processes until all the process completes its execution. So here we need to get all zeros. Allocated resources, all zeros. All zeros means all processes have been completed its execution, and every process have released the resources, deallocated the resources. So finally, after completion of the thing, the available resources will be the maximum resources available. So 10, 5, 7 and 10, 5, 7. So every process we are checking the condition need less than available, and we are proceeding with the further detection. So actually this deadlock detection can be done with the two approaches. So two scenarios. One is resources with single instance. So I'll tell what is this single instance and a multiple instance. Okay. And the second one is resources with multiple instance. So actually the same thing we have discussed about in the deadlock prevention also. Okay, sorry, deadlock avoidance. So the deadlock avoidance also done in these two approaches. One is resources with a single instance and resources with a multiple instance. So in our previous session, we have seen a banker's algorithm where we can avoid the deadlock situation. So there we have seen the resources like R0, R1 and R3, where R0 is having some 10 resources and 10 quantity, R1 with some 6 quantity and R3 some 7 quantity. So these are nothing but instances. So if there are only R0, R1 and R2, so only one resource is available in each set, then we will be saying it as a resource with a single instance. And this is an example for resource with a multiple instance. That means 10 resources are of category R0, 6 resources, 6 quantity of resources R1 and 7 quantity of resources R2. For example, R0, take one resource as a printer. So there are 10 printers and there are 6 scanners. There are 7 some external hard disk or any other requirement. Okay, resources, different resources. So if a process wants to get executed, so it requires some 5 resources. That means 5 printers and 2 scanners and some 1 hard disk. Like that, we have divided this one, right? So we have seen all these things in a banker's algorithm. So that's the same thing. If only one resource is there with each category, then we will call it as resources with single instance. That means only one quantity. And multiple instances. So multiple instances means there is a more quantity, more than one quantity. So here we have to go with the different approaches based upon the instance of these resources. If it is a single instance, then simply that can be done with 2 categories. One is a resource allocation graph. So we need to draw the resource allocation graph. So if that graph doesn't have any cycles, then we can say there is no deadlock. If there is any one cycle with a single direction, flow of control with a single direction, then we can say it as a deadlock. Okay, and another one is wait for graph. Wait for graph. So if it is a multiple instances, that also can be done with a one approach, and another one approach is a same Banker's algorithm. Banker's algorithm. So we have seen this Banker's algorithm, but here a little bit difference, a slight difference will be there, right? So once you refer this Banker's algorithm in our channel, so that you will be getting clarity what exactly done in this Banker's algorithm. I'll post the Banker's algorithm link in the description. So just go through that before understanding this concept. Okay. Yes. So these are the different approaches we are going to use for deadlock detection, right? So we'll go one by one. So we'll draw this resource allocation graph, and from this resource allocation graph, we'll go with the wait for graph. And also by taking multiple instances, we'll solve it with Banker's algorithm. Once again, I'm saying this deadlock detection will be applying only when the deadlock occurs. So we have to detect. So that means we have to, so we need to get the scenario, and we have to understand, and we need to find out whether the state is a safe state or an unsafe state. Unsafe means that results to the deadlock situation. Okay, so let us see first this resource allocation graph and wait for graph. So we'll take one scenario and we'll draw these graphs. Okay. So let us see this example. This is a scenario. So from this scenario, we need to find the resource allocation graph and corresponding wait for graph. So here, let us consider P as a process and R as a resource. So 4 scenarios are there where process P1 holds the resource R2 and requesting R1 to complete its execution. So let us take P1. It holds resource R2. Okay. So let us take R2. It holds. So if the arrow mark is towards the process, that means R2 is allocated to P1 and requesting R1 to complete its execution. So it was requesting. So arrow mark will be towards the resource. So this is R1. See, process is represented with a circle and resource is represented with a box. Next, P2 holds R1. So this one was allocated to P2. Okay, so this is the incoming. And requesting R4. P2 holds R1, requesting R4. So it will be requesting R4. Okay, then P3 holds R4. So arrow mark will be towards. So P3 holds R4, requesting R3. So towards the resource. Next, P4 holds R3 and requesting R2. Okay, so this is a resource allocation graph. Resource allocation graph. Okay, so here you can observe it forms a closed circle. Okay, it forms closed circle. That's the first point. Second point, you can see, so this is a closed circle. Second point, the flow is in single direction. The flow is in single direction. So obviously we can say there is a deadlock. There is a deadlock. See, simple. If P1 wants to complete its execution, it holds R2 but requesting R1. So it requires resource 1 to complete its execution, which was being allocated to P2. And if P2 wants to complete its execution, it have to get a resource R4, which has been already allocated to P3. And in order to complete the P3, it requires the R3, which is already allocated to P4. And if P4 wants to get executed, it requires resource R2, which has been held with P1. So if P1 wants to complete its execution, that's a never-ending process. Okay, so this is called as a resource allocation graph. Resource allocation graph. And the second one, wait for graph. So what is this wait for graph means? We can simplify this resource allocation graph. We can simplify the resource allocation graph by removing resources. By removing resources, just representing with the process. See, P1 depends upon P2. Okay, because P1 depends upon R1, which has been allocated to P2. So we can simply write it as P1, which can be represented, depends upon process 2. It will be depending upon P2. Upon completion of P2, then only P1 will be completed. So P2 depends upon R4, which was allocated to P3. So P2 is depending upon P3. P3 depends upon R3, which was allocated to P4. And P4 depends upon R2, which is allocated to P1. So again, you can see there is a closed loop. And flow in single direction. The flow is in single direction. So that means there is a deadlock. So in this way, we can detect the deadlock. So once again, I'm repeating, this deadlock detection will be done only after deadlock arises. So we need to draw the resource allocation graph as well as wait for graph in order to detect the deadlocks. And this will be suitable only for whenever the resources are with single instance. You can see there is only single instance. So if we are representing this with 2 dots, that implies there is multiple instances of resources. That means the quantity of resources are 2. So but here these are all single instance. So if the resources are single instance, this is approach how we can detect the deadlock. Welcome back to our channel. So in today's session, we'll see one more concept in operating system, that is a deadlock detection. So in our previous session, we have seen a deadlock detection method, and that is a resource allocation graph as well as a wait for graph. And in today's session, we'll see the deadlock detection using Banker's algorithm. So already in our previous session, we have seen this Banker's algorithm in deadlock avoidance. So the only difference between the Banker's algorithm in deadlock avoidance and the deadlock detection means, so in the deadlock avoidance, so before allocating the process itself, we are going to use this Banker's algorithm in order to allocate the resources to the process in order to avoid the deadlock situation. So coming to this deadlock detection, once already there is a deadlock, and now we are going to detect whether there is a deadlock or not. That means this process will be applied only when the deadlock occurs. Okay, where the deadlock occurs, that we are going to identify in this deadlock detection. So let us take a small example in that. This is also a Banker's algorithm. So whatever the thing we have done in the Banker's algorithm, the same thing we are going to apply here. Right. So I'll post the Banker's algorithm link in the description, so that just go through that, so that you'll be getting an idea what is a Banker's algorithm, and then you can refer this. So it will be very easy for you to understand this one. Right. Now in this question, so you can see there are 3 different resources. One thing, so this problem will be suitable for the resources if the resources are having multiple instances. That means the number of quantity of resources is more. Right. So here we are taking 3 resources, R1, R2, and R0, R1, and R2. So where R0 we are having 8 resources, and R1 we are having 2 resources, and R2 we are having 6 resources. So already the allocation has been done, and now the process are in a situation, right? So in an unsafe situation. You can see here allocation R0, how many R0 in the resources are there? 3 plus 3, 6 plus 2, 8. So all the R0 resources have been allocated, and R1, 2. So total 2 are there. Both the resources have been allocated with P0 and P3. Next R2, 6 resources are available, and among that 6, all the 6 resources are allocated to P2, P3, and P4. And still P0 requires 0 resources to complete its execution, and P1 requires 2 instances of R0, 0 instance of R1, and 2 instances of R2 are required to complete its execution, and P2, 0 instance of R0, 0 instance of R1, and 1 instance of R2 is required to complete its execution, and so on. Right. Now what are the available resources? So we know that available resources means the total number of resources minus the allocation of resources. So R0 are 8, and here also 8. The R0 is 0. So 0 instance of R0 resources are available. Similarly R1, total is 2, allocated is 2. So R1 is also 0. R2, 6 resources are there totally. Here 6 resources have been allocated, so it is also 0. So there are no availability of the resources. Still we are checking whether this kind of situation is safe or unsafe. So among that, what we have seen in the Banker's algorithm, we have seen need is less than or equal to available, then update available, right? Update available, right? So this is the thing we have seen in the Banker's algorithm. The same thing here we will be applying. So instead of need, we are using one more term called request. Okay, request. So here we need to find the request is less than or equal to available. For example, consider P0. So request is less than or equal to available. That means required resources. So request is 0, 0, 0, and availability is 0, 0, 0. So less than or equal to true, true, true. So if all the true, P0 completes its execution. We have seen the same thing, right? P0 completes its execution, and we need to update available. So update available. So how it will be available means available is equal to, so already available resources are 0, 0, 0. So once P0 completes its execution, whatever the resources allocated for process P0 will be deallocated. So this will be deallocated. So plus allocated resources for P0. So now the availability will be 0, 1, 0. So now the availability will update with 0, 1, 0. Hope you understood, right? And now P1. So what is the required? Required is 202. What is the available? Available is 0, 1, 0. So 2 is less than 0, false. 0 is less than 1, true. 2 is less than 0, false. So this is not possible. So P1 can't complete its execution with the available resources. So just skip this one. Move on with the next one. Okay, this we can't execute right now. Next P2. So P2 required is 0, 0, 1, and available is 0, 1, 0. So 0 less than 0, true, less than or equal to So you have to write this one, less than or equal to. And 0 less than or equal to 1, true, 1 less than 0, false. So this can also not able to perform. P2 can't able to perform. Next, it will move on with the P3. P3, what's the required? P3 requires 1, 0, 0. What are the available? 0, 1, 0. 1 is less than or equal to 0. It's a false. This is true and this is true. So 1 is false. So this is also not possible. So P3 can't able to complete its execution. Okay. Next P4. What happens? Required. What are the required? 0, 0, 2. What are the available resources? 0, 1, 0. So 0 less than or equal to 0. True. 0 less than or equal to 1. True. 2 less than or equal to 0. False. So 1 false is there. So this is also not possible. Okay. This is also not possible. It's not possible to complete its execution. Now reverse. I mean, it will move on with the P1. Again, still P1 requires 2, 0, 2. But we are having 0, 1, 0, which is not possible. So here, other than P0, all the remaining are in a deadlock situation, because here we can see with the available resources, no other process can complete its execution other than P0. Okay, you have seen this one. So then we can say that there is a deadlock. There is a deadlock. So the same algorithm we are using, the same banker's algorithm we are using, but here we are, the situation is once all the processes, I mean all the resources are allocated to the process, then we have to find out the deadlock situation. We will be finding whether the same the situation is a safe or unsafe, the state is a safe or unsafe. Okay, so hope you understood. So P0 has been completed its execution, but after completion of P0, some resources have been deallocated and they are available, but still no other process are able to complete its execution. Right? So in such a way, the same banker's algorithm will be used to detect whether it is in a safe state or unsafe state. So deadlock detection. Right? So for example, if I'm doing the small correction, okay, I'm doing the small correction in P2, if it also requires, see, 0, 0, 0. Okay. Now what happens? You can observe P1 can't able to execute. P2 still it is requiring 0, 0, 0. So then it will be true. Then available will be updated. See, then available will be updated. So then available will be 0, 1, 0 plus whatever the resources allocated with 303. So then it will become 313. So the availability become 313. So with the 313, P2 has been completed. Next P3. So P3 required is 100 and here it is we are having 313. So this is true. So this is also possible, right? So this is also possible. Next available should be updated. Available will be 313 plus 311, 623. The available becomes 623. So it was completed. Next go to the P4. Available are 623. So this is also true. Then what happens? Possible. So available will be 623 plus 002. So 625. This becomes 625. Okay. So this is also possible. Next again P1. Required 202. Available are 625. Okay. Then it is possible. So now available will be updated with 827. Somewhere we have got wrong. So 303. So 313. So 313 P3 after P3 completed. See 313 624. So this is 624. 624. And after completion of P4 62. Sorry. Yes. So here it is 202 not possible. So P2 it goes with the P2. Now it becomes 010 plus 303. So it becomes 3, 1 and 3. And then P3 624. Next here it will be 624 and it becomes 626. And now it becomes P2 P1 62. So here it is required 200. Sorry, required is 202 626. Then the availability will be 626 plus allocated resources 200. So that becomes available will becomes 826, which are equal. So we need to update. We are comparing with the available. And we are updating the available by releasing the allocation, right? So available will be updated with available is equal to available plus allocation, because whatever the resources allocated will be deallocated. So this is the thing, right? Don't get confused. So but see what happens when I give here 0, then we are getting a safe state. But whenever it is 001, that will be the deadlock situation. So this is how the banker's algorithm only will be used for both deadlock detection as well as a deadlock avoidance. Deadlock recovery. So the first point is, so this recovery will be after deadlock has been detected. After deadlock has been detected, how we will bring it to safe state. Safe state means, so avoiding the deadlock. Okay, so this deadlock recovery can be done in two procedures. Okay, so this deadlock recovery, I'll write here, deadlock recovery. So this can be done in two ways. So the first one is process termination. So just terminating the process. So we know that the processes will be waiting for the resources which are already allocated by another process, and by killing those processes we can avoid the deadlock. One more thing, resource preemption. Resource preemption, that means, so forcibly we will be deallocating the resources from one process and we are allocating the same resources for the required process to complete its execution. So in such a way also we can get out from the unsafe state. So here the process termination, so this can be done in two ways. So here the process termination, just now as I said that wherever the process yields to the deadlock, that process will be terminated. So here the two possibilities, abort all processes. So simply without any question, all the processes will be get removed, okay, killed. The process will be killed, that means terminated. So obviously there will be no deadlocks. The first thing, all the processes, whatever the processes are available, we have to delete all the processes. So here there is a drawback, because if, for example, if our if there are 4 processes, so let it be P1, P2, P3 and P4. So P1 completes around 10%, okay, P2 completes some 60%, P3 completes 95%, P4 completes 98%. So if there are 4 processes and P1 completed 10%, it have to complete 90%, okay, and P2 requires 30% of the work to be done, right, and P3 only 5% of work will be done, right, and P4 98. So if you go with this one about all processes, every process will be terminated. We have to kill all the processes. So whatever the process completed, that means 90% of the work has been done for the P4, that have to restart from the beginning. Okay, so this is an expensive, we will call such type of situation as an expensive. So whatever the process which completes a maximum work must also start from the beginning. So this is the drawback. And the second second approach is abort one process and detect using Banker's algorithm. Okay, so here what we are doing, so we are just killing one process, and again we are checking with the Banker's algorithm whether after killing the process whether there is a deadlock or not deadlock, that means a safe state or unsafe state. So if it is unsafe state, again one more process will be get deleted, and again we have to check the Banker's algorithm. We need to detect the deadlock with the Banker's algorithm, so that we will be getting whether the situation is safe or unsafe. So if it is still unsafe, one more process will be deleted, and again we have to check that. That here the drawback is, every time the Banker's algorithm will be keep on executing, okay, multiple times until there is no deadlock. We need to implement the Banker's algorithm. For example, imagine there are 100 processes. So if there is a deadlock, okay, so we have to repeatedly execute this Banker's algorithm in order to detect the deadlock situation multiple times. So there will be a overhead problem. There will be an overhead problem. I'll write here. Overhead problem. This is a drawback. Okay, so here how to select the process. So which process is to be get deleted? That will be based upon the process priority, or the number of resources allocated for that process, or how far it has been completed its execution. So these are the different ways to select the process. Okay, process priority, number of resources that are allocated for that process, and how far the process completes its execution. So similar way. Okay, so based upon all those constraints, we are supposed to select the process, and we have to kill the process. And after killing the process, we have to use a Banker's algorithm to detect whether the situation is safe or unsafe. So these are the two ways we can avoid the deadlock from the process termination. Coming to the second one, that is a process preemption. Preemption means releasing the resources, forcibly releasing the resources, allocating the same resources to another process which requires those resources, and let the other process complete its execution, so that the deadlock can be recovered. Okay, so here the problems arise here. So one problem is selection. So which process is to be get selected? Here also the same problem. Which process should be selected? And the second one, rollback. So as I said that we are forcibly removing the resources that are allocated to the process. So once we are deallocating the resources, we have to start from the beginning by allocating the resources to the process, whether that happens or not. That is a rollback. Okay, again the process have to start its execution from the beginning. So that's a rollback. And the third problem arises here is starvation. So starvation means if every time we are selecting the same process, okay, for deallocating the resources, and that process takes a lot of time to complete its execution, because again it have to start, and after some time the same process may be selected to deallocate the resources, and after deallocating again the process have to wait until the resources have been allocated to that process. So these are the problems arised in this resource preemption. Okay, preemption means forcibly deallocating the resources. So these are the two different ways how we can recover the deadlock. That means how can we avoid the deadlock? How can we make the unsafe state to safe state? Memory management techniques. So the name itself indicates, so this is a one important feature of operating system. So memory management. So how the memory can be allocated for the processes. So that is the topic. So in today's session we'll see what are the different types of memory management techniques, and in our further sessions we will discuss about each one clearly. Okay, so this memory management techniques. So these memory management techniques are divided into two categories. So one is uni-programming, and similarly multi-programming. So coming to this uni-programming, the name itself indicates at a time only one process can be loaded into the main memory for its execution. So only one process is allowed here. Okay, one process is allowed. Whereas multi-programming, so here also the name itself indicates multiple processes can be loaded into the main memory, and the operating system or the CPU will be switching between these processes, so in order to get the parallel execution. Okay, multiple programs, simple definition, multiple processes can be allowed into the main memory. Okay, so multiple processes are allowed. So whereas here the single process. So coming to this multi-programming, okay, multi-programming, that is very important to give the memory, allocate the memory, because here there is only one process, so obviously that process will be loaded into the main memory. But here what we are saying is multiple processes can be loaded into the main memory, so there we should be very careful while allocating the memory. Okay, so this multi-programming is again divided into two categories. One is contiguous, non-contiguous. Contiguous means a continuous memory locations, and non-contiguous means not in a sequence. Okay, so contiguous memory locations means, so the complete memory will be allocated in a continuous blocks of memory. But non-continuous means it is not necessary to maintain the consistency. I mean, it is not necessary to allocate the continuous memory locations. Wherever the free memory is available, that will be allocated to the process. That is non-contiguous. Okay, so again this contiguous is divided into two categories. One is fixed partition, another one variable partition. Fixed partition and variable partition. See, here the name itself indicates fixed partition means the complete memory will be divided into fixed size of blocks. Okay, so partition means block. So if the complete memory will be divided into different blocks, and all the blocks are of same size, fixed size. So here using this fixed partitioning gives one disadvantage, that is an internal fragmentation. So don't worry about in-depth concept. So we'll, in our further sessions, we'll go one by one. So what is contiguous in that, what is a fixed partition, and everything. So overview I am giving. So fixed partition, there will be internal fragmentation if you are allocating the memory in a fixed partition. Okay, and if what is the internal fragmentation means, if the process is less than the fixed partition. For example, the process size is 10 MB, and the partition size, the fixed partition size is 20 MB. Then this process can be accommodated in this partition, but 10 MB of space will be wasted because no other process can be accommodated here. So this particular partition, this complete particular partition, here partition is a block. This complete block will be assigned to the process where it will be occupying only 10 MB of space. The other 10 MB is a waste of process. So that type of thing we call it as an internal fragmentation. So that is the disadvantage of this fixed partition. And coming to this variable partitioning, so in order to avoid this kind of fixed internal fragmentation problems, so we are moving on with the variable partition where the name itself indicates the blocks will be created dynamically based upon the process size. So whenever a process wants to be allocated, whenever a memory can be allocated to a process based upon the size of the process, the block will be created. So dynamically memory will be allocated in variable partition based upon the process size. So this also called as static partition because it is a fixed. Variable partition, it is a dynamical partition, dynamic. So the memory will be allocated dynamically, the memory is allocated statically, that means equally. And coming to the non-contiguous, here also the same thing. So this is also non-contiguous also will be considered as both two parts. One is a paging, another one is a segmentation. Once again, I'll write here. Paging and segmentation. So paging means here both the physical memory as well as the logical memory will be divided into blocks. So in this contiguous, only the main memory will be divided into different blocks. But here both the physical and logical memories will be divided into blocks where we call them as a frames and a pages. So all the pages will be loaded into the corresponding frames. Okay, so one will be the main memory, one will be the secondary memory. So we know that if any one process wants to be executed, that process should be loaded into the main memory from the secondary memory. So the process will be moving from pages to frames. Okay, in this paging concept. Okay, so we'll discuss further. So there are paging page replacement algorithms are there. So we'll see what is a page, what is a frame, and how the movement will be done from pages to frames, etc., in our further session. And coming to the segmentation also, so here also the complete memory will be allocated, but based upon the logical units. That means the differentiation between a functions, data, etc., So based upon the logical functions or based upon the functions, so this complete segmentation will be divided into logical units. So each unit we will call them as a segments. Okay, so here we are calling them as a partition or a block in contiguous. In paging we are calling them as a pages and frames, and whereas in segmentations, so everywhere we are doing the same thing. Memory will be divided into partitions, memory will be divided into blocks. So here we are calling them as a pages and frames. Here we will be calling them as a segments. Okay, so this is the complete memory management techniques. How efficiently we need to use a memory is a very important concept in operating system. Okay, so uniprogramming and multiprogramming, there will be no problem with the uniprogramming because only one process will be allowed at a time. And coming to the multiple processes, then there will be a dilemma, or then there will be a question. So how efficiently we can allocate the memory? So there we will be having the contiguous and non-contiguous. So contiguous means contiguous memory locations, and non-contiguous means so it is not necessary to give the contiguous, and fixed a variable, and here it is a paging and segmentation. So this is a complete overview of memory management techniques, or we can also call them as memory allocation techniques. Memory allocation techniques. Logical address and physical address. See, so before going to see the difference, first we have to know that any kind of program will be executed only by the CPU. So whatever the programs we are writing, that will be stored in the secondary memory, and if you want to execute them, only the CPU can do that. So only the CPU will be accessing the main memory. So we are storing the files or data in a secondary memory. Okay, so for example, let us take a program. So this program will be stored in secondary memory. Okay, so this is a CPU, central processing unit, so which will be executing this program. So if this program wants to be get executed, so see, execution, if it needs an execution, so direct access will not be happens. So first, this is a main memory. So first the program will be loaded into main memory, and from this the execution will be done. Okay, the program will be executed by the CPU. So the direct execution, that means direct accessing the program from the secondary memory will not happen. Only the CPU will be accessing the data from the main memory. So what we have to do, the program should be loaded into the main memory. So whenever we are storing this program in the secondary memory, the address here is logical address. So obviously any kind of program or any kind of data will be stored in the secondary memory. So that is the address is called as a logical address. And whenever the CPU wants to execute, I mean the user wants to execute the program, first the program will be loaded into the main memory, and similarly from the main memory the program will be accessed by the CPU. So here the address, here also there will be address. Okay, in the main memory also there will be address. So whatever the program which is loaded into the main memory, here also the program will be stored in some address, and this address is physical address. Physical address. Okay, so this is the difference between the logical address and the physical address. So logical address is the address of a program which resides in the secondary memory, and physical address is the address of a program which is in the main memory. Okay, so this logical address will be translated to the physical address. Okay, so because this program which is available in secondary memory will be loaded into the main memory, so the logical address will be translated or computed to the physical address. So this will be done by MMU, memory management unit, which is done by the memory management unit. So this logical address will be done by CPU. It will be generated by CPU. Okay, it will be generated by CPU, but the CPU can't access the logical address directly. So the CPU, the memory management unit, will be converting this logical address into physical address so that this address can be directly accessed by the CPU. Okay, so see, we'll draw the diagram. So CPU, which gives a logical address, which generates a logical address for a program, which is MMU, memory management unit. So here there will be some relocation register. So that will be used to translate the logical address into physical address, and it will be stored in the main memory or primary memory. So you can say it as a physical or primary memory or main memory. So everything will be done by the CPU only. But if CPU wants to execute the program, this CPU will be accessing the main memory. Okay, so hope you understood the difference among the logical operators as well as logical address and the physical address. And a group of logical addresses is called logical address space. Okay, logical address space. And this one, group of physical addresses is called physical address space. Okay, physical address space, right? So hope you understood. Now we will write the differences. Okay, differences among these things. Hope you understood about what is a logical address and what is a physical address. Now I'll write the differences and we'll stop. So one thing we have to remember, so if any program wants to get executed, that should be loaded into the main memory first. So I'll write here logical address, physical address. So first one, it was generated. Who will generate this one? Generated by CPU. The logical address will be generated by CPU. But here the physical address computed. So it will be not generated. From this logical address, the physical address will be computed by MMU. So MMU means memory management unit. So as this is a logical address, user can directly access it. So we can directly access it. Okay. So because for example, we are storing the data in my computer C drive or D drive or E drive. So directly we can access it. If we want to execute that program, so that will be loaded into the main memory, that is a RAM, okay, or a primary memory where we can't directly access it. So here user cannot directly access, but user indirectly access with the help of logical address. User cannot directly access. So here the user directly access it, so it will be visible to the user. It is a visible address, visible to the user, and it is not visible, not viewable, visible or viewable, anything, right? And this is called a virtual address. This is called a virtual address. So this is a physical address. This is a physical address. This is very important. And just now we have seen a group of logical addresses is logical address space, and here it is physical address space. It's a group of physical addresses is physical address space. Okay, so these are the differences among the logical address as well as the physical address, right? So I'll stop here and hope you understood the differences among the logical address and the physical address. So the only thing behind this one is, so whenever the program wants to be get executed, it should be loaded into the main memory. So the address stored in the logical, secondary memory is called a logical address, and the address where the program stores in the main memory is a physical address. That's the only thing you have to understand. Address binding. So here the name itself indicates mapping of instructions and data. Mapping of instructions and data, okay, from secondary memory, because all the programs will be resides in the secondary memory to primary memory. So obviously, if any process wants to be get executed, that should be first loaded into the primary memory. So this is called as a address binding. So there are three categories of address bindings. So one is a compile time address binding, and the second one load time address binding, and the third one execution time, or we can also call it as runtime address binding. So the address binding means just a mapping of instructions and data from secondary memory to primary memory. So the conversion of a logical address to the physical address, simply we can say. If the same thing happens during the compile time, we call it as a compile time binding. If it doesn't happens, then it have to wait until it comes to the loading. So if the same process done during the load time, okay, during the loading, linking and loading, so then it is called as a load time. And even during the execution, if the process wants to be moved from one memory to another memory, then we can call it as an execution time. So here it will generate absolute code. So if we know the memory where the process resides exactly, okay, during the compile time, then it is called as an absolute code. And if we don't know the exact location where the process is moving, so then it have to wait until the load time. So here we will call it as a relocatable code. Okay, so these are the three categories of address binding, simply the conversion of logical to physical. So consider one program, okay, consider any C program, C programming or Python or whatever it may be, right? Consider any program. So it will be having a lot of instructions and data, right? So I will show you. For example, if there is a program, so this program will be having the instructions. Obviously, there will be some instructions and also some data. Okay, some data initializations. Okay, initializations. So that will be the data and instructions, and also predefined functions. So we will be using a lot of predefined functions. For example, in C, if you want to work with the strings, there are a lot of string handling functions. There are predefined functions. So we are supposed to insert the, we have to include the string.h header file, right? So predefined functions will be there, and also we'll be having the user-defined functions. So these are the functions which we are going to write in the program outside the main function. So these are all the things which will be available in the program. So first, the program is called as a source program. Yes, yeah, source program. So this source program will be given to the compiler. So whatever it may be, not only the compiler, we can call it as a translator. Okay, so either it can be compiler or interpreter or assembler, whatever it may be. So it will convert into the machine code. So obviously the result is a object code. So sometimes we can also call it as an object module. Okay, object module. And this object code will be given to linker. What is this linker? So as the name itself indicates, it links all other object files. What are the all other object files? We are going to use a lot of predefined functions here. So these predefined functions object code will be available in the header files. For example, string reverse, strrev, string reverse. So this function object code will be available in string.h. For example, string length, strlen. So this object code will be available in string.h. Okay, similarly power function, this object code will be available in math.h. So all those object codes of these particular predefined functions will be linked into our program. So other object files will be linked here. After that, we will be getting executable code. So which is ready to execute. Okay, which is ready to execute. And from this executable code, so if it generates the executable code, so what happens? The next one is ready to execute. Okay, that will be given to the processor, and the processor will execute the code. So this will be given to the loader. So we know loader means it will load the program to the main memory, because only from the main memory only the CPU will execute the code, right? So it will be given loader, and from that loader and there will be program in memory. So the program will be loaded into the memory. And here there will be one more thing, that is dynamical executable libraries. Okay, so there will be some sort of libraries which can be included during this process, and I mean during the runtime. So for example, in C language there is a concept called dynamic memory location. So dynamic memory location means during the runtime the memory will be allocated. So that type of things will be happens here. Okay, so here see, this process is called as a compile time address binding. So here itself we will be knowing the where the exact position where the source code will be copied. The process will be copied. Okay, the process will be moved into the memory. And if it doesn't happen here, the next process is here. It is a load time. Load time. So it have to wait until it comes to loader. So till here it will be waiting, and this here it will be I mean the process will be loaded into the main memory. Okay, and the next one is the last one. This is the executable time. Executable time. So if the process doesn't allocate, I mean the memory was not allocated to the process where exactly resides in the main memory in compile time or load time, then during the runtime or during the execution, the process will be moved into the main memory. So best example is a dynamic memory allocations in C program. Okay, so this process we call it as an address binding. That means, so only one concept behind this address binding means the CPU only execute the process, and the CPU will execute the process only from the main memory. So even though the processes are waiting in the, I mean residing in the secondary memory, that should be loaded into the main memory for execution. And also whatever the user defined functions which are written in programs, so that will be residing in the secondary memory. And whenever the program executes here, so it will be calling these user defined functions from the user defined from the secondary memory to the main memory. So in order to save the memory or memory efficiency, so these user defined functions, we can sometimes we can also call them as a routines. So these such type of functions will be available in the secondary memory. So obviously we know that if the user defined function, that will be executed only if there is an function call. So if there is a function call, immediately the corresponding user defined function will be loaded from the secondary memory to the main memory. So until the user call, the function call, the user defined functions will be residing only in the secondary memory. So such things will be done during the executable time. Swapping. So the swapping means, so we know that the CPU will be executing the process only from the main memory. So the CPU can access the process from the main memory itself. It can execute. So if the process is available in the secondary memory, so then that should be loaded into the main memory before it gets executed. So this process of moving in and out from the main memory is called as a swapping. Okay, so in and out of process from main memory is called swapping. So where this swapping is exactly useful, so this will be useful in multi-programming. So whenever we want to execute a multiple processes, okay, so multi-programming. So in the concept of multi-programming, in order to give an efficient memory management, so then it will be using. So it improves the efficiency of memory management. So it should be very careful, right? So the memory management is very important concept, very important. So for example, there is a main memory. Okay, there is a main memory. So in that main memory, one part will be the operating system. The next parts will be the user space where we'll be having the processes. For example, let us say P4. So, and the next one is a secondary memory. This is a secondary memory. Okay, I'll write here secondary memory. And this is a primary memory or a main memory. Anything you can write. Okay, primary memory and a main memory. And this is a CPU. So here there are different processes that are waiting for execution. For example, here there will be P5, P6, P7, and P8. There are 4 more processors waiting for its execution. But already CPU is executing these processes P1, P2, P3, P4. So now the primary memory, so we know that primary memory will be very less in size. Okay, very less in size. So it can accommodate only the 4 processes. Let us imagine. Okay, 4 processes are being executed by the CPU. So here the swapping will also improve the CPU utilization. CPU utilization. That's also most important, because we need not. So there will be multiple processes that are being executed, right, in the multi-programming. So in such a case, we should not keep this CPU idle, because the only processor is the what to execute all these processes. Okay, the processor will execute the processes. So we should not make the CPU idle state. So for example, so there are 4 processes which are being executed by the CPU, and now imagine if P2 is waits. P2 waits for IO. Okay, I'll write here. So for example, P2 waits for IO operation. Okay, who will do this IO operation? CPU doesn't do this IO operation. Okay, CPU doesn't do this IO operations. So who will do this? Operating system will do the IO operations. So until the IO operation completes by the OS, the P2 can't be executed by the processor. So one processor is in a wait state. So in a process states, we have studied about a waiting state and ready to run state. Okay, waiting state, when the process becomes to waiting state, means if the process gets any interruption, or if the process wants to complete the IO operation, then immediately the process will comes to the waiting state. Okay, so if the process is in waiting state, the CPU will be in idle, because among 4, 1 is in a waiting state. Imagine, instead of 1 in waiting state, why can't we load another process which is ready to get executed into the main memory? So instead of P2, so why can't we load P5 to execute, to complete its execution? So during the waiting time of P2. So in such a way, now what happens means P2 will be loaded back into the memory. P2. So this is called swap out. So swap out. So it goes out from main memory of primary memory. So see, in and out. So one process we are loading into secondary memory. We are moving the process which is being waited. Okay. So if the process is executed, is under the execution by the CPU, so we can't do that. So if the process is in a waiting state, so because of any IO operation or any interruptions, then immediately that process will be swapped out from primary memory to the secondary memory. Now in this empty space, the another process will be loaded. So this is called a swap in. So meanwhile means during the P2 completes its IO operation, we are loading one more process to the primary memory. That is called a swap in. So incoming to main memory is called a swap in, and outgoing from the main memory is called a swap out. So why this swap in and swap out means, so in order to avoid the CPU idle time. So we can't make the CPU in an idle state. So we must make the CPU in a busy, because these many processes are still waiting for complete its execution. Okay, now this completed. Now the next line is a P6. So if any one process among these 4 are still in a waiting state, for example, P4, the process 4 is having some interruption. Okay, it's having some interruption. So automatically again P4 will be swap out to the secondary memory. Swap out. So this is a P4 and this is a P2. So here P4. So meanwhile P6 will be inserted into main memory. This is a swap in. Swap in. So like that, whenever there is an interruption or in any circumstance, if any process wants to be in a waiting state, immediately that process will be loaded into the secondary memory. That we are calling it as a swap out, right? So hope you understood. And this will also be used if the process is higher size than the RAM. Large size of process can also be executed in such a way. Okay. So hope you understood this one. Swapping means in and out. The main thing is in and out of process from main memory is called a swapping. So from main memory to secondary memory. So here it will be, see, memory management. So the topic name itself indicates how the memory will be managed in our operating system. So this is one very important feature of operating system. Okay, so we can also say this is a resource. One of the resource. So we need to utilize the resource efficiently. How efficiently we can utilize the resource? For example, if there is a CPU, so we know that CPU is nothing but a processor, right? So any process in the operating system will be executed by the CPU. Now, where are the processes? So processes will be residing in the secondary memory. So this is the secondary memory. So from the secondary memory, so here the processes will be residing. The processes, okay, process 1, process 2, etc., etc. So these processes will be stored, the files, simply we can say the files will be stored in the secondary memory, and the CPU can be getting the files from the main memory. That means CPU can execute the instructions only from the main memory. So what we have to do, so whenever a process wants to get executed, that process will be retrieved to the main memory. So this is the main memory. So this process will be retrieved to the main memory, so that the CPU can be accessing the processes from the main memory and it will be executed, and those processes will be executed. Now, see, this we can call it as a RAM. Okay, RAM. So whenever there is a power off, automatically whatever the information stored in this main memory, that will be erased. But secondary memory, so if even though there is a power off, the data which will be available in the secondary memory will be safe. So only the CPU will be executing the processes which are available in the main memory. So immediately whatever the process wants to be get executed, that will be copied to the main memory. So everything will be taken care by the CPU. Okay, everything will be taken care by the CPU. CPU is nothing but a process. Okay, and in the CPU there will be one more memory. Okay, so this memory we call them as a registers. Registers, very small size. Registers will be very small size, and in between the main memory there is a one more memory called cache memory. Cache memory. So cache memory means the frequently used instructions or the frequently used processes will be available in the cache memory. Okay, so this cache memory will be in between main memory and the CPU. So the accessing will be somewhat speed than the main memory. Okay, so it will be loading into the cache memory, from the cache memory CPU. So here the hierarchy is whenever the process wants to be get executed, first the CPU will be checking that process whether it is available in the registers or not, because these registers are inside the CPU only. Those registers are designed inside the CPU only, right? So first it will check in the registers. If not, it will check into the, so this is the first one. If not in the registers, then it will check in the cache memory. If there is no cache, if the process doesn't in the cache memory, this is the third place where it will check. If this place also there is no process available, then it will find the process in the secondary memory, and from that secondary memory it will be copied into the main memory, and directly from the main memory it will be executed. If the same process is being executed multiple times, that process will be loaded into this cache memory. So here the operating system means how efficiently this memory will be utilized. Okay, so there will be different types of addresses, logical address and the physical address. So in order to load the data from secondary memory to the main memory, it requires some addresses, and it requires some address binding also. So the complete information about the addresses, different types of addresses, address boundings, and everything comes under this memory management. So how efficiently utilizing the resources? We are saying memory is one resource. Okay, now the three criteria we need to discuss in this particular memory means the first one is size. Okay, the first one is a size, and the next one is time to access or access time to access, and then the next one is cost. See, we need to use the same thing. We have seen four types of memory in this session, right? One is the registers, okay, which are very close to CPU, cache memory, main memory, and a secondary memory. Coming to the size, okay, so I'll write here, right? Size. According to the size, see, registers are very small in size. Mostly it will be in terms of bits only, 64 bits or 128 bits. So registers will be occupying, the size of the registers are very less. So first comes under registers. So I am writing the size low to high. Okay, low to high. The size is low for registers first. Then cache memory, which are larger than registers, but they are also very small. So cache memory. Next, coming to the main memory. So main memory will be the capacity or the size of main memory is more than cache. Okay, more than cache, but smaller than secondary memory. So the next comes under the main memory. And finally, we are having secondary memory. Secondary memory will be high when compared to the remaining. So this is low to high. This is the information from low to high. Coming to the second, time to access. Time to access. So coming to the time to access, see, registers are very close to CPU, so the access time will be very less. So it will be very speed to access the data, because memory, these registers are inbuilt in the CPU. So the accessing the data from the registers will be very fast. So access time comes with the registers according to speed, based upon speed. Okay, registers are fast accessing, right? And next, cache memory, so which is in between the CPU and main memory. So the next category is cache. The time to access the data will be fast, okay, and the access time will be somewhat more when compared to the memory. And next comes with the main memory, and next comes with the secondary memory. So if any process or a file that is available in the secondary memory, the access time will be more. Okay, the access time will be more. So if the data is available in the main memory, so the access time will be better when compared to the secondary memory. And if the file is available in the cache memory, the access time will be better when compared to the main memory. And if the data is available in the registers, then that will be the very, very best to access the data, because that is far close to the CPU. Okay, so this is about time to access time. Coming to the cost, okay, based upon the size, it will be expensive. Okay, if size is low, it is more expensive. So this coming to first comes with the registers. The expensive high to low. Okay, high to low, cost high to low. So registers will be very high, and then comes with the cache memory. When compared to the register, somewhat low. Next one, main memory. So when compared to the cache, main memory is somewhat low. And the next one is secondary memory. Okay, so if you talk about the memory, we need to know about the size of the criteria to access based upon the size or time to access or cost. So here we have seen different categories of memories, and now from the next session we are going to discuss about how the processes will be transferred from secondary memory to the CPU. So here, transferring the data from secondary memory to main memory or main memory to CPU is in terms called as a swap in and swap out. Swap in means loading, swap out means sending. So here we are going to use a different addresses, logical address and physical address. So all these things we will be discussing in our further sessions. So how efficiently we are using the memory, how efficiently we are making the process moving from secondary memory to main memory and main memory to the CPU. So once again I am saying, any process will be executed only by the CPU, only through the main memory. If the process is in secondary memory, the CPU can't access the file directly from the secondary memory. The CPU can only access the file from main memory or cache or registers. Methods. So there are possible methods, 3 methods are there where the memory will be allocated to the process. So one is first fit, another one is best fit, another one is worst fit. So actually the complete memory will be divided into different blocks. So we know that the primary memory, particularly the primary memory, okay, will be divided into 2 parts. One is a OS, another one is a user space. And this user space will be divided into different partitions, that may be fixed partitions or variable partitions. Now we have studied that this will be the secondary storage. Okay, this is a secondary storage. So where the processes should be loaded into these particular user spaces. So we have to allocate this particular partition to the process. So the process should be loaded into the main memory. So this is the main memory. So that from this main memory, the CPU will be executing that particular process. Now these are the methods: first fit, best fit, and worst fit are the 3 different methods. How many ways or how we are moving or allocating this particular partition to the process. So let it be P1 and P2, process 1 and process 2. On what basis we are just moving this process to the main memory? That's the methods: first fit, best fit, and worst fit. So coming to the first fit, we have to select the first partition that is enough to accommodate the process. So among all the partitions, we need to select the first partition, so where the process can be accommodated. Okay, and coming to the best fit, so here least partition which can accommodate a process. So here the least means based upon the size, least size. Okay, least size. So with respect to size. And coming to the worst, which is an opposite to the best fit, that is a maximum partition. We need to select a maximum partition where process can be accommodated. So these are the 3 different methods. In the first fit, we need to select the first partition where the process can be accommodated. In the best fit, among all the memory partitions, we need to select the least size partition where a process have to be accommodated. Coming to the worst case, we need to select the maximum partition where the process can be accommodated. Okay, so this is the difference. These are the 3 different methods how a process can be allocated to the memory. A memory can be allocated to the process. Sorry. So let us see a small example. So we will take a memory blocks, the capacity of the memory block and the process. So how can we accommodate in first fit, best fit, and worst fit, right? See here, we have taken a simple example. So these are the memory blocks, the size of the partitions. Okay, let it be a variable partition. Okay, imagine that this is a variable partition. So the partition sizes are 100 KB, 500 KB, 200 KB, 300 KB, and 600 KB. So based upon that, we have taken the three diagrams. One is for first fit, best fit, and worst fit. And next one is a process sizes. So there are 4 processes we have taken. So let it be P1, P2, P3 and P4. So there are 4 processes of different sizes. So P1 with the 212 KB, P2 with the 417 KB, P3 is 112 KB, and P4 is 426 KB. Now the question is, how can we accommodate this process into the memory blocks, which will be selected? Okay, so coming to the first fit, as we said that the first fit always select the first partition where the process can be accommodated. First, let us take this process P1 212. So check here, this is a partition with 100 KB. So 212, so 100 KB is a first partition. So 212 can't be accommodated in 100 KB. So it will move on with the second partition. So 500 KB, 212 KB can be accommodated in 500 KB. So process 1 will be moved into this particular partition. So this memory will be allocated for P1. Okay, and next 417, first partition 100 KB. Not it is not possible to accommodate. 500 KB already P1 is accommodated here. Next 112. So sorry, 417, 200. We can't accommodate 417 in 200. Next 300, 417 can't be accommodated in 300. Not possible. Next 417 can be accommodated in 600. So P2 will be loaded into this particular partition. And similarly 112. So coming to the third process 112, which cannot be accommodated in 100. 500 is already available. I mean already accommodated. 200, yes, 112 can be accommodated in 200. So P3 will be loaded into this partition. Next 426, first partition. So always first bit will be assigning the first partition only. So 426 can't be accommodated in 100 KB. Moves to the third one 300. 426 can't be accommodated in 300 KB. So here P4 can't be accommodated here. And one more thing you can observe, P1 is 212 and almost 288 KB of space is a wasted here. Okay, P1 is only of size 212. And what about the remaining 288 KB memory? So that will be wasted here. Okay, so that's the main drawback of this particular first fit. Okay, so memory, there will be a possibility of internal fragmentation. Internal fragmentation means memory wastage. Okay, much memory will be wasted here. And moving on to the best fit, what we have said, so the least partition based upon the size, least partition which can accommodate the thing. So first one is 212. So 212 can be accommodated in 500 KB, 300 KB and 600 KB. See, 212 KB process can be accommodated by this partition, either this or this. Among these, which one we have to select? We have to select the least size partition. What is the least size? 300. 500, 300, 600. 300 is the least size partition. So P1 will be accommodated by this particular partition. Okay, so we need to select the least partition with respect to the size. Next 417. 417 can be accommodated with 500 and 600. Among these two, which one is the least? This one. So P2 will be accommodated by this partition. Next 112. So 112 can be accommodated in 200 as well as 600. So if P3 is accommodated in 600, much amount of memory will be wasted. Much amount of memory. So we are selecting the least one, that is 200. So P3 will be accommodated here. And P4 426. So only one partition which can hold this P4. So assigning P4 to 600 KB. So this is the best way. This is the best way, but it will be very slow process. Okay, in first fit the memory will be wasted. In best fit the memory utilization will be very effective, but it will be the very slow process. Coming to the worst fit, so instead of selecting the least address or least partition with respect to size, we are selecting the highest partition with respect to size. So just quite opposite to the best fit. For example, 212. So 212 can be accommodated in 500 KB, 300 KB and 600 KB. So we need to select the highest. So in 600 KB, P1 will be accommodated. Okay, quite opposite to the best fit. Okay, next 417. 417 can be accommodated in only 500. So obviously P2 will be here. Next 112. 112 can be accommodated in 100, 200 or 300. So sorry, 100 is not possible, either 200 or 300. So among these two, which one is the largest? 300. So we need to assign P3 in largest partition. Next 426. So there is no partition which can accommodate the 426 KB. So this is also a drawback. So here it is not effective, not efficient. It is not efficient and much amount of memory will be wasted. You can see here P1 212 and we are giving 212, we are moving this 212 process to the 600 KB. So that means a lot of memory will be wasted than the first fit or a best fit. Okay, so a lot of memory will be wasted. So that is a drawback here. And this is effective, the memory utilization will be effective, but a slow process because we have to compare everything. And here It's also not possible because much memory will be wasted here also. Fragmentation, internal fragmentation is more, and here also internal fragmentation will be more. So these are the different memory allocation methods, how the process can be accommodated to the memory, how the memory will be allocated to the process, in what type of methods, the first fit, best fit, and worst fit. Fixed partitioning. So this fixed partitioning is also called as a static partitioning. So also known as static partitioning. So why we are calling it as a static partitioning means, so before the processes are started loading into the main memory, the complete main memory will be divided into blocks. So the main memory will be partitioned during configuration itself. Configuration, right? And also the name itself indicates fixed, that means fixed number of partitions. So main memory will be divided into fixed size partitions. Fixed size partitions, or we can say fixed number of partitions. So here, see, observe, fixed size means partitions can't be modified. So constant number of partitions, constant number of partitions. So there will be a little bit confusion that fixed size regarding this fixed size. So here the fixed size means a constant number of partitions. That doesn't mean that each and every partition should be of same size. Okay, so here size of individual partition may or may not be equal. See, this is the most important point. Okay, the size of individual partition may or may not be equal, right? So but here the complete memory will be divided into equal, a fixed number of partitions. That means those partitions can't be updated in further. For example, let us take a main memory. So this is a main memory. So this is a main memory, and we know the first part of main memory will always be the operating system. So operating system will be loaded, and this is a user space. Okay, this all is the user space, and this user space will be partitioned. Okay, so for example, so this is the partitions. Okay, for example, this is of 10 MB, this is of 15 MB, and this size is of 7 MB, and this size is of 10 MB, and this size is of some 8 MB. So you can see 1, 2, 3, 4, 5. So total 5 partitions. Total 5 partitions. So this architecture will be having only 5 partitions. So we can't able to modify these partitions. And these partitions, as we mentioned here, these partitions will be done during the configuration itself. So fixed size, that implies the number of partitions will be fixed. And another category, see, another possibility, not a category, another possibility. So let us say this is a main memory, and the first part of main memory is operating system. And see, for example, you can see 10 MB, 10 MB, 10 MB, 10 MB, 10 MB. So you can see here also we are having a 5 partitions, and each and every partition is having the same size. So this is also comes under the fixed partition. So this architecture is having 5 partitions which can't be changed, and here also we are having 5 partitions. But the difference among these two is, in this case, each partition, individual partition size is not equal, and here in this case, each and every partition size is equal. For example, our see, we are having 5 processes: P1, P2, P3, P4, and P5. So P1 is of some 4 MB, P2 is of some 10 MB, P3 is of some 5 MB, process P4 is of 9 MB, and P6 is of some 6 MB. So for example, these are the processes we are having, and these processes should be accommodated by these partitions, into these partitions. Okay, so in this case, in our just previous session, we have seen the memory allocation methods: best fit, first fit, and worst fit. Among these 3, we have to choose one thing, and we have to accommodate each partition to this process. I mean, we have to allocate the process to this particular partition. We have to load the process into the main memory. For example, P1, 4 megabytes, 4 MB. So let it be 4 MB. The 4 MB process can be loaded. If you are going with the first fit, the first partition which is having more than 4 will be accommodated by, will accommodate this particular process. So 10 MB, so 4 MB can be accommodated here. So we can simply write it as P. I'm using the first fit. So I'll post the link of these allocation methods: first fit, best fit, and worst fit, in the description, so that you can refer that one, right? So coming to here, I'm going with the first fit. So if P1 is 4 MB, the first largest is a 10 MB, so P1 will be accommodated here. P2 10 MB, the next one is this one, yes, P2 can also be accommodated here. P3, yes, P3 can be accommodated here. And P4, yes, P4 can be accommodated, and similarly P5 can also be accommodated. Okay, if it is a first fit. So here, this is how the fixed partitioning will be implemented. So if it is a static, then there will be less overhead on operating system while accommodating the partition to the processes. Okay, less overhead because of this static. Okay, it requires a minimum resources to allocate the memory to the particular process. And also, this is a static, it's a very easy to implement. Very easy to implement this fixed partition. So these are all advantages. All these are advantages. And there are a few drawbacks here. Very few drawbacks. So I'll tell the drawbacks. So first drawback is internal fragmentation. What is this internal fragmentation? So drawback of this one is internal fragmentation. Internal fragmentation is, for example, if you see P1 4 MB, so some portion of this part is empty, some 6 MB of space is wasted. Coming to the second one, some 5 MB of space is wasted, for example. I'll write here. Okay, so wastage. So I'll write this here. It is a first fit. I'm using the first fit method. And in this, how much? Some 6 MB is wasted, and here some 5 MB is wasted. Coming to the P3 is 5 MB and it is 7, so 2 MB is wasted. And coming to the P4, it's at 9 MB, here 10, so that means 1 MB. And P5 is 6 and 8, so 2 MB. So all these memory is wasted. Okay, right? So each and every individual partition, the wastage of memory, okay, the wastage of memory, unused memory in individual partition is called as an internal fragmentation. So that means some sort of memory will be automatically wasted for every partition. Here you can see, okay, some amount of memory. So that is the main drawback here. Okay, so here one more thing is, one process can be placed in one partition. See, so this is also most important. One process can be placed in only one partition. One process can't be placed in two partitions. So once again, one more, no overlapping. So because only one process can be placed, so there will be no overlapping on the partitions or process. So the internal fragmentation, the amount of space wasted in each individual this partition. Okay, this partition is also called as a fragmentation. Okay, every partition we can call it as a fragment. Okay, that fragment. So internal fragmentation means inside each and individual partition, if the amount of memory is wasted, is called as an internal. And coming to the second one, external. Obviously, there will be an external fragmentation. That's one more disadvantage. External fragmentation. External fragmentation means if you add all these things, see, overall in complete main memory, see 6 plus 5 11 and 5 16 MB of space is wasted. Okay, from entire main memory. For example, if you want to allocate P6 with a 10 MB, okay, there is no partition available here, and we are saying that only one process can be placed in one partition, so P6 can't be accommodated in any one of the partition. So see, already available space in main memory, so available space, that means unused space or free space in main memory is 16 MB, which is greater than P6, that is a 10 MB. Even though we can't load this P6 into this 16 MB, we can't accommodate the process into this unused free space. So how we are getting this free space means adding all the free space of the main memory, right? That we call it as an external fragmentation. So this 16 MB is called as an external fragmentation. Okay, the next one, limited number of processes can be accommodated. For example, you can see, as we are saying that a fixed partitioning, so during the configuration itself, this main memory will be partitioned. So here only 5 partitions have been done. So we can't accommodate 6 partitions. We can't accommodate more than 5 partitions into this main memory, right? So that is one drawback, the limitation of number of processes that are being, so the number of partitions divided, that many processes can only be loaded at a time. That is one drawback. Another drawback, limited number of partitions also. So processes and partitions. So as we are saying it is a static partitioning. So whatever the partitions that has been done during the configuration, that will be fixed. So we can't able to change it, okay, in further. So that's why we can't change the partitions also. There will be a limited number of partitions which can accommodate the processes. That is one of the drawback. Okay, so these are the drawbacks and these are the advantages. Advantages: less overhead on operating system because everything will be done during the configuration itself. So minimum resources will be required. And coming to the very easy to implement this fixed partitions. And drawbacks: internal fragmentation, external fragmentation. So memory will be wasted. And coming to the limited number of processes as well as the partitions. So this is all about our first technique in contiguous memory allocation, that is fixed partitioning. So once again, I am concentrating about fixed size partitioning, means the number of partitions will be fixed, but the size of each partition may be fixed or may not be fixed. So see, this is important. So the first point, so these partitions will be used in a multi-programming. So whenever we are dealing with the multi-programming, then these memory allocation techniques will be used. Because, so coming to the uni-programming, so we have seen in different types of memory management techniques, right? In that video we have seen the two categories, that is a uni-programming and a multi-programming. So where uni-programming, only one process can be loaded into the main memory at a time. So there will be no problem with that. Okay, after one process, the another process will be coming. But coming to the multi-programming, multiple processes will be waiting for the CPU. So multiple processes can be loaded into our main memory. So then we'll be having the problem. So where and how much memory should be allocated? So in that we are using this variable partitioning. So this will be suitable for multi-programming. Suitable for multi-programming. And the next immediate point is, so depends upon the partition size, the partition will be created during runtime. So these partitions, so we can call them as a partitions or fragments or holes. Okay, and these partitions can be done during runtime. So this is called as a dynamic partitioning. So if we want to load a process into this main memory, so based upon the size of the process, okay, based upon the size of the process, and the partition will be created, right? So based on process size, the partition will be created during runtime. Okay, so that's why we are calling it as a dynamic partitioning. So also known as dynamic partitioning. Right, also known as a dynamic partition. So there will be no overlapping. Here also there will be no overlapping. No overlapping of partitions. And here also only one process can be loaded into one partition. So there will be no overlappings. Okay, one partition. So example, let us take an example. This is the main memory. So the first part will be always the operating system. Let us take partition 1, partition 2, partition 3. And this is of 10 MB size, process P1. This is of 5 MB size, partition P2. This is of some 7 MB size. Okay, so during runtime, so all these will be the free memory. Okay, so this will be the free space or a free memory, unallocated memory. We can call it as an unallocated memory. Now, whenever P1 wants to store into the main memory, what is the size of P1? 10 MB. So from this free space, 10 MB of space will be allocated, created, and P1 will be loaded into here, right? And coming to, and all the remaining is a free space. Okay, all the remaining is a free space. So whenever P2 wants to load into the main memory, and again this from this free space, only 5 MB. So P2, only 5 MB size partition will be created, and P2 will be loaded into that partition. And now coming to the P3, 7. So one more partition with 7 MB will be created, and P3 will be loaded, and all the remaining will be the free memory or unallocated memory. So we can accommodate some more processes into this free memory until the main memory is full. Okay, until the main memory is full. Okay, so during the runtime, depends upon the size of the process, these partitions will be created. So that's why we are calling it as a dynamic partitioning. Now, what are the advantages of these dynamic partitioning? So you can observe. So advantages. So the first advantage is, so there is no wastage of memory. Okay, so in fixed partitioning, so all the partitions will be with a fixed either fixed number of partitions or a fixed size partitions. So there we have noticed that there will be an internal fragmentation. So obviously, if the partition size is less than, it's a greater than the process size, some memory will be wasted because all the partitions are already created during the configuration itself, right? So obviously there will be some wastage of memory, that we are calling it as an internal fragmentation. But here depends upon the process size we are creating the partitions, so there will be no wastage of memory. So the first advantage, no internal fragmentation, which is a drawback in variable size. Fixed size. No internal fragmentation. There will be no internal fragmentation. And another one. So number of processes can be. It is not limited to the process size. Okay, no limitation of process size. No limit on processes or process size. So if P4 is of 50 MB. And if there is a free memory, automatically 50 MB can be loaded into this particular partition. So there is no limit on the process size or processes. Number of processes can be accommodated in the main memory until there is a free space in the main memory. So these two are the advantages. No internal fragmentation. Coming to the disadvantages, I'll write here. Disadvantages. See. So during runtime, the partitions are being created. So complex to implement this kind of architecture, somewhat complex when compared to the fixed partition. And the second one, there will be external fragmentation. So this is a common external fragmentation. I'll explain you. There will be a possibility of external fragmentation. For example, let us take here a few more processes. See, let it be P4 50 MB and P5 20 MB, for example. Okay, so 20 MB. Now, so all the memory has been filled. Okay, complete memory has been divided into partitions. Now, there is a one more process we want to load into the main memory. Okay, so which is of some 10 MB. But here there is no space to accommodate this process. So meanwhile, P2 completed its execution and P3 completes its execution. Okay, for example. Okay, so let us take P2 and P3. See, P1 completes its execution 15 MB. Okay, P3 completes its execution. Now you can observe in this example. So one process we want to accommodate, which is of how much? 15 MB space. Okay, 15 MB size. And here we are having, so total free memory in this main memory is 10 plus 7 because P1 completes its execution as well as P3 completes its execution. So total free memory is 17 MB free memory. So we know that if there is a free memory, we can easily accommodate a process into that free memory. But here these two are not in a contiguous memory locations. So this partition is already allocated, created. So these two, the complete 17 MB is associated with two different partitions. So we can't combine these two partitions. Okay, so here we are having the external fragmentation. So that is a one drawback in this particular variable partitioning. So one thing can be overcome this external fragmentation by using the process called compaction. We can avoid the external fragmentation by using the word compaction, the process compaction. Compaction means, so all the processes will be loaded top and all the free memory will be allocated down, and all the free memories will be merged and forms a single partition. For example, the compaction of this one will be, so you will be seeing P2. So P2 will be allocated here with a 5, and P4 is allocated here. P5 is allocated here with a 50 MB, and yes, P5. This is P4. P5 is allocated here with a 20. Okay, and all the remaining free space will be joined here, right? So what is the free space? 17 MB is the free space. So this is a free space. So obviously what we are doing, so we can accommodate this P6 into this particular free space. Okay, this process we call it as a compaction. Okay, making the partitions, combinedly making these partitions in a free space to avail or to accommodate one more process. Okay, so whenever a process wants to be loaded into the main memory, so first it will check whether the size fits with the already available free partitions or not. So already partitions are here. Now for example, after some time P7 should be accommodated with some 10 MB. Okay, and P4 completes its execution, see, P7 can be accommodated here. So that's why first it will check with the available partitions, whether available partition can accommodate the process or not. If not, then it will go with the compaction process. So is it possibility to join two or more free space partitions to make a single partition. So if there is a availability, then automatically P7 will be loaded into that particular partition. If it is not availability, then it will go with the compaction. It will check for the compaction. Okay, all these happens only when the main memory is completely allocated with the processes. If there is a free space in the main memory, there is no question of compaction also. So directly one more partition will be created and process will be accommodated in that particular memory. So when the complete memory is filled with all the processes, then if one more process wants to be loaded into the main memory, in such case it will check for the free partitioning, whether this process can be accommodated or not. If not, then it will go with the compaction. Right? Yes. So this is called a variable partitioning. So advantages, no internal fragmentation and no limit on the process size or a process. And one disadvantage is complex, because during runtime it have to create the partitions. So somewhat complex when compared to the fixed partitioning. And another one is an external fragmentation. External fragmentation. Table. So we have discussed that there will be two memories, the secondary memory, which will also be called as a virtual memory, and the physical memory, which is called as a primary memory. So whenever a process wants to be get executed, the process should be loaded from the virtual memory, that means secondary memory, to the primary memory. So that means there are different addresses. So in the virtual memory, the address we call it as a logical address, and the memory of primary memory, the address of primary memory, we call it as a physical address. So there should be a conversion between a logical address to the physical address. And after that, we have seen the concept of paging. So paging means dividing both virtual memory as well as the physical memory into pages and frames. So that we have seen in our previous session, right? So a process which resides in the CPU will be divided into pages, and physical memory will be divided into frames. And one important point is the frame size and the page size both should be equal. So in between these two things, that means a physical memory and the virtual memory, there will be a page table where there will be each and every entry of a page which is referenced to the frames. That means where the page has been loaded into the physical memory, right? So page table gives the frame number where the page has been loaded in physical memory. So for every page there will be an entry. Okay, so see, this is a page table. And see, this is the CPU. So CPU, that means the virtual memory or a secondary memory. For example, there are a few pages. Okay, so a process is divided into 5 pages. So here P stands for page, right? P1, P2, P3, P4 and P5. Page. Okay. Now, as we said that this paging is a non-contiguous memory locations. So these pages can be loaded into the primary memory, not in a contiguous memory location. For example, let us take here, this is a primary memory. This is a primary memory. Okay. So this is a primary memory. And the primary, as we discussed it here, the paging means dividing both process as well as, virtual address, virtual space as well as a logical physical space will be divided into frames and pages. So this is divided into pages. This is a process, and here it is a frames. Let it be F0, F1, F2, F3, F4, F5, F6 and F7. Okay, so this is a page table. This is a page table. So whenever the CPU wants to execute a process, first it will generate the virtual address, and which is where the page or a process resides here. Okay, so this will be loaded into these frames, not in a contiguous memory location. So how? So based upon the availability of a frame, the page will be loaded. For example, P1. So here this is a pages. Okay, these are pages, and these are frames. And these are pages. Now, see, based upon the availability, P1 can be loaded here, P2 can be loaded here, P3 can be loaded here, P4 and P5. You can observe P1 is loaded in frame 2. So based upon the availability, the pages will be loaded into the main memory. On this we call it as a physical memory. Physical memory. Now, in this page table, okay, so these are the pages P1, P2, P3, P4, P5, 4 pages. Now, what is the available of P1? So this page table will be having the corresponding frame numbers. Okay, frame numbers. So P1, where it has been loaded? F2. So the page number, the frame number will be loaded here. And similarly, P2 is loaded in frame 4, so F4. P3, F7. P4, F0. P5, F5. So the corresponding frame number, not only the frame number, there are some optional bits, so which may also have the permissions. So apart from this frame number, so there will be a lot of options will be available in each and every entry of this page table. Now, coming to this thing, how the logical address will be converted into physical address. So how the CPU finds the page which is available in the physical memory. So first, it will take the complete page, so which will be having the page number and corresponding displacement. So here the displacement means, so a program or a page will be having a lot of instructions. We are saying a process is a lot of set of instructions. Okay, a process we call it as a set of instructions. For example, let us take one program. Okay, let us take one program. So one program will be having multiple lines of code, right? Set of instructions. Each line we can call it as a set of instructions. So the page 1 and corresponding instruction. So whatever the instruction that is available, that instruction we call it as a displacement. Okay, so this is a logical address which gives the logical address, the page number as well as displacement. So it goes here and it will go with the frame number, so F2, and finally the same displacement, which gives the physical address. So in this way, okay, in this way the conversion of logical address to physical address will be done. Okay, so first, how the CPU know the exact location of the physical memory, physical address of that particular page, means it will get the page number along with the displacement which gives the logical address, and here in the page table entry there will be a frame number in which this page has been loaded. So that frame number plus again the same displacement combinedly we will be getting the physical address. So that is a reference to the physical memory, right? Now the question is where this page table will also be residing, so where it will be available. So this page table will also be available, I'll write here itself, available in main memory only. Main memory only. So the page table will also be in main memory. Okay, and the next question, if the process, each process will be having different page tables, or all the pages of processes will be available in the single page table. Hope you understood. Every process will be divided into pages. So if we are talking about a multi-programming, so if you are talking about a multi-programming, we know that multiple processes will be loaded into the main memory for execution. So multiple processes means every process will be having different pages. So the process is divided into different pages, right? So the question is whether all the pages of all the processes will be available in a single page table or multiple page tables. Obviously, the result is every process will be having different page tables. Every process will be having different page tables. So every page table will be having the entries. And the main reason or main aim of this page table is to convert the logical address into the physical address, to map the logical address to corresponding physical address, right? So hope you understood. And the advantages of this page table. What are the advantages? So no external fragmentation possible. No external fragmentation. That is the most important. So we have seen this will be the drawback in contiguous memory locations, right? So here that doesn't happen. And the next one, so effective memory management. Effective memory management algorithm to convert the logical address to the physical address. Okay, it's effective. And obviously there are some disadvantages. So whenever we are saying a page will be loaded into the frame, obviously there might be a chance of having the internal fragmentation. So one possibility is internal fragmentation. Internal fragmentation. So the next disadvantage is it requires some more memory to load different page tables, because we are saying every process will be having its own page table. So it requires some more memory to store different page tables. Right? So this is all about the page table, the importance of page tables, mainly to convert the logical address to the physical address, right? And there are different structures, different ways to structure this page table, to design this page table. So what are there? First one is a hierarchical, and hashed page tables and inverted page tables. see, there are 3 different ways to structure this page table, to design this page table, right? So we will stop here, and in our next session we'll concentrate on these structures one by one. So first we'll see hierarchical, how the page table will be structured, and coming to the hashed, and finally inverted. Hierarchical page table. So this hierarchical page table is also known as multi-level page table. Also known as multi-level page table. So as the name itself indicates, see, this page table can be represented in different levels, okay, different levels. So that can be a 2 level, 3 level, 4 level. So before going to that, let us see what exactly happens in a 1 level. That means a basic, right? So we have said that there will be a CPU which will be generating the logical address. So in this logical address, it will be having, so this is the logical address. It will be having 2 parts. One is a page number, another one is a displacement or offset, okay, the location of the instruction. Now this page number will be referencing the page table, right? So this is a page table, so which will be having a lot of entries, and here, from here, they will be having a frame number, corresponding frame number. So this frame number will give, so getting the frame number plus getting this particular offset or displacement, which will give the entry in physical memory. So this is the physical memory, right? This is a physical memory. So this is the logical address. We are getting the logical, sorry, this is a physical address, sorry. So this is a physical address. So adding off the frame number plus a displacement, and here the page number plus displacement is the logical address. So this is the normal way we are having. So how many? So here the question is the page number and the displacement. The logical address is given as a page number and displacement. For example, this logical address can be represented with 32 bits. 32 bits. And see, the page size. The page size is some 4 KB. So 4 KB means, so here we are representing in bits, so we need to represent this also. So 2 power 12 bits. Okay. So here displacement, what we are saying it as a displacement or offset, whatever it may be. So this is the location of the instruction. Okay. Which instruction? Page instruction. So process can be divided into different pages, PG1, PG2, and so on, PGN. And every page will be having different instructions, offset D1, D2, D3, and so on, DN. So every page is of size 4 KB. That means a page can hold a different locations like 2 power 12 bits. That means 2 power 12 locations. For example, see, the address is 32 bits. The address is of 32 bit. So this is a 32 bit. So in the 32 bit, 12 bits, see, these 12 bits are representing this page offset. So that means D. So which is of 12 bits. What about the remaining pages? How many pages we can load? So obviously 32 minus 12, so 20 bits are representing the pages. 20 bits representing the pages. So that implies 2 power 20 pages can be loaded. Okay, see, logical address is represented in 32 bits. So I'm saying it as a maximum. Okay, so if the page size is of 4 KB, page size, okay, not a process, process will be divided into pages, and now the page size is of 4 KB. That means 2 power 12 bits. So that means 12 bits. Let us assume 12 bits to represent a page locations, the different locations of a page. So the 12 bits will be representing the instructions or offset, we are saying. And among the 32 bit, if you take 12 bits to represent the displacement or offset, remaining 20 bits are representing the pages. 20 bits are representing the pages. So a maximum of, it can represent 220 pages. Okay, 220 pages. So if the logical address is 32 bit, how many pages can be represented? 2 power 20 pages can be there. That implies 2 power 20 entries should be there. 2 power 20 entries in the page table. So imagine this page table will be having, see, the page table is having 2 power 20 entries starting from 0. This is 2 power 20 minus 1 because we started with 0. So these many entries should be there in a page table, and every page will be again representing a different locations. That is a 2 power 0 to 2 power 12 minus 1. So these many entries will be there for each and every page. So imagine this is only for a one process, and we are saying that every process will be having a different page tables, their own page tables. Every process will be having a different page tables. For example, 2 processes are there, P1 and P2. So P1 will be having a 2 power 20 entries if the size is this in this way. P2 again, it will be having its own page table with a 2 power 20 entries. So imagine that 2 power 20 entries means more than 1 million, 10 lakh. Okay, more than a 10 lakh. Million means 10 lakh. So more than 1 billion means more than 10 lakh entries should be there in each process. Okay, in each process. So automatically, in order to generate the physical address from this logical address, it will be definitely a memory overhead. Okay, it's a very complex. Okay, so one drawback is complex, too much complex in order to generate and retrieve the data. And the second important problem arises here is it is very difficult to store a one page table with a contiguous memory locations. Obviously, the page table means we will be having a contiguous memory location. So imagine that here we are having a 10 lakh entries. So 10 lakh memory location should be there, that too in a contiguous manner. So that is very difficult. So difficult to store contiguous memory locations. So these two are most disadvantages of having the single page table. Okay, one is a complex because we have seen here almost more than 10 lakh. Yes, more than 10 lakh entries will be there, not 1 lakh. More than 10 lakh entries will be there. And the second one, so finding the contiguous memories for the 10 lakh entries is difficult. This is not only for one process. If you are executing multiple processes, because all these we are discussing about the multiprocessing, right? So if we are having a 3 processes or 4 processes, that many lakh of entries should be available. So in order to avoid these difficulties, we are moving with the hierarchical page table, and we are also calling it as a multi-level page table. So in this multi-level page table, what we are doing is, so the displacement or offset is same. So here the displacement or offset is same, right? So I'm erasing this one. What we are doing, so this displacement is same, we are not disturbing it, displacement with a 12-bit representation. And coming to the page representation, we are dividing that into 2 parts. Let it be PG1 and PG2, right? So let it be, this represents a 10-bit and this is also 10-bit. Okay, 2 pages, that means a 2 page tables. We are creating a 2 page tables. So this is called outer page table. Outer page table. So what will be available in this outer page table means all the index of all the remaining page table. Okay, all the index of remaining page tables. So here one page table, for example, let us have this one. So 10 bits means it will be 0 to I think 2 power 10 minus 1, so which it will be 1023, for example. Okay, this many entries. Now you can see we are dividing the complete 10 lakh entries to 1000 entries, and what happens means this 0 will be pointing towards one page table from 0 to 1023, and this one will be pointing towards another page table which is 0 to 1023, because the second one is also 10 bit, and the third one will also be representing, I mean pointing towards the, sorry, this is 0. Hope you understood. So like this 1023 tables, the outer page table will be representing 1023 tables. Okay, the base address of 1023 tables, not all the base address of this one, right? The base address of this table will be stored at 0, and the base address of this table will be stored at 1. The base address of this page table will be stored at here. So this is the outer page table. This is the outer page table. Hope you understood. So it will be representing the actual offset. Okay, it will be representing the actual offset and a frame number, which gives the physical address. So this is the 2 level. Okay, because here we are using a 2 page tables. One is the outer, another one is the inner page table. So this is a 2 level. So even it can be decomposed into 3 level. Okay, we will be taking 3 levels. The first level, that means outermost page level, will be referencing the addresses of the remaining page tables, and the remaining page tables will be referencing the addresses of another page tables where the actual frame will be available. So that can be done based upon the complexity. Okay, we can reduce it. And see, previously how a page table will be having 10 lakh entries, and we are supposed to store all the 10 lakh entries in the contiguous memory locations in the primary memory. But here it requires only 1023 contiguous memory. So here also all the page tables will be residing in the primary memory. But here what happens means the contiguous memory locations means only 1024 contiguous memory locations are needed. So in the primary memory, wherever there is a space or free space of 1024 entries, so there one table can be accessed. So that particular base address will be represented in this outer page table. So hope you understood, right? So we are reducing the number of entries of a page table. So the page table is decomposed into multiple levels. Okay, and outer page table will be referencing only the base address of other page tables. That is most important. Yes. Now what happened? See, instead of going here, this will be, so this is the outer page table. Outer page table. This will be referencing one more page table. Okay, and from here we will be getting the frame number. See, here how we are getting means the base address of this outer page table. See, remember this outer page table, base address. Okay, base address will be stored in PTBR. PTBR means a page table base register. Page table base register. Okay, page table base register. Sorry. So page table base register will be having the address, the base address of outer table. So this will be added to this page so that it will be referencing to this one. And coming to here, so here we need to divide it into two categories. So PG1, PG2, and displacement. So let us be more clear. Okay. Now here it gives the base address of the inner page table. Okay, inner page table, base address of inner page table. So how can we get the exact location here? So this page 2 address will be added to this so that it will get the exact location of the frame. Okay, exact location of the frame. Hope you understood. From here we'll be getting the frame number, and here the displacement and the frame number will be added to get the logical address. Okay, see. Hope you understood. The page table will be divided into multiple levels, right? So outer page table will be having only the base addresses of another page tables. So here the page one location will be added to the base address because these are all the locations. Okay, so that will be added to the PTBR. PTBR means a page table base register. A page table base register. So which will be holding the address of the starting address. Okay, the starting address of the outer page table. So that will be added to get the exact location of the page number. So from this page number again we are adding. So here for example it is a 2000. That is the base address of the next table. So in that next table, what is the exact location of the required page means? So this 2000 should be added to the location which we are giving in the logical address PG2. So that gives the exact location here. So from that we are getting the actual frame number. So actual frame numbers will be available in this particular inner page table. So this is called as a two-level paging. Two-level paging. So depends upon the complexity. If you want to decompose more the logical address, so this logical address will be divided into 3 pages. Okay, so 3 parts. It will be divided into 3 parts. So PG1, PG2, PG3, and displacement. PG1 will be having the addresses of PG2. PG2 will be having the addresses of PG3, and PG3 will be having the exact frame numbers. It will give the exact frame numbers. Right? So hope you understood. So previously the main goal of moving on this hierarchical page table means reducing the number of entries of a page table. So in order to reduce the memory overhead. Okay, so instead of searching and retrieving from the 10 lakhs of entries, so we are reducing into levels. Page table. So one major reason why we are using these techniques to structure a page table means, so the page table will be having a lot of entries. So we are supposed to store some 10 lakhs of entries in a single page table. So that means that many contiguous memory locations should be needed, and this page table will be residing in the main memory itself. And there is a one drawback of having the page table, and the two, we are using the multi-programming. So multiple processes can be executed parallelly, right? So multiple programming means multiple processes will be there. So multiple processes means each process will be having their own page tables. So it will be difficult to maintain lakhs of entries in the main memory. So that's why we are moving on with these kind of techniques. So in this technique, we are using, the name itself indicates here, we are using some hash function. So we have studied a lot of hash functions, okay, in data structures concept. So division method, folding method, like that we have studied a lot of hash functions, right? So I'll post the link of these hash functions in the description so that you can go through that one, right? So why we are using this hash function means it will give less accessing time. So this is a one more point we have to remember. So we need to access the data very fast. So access time should be less. So within the less time we have to access it. So obviously the complexity of using this hash function in order to retrieve the data will be always a constant. So which is very efficient. Okay, efficient. So we are using such type of hash functions in order to map the logical address towards the primary address. Okay, so let us see this. We know how the logical address will be converted into a physical address. So I'm drawing the same diagram. So here the CPU, and here it will be 2 parts. One is a page number and another one is a displacement or offset. We can also call it as offset. So actually what happens means, so this will be referencing the page table. This will be referencing the page table. So this is a page table, and from this page table we'll be getting frame. So frame number and a displacement. So this, the same displacement will be given here, and this points towards a frame in the main memory. This points towards the frame number in the main memory. So this is the main memory. Okay, right? So that's the same thing we have studied here, right? So now hashing means before getting the page reference, we are using here hash table. Okay, instead of using the page table, we are using the hash table. So this page, whatever the page we are having, so this is a logical address. Okay, this is a logical address, and obviously this is a physical address. Right? So hash table and all these are the hash values, right? How we are getting the hash value means, so applying some hash functions on this page, that means a page number. Okay, so this page number will be given to some hash function, okay, so that it will give one hash value. Okay, so it gives some hash value which makes a reference in the hash table. So hash table will be having all the hash values, and from this hash value we will be getting a page, I mean a frame number, directly a frame number. Okay, after applying some hash functions, so those hash functions, so division method, so one method is a division method. For example, if the page number is 125, so the division method 125 mod 10, which gives the value as a 5, so 5 is the hash value, and it will be locating, or it will be pointing towards this value 5 in the hash table. So this hash table will be having all the hash values. So for example, if it is a 5, so in this particular entry there will be a frame number, so that frame number will be taken and that will be applied to the displacement, so that we will be getting the physical address. Now see, this is a one hash function, division method. So there are a lot of hash functions, as I said that I'll post the link. So once again, after some time, I mean if there is another page which is of 225, so applying 225, again we are getting the hash value 5. Now what happens? So here in such way we call it as a collision. So already all these things we have discussed in our hashing concept, right? So collision. So whenever the hash function applies on a page which gives the same hash value. So here the page number is 125, page number is 225. So applying the same division method, that means the hash function on this page number which gives the same hash value. So that means it's a collision. In such a way, what happens means it creates a linked list. So creates linked list. So what is it that linked list means? See, for example, if it is pointing here, so it will be having the three parts. One is a page number, another one is a frame number, another one is a address. See, I'm writing here. So the linked list node will be having, one is a page number, so which page we are getting, and the corresponding frame number, and the third one is the address of the next node. So address of next node means here we are having a two possible hash values, I mean two possible inputs which gives the same output. So here in such case, see for example, here it will be linking towards a one more node with the same page number, frame number, and here it will be, for example, the address of this first one is 1000, address of the next one is 2000. This 2000 value will be stored here. Okay, 2000 value will be stored here. For example, so there is a one more page with the 325. So 325, applying the hash function, we will get the value as 5. So again the third value, I mean the third page also getting the same hash value. So here one more link will be added, node will be added. So page number, frame number, and this is a 3000. This 3000 will be linked here. So the address of next node will be getting here. Okay, so this way. So what about the address of the last node? If there is no link forwarded, so then it will be a null. Okay, if there is no link and this node is the last node, then obviously it will be a null. So whenever the page comes here 125, so it will check whether I mean if the hash function will be applied and it will be having 5, so it will be referencing towards the 5 in this hash table, and it will be getting this particular linked list. Okay, this particular linked list. So in this linked list, this page number you will be having 125, and here it will be having 225, and here it will be having 325. So it will check whether the page number 125, 225 or 325, the corresponding frame will be added to the displacement to get the physical address. Okay, so I think arrow mark will be here in this way. Okay, so this is the linked list concept. What I'm saying is this is a linked list. Why we are going with this linked list means, so if a multiple pages will be having the same hash value, producing the same hash value, then all the similar hash value page numbers and the frame numbers will be linked in a single place. That we call it as a linked list here. So obviously, so if the page number is some 123 and 223 and 323, so obviously the hash value will be 3 here if you apply the division method. So in the third one we'll be having the 3 nodes. So each node will be having the page number, frame number, as well as the address of the next node. And if it is a last node, then the address will be 0, null. Okay, so by using this kind of hash functions in order to get the physical address, so the access time will be very fast. Okay, so the logical address, the theme is same. The logical address will be the page number and the displacement, and page number it goes with the page table, and in the page table we'll be having the corresponding frame number, and that will be added to the displacement for getting the physical address. But here instead of page table we are using this hash table, and some hash functions are applied on the page number so that we are getting some hash value, and based upon that hash value we are linking up all the related frames here. Okay, so this is called a hashed page table. This is a one more technique to structure the page table. So in our previous session, we have seen the hierarchical page table, where the page table was divided into a lot of page tables. The outer page table will be having the addresses, base addresses of all other page tables. But here, the access time will be also very fast. So for large entries, for any large entries also, this will be suitable, as well as in order to get the accessing fast, then also we are going to use this hashed page table. So inverted page table. So the structure of page table or the page table hardware is common, right? See, the CPU, and this is a logical address where we will be having a two parts. One is a page number and another one is a displacement or offset. So we are calling it as logical address. Okay, so from this we are getting an entry in the page table. So this already we have discussed all these things, right? The same thing I'm repeating, page table. So from this page table it will be giving the frame number, corresponding frame number, right? Frame number and the same displacement, and this we are calling it as a physical address. Physical address. So sorry, this will be pointing towards an entry in the primary memory. So this is a primary memory. Primary memory, right? So this is what happens here. So as we discussed here, every process will be having this different page tables. So here, see, for example, we are having some three processes. Example, right? So P1 means a process 1 which is having one page table, and P2 again we are having one more page table, and P3 again we are having one more page table. So in our previous session we have discussed that every page table will be having a lakhs of entries, because that depends upon the number of pages. So here P1, P2, P3 means a process. Okay, so for example P1 is having some four processes, four pages. Okay, so this is page 1, page 2, page 3, page 4. Okay, and P2 again we are having some 3 pages, page 1, page 2, page 3, and P3 again we are having some 2 pages. Example, let us take it 2 pages. So page 1, page 2. So 3 processes, and every process having a different pages. P1 is having 4 pages, P2 is having 3 pages, and P3 is having 2 pages. So all these 3 page tables should be reside in the primary memory. Okay, example. So for example, page 1 is loaded in a frame F0, and page 2 is not available in the primary memory. Okay, so it doesn't mean that every page of a process will be available in the main memory. So if the page is not available in the memory, then the request will be taken and it will be loaded from the secondary memory. For example, at a given instance, page 1 is loaded in frame 0, page 3 is loaded in frame 4. So page 2 is not available, right? So see. And similarly, page 2 is available in frame 5. Page 2 is available in frame 3, right? So these are the pages available in the primary memory. Okay, so in process P1, let us imagine page 2 and page 4 not available in the primary memory. Coming to the page 2, process 2, page 1 and page 3 are not available in the primary memory. Process P3, page 1 is not available in the primary memory. So even though the pages are not available in the primary memory, it is mandatory that all the page table entries should be available in the primary memory. So this is a empty. Okay, this space is empty. Page 2 and page 4, the space, the entry is empty. Okay, the entry is empty. And in the process P3 page table, this first page entry is empty because it is not allocated to any frame. And coming to the process P2, page 1 and page 3 are empty. The entries are empty because page 1 and page 3 are not available. So what are the available pages? Available pages in primary memory. From process 1, page 1 and page 3. From process 2, page 2. From process 3, page 2. Right? For example, these are only the pages available in the primary memory. So as I said that even though the page is available or not, the complete page table with all the entries should be available in the primary memory. So you can imagine 1, 2, 3, 4, 5. Total 5 entries are empty. In this case, 3 processes. So 3 processes. For process P1, 2 entries are empty. Process P2, 2 entries are empty. Process P3, 1 entry is empty. So even though it is empty, we have to load the complete page table in the primary memory. So there will be a lot of memory which has been wasted. So these entries, the page was not available in the primary memory, even though the entry is available. So that means a lot of memory is wasted. Okay, memory is wasted. Right? So because of storing each and every page table in the primary memory. So what is the solution for this kind of thing is, so maintaining global table. So what is this global table means? This is a single table which can hold all the pages which are only available in the primary memory. So it will avoid the empty entries in the page tables. Okay, so in this case, see, only these are the pages available in the primary memory. So it will maintain one page table, only one page table, okay, with all the available pages. So this is a page table, ready? So this is a page 1, page 3, page 2, page 2. So only 4. Page 1, page 3, page 2, page 2. Okay, this is the global table. This is the global table. Only these pages are available in the primary memory. So the global table will be containing only the pages of all the processes, not all the single process. So all the processes, whatever the pages available in the primary memory, that will be maintained in a global table. Now the question is, if you want to get the frame number of PG2, page 2. So here there is a dilemma that this page 2 representing which process. Okay, because these two entries are page 2. These two entries are page 2. So here we are having a dilemma that which page belongs to which process. So this page belongs to which process? This page belongs to which process? So in order to avoid that thing, so it will also maintain one process ID. So PID, which is a process ID. Every process will be having some unique ID. So that will be added to this particular thing. So one more field will be added, and here it will be giving the process ID. See, coming to the page 1, page 2. So this is a process 1, process 1, process 2, process 3. So here, coming to the logical address, so this will be modified into 3 parts. The last one is a displacement, that is a common thing. So the first one is a process ID, PID. The next one is a page number. Process ID, page number, and a displacement. Okay, so with this, the entry will be here. Okay, from that, the frame number will be added to the given displacement, so that we'll be getting the physical address. So why we are calling it as inverted page means, here the conversion will be done with the help of the frame based indexing. So not with respect to the page number, with respect to the frame number, it will identify the process and page. For example, this page 1. So page 1 it is a F0. Page 3 it is a F4. Page 2 here, page 2 F5, and page 2 again with the process P3 it's EF3. So this is the frame based indexing. So here frame numbers will be acting as an indexes. Okay, so frame number will be acting as an index to identify the corresponding logical address. Okay, so this is a reverse process of regular paging hardware. So normally we are using the logical address, and from that logical address we are finding out the frame number, and we are calculating, we are adding the frame number plus a displacement, so that we are getting the physical address. So the logical, that means the page number will be the indexing, but here the frame number is an indexing. With the help of frame number, we are going to identify the page number and the process number, process ID. So that's why we are calling it as an inverted page table. Okay, so hope you understood. The main reason of going to this one is every process will be having their own page table, and all the page tables will be loaded in the primary memory. So it is not mandatory that every page will be loaded in the main memory. So some pages will be loaded in the main memory and some pages will not be loaded, right? So that means there will be an empty entries in the page table, empty entries. So if there is an entry, I mean if the page is available in the primary memory, then only the entry will be in the page table. So in such case there will be a lot of memory wasted. So in order to avoid that, we are maintaining a global table which will be holding the page numbers which are only available in the primary memory of all the processes, and with the help of page numbers, we will be identifying the process ID also. So with the help of these two, and mainly with the help of frame indexing, it will be identifying the logical address. So this is the process done in the inverted page table, right? So hope you understood this one. And so these are the 3 structures of a page table. So these many ways we can structure any page table. Copy on write, so which can also be called as COW, copy on write. So usually operating system will be using the fork system call to create a child process. So whenever a child process is created, and this child process will be sharing all the common resources, of parent process. Okay, so as we are saying it as a child process which is inherited by the parent, so whatever the memory or the resources, everything will be shared by the child process. So for example, if the process, a main process, is having different pages, okay, so this is a page 1, page 2, okay, and page 3, right? So this is a process. Obviously we know that a process will be divided into different pages, so this one. So whenever it gives the fork, automatically a child process will be created. So here it is a child process, which will be sharing the same resources. So again, this child process will also be pointing towards the same kind of pages. So there will be no problem until we access the same page. So actually, instead of creating the same pages one more time, the same pages will be accessed by both the parent process and the child process. Hope you understood, right? So whenever either process have modified a page, either process means either a parent process or a child process. So either process have modified a page, then copy of that page will be created. So until there is no modification on the pages, there will be nothing changes. So all the pages will be accessed by both the parent process and the child process. Once if either of these two processes, that means either parent process or a child process, modifies a page, then only it copies that particular page. I mean, a copy of that particular page will be created. So for example, so this process example, process, a parent process, okay, parent process or a child process, anything, okay. Let us assume a parent process modified page 2, then copy of page 2 will be created. See, for example, page 2, this parent process have modified this page 2, then simply copy of page 2 will be created. So again, there will be a reference to this one. Okay, unless there is no modification, this kind of duplication will not be done. So once there is a modification, then a copy will be created. So that's why the concept we call it as a copy on write. So write means modification. So if there is any write operation performed on any one of the page, then a copy will be created, right? So this concept will be, see, whenever the process applies whenever the fork system call has been executed, a child process will be created, which will be accessing the common memory in the pages. So a copy of that page will be created only on write operation. That means whenever the page has been modified. So that's a simple concept in virtual memory. So for concurrent execution, parallel execution, obviously one process will be created a number of childs, okay, in order to efficient execution of processes. So a child process will be created here. So in such case, so instead of copying all the pages which are referenced to this particular process, so the same reference will be done for the child process also, and for modification only a copy will be created. So this is called as a copy on write. Paging. So demand paging. So paging, we know about this paging concept. So the primary memory will be divided into frames, and the logical memory will be divided into pages. So the CPU will be executing only the process which is available in the main memory. So the pages of logical memory will be loaded into the frames of primary memory. Okay, so that the conversion of logical address with the physical address that we have seen. See here, demand paging, the name itself indicates demand, means so not executing all the pages or not loading all the pages into the main memory. So with the demand from the CPU, the required pages only be loaded into the main memory from the secondary memory. See, so the main reason for this demand paging is to optimize wastage of memory. So the memory will not be wasted. So why means, because so here you can see this is a logical address, for example. So this is a process, okay, and this is a process 1. Okay, so for example, the process 1 is having some 4 pages. Okay, so let it be page 0, page 1, page 2, page 3, and for example, let it be, this is a page table. Okay, so we know that the page table will be having all the entries. So page table of P1, Similarly, let us take one more process. So 3, that is a page 0, page 1, page 2. This is a process P2. Okay, so in order to avoid the confusion, let us take this one as page 4, 5, and 6. Okay, there is no continuity. Just to avoid the confusion, I am giving the unique page names. And this is a page table of P1, and this is the page table of P2. Page table of P2. Now, this is the main memory where we have to store the pages. This is the main memory. Okay, so for example, this particular page table will be divided into 2 columns. So we know that the page table will be having the corresponding frame numbers. So we have studied that in our earlier sessions. So this page table will be having a frame number which points towards the location at the primary memory or main memory. So apart from that, there will be a lot of bits, and in that the additional bit is, and this portion is valid or invalid bit to represent the status. Okay, valid or invalid. Okay, similarly here also this is a valid or invalid. So which is represented as valid as V, invalid as I. Here also valid as V, invalid as I. And here there will be a frame numbers. So let us take this one, frame numbers. Let us assume these are all the different frames, and we know that the frame size is equal to the page size. Okay, to fit it. So let it be, this one is a F0, F1, F2, F3, 4, 5, 6, 7, 8, 9, 10, and 11, for example, right? Now the page numbers. For example, it doesn't mean that we have to store all the pages in the main memory. Okay, all pages should be loaded in the main memory. So if demand paging, the name itself indicates, with the demand of CPU, only the required pages will be loaded into the main memory. For example, among these 4, let us take, so this is a page 0, page 1, page 2, page 3, and here also page 4, page 5, page 6. For example, this is a invalid, this is a valid, valid, and invalid. For example, this is at F1, F3, and here it is a valid, invalid, valid. Okay, let it be, it is at F4, F11, sorry, invalid no, so F11. So that implies valid means the page is already available in the main memory. So F1, so page 1 is loaded here. So it is a page 1, and page 2 is loaded at F3. So here it is a page 3, and here page 4 is loaded at F4. So this position page 4, and F11 it is stored at page 11. So like this, so you can observe here, totally 2 processes are there, and among these 2 there are total 4 plus 3, 7 pages are there. And here we are in the main memory, there is no 7 pages loaded, only the required pages are loaded. So only page 1, page 2 from process 1, and page 4 and page 6 from process 2, only these pages are loaded. So there is no wastage of memory. Okay, so whenever the CPU demands for a page, so the page will be available, so it will check in the main memory. So now see, if the CPU wants to execute, for example, page 3, okay, page 3, if CPU wants to execute this page 3, so once again I'm saying CPU will be executing only the process from the main memory. So first it will check in the main memory. So CPU checks for page 3 in the main memory. So how it will check? So it will be checking in the main memory. So if the page is not available, so here you can see, page 3 is available. So this is a page 2, because this is a page 2, page 2. So page 3 is not available in the main memory. So if the required page is not available in the main memory, which was demanded by the CPU, that we call it as a page fault. Okay, so page fault. Page fault. So page fault means whenever the CPU demands for a page which is not available in the main memory, then it is called as a page fault. So if there is a page fault, what happens? So immediately the CPU will be transfers a control, okay, the trap control or trap system call to OS, okay, to OS, to the operating system. So CPU will be transfers a control to the operating system that there is a page fault. Page fault means the required page is not available in the main memory. Then immediately the OS will copies or load page 3 from secondary memory to free space in main memory. So this happens. So first the CPU will be demanding for some page. Okay, the CPU will be demanding for some page, and if the page is not available, then page fault occurs. And in order to handle this page fault, the CPU will be transferring a control to the operating system by conveying that there is a page fault. Immediately the operating system will load the page 3 from the secondary memory, because the complete pages will be available in the secondary memory only. By the demand of CPU only, we are loading the pages to the main memory. So P3, the page 3 from secondary memory, SM means secondary memory, to free space in the main memory. So what happens? Let it be, this is the free space. So page 3, okay, it will be loaded here. Then what happens? The page table will be updated. So the page table will be updated. So because the page table will be having all the entries of the pages which are loaded in the main memory. So the frame number is F7. So F7 will be kept here and this invalid will be modified to valid. Okay, this what happens. And after updating this table, so the instruction or a page will be re-executed. So the page will be re-executed by the CPU. The page will be re-executed by the CPU. Okay, so this happens when page fault occurs. Okay, whenever the page fault occurs, this is the process happens. The CPU will be transferring the control, OS will be loading the required page from secondary memory to the main memory, and the page table will be updated, and then, so this will be reference, okay, and then the page will be re-executed by the CPU. Now, there is one more question. If, for example, these are all also filled with some other processes. Okay, now you can observe the complete main memory has been filled with all processes. Okay, for example, there is one more process, so let it be some P10, and here there is a P11, here it is a P12, and here is a P13, and here it is a P14, and here it is a P15. For example, let us imagine that. So the main memory is completely filled with all the pages. There is no free space. So what happens here? See, whenever there is a page fault, for example, CPU now requires to load page 0, okay, page 0 to the main memory. But you can see the complete main memory is filled with the pages. There is no entry. So what happens here? So automatically the first step, that means it will transfer the control, the trap to the operating system. Now the operating system finds that the main memory is completely full. Now what happens means, now it will happen the swap in process and the swap out process. So this we have already discussed in our previous sessions, swap in and swap out. So first swap out will be done. Swap out means whatever the page completes its execution, that page will be removed from the main memory and it will be loaded back to the main secondary memory. For example, page 11 completes its execution. So page 11 will be removed here and it will be transferred to the secondary memory. Now there is a free space. So this process we call it as a swap out. Okay, the page which completes its execution, the page will be moved to back to the loaded back to the secondary memory from the main memory. So now there is a free space. Now the CPU will be loading page naught from the secondary storage to the main memory. So this is called swapping. Okay, loading the required page from secondary memory to main memory is called as a swapping. So these two processes will be done when the memory is full and CPU still wants to execute a required page. So there is no memory in the, there is no free space in the main memory to load the required page from secondary memory to the main memory. So then the swap in and swap out will be done. So swap out will be done. So the page which completed its execution will be immediately loaded back to the main memory, moved back to the main memory. So swap out. So obviously the main goal is optimizing the wastage of memory. So instead of loading all the pages which is required or not required, so loading only the pages whenever it is required. So the CPU demands the pages which are going to be get executed by the CPU. So only those pages will be loaded from the secondary memory to the main memory. If the page is not available, page fault will be occurs. So we are going to handle this page fault. So page fault will be handled. So by sending the control to operating system, and it will be loaded from the secondary memory to the main memory. It will update the page table, and finally the complete instruction will be re-executed by the CPU. So this is what happens in the demand paging, and it's also known as virtual memory. Virtual memory, right? So because the complete process not loading into the main memory, still we are executing the complete process. Okay, so that's why we are calling it as a virtual memory.
We are going to discuss about one more concept in operating systems, that is page replacement algorithms. So in that, we'll see what are the basic terminologies we are required to know before going to this page replacement algorithms. So the basic terminologies used. The first one is page. So what is meant by a page? Second one is frame. Frame. Third one is swapping. The fourth one is page fault. Fifth one is hit. And the next one is the techniques used. Right? So page, frame, swapping, page fault, hit, and techniques. Now coming to this page replacement algorithm, we know that so the processor will load the process which is going to be executed into the main memory from the secondary memory.
So we know that all the files and all the processes will be stored in the secondary memory. So whenever we are executing the process or a file, whenever we are loading the file, that file or that process will be loaded into the main memory and then it will be executed. So for execution of the process, it should be loaded from the secondary memory to main memory. That's the important concept, right? Now the question is it required to load the complete process into the main memory? The answer is no. So here the process will be divided into different parts and each part will be loaded from the secondary memory to the main memory whenever it is required. So that each part of the process is called page. So process will be having pages, page 1, page 2, page n. So there will be page number, right? So a process can be divided into number of pages, n number of pages. Now this is about the page. It's a part of a process. It's a part of a process. So if we want to execute this page 1, first the page 1 should be loaded from the secondary memory to main memory and then only it will be get executed by the processor. Now coming to this frame. Similar to the process, the main memory is also finite and the main memory is also divided into different frames. See, main memory. So frame 1, frame 2, frame n, right? Now, if page 1 is to be get executed, the page 1 should be loaded from the secondary memory to main memory in one among these frames, which is available, right? So this is a frame. Frame is a part of main memory. Swapping. See, this is a main memory. See, this is a frame 1, frame 2, frame 3, frame 4. So memory is divided into 4 frames. Similarly, we are having some process P1, P2, P3, P4. Sorry, you can write here P1, P2, P3, P4, P5, P6, P7. So there are here P1 is nothing but a page 1, page 2, page 3. So this is the process. Right? If you want to execute this process, first we have to load these pages into these frames. So, see, we are executing this one. So, page 1 is here, next page 2 is here, page 3 is here, page 4 is here. Now, the processor wants to execute the page 5. Right? Now, the processor wants to execute page 5. Now, this page 5 should be loaded from the secondary memory to main memory. So, this is the secondary memory. Okay, this is the process. Right. So we want to, the processor wants to load this P5, execute this P5. So first the processor will check for the main memory, check for this required page in the main memory. If it is not available, then it will load this required page from the secondary memory to main memory. And before loading that, it will check for the availability of frames in the main memory. If it is available, that directly the required page will be loaded into the available frame. And if the frame is not available, what we have to do? So one page should be replaced with the required page. So in this example, so here there are 4 frames in the main memory and already the 4 pages are filled in these frames. Now the processor wants to execute this P5, page 5. So page 5 should be loaded from the secondary memory to main memory. But here no one frame is available. Not even one frame is not available. So we have to replace one page from the main memory with the required page. That is called the technique. So with the help of, this process is called a swapping. Swapping. Okay, so here replacing, that means removing the page, from main memory, that is one step. Load page from secondary to main memory. Okay, these are the two things must be happen. So before loading, we have to check for the available frame. So this process is called swap out. So because we are removing, that means we are removing the page, one page among the several from the main memory to the secondary memory. So that is called swap out. And immediately the required page will be loaded from the secondary memory to the available frame. So if you remove the page from the main memory, that particular frame will be in an available state. So we can load the required page from the secondary memory to the main memory. So available frame to the available frame. So this is called swap in. So finally, the process of switching the pages from secondary memory to main memory is called swapping. So that can be swap in or swap out. Right? Now, so page part.
So page fault means loading the required page from the secondary memory to main memory. If the required page is not available in main memory, then that is called page fault. So there is a page fault. So we have to load the required page from the secondary memory to main memory. Right? So this is called a page fault. So that means the required page should not be available in the main memory. So that is called a page fault. And if the required page is available in page fault, I mean in main memory, that is called a hit. So the required page is not available in main memory. Hit means the required page is available in main memory. Okay, right? See, for example, now let us consider this example itself. So already all the frames are full, right? See, okay. Let us take an empty frame. So let us start from the beginning. So the page sequence is same: the P1, P2, P3, P4, P5, and similarly again, P1, P2, and P3. The page sequence. The processor wants to execute the process in this way. Okay. So first of the P1, first it will find, the processor will find whether the page 1 is available in the frame. So all frames are empty, it is not available. So that means there is a page fault. So P1 will be here. So there is one page fault till now. Coming to the P2, P2 is also not available in main memory. Second page fault. P3, third page fault. P4, fourth page fault. Again P1. So P1 is already available in main memory. Okay, so we need not swap any page. P1 is already available in this one. So there is no page fault. So there is one hit. Again P2, P2 is also available in main memory. So second hit. P3, P3 is also available in main memory. So third hit. So for executing this one, we are having 4 page faults and 3 hits. Hope you understood. So whether the required page is available in main memory, then we call it as a hit. Whether the required page is not available in the main memory, that is called a page fault. So the next step of this page fault is we have to load the page into the memory. So for that we have to again check for the free slots of a memory, that means the free frames. So if there are no free frames, what we have to do? We have to swap. That means we have to replace one page with the required page. So that swapping will be taken about these page replacement algorithms. So based upon the page replacement algorithms, this swapping will be done. So which page have to be replaced from the main memory and which page, to replace the required page. So the selection of a page to remove from the main memory. So that is called this page replacement algorithms. Thus there are three page replacement algorithms. So first one is first in first out, FIFO page replacement algorithm. First in first out page replacement. LRU, least recently used page replacement, least recently used. And the third one is optimal page replacement algorithm. Optimal page replacement algorithm. So these three are nothing but techniques. Techniques to replace the page from the main memory with the secondary memory, with the required page. Okay, so hope you understood this one. So in order to select which page has to be replaced, depends upon the technique which we are using, either FIFO, LRU or optimal. Right? So these are the basic terminology which we have to learn before going to these page replacement algorithms. So page, which is nothing but a part of a process. A frame is a part of a memory. Swapping, that means replacing the pages from secondary memory to main memory. Okay. Then page fault, if the required page is not available in the main memory, then this page fault occurs. And hit, if the required page is available in the main memory, so we have to do nothing. So that is called a hit, one hit. And techniques, so if the memory is full, and if the required page is not available in the main memory, then we have to replace one page with the required page. So which page, the selection of page to be removed from the main memory will be done with the help of these techniques, FIFO, LRU and optimal. Right? So hope you understood, guys. This is introduction to a page replacement algorithms. So from the next session, we'll go with the 3 techniques. So next session we'll go with the FIFO and then LRU and then optimal. FIFO page replacement algorithm. Right. So if the required page is not available in the main memory, we have to load the required page from the secondary memory to the main memory. And in order to load the required page, first the memory should be having a free frames. So if all the frames are filled with some other pages, so we have to replace the existing page with the required page. For that we will use this page replacement algorithms. So the question is, which page of the main memory should be replaced with the required page? So that is, it depends upon the algorithm. So here in this algorithm, we will replace the first page loaded into the main memory with the required page. Right. So we go with some page strings, page reference strings.
So page reference string 1 3 2 4 2 3 1 4 2 4 1 3. I have taken this as randomly. Okay, so here the pages are 1 2 3 and 4. So there are 4 pages. So a process is divided into 4 pages, and let us assume that frames are 3 frames, frame 1, frame 2, frame 3. Now see, frame 1, frame 2, frame 3. So we know that, so if the required page is not available in the main memory, so here this frames is nothing but our main memory, right? So if the required page, so these are the page reference strings. So if the required page is not available in the main memory, that gives a page fault. And if the required frame or required page is available in the frame, then it is called a hit. Now we will have to find the page faults, number of hits, and hit ratio. So we have to find all these things. Now let us consider. So now all these frames are empty. Consider the first one, page 1. So first we have to, the required page is page 1. So we have to check whether the required page is available in the main memory. So here the required page is not available in the main memory because all the frames are in a free. So just I am loading the first page, the required page in frame 1, right? And the 2 frames are empty. So first, okay, so before loading it, so the required page is not available in the main memory. That is, here there is a page fault. The page fault occurs. So first we have to load this in the main memory. Next, page 3. Again, see, in the given frames, 3 is not available. So again there is a page fault. Now the question, we have to load the required page into the frame. So there are 2 slots are free. So we are loading this 3 here. And coming to the third string, second page number 2. So it is also not available in the main memory, and 1 slot is free. So see, again it is not available in the memory. So we said that if it is not available in the memory, there is a page fault. So I am loading these 2 in frame 3. Now our main memory is full with all the pages, right? So 3 frames are there. So 3 pages has been loaded. Now the next string is 4. So 4 to be loaded into the main memory, but 4 is not available because frame 1 is having 1, 2 is having 3, 3 is having 2. So not available in the main memory. So again there is a page fault. Okay, again there is a page fault. Now the question is, whenever we got the page fault, we have to load the required page into the main memory. So but here there is no free slot. All the slots are free. All the slots are full, right? So now we have to replace. That means a swap out should be done. Swap out means one page should be removed from the main memory. So which page should be removed? That is first in, first out. Our algorithm gives the first in, first out. So among these 3, which page is loaded first, that should be removed. So by your observation, we can know that 1 is the first page to be loaded among these 3, 1, 3, 2. So 1 will be replaced and 4 will be loaded here. Hope you understood. Again, coming to the next string, page 2. See, page 2 is already available in the frame 3. So there is no page fault. So hope you understood. If the required page is not available in the frame, then the page fault will be there. If the required page is available in the frame, that is nothing but hit. So nothing will be changed. So we need not go any change because page 2 is already available in our main memory. Okay. Next, string 3. Next one is 3. Again, the same process is applied. So we can know that 3 is already available in frame 2. So again, hit. So no change will be done. Next again, 1. See, you can observe 1 is not available in the main memory. So there is a page fault. So 1 should be replaced with 1 among these 3. So which to be replaced? Which page to be replaced? So that is first in, first out. Among these 3, 3 is the first. Okay, so 4 is having only 3, 3 is having 5, and 2 is having 4 iterations. So 3 is the first loaded into the main memory among 4, 3 and 2. So replace 3 with 1. So 4, 1 and 2. Next, 4. Again, the same process. So but 4 is available in the memory. So no page fault occurs, hit. It's called a hit. So no change will be done because 4 is already in main memory. Next, 2. Again, 2 is already in the main memory. Okay, so I'll replace this one, erase this one.
So again, see 2 is already available in the main memory. So again it's a hit, no change. So 4, 1 and 2. Again 4. So 4 is also available. So there is no page fault. Okay, there is no page fault. It's again hit. Again 1. 1 is already in main memory. So again there is no page fault. It is a hit. Again the last one 3. So 3 is not available in the main memory. So which page should be replaced among 4, 1 and 2? So 4 starts from here, 1 starts from here and 2 starts from here. So among these 4, 1 and 2, 2 is the first to be loaded in the main memory. So 2 will be replaced with the required page. So what is the required page? The last one 3. 4, 1 and 3. So here it is not available, so it is a page fault. So this is how we will load the required pages from the page reference string to the main memory. So in this process we have to find out the number of page faults, number of hits and the hit ratio. So now we can see, so number of page faults is equal to 1, 2, 3, 4, 5, 6. 6 page faults. And number of hits 1, 2, 3, 4, 5 and 6. Right? And a hit ratio. The hit ratio is equal to number of hits by total pages in reference string. So that is equal to number of hits is 6 divided by reference strings 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So 6 by 12 that is 1 by 2. The hit ratio is 1 by 2. Right? Hope you understood this one. So we have to find the number of page faults, number of hits and the hit ratios. So one thing, again I am repeating, if the required page is not available in the main memory, then this page fault will be occurred. Once the page fault occurs, the next step is we have to load the required page into the main memory. In that process, we have to check whether the memory is available or not. If it is not available, we have to apply the swap out and swap in. So that means remove the page, one page from the main memory and load the required page into the main memory. So in this algorithm, we will select the first page which is to be loaded in the main memory, that will be replaced with the required page. Here we'll go with another session on FIFO, that is Belady's anomaly problem. So first of all, let us explain what is this Belady's anomaly. So in the previous example, we have taken the same reference string and we have applied the FIFO replacement algorithm, page replacement algorithm. So we have taken the frames is 3 so that we got the page faults as 6. Now, if we increase the frames, that means if the main memory contains more frames, so automatically the page faults should be decreased. Right? So in this FIFO, this may not happen for all the reference strings. So for some reference strings, even though you increase the frames, the number of frames, the page faults may also be increased. So such type of phenomena is called Belady's anomaly problem. Right? So let us check with the reference strings. So this is the reference strings we have solved in the previous session. So with the 3 frames, so that we got the 6 page faults. Right? So once go through the video of FIFO and then you will get clarification. So I will post the link of the FIFO page replacement algorithm in the description, so you go through so that you can understand. Now here we will solve this with the number of frames 4, so that we should get the less number of page faults. That means we have to get less than 6 page faults because we are increasing the number of frames. Right? See. So frames F1, F2, F3 and F4. See. Right. So you can observe first, the first one. So page 1 is occupying the frame 1. So it is a page fault because 1 is not available in the main memory. So we will call it as a page fault. Second reference, the page 3 should be inserted and that page is not available here. So again there is a page fault and again I am including this one. Coming to the third one, 1, 3 and again 2 is not available. Again there is a page fault 2. Coming to the fourth one, so 1, 3, 2, 4 is not available, so 4 is placed in the fourth frame. Again, page fault. Now, see, you can observe here. Now, 4 frames are filled. 4 frames are filled. So here 2. Next one is 2. 2 is already available. So hit. There is no page fault. Okay. So no page replacement should be done here. Next 3. So coming to the 3. 3 is already available in the main memory. So there is no page fault. Again, there is a hit. Coming to the next one. See 1. 1 is already available, so again there is no page replacement, again it is a hit. Again next 4. 4 is available, again hit. 2. 2 is available, so there is no page fault. so it is a hit. Okay. Again 4. So 4 is also available, no page fault. Again hit. Next 1. So 1 is also available, it is a hit. 3, and again 3 is also available here. So again hit. So after completing all the reference string, you can observe there are only 4 page faults. So we have applied the same reference string using the FIFO algorithm with the 3 frames. We got a 6 page faults, and this is also a FIFO. So we just followed the FIFO. Okay, we just followed the FIFO, but here we got only 4 page faults, so reduced. So if you increase number of frames, automatically the page faults will be reduced. But here in this, this is a problem we will get in FIFO. That is, it may not reduce the page faults with the increase of frames. So in some reference strings, even though we are increasing the frames, the page faults may also be increased. So let us see such type of example, so your doubts will be clarified. Right? So in this case, in the previous session we have solved with the same reference string, but the page faults have been decreased because increase of frames. See. Now we'll go with the next one. Okay. So we'll take one more reference string and we'll apply the FIFO with a less number of frames, and we will increase the frames and we will observe how much we'll get. Okay. See. Okay. First we'll observe with the three frames. Okay. So the reference string. Right. This is the reference string. So we'll get, first we'll see with the 3. Okay. Now we'll observe here. See. So 1 is placed here. It's a page fault because 1 is not available. And coming to the second one, so 2 is also not available. Again, it's a page fault. So 1 and 2, and then 3. Again, it's a page fault. So 1, 2, 3. Again, now 4. 4 is also not available in the string. In the memory. So we have to replace. Again, it's a page fault. We have to replace. Which one we have to replace? The first in, first out. So first page we are allocating in the frame that should be removed. So here 1 is the first page among these 3. So we are replacing 1 with 4. Next, see. Again, 1. So 1 is not available here. So again we have to apply the FIFO for replacing the page. So among these 3, 2 is the first string. So 4, 1, 3. It's again page fault. See, again 2. 2 is also not available. Again it's a page fault. So which should be replaced? Among these 3 is the first. So 4, 1 and 2. Again you can observe, again it is a page fault because 5 is not available. We have to replace. So among these 3, 4 is the first one. So 4 will be replaced with 5. So then again apply here. 1 is already available. So it is a hit, not a page fault. So nothing should be replaced because 1 is already in main memory. Next 2 is also available in the main memory. So it's not a page fault, it's a hit. And we need not replace any page. So again next 3. So 3 is not available. So we have to replace a page. So again it's a page fault. Which page we have to replace? So 5, 1, 2. Among these 3, 1 is the first one. So 5, 3 and 2. Next 4 is not available in here. So again it's a page fault. Among 5, 3, 2. So 2 is the first one. So 2 is replaced with 4. And again last one, that is a 5 which is already available. So we need not go for the replacement. So it is a hit. So after completion of this reference string, we can count the page faults. 1, 2, 3, 4, 5, 6, 7 and 8, 9. So there are 9 page faults. For frames is equal to 3 frames. So if you go with the frames 4, see, if you observe here, the same thing we are applying with frames 4. So according to our assumption, if you increase the number of frames, automatically the page fault should be decreased. So let us take. So first one, take the first one. So again it's a page fault because it is not available. 1. Coming to the second string. Second one, 2 is not available. So again it's a page fault. We have to load it in the main memory. And the third one is also not available. Again it's a page fault. See, fourth one, 4 is also not available. Again it's a page fault. 1 is already there, so it is a hit. So we did not change the page. 2 is also not available in the memory, so it is again hit. 5, so 5 is not available. We have to replace 1 with 5. It's a page fault. 1 is not available here, so we have to replace this one 2, because among all these 3, 2 is the next one. So 2 will be replaced with the required page 1. So 5, 1, 3, 4. Again, the next one is 2 is not available. So among these 1, 3 is the first one. So 2 is replaced with the 3. Sorry, the page 3 is swapped out and 2 will be swapping in. So again, this is a page false. Okay. Next, 3 is not available. So among 5, 1, 2, 4, 4 is the first one. So we have to replace the 4 with required within 3. That is a page fault. Again, coming to the 4 is not available. So among 5, 1, 2, 3. So which one comes first? Fifth one. So 4, 1, 2, 3. So it is a page fault. And again, 5 is not available here. It is also a page fault. Okay. So which we have to replace. So 4 starts here, 1 starts here, 2 starts here, and 3 starts here. So 1 is the first one. So we have to replace 1 with page 5. 4, 2, and 3. Right? So this is how we can solve with the 4 frames. Now if you count this page faults, see 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So the page faults are 10. So even though you increase the number of frames, there is no chance of, there might be a chance of increasing the page faults. Okay. Right? So in some cases, not in all cases, in some reference strings, this will happen. And this phenomena is called Belady's anomaly. Right? So hope you understood. So increasing the number of frames may not decrease the page faults, particularly in FIFO replacement algorithm, page replacement algorithm. In this session, we'll go with another page replacement algorithm called LRU. So LRU stands for least recently used. So while loading the required page from the secondary memory to the main memory, so we'll find whether the memory is full with the pages or not. So if the memory is full, then we have to replace the existing page in the main memory with the required page. So that will be happen. That means here the question is which page should be replaced. So that depends upon these algorithms. So in this algorithm, whatever the page least recently used, that page will be replaced with the required page. So let us consider this reference string. So these are the pages. Okay, these are the pages. So we will consider this reference string and we'll solve by using this least recently used. Here, the number of frames is equal to 3. Now we have to find the page faults and hits. How many number of hits? Now we'll see. So how it can be solved. So first, page number 1. So all 3 frames are available. So there is a page fault because the required page is not available in frames. So now we can load that in the main memory. Next, coming to the 3. 3 is also not available in the main memory. Okay, you can observe only 1 is there, 2 empties. So 3 is not available in these 3 frames. So again, there is a page fault. So I will load this 3 in frame 2. Now 2, reference string 2. So 2 is not available in the frames. So again, there is a page fault. So we have to load this page 2 into the main memory. So I will load this page 2 in frame 3. Now all these 3 frames are full. Now next reference string is page 4. The required page is 4, and if you check whether 4 is available, here the 4 is not available in the main memory. So again, there is a page fault. So what we have to do? Again, we have to replace one page among all these 3 with this 4. So if you observe here, so we have to replace the least recently used. For that purpose, just follow towards the left side and find out the least recently used. So the required page is 4. So next to this 4, the leftmost one is 2. 2 is recently used, most recently used, because in the previous session itself, in this previous thing itself, we have loaded 2 because so this 2 is a most recently used. Again 3 is also used. 1, so 1 is the least recently used. Among these 2, 3, 1. So if you give the priority, 2 is in first second, 3 is in second, 1 is in third second. So 1 is the least recently used among these 3. So you have to replace 1. So replace 1 with 4, 3, 2. Hope you understood. So travel from the required page towards the leftmost and find out which page is the least recently used. Right. Coming to this 2. So 2 is already available in main memory. So it is hit. So no change will be done. So no replacement will be done. So 3 is also available in here. So again it is a hit. So no change will be done, no replacement will be done. Now 1. So 1 is not available in the main memory. So we have to find out the least recently used page. So travel towards the left. So 3 is the most recently used. 2, the next recently used. 4. So among these 3, 4 is the least recently used. Right? Replace 4 with 1. So it is a page fault because it's not available. Right? Next 4. So 4 is also not available in the main memory. So again find out the
least recently used, right? So because of here the number of frames 3, we can travel only 3 sessions. I mean 3 reference strings. So 4, 1 is the most recently used, 3 is the next recently used, and 2 is the least recently used. So 1, 3, 2. Among these 3, 2 is the least recently used. So 2 will be replaced with a 4. Okay. Then 2 is again not there. Okay. Again it's a page fault. So we have to replace one page. Again travel towards the 3 reference strings. 4, 1, and 3. 4 is the most recently used. 3 is the least recently used. Replace 3 with 2. Right. So again 4 is available. So it is a hit, not a page fault. So nothing will be happen. So no page will be replaced. Again 1. Again it is available in the main memory. So no change. So no replacement. So it is a hit. Again 3 is not available. It's a page fault. So again what we have to do? We have to travel towards its leftmost. So 1 is most recently used. 4 is the second thing. 2 is the least recently used. So replace 2 with 3. 1 and 4. Right? So hope you understood this least recently used algorithm. So if you count this one, 1, 2, 3, 4, 5, 6, 7, and 8. So 8 page faults are there, and 1, 2, 3, 4. 4 hits are there. Okay. So hope you understood this one. So all these one are reference string. Okay. All this one is a reference string. Right? So don't get confused here. So this is completely reference string. And this is a main memory where we are loading the pages. Okay. Right, don't get confused. So here we have to find the least recently used page, and that should be replaced with the required page. So for that we will travel from towards the leftmost 3 frames. 3 frames means here we are using 3, so we will travel 3 frames towards the left side from the required page. So in today's session we will see another page replacement algorithm called optimal page replacement algorithm. So in this situation, so we have to replace the page which is not be used for a long duration in future. Right? So hope you understood. So we have to replace a page such that should not be used a long time in future. So coming to the least recently used algorithm, we have seen if we want to load this page, page 2, so we have to select the page which is least recently used. For that we have traveled from the required page towards the left side. And in this, we have to load the page such that, we have to replace the page such that it should not be used long in future. So we have to travel the same thing in right direction. Right? So we'll solve a problem so that if you are having any doubts, so that those doubts will be clarified. Right? So here also I am taking the same reference string, so which we have solved in both the FIFO and LRU. The same reference string I have taken, and I have taken 3 frames. The number of frames are 3. So now we have to find out the page faults and number of hits. And page fault is if the required page is not available in the main memory, that is called a page fault. And if the required page is available in the main memory, it is a hit. Right? Now we'll start the solving. So first 1. So all the 3 frames are empty, so we can load the page 1 in the main memory. So I will load here. So that means here it's a page fault. Okay. So here it is a page fault. Now next reference string is 3. So again 2 frames are free. So again I am loading it here. So again it is a page fault because 3 is not available in the main memory. And 2 is also not available in the main memory. So again it is a page fault, and I will load this 2 in frame 3. Now 4. Page 4 is not available in this main memory. So there is a page fault. And there is no empty frame available in the main memory. So we have to swap in and swap out. So we have to first swap out the one page from the main memory, and we have to swap in the required page from the main memory to, load from the secondary memory to main memory. So for this, we have to select the page which is not going to be used for a long duration in future among these 3, 1, 3, and 2. For that, the required page is 4. So travel in this way. So 2. So immediately we require the 2. 3. Immediately we require the 3. 1. So the third position is 1. So among these three, 1 will be having a lot of time to load. So replace 1 with 4. 4, 3, and 2. Hope you understand. Right? So among these 3, 1, 3, 2, 2 is the immediate reference page. Immediate page in the reference string, and the 3 is the immediate page after the 2 and 1. So among these 3, 1 is have to wait until it loads the 2 pages. So 1 will be replaced with 4. Now again 2 is available in main memory. So it is a hit, no page fault. So we need not change any page. We need not swap in and swap out the pages. Right? Again 3 is also available in the main memory. So again it's a hit, it's not a fault. So again no need of replacing any one of the page. Now 1. So 1 is not available in the main memory. So it is a page fault. Now we have to replace 1 among these 3 pages. So for that we have to select the page which is not going to be used for a long time. See,
travel towards its right. So 4, 3, 2. So 4 immediately we require 2, immediately we require 4 and 1. Immediately, so 1 here no not there, right? 3. So 3 is the 3 in order to load this page 3 into the main memory. It requires around 4 iterations, right? So after loading the 4 pages, the next one is a 3. So 3 is waiting time of a 3 is more, right? So the 3 will be replaced with 1, 1, 2, and 4. So hope you understood, right? So among these things, 4, 3, 2, 3 is not being used for a long time. Okay. Next, coming to the 4. 4 is already available, so it is a hit. So we did not change anything. And the 2, till 2 is also available here. So again hit. So we need not change here. And a 4 is already available. So need not change. Again it's a hit. 1 is already having. So again it is a hit. And a 3 is not there. 3 is not there. And 3 is a last string, last page. So after 3 there are no other pages. So we can replace any one of the page from the main memory. So I will replace 1 or any page. Okay. So I will replace 4. Okay. Right. So if you observe here, see. So these are the hits and page faults occurred while loading the page reference string into the main memory, applying the optimal page replacement algorithm. So only one thing, the page should be the replacer page. I mean the page which is not being used for a long duration in future, that should be replaced with the required page. For that we have to travel from the required page towards the rightmost direction. Right. So this is how we can implement this optimal page replacement algorithm. So here the number of page faults 1, 2, 3, 4, 5 and 6. 6 page faults are there, and number of hits 1, 2, 3, 4, 5 and 6. 6 hits are there. So this is the procedure of optimal page replacement algorithm. Hope you all understood this optimal page replacement algorithm. Let us
see. So before going to the techniques, so let us know what is the advantage of allocating the frames in an optimized way, okay, in an efficient manner. So obviously, optimized allocation results, the first one, okay, no fragmentation, okay, minimal fragmentation. The wastage of memory will be minimal. Similarly, it reduces the page faults. So we know page fault means if the CPU, if the page which needs by the CPU is not available in the main memory, then that is called as a page fault. Immediately, the CPU will be loading the page from secondary memory to the primary memory by swapping in and swap out operations. Okay, so the minimal page faults, it reduces the page fault. Obviously, if there is minimal fragmentation and reducing of page fault, automatically the efficiency will be more. Okay, efficient usage of memory. So obviously there will be a minimal, that means the wastage of memory will be reduced and the maximum number of pages will be loaded into the frames. So there will be efficient usage of memory. Right. So if you allocate the frames, right, to the processes, then these are the advantages. Now, what are the different techniques? Okay, what are the different approaches to allocate the frames? So the allocation can be done in 4 ways. One is equal allocation. So if there are multiple number of processes, equal number of frames will be allocated for each and every process here. And the second one, proportional allocation. So it depends upon the size of a process and the requirement of a process, the frames will be allocated. Next, priority allocation, not primary, priority allocation. Okay, based upon the priority of a process. So we have seen that some process will be having the highest priority to complete its execution. So in such case, based upon the priority, the number of frames will be allocated. And the next one, global and local replacement allocation. These are 2 different types. Okay, so these are the different allocation techniques. These many ways we can allocate the frames to the processes. Now we'll see one by one. Equal, proportional, priority, and global and local replacement allocation techniques. First, let us move on with the first technique, that is the equal allocation. This is very simple. Okay, it's a very simple. So the first one is an equal allocation. So equal number of frames will be allocated to each process. For example, process, we are having some process P1 and process P2, and number of frames is equal to 30. Number of frames equal to 30. So here equal number of frames will be allocated to each process. So how many frames will be allocated to P1 and P2? So this is for just simplifying the explanation and taking only two processes. So it may be having a more number of processes. Okay, so two processes and number of frames in the primary memory, let us take it as a 30. So this is an equal number. So 30 divided by 2, which gives 15 frames. So simply P1 will be, P1 will be allocated to 15 frames. 15 frames will be allocated to P1, and similarly P2 will be allocated with the 15 frames. 15 frames. Okay. So for example, so this is okay. 15 frames given to P1 and 15 frames given to P2. So if the same thing happens with two more processes, let it be 4 processes are there and number of frames are 30. Now 30 divided by 4. Okay. So which gives 7 frames. Okay, so P1 will be giving a 7 frames, P2 will be giving a 7 frames, P3 7 frames, and P4 7 frames. Okay, then 7 plus 7 plus 7 plus 7 total 28 frames. But how many frames we are having? 30 frames. So addition to that, 2 frames are unallocated. Okay, so we can't divide a frame and share this frame to two more processes, multiple processes. So we have to give the equal number of frames, and the remaining frames can be unallocated. So which we can call it as free frame buffer pool. Free frame buffer pool. Okay, so those frames will be kept there. And see, this is for a future purpose. This will be for a future purpose. So like that, the equal allocation will be done. Okay, equal allocation will be done. Now, the second category is a proportional. Proportional allocation. So in this proportional allocation, the frames will be allocated based upon the size. So frames will be allocated based on size. Okay, so why? Because here if the P1 is having only 3 pages, P2 is having only 2 pages. So this is a pages example, and P3 we are having some 8 pages. It is having some 7 pages, right? So 3 pages will be loaded into 3 frames. 3 pages will be loaded into 3 frames. But here the 4 frames are wasted. Okay, no page will be loaded into that 4 frames. And in this case, 5 frames are being empty. And here 1 page should be waited until it completes one page completes its execution of process P3. Okay, beyond the frames, right? So in such case, you can see some portion, some wastage of memory will be there. Okay, some wastage of memory. So in this case, 4 frames, and in this case, 5 frames is wasted. Right? So in order to avoid that, based upon the size of the process, we can allocate the frames. So based upon the size, frames will be allocated. For example, if you take the same thing, so the number of frames are 30, and P1 size is some 5 KB, P2 size is some 10 KB. Okay, then the frames of a process will be calculated as the size of the frame divided by capital S, sum of all the sizes, okay, into number of frames. So this is a formula, just remember this to calculate the number of frames which can be allocated in this proportional allocation. Okay, see, for example, in this case, you can see, so what's the size of P1? Yes, so frame 1, F1 means total number of frames that have been allocated for process 1. So is equal to size of frame, that is a 5 divided by sum. Sum means 5 plus 10. Okay, and into what is the number of frames? 30. So we can write it like this: 5 divided by 15 into 30. So is equal to 10 frames. See, previously the same P1 we are allocating some 15 frames, but here 10 frames will be allocated here. Next, similarly F2, that means number of frames allocated to the process P2. So this is size is a 10 divided by sum 5 plus 10 into the number of frames 30. So which is 10 by 15 into 2, which becomes 15 frames. Sorry, 30, so 20 frames. 20 frames. So depends upon the size of the process. Here 20 frames have been allocated and for P1 10 frames have been allocated. You can observe here. So there will be less memory wastage here, less memory wastage. Okay, so when compared to the first approach, equal allocation, this will be the efficient proportional allocation. Okay, next, the next one is a priority allocation. So coming to the priority allocation, as we have said that so we know that if any process with a high priority comes to the CPU, first it will allocate the CPU, I mean it will complete its execution for that particular process. That means based upon the priority, the process will be allocated. So here also based upon the priority, okay, based on priority, more number of frames will be allocated. So highest priority process, if there is any highest priority process, then more number of frames will be allocated there. Okay, that's the only thing. There will be no formula. So the complete frame allocation depends upon the priority of the process. And the next one is a global replacement allocation and local replacement allocation. It's a very simple concept here also. Right? For example, in previous case we have taken two processes. Okay, so for example, let us take the memory. Let us take the memory in both the cases. So for example, this is for process P1 and this is for process P2, and similarly here also this is for process P1 and this is for process P2. Let us assume, okay, let us assume. Now in this case we know that if the CPU requires any page which is not available in this particular memory, so this is a main memory, okay, this is a main memory, this is also a main memory. So for example, page 1, page 2, page 3, page 4. Okay, so here also let us take here also let us take page 1, page 2, page 3, page 4. Right. So for example, P1 is having 5 pages. Here also P1 is having 5 pages. Right. Now you can observe P1, I mean number of frames allocated for P1 is a 4 frames. So obviously 4 pages have been already allocated here. So if the CPU requires the page 5, okay, if CPU wants to execute the page 5, it was requesting for page 5, then it will check whether it is available or not here. Otherwise, so one should be swapped out and the page 5 should be swapped in. In this case, in the global replacement allocation, one process, okay, the one process can allocate its page in the free space of another process. So here you can see P2, for example, P2 already the 3 pages has been fixed. Okay, so these 3 pages has been fixed. So this is empty, and here also this is empty, and this is empty. So if it is a global replacement allocation, the page of P1 can be loaded into the empty frame of another process. So it can utilize the empty frames of any process in the main memory. Okay, the frames allocated for the any process in the main memory. So P1 can utilize the space of P2, or if requires, P2 can utilize the empty space of P1. So this is called a global replacement. So one process page can be loaded anywhere in the main memory. So it can utilize the memory space of another process. But here that cannot be done. So local replacement allocation. So P1, the pages which are related to P1, process P1 should be loaded into only the frames which are being allocated for P1. So here P1 process can't be allocated in the process P2. Okay, the frames allocated in P2. So this is called a local replacement allocation. So P1, so here what happens? One page should be swapped out. That means one page should be removed and moved from main memory to the secondary memory, so that one frame will be empty. In that empty frame only the page 5 can be loaded. So page 5 can't be loaded in this location, in the empty frame of P2. But here the page 5 can be loaded in this particular empty frame. So that is the difference between the global replacement and the local replacement allocation. Right? So hope you understood. And the 3 points we have to remember in this particular allocation of frames, it is the minimum number of frames, a minimum number of frames should be allocated to each process. Should be allocated. So we should not avoid the process without allocating the frames. We have to allocate a minimum number of frames for each and every process. And the second one, the total number of frames, total number of allocated frames for all processes should not be more than total number of frames in primary memory. This is one more important. So whatever the frames we are allocating to the processes, that should not be more than the available frames. Okay. So previously we have seen total number of frames are 30. Among 30 only the 10 frames have been allocated to P1 and some 20 frames have been allocated to P2. Okay. So in the proportional allocation technique, right? And coming to the equal allocation technique also, so 15 frames are allocated to P1 and 15 frames are allocated to P2, where total number of frames becomes 30, which are equal to the available frames of main memory, that means a primary memory. And also the unallocated frames. So this also we have discussed. Unallocated frames should be in what's that? Free frame buffer pool for future use. Free frame buffer pool for future use. So these are the points we have to remember while allocating frames to the pages or a process. Okay, minimum number of frames should be allocated, and the total number of allocated frames for all the process should not be more than total number of frames in the primary memory, and unallocated frames should be in a free frame buffer pool for the future purpose. Okay, so hope you understood the main purpose of allocating the frames means if you allocate if the allocation of frames is optimized, then automatically there will be less fragmentation, and also it reduces the page faults, which can improve the efficiency of using the memory, the fast loading of pages to the CPU. Thrashing. So it is a situation when the CPU spends more time on servicing page faults. Okay, so here what is a page fault? We know that CPU will be executing the process only from the main memory. So this is the main memory. Okay, so we know that the main memory will be divided into different frames, and there will be one more memory which is a large in size. It is called as a secondary memory. So the processes will be residing in this secondary memory, and each process will be divided into pages. So here we are calling it as a pages, and the main memory we are calling it as a frames. So what happens? The CPU executes the process only from the main memory. So these pages will be loaded into frames of a main memory that we have discussed. So whenever the CPU is requesting a page from the main memory where the page is not available in the main memory, then immediately the OS will be loading the page, already existing page, from main memory to the secondary memory, and it will load the required page, whatever the page required by the CPU, that page should be loaded from secondary memory to the main memory. So that concept we are calling it as a swap in. Another one is a swap out. So swap out means loading pages from main memory to secondary memory. Okay, so whenever the CPU doesn't find the required page in main memory, so one page will be moved back to the secondary memory, and from the secondary memory the required page will be loaded into the main memory. That is called an in. In means secondary memory to main memory, secondary memory to main memory. So this is called as a swap in, swap out, that we are calling it as paging. Okay, paging. And if the CPU doesn't find the required page in the main memory, that we are calling it as a page fault. So what happens here? So if CPU doesn't find the required page in the main memory, so the page fault occurs, and now the OS will be applying the swap in and swap out operations to load the required page into the main memory. So the CPU will be spending a lot of time in servicing these page faults, okay, not in the execution, right? So hope you understood. It spends more time not in the executing the process, but swap in and swap out procedures. That means a paging, right? So then that situation we call it as a thrashing. So when the thrashing occurs, when it occurs, obviously, so thrashing occurs, first condition, when there are a lot of processes, running. Okay, a lot of processes running in the main memory. So this we can call it as high degree multiprocessing, multi-programming. High degree multi-programming. So this concept we have discussed in our previous sessions. Multi-programming means so multiple processes executing at the same time. Okay, and the second one, if existing physical memory cannot accommodate the pages. Okay, so obviously these both are related. So one is a lot of processes running, that means the number of processes are running in the main memory. So then there will be a lot of page faults occurs. For example, so main memory we are having, so without diagram I'll explain it. Okay, so the physical memory we are having some 10 frames. For example, let us imagine. Okay, so the number of processes running is equal to 5. Okay, so P1, P2, P3, P4 and P5. For example, P1 requires some 5 pages, P2 requires some 4 pages. I mean, P1 is divided into 5 pages, P2 divided into 4 pages, P3 is divided into 7 pages, and P4 is divided into some 4 pages again, P5 again 3 pages. So total frames are 10. So 10 should be distributed among these 5. Okay, for example, let us take equal distribution. In our previous session, we have seen what are the different ways allocation of frames. So equal distributions has been done. So 2 processes given for each and every process. So what happens here? Among 5 pages, only two pages can be accommodated in 2 frames. What about the other 3? They have to wait in the secondary memory. So whenever the CPU requests that particular page, one page from these 2 frames should be moved back to the secondary memory, and the third, one among the 3 pages which resides in the secondary memory should be moved to the main memory. So swapping will be done here, swap outs and swap ins, right? So this is the situation where the CPU spend more time in servicing this page faults. So this is called as a thrashing. Now, so these are the two situations where the thrashing occurs, right? Next, what are the, and also if it spends a lot of time in servicing or in solving these page faults, automatically thrashing leads to decrease in response time. Automatically the response time will be decreased because it takes much more time to get the required page from the secondary memory to the main memory. So in order to complete a process, right, automatically it will be taking a lot of time. So there will be a decrease in response time. So thrashing decreases the response time. And then see, what are the symptoms? Okay, how we can know that thrashing occurs? Okay, so the first one is high number of page faults. Okay, if there are more number of page faults, automatically that says that is a thrashing. Okay, high number of page faults. Next, increase in disk activities. So what is meant by this disk activity? Means a swap in and swap out process. Okay, so required page will be swapped in, and the page which completes its process, it will be swapped out. So disk activity, that will be increased. Okay, so this is nothing but swap in and swap out. Paging, simply we can say it as a paging, swap out. And the third symptom, okay, is just now we have discussed it, slow response time. So if the response time is very slow, then automatically the reason is thrashing. Okay, so these are the symptoms how we can know that thrashing occurs. Okay, and the next, causes. Okay, causes. So why the thrashing occurs? Okay, why the thrashing occurs? So here the first one is page replacement policy. Page replacement policy. If the page replacement policy is very poor, then automatically the thrashing occurs. Okay, the page replacement policy is very poor. Among the different page replacement algorithms, okay, different page replacement algorithms, if the page replacement policy is poor, then automatically we can say it is a thrashing. That occurs a thrashing. Next, this also we have just now we have seen high degree of multi-programming. So all these are related. So if we are saying it as a multi-programming, more number of processes will be loaded into the main memory, right? So there will be a lot of processes that are to be executed by the CPU. So if that many processes, the number of processes has been increased, automatically that may lead also to thrashing. So high degree of multi-programming, that's one more cause. Next, insufficient physical memory. insufficient physical memory. That means if the physical memory or main memory is very, very low, then automatically that may also lead to thrashing, because if the physical memory is very low, the number of frames will be very less. So if the number of processes are more and the number of frames are very less, it is very difficult to execute each and every process with a limited number of frames. So that leads to paging concept. Okay, that leads to paging, swap in and swap out. And the last one, just now we have seen, that is a lack of frames. Lack of frames. So these are the different causes thrashing, different situations which cause the thrashing. So one is a poor replacement policy, high degree of multiprogramming, insufficient physical memory, and the lack of frames. Now, what are the techniques to prevent this thrashing? Okay, what are the techniques? Techniques to prevent thrashing. So majorly there are two techniques. So one is working set model. So we'll discuss these things in our next session. I'm just listing out the techniques. Working set model. Another one is page fault frequency. Page fault frequency. And other rest of the things are, one is improving the page replacement policy. So selecting the optimized page replacement policy. So one is just identifying the effective page replacement policy, and so increasing the physical memory. Increasing of physical memory. So if you increase the physical memory, automatically the number of frames will also be increased, right? So next, high degree of multiprogramming. So reduce the degree of multiprogramming. Okay, so if we reduce the number of processes that are being executed by the CPU, automatically the thrashing will not be occurred. Okay, so these are the cases to prevent the thrashing. Okay, so again, causes, selecting the inefficient page replacement algorithm policy, and the high degree of multiprogramming, and insufficient physical memory, as well as a lack of frames. And in order to prevent the thrashing, so there are mainly two models, that is working set model and the page fault frequency, so which we discuss in our next session. And optimizing the page replacement algorithm, selecting of very good page replacement algorithms, and increasing of the physical memory. Automatically, if we increase the physical memory, the number of frames will also be increased. Automatically, the pages can be accommodated in the frames. And next, we can reduce the degree of multiprogramming. So these are the techniques to prevent the thrashing. So hope you understood what is thrashing. So once again, I'm repeating the definition. Thrashing means it's a situation when the CPU spends more time in solving the page faults, okay, rather than execution of a process. So page fault means if the required page is not available in the main memory, then the operating system have to load the required page from secondary memory to the main memory. So that is called as a page fault, and swap in and swap out, we are also calling it as a page. Right? So techniques to prevent thrashing. So very simple techniques. So first one is a working set model. Working set model, and another one is a page fault frequency. So coming to this working set model, the name itself indicates, so this mainly works on principle of locality. Principle of locality or locality model. Okay, we can say it as a locality model. Now, what is this locality? So locality means at a certain time, okay, at a certain time period, the number of pages being executed repeatedly. So if some sort of pages were being executed repeatedly for a certain time period, that we can call it as a locality. And this will be representing with a word called a working set. Okay, working set. So working set means it will be having all the active pages that are being executed. All the active pages that are being executed. So we know that there will be a page reference table, that we call it as a page table. So all the page references, that means whatever the page moved from secondary memory to the main memory, so the complete information about the pages which are being swapped in and swapped out, everything will be available in the page reference table. So the CPU will be executing a multiple pages, okay, multiple pages which are being loaded into the frames in the primary memory. So sometimes a few pages can be executed multiple times, okay, so that we call it as a locality. And this working set means it is an active pages and represented as, represented as the symbol delta. So delta is a working set. Delta is a working set. So this delta can be, the delta should not be too small. So if the size of working set, okay, here the delta is a working set, so the size of working set should not be too small. If the size of working set is too small, the number of page faults will be occurred. So for example, if the working set is only 2, so that means the 2 pages, we are just considering the 2 pages, okay, the last executed 2 pages. So obviously there will be a more page faults. So here we will be having a more page faults. And similarly, the delta should not be too large, because the number of pages will be loaded into that. Okay, the number of pages will be loaded, so we can't able to find these page faults, right? So the delta should be a moderate, that should not be too large and should not be too small. So that we are representing the set. How many pages we are considering is called as a this working set. Okay. Now, for example, let us take this is a order of executing the pages. So 2, 3, 3, 4, 4, 2, 3, 4, 3, 2, 2, 5, 6, 7, 7, 5, 5, 6, 4, 3, 6, 5. See, let us take the working set size as a 10. Okay, some 10 pages, the last 10 pages we are referencing. So here, let us consider 3, 4, 5, 6, 7, 8, 9, 10. So this is a one set with a time period T1. Okay, and for example, last, so 3, 4, 5, 6, 7, 8, 9, 10. So this is another time period. So this is a one time period and another time period. So we are considering 2 time periods. So there are more number of pages that are being executed. Okay, this is the order of executing the pages. Okay, so we are considering the time period up to 10 pages. So here the working set will be, what we are saying, working set means whatever the active pages. Okay, so here what are the pages? There are page number 2, 3, 4, 5, 6, 7. Okay, there are a lot of page numbers, but we are considering the working set as active pages at that particular time period. So in this particular time period, what are the active pages? You can see 2 and 3 and 4. That's it. So there are no pages of 5, 6, 7 in this particular time period. So the operating system will be allocating frames for only these pages. That means it will be allocating only 3 pages. Okay, 3 pages for this particular time period. Coming to this next time period, that means the time period means the last. Here we are considering the last 10 pages. Okay, that are being executed. So we can also calculate the working set for this particular time period. So you can see, yes, 5 is there, 6 is there, yes, 4 is there, and also 7. So this is a working set here. This is a working set. Okay, so here in this case, in this time period, only 4 pages will be allocated. That is, the 4 frames will be allocated, right? So in this way, we can allocate the frames based upon the active pages which are being in working set. If the pages are not active, automatically those pages will be deleted or removed from the working set. So this will be keep on updating from time to time. Okay, so this is a one approach. This is a one approach. So if you consider this D, I mean the sum of working set as D, that means a demanded frames. Okay, and M is a frames available in a memory. Okay, frames of main memory. Frames of main memory. So here D means demanded frames. So not all the frames will be comes here. So the sum of the working set. Okay, the sum of working set. In this case, only 4. Okay, only 4. In this case, okay, sorry. In this case, only 3. In this case, only 4. So here, once again, the 2 conditions will be taken. That is, sum of working set SI, that means it is represented as D, which is a demanded frames. So that are required. Okay. So because the working set will be having the active pages, these are the demanded frames. So if demanded frames are less than, okay, demanded frames are less than M, that means allocated frame, I mean available frames. So that implies what happens? Demanded frames are less than frames in the main memory. Okay, frames in the main memory. So no thrashing occurs. No thrashing occurs because all the frames can be allocated to the all the pages will be allocated to the memory. So when the problem occurs means when the demanded frames are greater than the frames in the main memory, then the thrashing will be occurs. So always we have to work on this one. So always the demand frames should be less than the frames of a main memory. So this is called as a working set model, which will be working with the help of principle of locality. So this is the first approach, how to prevent the thrashing. First approach to prevent the thrashing. So let us move on with the second approach, that is page fault frequency. So hope you understood this one, and we'll see the second one. There is a page fault frequency. The second technique to prevent the thrashing. Okay, see, this is a very simple approach. Page fault frequency. So coming to this page fault frequency, so let us consider a graph. Let us take some x-axis and y-axis. So x-axis, this is the number of frames. And y-axis the page fault rate. Okay, the page fault rate. So always we know that always the page fault rate should be low. So for example, if the number of frames are less, okay, if the number of frames are less, the page fault rate will be high. Okay, for example, if the number of pages are 4, okay, sorry, number of frames are 4 and number of pages are 10. What happens? Well, only four pages can be loaded into 4 frames. What about the remaining 6? So there will be a swap in and swap out operation, that is called a paging, and obviously we'll be having the page fault rate. So the page fault rate will be very high if there are a very less number of frames. So that will be gradually decreasing with the increase of the number of frames. Okay, obviously if the number of frames are some 20, so automatically there will be no page fault because the 10 pages will be directly loaded into the frames of main memory. So there will be no page fault. So that's why gradually, so with the increase of frames, with the increase of number of frames, the page fault rate will be decreased. So here we'll be having the two things. One is the upper limit and the lower limit. So this is the upper boundary, upper limit. We will be setting the upper limit as well as the lower limit. Okay, lower limit. Right. So if the page fault, okay, the page fault is greater than upper limit. If the page fault is greater than upper limits, what we have to do? So then the number of frames should be increased. So the number of frames should be allocated, should be increased. Okay, so by suspending the other processes, the frames should be allocated to the current process. And reverse the second one, if the page fault rate is less than, is less than lower limit. So here, what happens? The number of frames can be decreased. Okay, the number of frames can be decreased. Okay, how it can be decreased means we can suspend the frames which are not active. Okay, the pages which are not active in the frames. So those frames can be allocated to the process which needs a more number of frames. So these two things happens in this one. So based upon the page fault frequency, the number of frames can be either increased or decreased. If it comes with the increase, so whatever the frames which are inactive, so that will be removed and that will be allocated to the process which needs more number of frames. So this happens in the page fault frequency based upon the upper limit and the lower limit of the page fault rate. So we'll be deciding the number of frames which are going to be increased or decreased. Right? So this is the page fault frequency. By using these two techniques, working set model and the page fault frequency, so we can prevent the concept of thrashing file system. So here, first let us see what is a file. A file is a collection of related data. So related data means the file may have the textual data or the image or any records of a database. That also we will be calling as a file. So we can define a file as a collection of related data, and a file will be different from a directory, right? So directory means it is a collection of files. Okay, so a file is different from a directory. Now here what we are saying, file is a collection of related data. So this data can be either text or image or video. It may be a video file, image file, text file. So characters, strings, so all these comes under the text data, right? So these are different types of data which can be stored in a file. So every file will be having an extension. So the file will be having extension. What is this extension? So without opening the file, we'll be knowing what kind of data is stored in that particular file. That means this represents type of data, the type of data stored in a file. A type of data stored in a file. For example, so for every file there will be an extension. Okay, for every file. For example, if it is an image file, the extension will be .jpeg or .png, .bmp, okay, etc. There are a lot of extensions. So without opening the file, if you find these extensions for any file, then automatically you can know that this is an image file. For example, if it is a video file, then .mp4 or .mpeg, etc. So .vob. So these are all different extensions which represents the video file. Okay. Similarly, text file. So .txt, .doc. Okay, these are all text files, right? Similarly, we know .ppt, which is a PowerPoint file. .xlsx, which is an Excel file. So like that, for every file there will be an extension. Every file there will be an extension. So with the help, which represents the type of data stored in a file. So without opening that file, we can able to know the type of data. Now, what are the different attributes of a file? So now you have an idea about what a file. File is a collection of related data, right? Now, what are the different attributes of a file? So attributes means which describes that file. Okay, so we can also call as metadata. Okay, metadata, which describes the file. Okay, the first one is name. So every file will be having its own name. Okay, it's a file name. A file name. So based upon the type of data or type of, what kind of data is stored, that based upon that we can give a file name. Okay. Now the second one is an extension. Just now we have discussed about this one, extension. For any kind of file there will be an extension. So which starts with a dot. So there will be .exe file, which is an executable file. So coming to either C program or Java program, definitely final output is an exe. .exe file will be generated. If once a program has been successfully executed, then .exe file will be generated. Similarly, .obj, which is an object file, machine understandable language, right? So for every file there will be an extension. So we know .c represents the C file, .cpp represents the C++ file, .py for Python file. Like every file will be having an extension. And the next one, identifier. So every file will be having a unique identifier which will be used by the file system to access. Okay, so unique identifier. Okay, unique identifier. For every file there will be a unique identifier. Next, extension, yes, size. The size of a file. Okay, so how much space, how much storage occupied by a file. So usually the storage of any file can be represented with bits or bytes or kilobytes, megabytes, etc. So the file storage, the file size will be in this way. And the next one is a location. Location means a path where the file is located. So obviously the files will be stored in the secondary storage, right? So files will be stored in the secondary storage. So the path where the file is located, because if you know the location of this file, we can easily retrieve the data whenever it we require, right? So every file will be having the location, right? So name, extension, identifier, size, location. Similarly, time and date. So every file will be having the time and date when it was modified or created. Okay, time and date when file created, see, last modified, similarly last accessed. So all these things will be there, right? See, file time and date for a file, when the file is created, when the file last modified, when the file has been last accessed. So every detail will be there. And next, protection. Okay, so that means access to the data. That means a permission to the data. Okay, protection means access to the data. Similarly, encrypted files. There will be some encrypted files where the data had a protection, which is an unreadable format. Right? Next, there is a system file. System file. So system file means which will be used for operating system. So very important for the operating system. Similarly, here the protection which will be read only, read write. So if it is a read write, then the user can modify the data, access the data as well as modify the data. If it is a read only, the data can't be modified, but only it can be accessed. So that is the protection. And encrypted as usual. And similarly, there is one more thing, that is a hidden. So a file can be hidden. The file can be hidden. So you can find all these attributes, okay, for any kind of file in an operating system. So you can go with the folder options, file and folder options. You'll be having a file and folder options in the operating system. So there you can see all these things. We can protect the file, okay, and also we can hide the file, right? So these are all the major attributes that represents the file, right? So location, size, similarly time and date, when it was created, when it was modified, when it was last accessed, and everything, right? So hope you understood. the definition of a file as well as the attributes of a file. So a file can be defined as a collection of related data which is stored in a secondary memory. Obviously, the files will be stored in the secondary memory. Okay, secondary memory means hard disk. So hard disk or magnetic tape, anything. So usually we will be calling it as a hard disk. So the files will be loaded in the hard disk itself. The concept is file operations. So we know that a file is a collection of related information which has been stored in the secondary storage. So what are the different operations? So the first operation is create, write operation, read operation, close operation, yeah, okay, open operation, and then okay, I'll write the first one as open, right? Okay, yeah, open, create, close, delete. Right? So these are the major operations that can be performed on a files, right? The first one is a open. So we know that in order to perform any one of these operations, the first thing should be open a file. So every file will be having a name. So in our previous session, we have seen the attributes. In that, the first attribute we have seen is a name. For every file, there will be a name, right? So for even to perform all these operations, compulsory the file is accessed with the help of its name. And the first one is open. So in order to read or write operation, in order to read or write operations, we have to open the file, right? So open a file to perform read or write operations. So reading means reading the data from the file, and writing means writing the data into the file, right? Next, create. So in order to open a file, first a file should be created. So during the creation itself, we are giving some name, right? So here a file can be created. Creates a new file with a name. So it will be stored, and one unique number will be given by the operating system in order to access, and in one location that file will be created. So in order to retrieve the data, right? So there's a creating a file, a new file, creating a new file. And then once it was created and once it was opened, right? Then the write operation. Write operation means writing the data, writing or storing data into a file. So writing the data or storing the data. Okay, so that is called as a write operation. And read operation, so that is only to access the data. It is not meant for writing the data. So reading means accessing the data. Accessing doesn't mean to write the data, right? Accessing the data from a file, right? And once a user completes the read and write operations, then immediately the file should be closed. So if the file is not being closed, automatically there is a chance of damaging the content of a file if there is a sudden power off or a file crash. Right? So obviously we have to close a file. So user have to close a file once the read and write operations has been completed. So close the file after read and write operations. Okay, and finally delete. So it will permanently remove the file from the storage, and that means the memory will be free. The memory will be free, which can be used for storing other files, right? So removed from secondary storage. So because we are saying that a file is a collection of related information which is being stored in the secondary storage. So removed from the secondary storage, and memory will be freed. Memory will become free. And this free memory can be allocated for some other files. Okay. And apart from these things, there is a one more operation which is called an append, which is similar to write operation, in order to add a few more information to the existing content. Okay. So write or store data to an existing file. Then this particular operation can be performed. Append. Okay. See, coming to the read and write. Okay. So the file should be available, and with the help of a file name, the read and write operations will be done. And in order to create, there will be no file. Now, while creation itself, a file name will be generated, right? And in order to read, write, or append, okay, the file should be opened. Okay, the file should be opened. So without opening the file, you can't apply the read operation or write operation or append operation. Even this close operation also not able to perform. Okay, but delete, the file must be closed and then only the delete operation can be done. Okay, similarly create means creating a new file, right? So these are the different file operations, okay, different operations that can be performed on a file by the user. File accessing methods. So here the file accessing methods is nothing but accessing the data, right? So here the accessing of data, accessing data. So accessing means either reading from a file or writing into a file. So accessing means reading or writing. So we can also call it as a manipulations, right? So we know the definition of a file. A file is a collection of data, similar data, which is stored in the secondary device. So the data can be anything. So it can be a group of characters, it can be a records, etc., etc. So here, how many ways we can access that kind of data? So there are three types or three categories or three ways we can access the data from the file. So one is sequential access. Sequential access, and the second one direct access, and the third one indexed sequential access. Indexed sequential access. So we'll see one by one. So what happens and how we can access the data in the sequential mode or direct mode or indexed sequential. So let us start with the sequential access. So here the name itself indicates, so the data will be accessed in a sequence. Okay, so data is accessed in a sequence. So whatever the sequence we are inserting the data, in the same sequence the data will be accessed. Okay, so here if you want to read an instruction, the command will be, the instruction will be read next. So read next means the pointer will be pointing towards the next pointer, right, next memory location. Similarly, write means write next. Write next. Write next means, so the pointer will be moving towards the end of the data, and whatever the data we are writing, that will be appended at the end of the data. So here data will be appended or written at end, always at end, right? So the best example for this sequential is our compilers. So example for the sequence example is our compiler. So because, so whatever the compiler do means, in whatever the sequence we are writing the instructions, in the same order the sequence, the instructions will be executed, right? So you might be knowing about the C language or Python or Java. So the default control access is a sequential access. So what in whatever the way we are writing the instructions, in the same way the instructions are being executed in all the different cases, right? So the compiler will be an example for the sequential access. Now what are the advantages? Advantages of using this sequential access means, so simple to implement, very simple to implement, very simple to implement. Okay, and the main disadvantage, the disadvantage of using this particular sequential access means, so if you want to read the data which is far away, you have to traverse each and every instruction until you reach to the destination. So large amount of data should be traversed. Okay, so more traversal should be needed. More traversal should be needed, right? So if we want to access the data which is at the beginning, then it will be very easy for us. So if the data which we want to retrieve is at the end, automatically the data should be traversed, the file pointer should be traversed from starting point to the end point, because the data will be accessed only in a sequential way. Okay, so this is all about our sequential access. Coming to the second category, so that is called as a direct access. Direct access. So here the data is accessed in random way. Random way means we need not go in a sequential order. So we can directly move on to the block or record which we want to retrieve or which we want to access. So it is not necessary to go in a sequential order. So data can be accessed randomly. Randomly means whatever the block we want to access, directly we can access that particular block. Okay, instead of going in a sequential way. So this is a direct access. And here the main disadvantage, so advantage means less traversal, because we need not traverse each and every instruction. And disadvantage is it's a more complex to implement. It is more complex to implement. This is the main disadvantage of direct access. For example, if our file consists of a number of blocks, different blocks of data, so let it be B1, B2, B3, B4, B5, B6, and B7. B means a block. Okay. So if now we are at this position, if you want to access a B6, directly you can move towards this B6 in this particular direct access. But if it is a sequential access, B1, then B2 should be read, B3, B4, B5, and this B6. And we have to traverse everything until you reach the destination. That in a sequential access. But in direct access, directly you can move from B1 to B6. Directly we can select the required block. So a little bit complex to implement such kind of access mechanism, and very less traversal. It need not traverse each and every block of instructions. And the third category is an indexed sequential. So which is an extension for the sequential. So it is an indexed sequential. Okay, so here the indexed sequential, what happens means the name itself indicates. So for every block there will be an indexing. Okay, so similar to our book. So if you consider any textbook, we'll be finding the index at the beginning. So we can easily find out the chapter which we want to read by directly moving on to that particular page number. So that index page will be consisting of the chapters and the page numbers. In a similar fashion, indexed sequence also, it will maintain an index of all the memories. So this is an index. So let it be some 10, 1000, 1010, 1020. So whatever, maybe this is an address, for example. Okay, so if you want to access this 120, 1020, so there will be a memory. So there will be some data. Okay, so all the memory addresses will be arranged in an index. So this is an index. So which is being referenced to the actual memory. Okay, so this is called as a indexed sequential. So here the advantage is accessing will be efficient. Okay, accessing will be efficient. But the main disadvantage, so this is advantage and main disadvantage. See, extra memory should be required. Extra memory is needed to store index of every memory. So we require some extra memory to store this particular index page. Right? So this is called as an indexed sequential. So these are the three mechanisms to access the data from a file. So sequential access, direct access, and indexed sequential access. Right? So every access mechanisms are having the advantages and disadvantages. So these many ways we can access the data. Access the data means reading the data from the file or writing the data into the file. So manipulation, some sort of manipulations will be done. Right? So this directory is a collection of files, and this file is collection of data, or we can also call it as a records, collection of data or records, right? So how many ways these directories will be structured? So there are four categories mainly. The first one is single file directory. Next, two file directory, tree structure or hierarchical structure. And finally acyclic graph. So these are the different ways a directory can be structured in operating system. So let us start with the first one. So coming to the single file directory. The name itself indicates only one directory will be there and all the files will be created in that particular directory only. So single directory. So all files will be stored in same directory. Okay, so for example, let us take A is a directory. Okay, so square box represents directory, circle represent file. Okay, so as per this session, so just remember, if I represent anything with a square or rectangle, that represents a directory and a circle represents a file. So one directory where it will be having, so file 1, file 2, file 3 and so on, file 4. So all the files will be residing under the same directory. Okay, so here what is the advantage of using this particular single file directory? So one advantage is easy implementation, because only one directory will be created. Easy implementation. And another one, easy searching. So if you want to search any file, so you can directly search that one in only one directory. So these are the advantages. Coming to the disadvantages, what are the disadvantages? So only one disadvantage here is we need, so there might be a chance of having a naming collision. So naming collision is a one disadvantage. Naming collision. That means, so we are storing all the files in a same directory. So we have to give the unique name for each and every file. So if it is not possible to give the same name for multiple files, so there might be a chance of naming collision. Okay, and also searching. So whatever the advantage, that same will be the disadvantage. When directory is having large files, so if directory is having a large amount of files, number of files, then automatically the searching is some sort of difficult process. So this is the advantages and disadvantages of single file directory. Only one directory will be maintained and all the files will be residing under the same directory. Now coming to the second one, that is a two file directory. So coming to the two file directory, so there will be a root directory which we call it as a master directory, and every user will be having their own directories. So that will be in a two level, right? See, so instead of creating a single directory, there will be a root. There will be a root. So in the root there will be different users. See, U1, U2, U3 are different users. So every user will be having their own directory, and in the users there will be files. See, this is a user level directory, and these are all files, and this is a root, which also called as a master directory. Master directory. So in this case, you can see the files, whatever the disadvantage here, that can be overcome. So the disadvantage of one file directory is a naming collision. So here there will be no naming collision. Okay, no naming collision. So it becomes the advantage. Okay, no naming collision. No naming collision. So because every user will be having their own directory, and all the files related to that user will be stored in their directory itself. So you can see F1 and F2 are the files in user 1, and you can give the same names for the files which are stored in user 2 also. So here this one is an advantage, and searching becomes easy. Okay, searching also becomes easy. Searching becomes easy because we are grouping here. Okay, based upon the users. Based upon the users. Whereas disadvantage, what is the disadvantage of this particular structure? Means we can't group the files, okay, under the same directory. So grouping of files is not possible. So here a grouping means creating the subdirectories. I am writing here subdirectories. So user 1 will be having only the file 1 and file 2, user 2 will be having file 1 and file 2, user 3 will be having file 3, user 4 will be having file 4. So under the user we can't create a subdirectories, right? So again we can't group the similar files into a subdirectories. So that is not possible in this two file directory. So in order to overcome this disadvantage, we are moving on with the third one, that is a tree structure. Tree structure or hierarchical structure. So in this hierarchical structure, what happens means, so that the same thing happens. So see, there will be a root. Under root, you will create a user directories. Different user directories will be created. And under user, so there will be a files which can be stored, as well as you can also create subdirectory. So in this subdirectory, we can create a files. See, so under the root, every user will be having their own directories, and in their directory there will be different files. And apart from that, user can also have a subdirectory. Usually the same thing will be implemented in our personal systems. In our personal computer, the same tree structure will be applied. Okay, if you click on the Explorer, you can see the C drive. So under the C drive, some desktop, okay, and downloads. So like that, you can find out different directories, and in the directories we'll be finding these files, right? So this happens here. So user directory, and then the subdirectories. User directories will be having the subdirectories, and subdirectories will be having the files. So here, this is the advantage. Whatever the disadvantage here in our previous structure, that will be the advantage. That means grouping is possible. The grouping is possible. And here the disadvantage. What is the disadvantage of this particular thing is, so the files of one user can't be shared by other user. Okay, so files can't be shared among different users. So user 1 can't access the subdirectory or F3. User 1 can't access file 7 because file 7 is under user 4. So this is the main drawback of this particular tree structure. So grouping is possible, there will be no problem, and files can't be shared. So only F1 and F2 can be used by user 1 itself, and similarly F3 and subdirectory 1 can be used by user 2 only, and similarly F4, F5 and F6, all these three files can be used by only user 3. Similarly, so this can be happens. This is a disadvantage. So in order to overcome this advantage, we are moving with the fourth category, that is acyclic graph. Acyclic graph structure. So what is this acyclic graph structure means? So whatever the disadvantage here, that becomes the advantage. So one user can access the files of another user. See, user 1 can access another user. Similarly, user 4 can access this one. Similarly, user 2 can access this one. So that means the files can be shared. So this is the advantage here. Whatever the disadvantage we have learned in the third one, that is a tree structure. So files can be shared among different users. Okay. So here you can see user 1 can access the subdirectory which was created in user 2. And similarly, user 2 can access the subdirectory and files which are created by user 3. And similarly, subdirectory 2 can be accessed by user 4. So this happens here. So the data can also be shared. The files can also be shared. So what is the disadvantage? So only one disadvantage over here is complex to implement. Complex to implement. It's a complex to implement. So sharing of one user files to another files, right? So that is a disadvantage. So these are the four ways how the directories can be structured to access the files efficiently. Okay. So see, single file directory, two file directory, next a tree structure or a hierarchical structure, as well as acyclic graph structure systems. So here the name itself indicates the file system means it helps the operating system to organize and store the data. Okay, so this file system is used to organize the data or organize the files, organize, store and manage files, right? So we know the operating systems will be different types, okay, types of operating systems, like we know Windows operating system, okay, similarly Linux operating system, similarly like Mac OS. So these are different operating systems. Linux or Unix also, it's an operating system. So different operating systems will be supporting different file systems. So every operating system will be having their own file system. So in order to organize, store or manage the files. Now we'll see what are the different types of file systems. So coming to the first one, which is a FAT. So FAT stands for file allocation table, file allocation table. So there are a lot of extensions like FAT16, similarly FAT32, etc. Okay, so this is compatible with older systems. Okay, older systems. The two Windows. Okay, the two Windows. So in the earlier versions of Windows operating system, the file system, default file system will be the FAT, file allocation table, right? So here it is a limit with file size. So it supports only a limited file size, which is usually less than 4 GB. Okay, it supports only with limit with the file size. So it is, as we said, that this is a compatible with older systems of Windows operating system. And there is one more file system called EXFAT. So EXFAT means extended file allocation table. Extended, so extended version of FAT. So this means it supports large files, which is usually greater than 4 GB. So the FAT16 or FAT32 will be supporting only the files which are less than 4 GB. But coming to the extended FAT file system, it supports larger files which are usually greater than 4 GB. And the next one is NTFS. So which stands for New Technology File System. So it stands for New Technology File System. So one thing, supports larger files, and also provide security, okay, or protection, etc. for files, okay, encryption forms. So that will be supported in this NTFS, and is also default for Windows operating system. So whatever the versions now available in the market, the default file system for Windows is NTFS. So that means if you are installing Windows 11 or 10, okay, the default file system is a Windows file system, right? Next, so FAT, exFAT, that means extended. Next, NTFS. The next file system. So these are different file systems which support different operating systems, right? The next one is ext4. Okay, so there are different versions, ext2, ext3 also. This is default file system for Linux operating system, Linux or Unix also. So there is one more operating system called Linux or Unix. Okay, it's open source. So the default file system is ext2 or ext3, and HFS plus, which stands for hierarchical file system plus. So this is the file system compatible with older versions of Mac OS, okay. So similar to our FAT, okay, file allocation table, FAT, FAT16 or FAT32 file systems, which are compatible with the older versions of Windows. So here HFS plus is a hierarchical file system plus, which is compatible with older versions of Mac OS. And the next, APFS, which is called as Apple file system. So this is default file system of newer versions of Mac OS, So similar to FAT and NTFS. So here HFS plus and APFS. So these are all different types of file systems. So now we have seen for Windows operating system. It will be FAT16, FAT32 or NTFS. These are different file systems which supports the Windows operating system. So coming to the Linux or Unix. So ext2, ext3 and ext4. These three are the file system supports for Linux environment. And similarly, Mac OS, which is HFS plus, hierarchical file system plus, and similarly APFS. So these two file systems which supports Mac OS. Apart from all these three, there is a few more file systems called NFS. NFS stands for Network File System. So which is used in a networks, okay, in a network, right? Similarly, database file system, which are where the data will be represented in terms of records. Here records, stores in terms of records. So these are a very few file systems, but these are the major file systems for operating systems, different operating systems. Okay, so as I said that a file system is mainly used to organize or store and also manage the files. Okay, file consists of some data, related data. So every operating system will be supporting different file systems. File allocation method. So it defines how the files are being allocated in hard disk or storage. So we need not call it as a hard disk, we can call it as a storage. So usually the files will be stored in the secondary storage. So how these files will be allocated? So there are three ways how the files can be allocated. First one is a contiguous file allocation. Another one is a linked file allocation. Another one is a indexed file allocation. Okay, indexed file allocation. So initially we have to know that the secondary storage will be having a lot of disk blocks. Okay, lot of disk blocks. So among that disk blocks, how this file can be allocated? So file will be divided, and each portion of the file will be allocated to each disk block. So let us start with the first one, that is a contiguous. So let us take the hard disk. So let us assume this is a hard disk, and this hard disk will be having a different disk blocks. So let us assume these are the disk blocks of a hard disk. These are different disk blocks. So in these disk blocks, we have to allocate the files. How many ways we can allocate? So this is a hard disk. Hard disk for a storage. Okay, storage. So each disk block will be having the values 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So these are the numbering given for the disk blocks. Right? Now each file will be allocated to these disk blocks. As the name itself indicates, this contiguous. So the file is allocated to continuous disk blocks. Continuous disk blocks. Okay. So the complete file will be allocated in a continuous disk blocks here. And here it will maintain some file allocation table. So file allocation table. And this table consists of directory entries. Okay, directory entries. So directory entries means the information related to the file. Okay, and this directory entries will be having the three fields. One is a file name, another one is a start block, so from where it starts, and the next one is the length of that particular block, length of that particular file, sorry. So these are the three fields that are used in file allocation table. So as we are saying, the file will be allocated to continuous disk blocks, right? So for example, a file size is some 15 KB, okay, and disk block size is around 5 KB, and if the file starts at disk block 4, then automatically the remaining blocks will be at 4, 5 and 6. So these are the disk block numbers where the file will be allocated, because each block consists of 5 KB, so total file size is 15 KB. So continuous blocks only the file will be allocated. Okay, for example, if it is of 18 KB, then 4, 5, 6 and also 7 and also 7. So the file will be allocated in this way. So what happens? This is a 5 KB, this is a 5 KB, this is a 5 KB, and this is a 3 KB data will be stored. What about the remaining 2 KB? So there is a memory wastage. So that we are calling it as an internal fragmentation. So that is one drawback of this contiguous memory, contiguous file allocation. That is an internal fragmentation, right? So it allocates. So one concept is it allocates the file in a continuous disk blocks, only in the continuous disk blocks. For example, let us consider this disk space. This is a hard disk. So here the file name, some A is a file name. So which starts at 1 and the length is 2. So that means here this is a okay, and the length is 2. That means only 2 disk blocks. That is also contiguous. After 1, the second block. So these 2 blocks will be storing file A. So this is of file A. And similarly, if it is B, and if it starts with a 4, and if the length is 5, so it starts with a 4. Okay, and if the length is 5, so 5 blocks, 5 contiguous blocks. See, these are the contiguous blocks. So 1, 2, 3, 4, 5. So this is a B. The file B will be stored in 5 contiguous blocks. 5 contiguous blocks. Okay, so this is how the contiguous file allocation will be done. So one point, the file will be allocated to continuous disk blocks, and the file allocation table will be maintained, and this file allocation table will be having the directory entries of all the files. So one is a file name and where it starts and what is the length of the file. Now, what are the advantages? So advantages of using this file allocation is very simple to implement, because it is contiguous, simple to implement. It is simple to implement, as well as sequential access will be supported. Okay, so we have seen file accessing methods. In that accessing methods, we have seen sequential, direct, and indexed. So sequential access will be supported. Sequential access. So that means data by data, line by line, or the sequential form, right? And what about the disadvantages? What about the disadvantages? The one disadvantage is for very large files. For very large files, it is difficult to find out the contiguous memory blocks. For example, if the file size is some 100 KB, okay, and disk block size is let it be so 5 KB. So how many blocks required to allocate this file means 20 blocks. So all the 20 blocks should be in a contiguous manner. So it is difficult to find a large number of contiguous blocks, okay, in order to store a large files. That is the main disadvantage. So coming to the large files, allocation is difficult. Large files allocation will be difficult, and similarly internal and external fragmentation also there. Internal and external fragmentation is also there. So what is the internal fragmentation? Just now we have seen. For example, if you consider this B, so B is of some around 21 KB. Okay, 21 KB. See here, I will tell you 21 KB, and this block is 5. So how many blocks it requires? 4 blocks. If you take 4 blocks, it can accommodate only up to 20 KB. So now we have to take one more block, which is a 5th block. So in the 5th block, how much KB, how much data will be stored? Only 1 KB of data will be stored. What about the remaining 4 KB? That is a wastage. So that is called as a internal fragmentation. Internal fragmentation. For example, if you consider C, okay, if you consider C, and I'll write here. if you consider the file C, okay, C is of capacity, for example, 17, okay, 17. How many blocks are required? So disk block size, for example, disk block size is 5. How many number of blocks it requires? Some 4 blocks of memory will be required, right? So all the 4 blocks should be in a contiguous. But here you can see this one is available, this one is available, this one is available, and this is also available, but there is no contiguous. Okay, there is no contiguous. So total how much memory is available? 5 plus 5, 10, 15, 20, 25. So 25 KB of data can be stored in the hard disk, but we can't store the file C in this one because file C is having only 17 KB, which have to be accommodated in a contiguous blocks in this particular file allocation method. So this is called as an external fragmentation. Internal fragmentation and external fragmentation is also difficult. And file size problem. There is one more problem, file size problem. So what is this file size problem? If the file is being increased, okay, the data is increased and file size is increased, and it is difficult to accommodate the new block. So because it is a contiguous. So in order to find the contiguous block, that will be difficult. So this is also one disadvantage of this contiguous file allocation method. So in order to overcome all these disadvantages, we are moving on towards the second one, that is a linked file allocation method. So let us see what is a linked file allocation method, what happens in that. Okay. Linked file allocation method. So these are the disks as just we have seen. So these are the disks, just give the number. Yes. So in this link, it is not necessary to store the complete file in a contiguous. So data is not, so instead of data we'll write a file. Okay, file is not stored in contiguous blocks. So in order to link up the blocks, every block will have a pointer which points towards next block, which point towards the next block. So here one pointer will be given for each and every block, and that pointer will be pointing towards the next block. So that is why we are not storing the file in a contiguous blocks. And see, pointer in last block points to null. Okay, points to null in order to say that is a last file. Okay, last block. So here also there is a file allocation table. In the file allocation table, it will give the 3 terms. One is a file name, start and end. So let it be file A. It starts at some 2 and it ends at some 7. So it starts at 2. Okay. So the pointer at this 2 will be pointing towards the next block. So whatever the next block, right? So the next block is 6, for example. Okay. So let us write here A, file A. It starts with a 2. So the next one is links to 6, where it links to 11 and which links to 7. So that means A requires some 4 blocks, and that 4 blocks are not necessary to be a contiguous. So one block, the pointer at one block will be pointing towards the next block. So first starting with the 2, the pointer in 2 will be pointing towards the next block. So next block is 6. So the pointer in 6 will be pointing towards the next block, which is 11. So 11 points, the pointer at 11 links with the block 7. So the 3 fields, one is a file name, start and end. Okay, and for example, second one, the B, so it will start at some 10, and the last one, maybe it is 1, right? So it starts with 10, the pointer at 10 will be pointing towards another one, the next block, so which is a 5, and 5 points to 1, for example. 5 points to 1. Okay, so this is how the allocation will be done. So where it need not require any contiguous memory allocation. So there is no external fragmentation. Here there is no external fragmentation, right? So here the advantage is no external fragmentation. No external fragmentation, because so the blocks need not be in a contiguous manner, right? And also the file size problem is also removed, because if the file is increased, then automatically wherever the block is empty, the file can be accessed to that particular empty block. So no file size problem. There is no file size problem. Okay, And drawback, no direct access, So if one process, I mean, if we want to access a block 7 directly, it is not possible. So it have to access from 2 to 6, 6 to 11, 11 to 7. It is a sequential, there is no direct. Okay, that's a one problem. And the next problem is every block contains a pointer, so where some memory should be allocated for that pointer. So obviously pointer overhead is also there. Pointer overhead. Okay, so hope you understood. Every block will be having a pointer, we are saying, which points towards the next block. So every block should leave some memory to store this pointer. So memory, some sort of memory will be wasted, or we can also say it as a pointer overhead. That's the problem. Okay, and in order to overcome all these things, mainly the direct access, there is no direct access in this particular method. So we are moving on towards the third method, that is called indexed. See. Yes. So coming to the indexed, what happens in this indexed? In this indexed, every file will be having indexed block, one indexed block. Okay, every file will be having one indexed block. Okay, so what will be there in this indexed block? So this indexed block, it stores addresses of all blocks of a file. So if your file consists of some 5 blocks, it will store the addresses of all the 5 blocks. It will store the address of 5 blocks. For example, see, this also contains the file allocation table. So where we are having only 2 columns, which is a file name. Okay, file name. So the indexed block. Okay, then indexed block. Only 2 files, file name and indexed block. For example, so 7 is an indexed block. Okay, 7 is an indexed block, and all the related blocks, I mean the block 7 will be having the addresses of all blocks of this particular file. So for example, the file has been stored at 8, 2, sorry, let us go with an order, 1, 3, 6, 8 and 12. So if the file is stored in 5 blocks, and the address of all these 5 blocks will be stored in indexed block called 7. In order to avoid confusion, let us take this one, file. If a file is stored in these blocks, so address of all these blocks will be stored in address. So this is called as an indexed block. Okay, so this block number will be displayed in the file allocation table. For example, file A. So file A, so which is having the indexed block, which is a 7. Okay, 7. So 7, from here there will be location 1, 3, 6, 8, 12. So these are all the files, the blocks which stores the file. Okay, so file A is stored in 5 blocks. File A is stored in 5 different blocks. So all the addresses of all 5 blocks will be stored in one block, which is a indexed block, which is called as an indexed block. So here 7, so which can be having 1, 3, 6, 8 and 12. So what is the advantage of this one is direct access. So we need not perform the sequential access. If you want to access some data which is at 12, directly we can access the block 12. So we need not go process with the 1, 3, 6, 8, 12, because 12th address will also be available in the 7th block. Okay, direct access will be there. Okay, and also no external fragmentation. No external fragmentation. This is also advantage. No external fragmentation. Coming to the disadvantage. So what is the disadvantage of this one is? So this is a automatically it's a pointer overhead or index overhead, because so it contains a lot of indexes. There will be an index overhead. Okay, and also we are storing one file dedicatedly as an indexed block. So there will be some sort of memory. If it is a very less, if the file size is less, automatically one block will be wasted for storing the address of that particular file. Okay, and also if you lost this indexed block, automatically the file can't be accessed. Okay, so if indexed block is lost, file will be lost. Okay, if indexed block is lost, automatically we can't access the file, because the complete address of all the blocks of a particular file will be stored in the indexed block itself. Okay, so this happens here. So these are some advantages and disadvantages. But direct access can be done in this indexed file allocation method. System protection. So here a protection means giving a security. So to what we are giving this protection? So one thing, the data, process, and very important thing is a resource, right? So this system protection is a process of providing security to data, a process, or the resources used by the users. Okay, here the security means to provide unauthorized, authorized access only. So that means we can simply say it as an access control. Access control. So access control on data, process, or the resources. Okay, avoiding the unauthorized access. So that we call it as a system protection. So here the system includes the data, process, as well as the resource. Now, what are the different goals of system protection? So the first goal is to prevent, very important, to prevent misuse of resources. So every process will be using a lot of resources. So this one major goal of system protection means to prevent the misuse of the resources. So to prevent from the unauthorized access. And the next one, see, this is one more important, access control. So access controls means unauthorized access. So accessing of data or resources, etc., etc. And the next one, system reliability. What is the system reliability means? It prevents the errors, okay, from crashing the system. Okay, so it prevents errors from system crashes. So whenever the system crashes, whatever the error we may expect, that will be prevented. System crashes. And the next one, security and protection. Security and protection. So security and protection means, so access to data is restricted from one user to another user. Okay, one user can't be able to use the data of another user. So that kind of security and protection will be given for the data. So this is one more goal of system protection. Okay, then we'll see what are the different mechanisms. What are the different mechanisms used in this system protection? So system protection mechanisms. So the first one is authentication. So every user have to authenticate himself or herself. So this usually done with the help of passwords or some biometric information, whatever it may be. So passwords, the login passwords. And the next one, authorization. So that means verifying the user. Okay, so the person have to verify himself or herself. So verifying user to access. So what access will be done? So access may be on data or resource, etc., etc. And then, so the one of the goal, that is access control. Access control means preventing the unauthorized access. So preventing unauthorized access. Okay, preventing from unauthorized access. So the next one, file permissions. So coming to restrictions on data, so file permissions will be given. So in Linux, for example, in Linux, we are having chmod command, which gives the permissions or privileges to the users. Okay, so who can be accessing the files. So this kind of thing. So we can restrict the access on data. Okay, next, memory protection. So which is restriction on memory usage. Or memory access. So there will be restriction upon accessing the memory. Okay, that's a memory protection. Similarly, I'm erasing this one. Similarly, the next one is a CPU protection. So in this CPU protection, so it will be prevented from unidentical CPU usage. That means continuous usage of CPU. Okay, efficient usage of CPU. So it avoids or it gives interruptions. Okay, simply we can say it gives interruptions to avoid continuous usage of CPU. Okay, infinite usage of CPU, so we can use some interruptions, timing interruptions like that. And then the next one is IO protection. So here also it will restrict on IO access, so which may prevent the hardware damage. So if you are not using the input and output operations carefully, that may lead to the hardware damage. So it prevents the hardware damage. It prevents hardware damage. Okay, so efficient use of IO protection. Simply we can say efficient use of IO protection. And the next one is an encryption. This is also most important. Encryption. So encryption means protecting data. Protecting data. Okay, by encrypting the data, by encryptions, by encrypting the data. So what is meant by encryption means, so it will convert the readable format into unreadable format. So that kind of protection will be given for data in order to avoid unauthorized access. So these are the system protection mechanisms: authentication, authorization, access control, file permissions, memory protection, CPU protection, IO protection, and encryptions. Right? Yes. So now we will see what are the different types of security protections that has been given. Right? So types of protections. Types of protections. First one, hardware protection. Hardware protection. So it will use a different registers. Okay. So memory, restrictions of memory, or previously we have seen IO, etc., will be taken in order to avoid this unauthorized access or damage of hardware. Okay, damage of hardware, mainly damage of hardware. Similarly, the next one is a software protection. Software protection. So for the software protection, obviously we will be using the firewalls to protect. Okay. Similarly, network protection. So protecting the network. So here also we'll be using firewalls, because so it will control the incoming and outgoing packets from the network. So firewalls, as well as some intrusion detections. So by the means of these things, we can protect the network, as well as the last but not the least, the application protection. Application protections. So that means protecting the different kinds of applications. Okay, so different kinds of applications. Similarly, here also we'll be using some antivirus, etc. Okay, protecting the applications. So these are the different types of protections given in the system protection. So once again, the system protection is a process of providing security to data, process, or resources used by the users. So here the word called security mean the access control. So who will be accessing the files? Okay, the privileges given for the users. So not every file should be shared among the different users. So there should be some privileges or some access permissions for the data as well as the resources. That's the most important. Domain of protection. So we know that a protection means providing the security. So for what we are providing the security means, so for resources and the data or files or a memory, right? So similarly, this domain of protection in operating system is defined as what resources are being used by users and what operations can be performed on resources. So these two things will be comes under this domain of protection. What are the resources accessed by the users, and what are the operations that can be performed on the resources? Simply we can say them as access rights or privileges. Okay, so for example, you can take one company. So there will be a lot of employees, so with the different designations. So every employee will be having their own privileges to use the resources. Okay, so similar kind here also, what resources can be used by the users as well as what kind of operations that can be performed. So here let us go with the basic terminologies in this domain of protection. So first one is a subject. What we are calling it as a subject. So a subject is either users or processes. So users will be using the resource, or process will also be using the resource during its execution. And the next one is an object. So object means the resources. What are the resources that are being used? So resources. So like files, okay, some memory, files, memory, or printers, etc. All are the resources that we are calling them as a object. Okay, object. And then access rights. So what is these access rights means? Operations performed. Operations performed. So what kind of operations that can be performed on files or memory or printers? So operations on files means read operation, write operation, or we can execute the memory segments. So execute operations, okay, and accessing the printer. All these comes under this access rights. Access rights. Now domain. Domain. So domain means it is a collection of objects with access rights. So it is a collection of resources and their access permissions is called as a domain. So these are the basic terminologies that will be used in domain of protection. Right. The next one is a domain switching. Domain switching. So this domain switching means the operating system will switch the domain, switch the process from one domain to another domain. So whenever it is required. So if a process requires more number of access permissions, so then automatically it will be shifted from one domain to another domain. So this is the operating system switches process from one domain to another domain. For example, let us take there are two modes of operations, user mode and a kernel mode, right? So two modes of operations, which is a kernel mode and a user mode. So we know that the user mode will be having a few limited permissions, okay, whereas kernel mode will be having a little bit more permissions to execute the process. So if one process is being executed in the user mode, if it requires more number of more access permissions, then automatically the mode will be shifted to the kernel mode. So that kind of thing we call it as a domain switching. So operating system switches a process whenever it is required from one domain to another domain, so in order to improve or increase the access permissions. So best example you can see a subject. Here the subject means let us take an example. It's a company, okay, it's a corporate company. So if it is a corporate company, you can say subject means whatever the employees, okay, managers will be there, HRs will be there, admins will be there. So there are different kinds of employees will be there, right? So all those are the subjects. And coming to the objects, so objects are nothing but resources, whatever the programs, applications, or resources, files, printers, all these comes under the resources that can be used by the employees of the organization. And coming to the access rights or a domain, so access rights is same, read operation. So not everyone can modify the data, not everyone can access the files, right? So not everyone can access the printer option. So there are the same access rights will be there for the employees in the organization. Coming to the domain, so if you say every employee will be giving one access ID, that means a personal, ID card, for example, let us take an ID card. So based upon their ID card, they'll use their access to some of the resources. So if one employee got a promotion, right? If one employee got a promotion, automatically the employee's access rights will be improved, right? So that kind we can say it as a domain switching. So just an example on all these things, right? So domain switching means whenever it is required, the operating system will be switches a process from one domain to another domain. Okay, yes. Now next, the implementation of this domain of protection. How this domain of protection can be implemented. See. So before we go into that, what is the purpose of using this domain? So need, what is the need of domain of protection? So one is to prevent unauthorized access. In our previous class also we have discussed about this one, to prevent unauthorized access. And one more thing is very important thing, that is utilization of resources in multi-user environment or multitasking environment. So efficient usage, efficient utilization of resources, whatever they are available, right? Efficient resources, okay, in multi-user. If it is a single user, there will be no problem. Multi-user or multitasking environment. So multiple tasks can be implemented in a single time. So multitasking environment. So this is the main reason for getting this domain of protection. One is prevent unauthorized access. So only the users, those who can access the data, they can access. Otherwise, the permissions will not be granted. And the next one, efficient utilization of resources. Now, the implementation. How this domain of protection will be implemented? Implementation. So this can be implemented by using access matrix. So what is this access matrix? So when we call it as a matrix, we know that will be represented with the rows and columns. Rows and columns. So what represents these rows and what represents these columns? So this rows represents the subject. Okay, so subject or domain. And columns represents objects objects or resources. Objects or resources, and whatever the cells which represents these columns and rows means access rights. So the cell, the corresponding row and column cell represents access permissions or access rights. So that means the permissions, what the resources can do, right? So it will be represented as, so for example, we can say it's a subject or domain, okay? So let it be some files, we are saying it as a files, sorry. So file or a memory or a printer. We are taking only three resources, for example. Let it be domain 1 and domain 2. Two domains are there, okay? Two domains are there. And you can also represent it as a process, okay? Process 1 and process 2, or user 1 and user 2. Okay, process 1 and process 2, or user 1 and user 2. So this can be either domain or subject, whatever it may be. I'll represent it as this is a subject and this is an object. This is an object, this is a subject. So for example, let us write here read, write, execute, access. For example, let us take this one, right? So this matrix, this is called as an access matrix. This is called as an access matrix. So that implies the name itself indicates it will use the complete access permissions for particular domains or processes. So in this example, you can see D1 or P1 or P. So D1, you can call it as a D1. So I'll write everything here. So in order to avoid the confusion, D1 or P1 or U1, D2 or P2 or U2. So D for domain, P for process, U for user. So we can use any term, right? So this implies the process P1 will be having only read operation on file 1 and also accessing to the printer. But P1 doesn't have any permission to execute the memory segment. Coming to the P2, process P2 having the access rights, read and write operations on file 1 as well as execute the memory segment, but P2 can't access the printer. Okay, so in this way, they will maintain some access matrix where it will having all the information about the domains. So what we are saying, it as a domain means it's a collection of resources, a collection of resources or a collection of objects with access rights. So this is also same thing, collection of resources and access rights. So this is a row, this is a column, and this is a cell. So we are saying rows as a subject or domain. So this is a subject or domain, and columns are objects or resources, and cell is a access permissions, either read permission, write permission, execute permission, or accessing the resources. So this disk structure mainly focus on how the data can be stored on the secondary storage and how can it be accessed. So it deals with how the data been stored and accessed from hard disk drive. HDD means hard disk drive. So we'll see one by one, right? The first one is a platter. So platter means, so the circular disk, okay, with magnetic tape or magnetic field are called platters. Okay, see. These are all platters. So number of platters can be there. So number of platters will be connected through spindle. So these platters were connected using this spindle, and more number of platters mean more storage capacity. So there will be a lot of platters will be there. So the number of platters increased, automatically the storage capacity will also be increased. That means much amount of data can be stored in the platters. So these are the platters. So in this example, so there are 3 platters. Okay, then all these 3 platters are connected with a spindle. Okay, spindle, and data is stored in the form of magnetic material or magnetic form. Okay, in the form of magnetic. So the data will be stored in these platters. Okay, more number of platters, automatically the more data can be stored. This is the first point. platters. And the second one, and each platter, the second term is a tracks. So each platter will be having circular forms called as tracks. Okay, again these platters, so there will be a circular forms. These are all tracks. So each one is a platter, and in that platter again there will be a concentric circles, and these are called as a tracks. So there are thousands of tracks in each platter. So in each platter there will be thousands of tracks, but here each platter is nothing but a disk, okay, circular disk. So each platter will be having thousands of concentric circles. And see, for simple explanation I am taking only 3 circuits, okay. And see, this is a spindle which connects all these platters, okay. This is a spindle, okay. Each disk is a platter. Inside the platter the circular disks are called as a tracks. Thousands of tracks will be there for each platter, right? So I am taking only three tracks, okay. So 1, 2 and 3, and all these tracks will be numbered from outer edge towards the center of a platter. So each track will be numbered from outer edge to center. So that means this will be the 1, this will be 2, this will be 3. So there are 3 tracks here, okay. Right, 3 tracks are there. Now each track will be numbered so that the numbering will be given from outer edge, that means outer track towards the center track. So that will be rotated. Okay, this is all about tracks. So every platter will be having a different number of tracks. So the data can be stored in these tracks also. And the third component of disk structure. So I'm explaining one by one and I'm drawing the diagram. And the next one is sectors. So each track is divided into small units called sectors. So again, see, each track is divided into, each track is divided into different small units, okay, small units called sectors. Okay, so this portion, see, this portion is called sector. Okay, now let us take this portion is called a sector. So each track is again divided into a sector. Then, so the data can be stored in the sectors. So data will be stored, or data is read or write into these sectors one at a time. So at a time only one operation will be done here. Okay, so this spindle will be keep on rotating in a fast, okay, in a very fast. It spins the complete cylinders because all the cylinders are connected with the spindle. Okay, and see each okay, this is all about sectors. And the next key component of this disk structure is read-write head. So what we are saying, the data will be stored in the sectors. Okay, data will be stored in the sectors, and the sectors are a part of each track. Okay, track is a part of a platter. Okay, and read-write head. So this read-write head, it will be pointing towards sectors to perform read-write operation. In order to read-write operation, that means we know that hard disk maintains some data, will store some data in the hard disk. So in order to access the data, or in order to store the data into the hard disk, this particular read-write head will be used. So every platter will have their own read-write head, and also, see, I'll show you. See, this is a normal arm. See, these are the read-write heads. Read-write head. So which will be pointing towards the data on sectors. So every platter will be having their own read-write head. So this read-write head will be moving forward and backward to perform read-write operations. So in order to perform these read and write operations, these particular heads, okay, read-write heads will be keep on moving forward and backward. So so the read-write head can be moved towards the center of the platter, and it moves outer track of the platter, right? So if the data which we want to access is at the outer track, okay, it is in the sector which is available in the outer track, then it will be get in a very fast time. Okay, the accessing time is very fast. And if the data is available in the sector which is close to the center of the platter, then it may take some time, because the head should move towards the center and it have to access it. So read-write head will be moving forward and backward to perform read-write operations. Okay, these are the heads. So there will be two heads. Okay, two heads. So one is on top of platter. One is on top of platter. The second one is on another on bottom of platter. Bottom of platter. Because so in the platter, I mean, the data can be stored on both the sides. That means top of the platter as well as the bottom of the platter. So that data will be stored on both sides. So there will be two heads. One is on top of the platter, another pointing at the bottom of the platter. So whenever you want to access the data, immediately the data, it will find the data and it will retrieve the data. So this is all about read-write head. Next, the next one is a clusters. Clusters. Say group of sectors are known as clusters. So grouping, for example, you group all these things. If you group all these things, this becomes one cluster. Okay, so grouping means combining these three sectors forms one cluster. So why to form these clusters means, so clusters are used to store files in a file system. So if we want to store the file, so that file can be stored in a multiple clusters. I mean multiple sectors. By grouping them, we call them as a clusters. So these are the clusters. And the next one, cylinder. Cylinders. Now grouping up of tracks. So grouping of tracks radially of all platters is known as a cylinder. Is known as cylinder. For example, let us take, so if you consider this one, see this one, and coming to here, this one, and coming to here, this one. So the grouping of tracks, what are the tracks? The circular forms on a platter, we call it as a tracks. So grouping of tracks, okay, grouping of tracks of all platters is known as a cylinder, right? So this is the disk structure. Once again, I will repeat. First, there will be a platters. Platters are the disk. These are disks which are having both sides, top and bottom. So these disks, I mean, the data will be stored in these disks, and these platters will be stacked with the help of one spindle. This is called a spindle. This is called a spindle. Okay, spindle which will be rotated. Okay, this spindle will be keeps on rotating. Okay, in a very fast way, very fast way. So this particular platters will be stacked through this spindle and it will be rotated. Okay, and these platters will be again divided into tracks that are represented in a circular forms. So every platter will be having a circular form, which we are calling it as a tracks. And the tracks are further divided into sectors. So you can see these are sectors. This is one sector, this is another, this is another, this is another, and this is another. So every tracks will be divided into sectors. So each platter will be having thousands of tracks, and each track is further divided into sectors. So now the data will be stored in these sectors. So in order to store a file, a group of sectors will be called as a clusters, and in that cluster the file will be loaded, right? And there will be a read-write head pointing towards the sectors on both the sides of platters, top and bottom. So in order to access the data from the sector, this particular read-write head will be used. If you want to write the data onto the hard disk, or if you want to read the data from the hard disk, so these read-write heads will be useful. Okay, so this read-write head will be moving forward and backward in order to get the position of the data. So this particular read-write head will be moved from outer track to excuse me, center track. If the required data is available at the outer track, then automatically the data can be accessed in a speed. Okay, very fast it will be accessed. And if the data which we want to retrieve it is near to the center track, then it may take some time to retrieve the data, because the read-write head have to move forward towards the required data. Okay, so hope you understood. This is a disk structure, how the data can be read from the hard disk and how the data can be written into the hard disk. Scheduling. Introduction to disk scheduling algorithms. So the first thing, we need to know some key terms. Okay, so before that, this disk scheduling means it is a method used by OS, operating system, to know what IO request. So here the IO request means either read operation or write operation. What IO request should be processed. Should be processed, right? So here there will be a number of IO requests. Okay, so the computer system can have multiple IO requests. Multiple IO requests. So all these requests will be maintained in a request queue. Okay, so there will be maintained a request queue. So how these requests will be processed? That means either writing or reading, right? So from this request queue, the data or the request will be processed and it will complete its operation, right? So here how this will be happens. So if all the requests will be processed in a random manner, okay, then there might be a chance of having the starvation problem. So starvation problem is one problem that may occur in during this one. So similar to our process scheduling algorithms. So in our previous sessions, we have seen the process scheduling. So if you are talking about multi-processing system, multi-processing environment, so multiple processors can be executed at a time, but the CPU will be executing one process at a time. So how these processes will be get executed, how the CPU will be given to each and every process. So in that session also we have seen about the starvation problem. So one problem in this algorithm, I mean this disk scheduling, is starvation. So starvation means the request with lower priority. So the request with low priority may not be processed. May not be processed. So if some requests are not being processed for a long period of time, that we call it as a starvation. So we should be very careful that all the requests should be processed. Okay. So efficient disk scheduling algorithm will give no starvation. Okay. So first let us see the terms which are being used in this disk scheduling, and then we'll see what are the different disk scheduling algorithms. We'll list out the different disk scheduling algorithms. So the first thing, very important thing for this disk scheduling algorithms is seek time. Seek time. Seek time means we know that the read-write head will be moving forward and backward. Okay, so in order to access the data on the sectors, because sectors will be having the data, right? So the time taken to move read-write head towards a desired sectors or cylinders. So cylinders means a group of tracks. Okay, group of tracks on every platter is called as a cylinder. So time taken to move this read-write head towards the desired sectors is a seek time. And the next key term is rotational latency. So what is meant by this rotational latency? So as I said that all the disk, okay, all the disk, so here platters we are calling it as a disk. So all the disks will be connected to a spindle, and this spindle will be keep on rotating, right? So This rotational latency means time taken by the disk. Here the disk means the platters, okay, by the disk to rotate until the desired sector, that means a required sector, comes under the head. Head means read write head. Okay, so previously seek time means time taken to move the read write head forward or backward, and rotational latency means rotation. Okay, how many rotation, the time taken to rotate the disk. Okay, and the third one, access time. So access time means the time taken to complete the operation. So to complete the read write operation. So only the two things can be done, either read operation or write operation. And the last one is a starvation. So starvation means so not processing the IO request much more time. Okay, it will we keep on waiting for its execution. So that is a starvation. So what are the main goals? Main goals for disk scheduling is seek time, reduced seek time. Okay, reduced latency. So it must take minimum time. Okay, throughput should be very high. Throughput means the number of IO requests that are being processed at a particular time period. Okay, so more number of requests should be completed, right? So that is a throughput. And no starvation. This is the most important. So if any one of the algorithms satisfies all these things, that means low seek time, low latency, rotational latency, more throughput, as well as no starvation, such algorithm is called as a efficient algorithm. So there are many algorithms how we can process the IO request. Okay, so the algorithm which follows all these things, that is an efficient disk scheduling algorithm. So efficient usage of read write operations. So within a less amount of time, so the accessing should be there. Okay, optimized accessing of data. Now we'll list out what are the different disk scheduling algorithms, and one by one we'll see in our next session. I'll explain you about one by one in our next session. So I list out all the disk scheduling algorithms. So this disk scheduling algorithms mainly divided into 6 categories. Disk scheduling. So first one is FCFS. FCFS means first come first serve. Okay, so whatever the request comes first, that will be executed first. Next, SSTF, shortest seek time first. Shortest seek time first. I'll write the abbreviation. Shortest seek time first, and this is first come first serve. And the next one is scan, which is also called as an elevator algorithm. Scan, and C scan, which is a circular scan. Look, and C look, which is a circular look. So these are the different disk scheduling algorithms. Okay, so whatever the algorithms we have seen earlier, those are process scheduling algorithms. Okay, so these are the disk scheduling algorithms, and these algorithms are mainly used to process the IO request. So process IO request. IO request means both read and write operations, reading the data from the hard disk and writing the data into the hard disk. And it also gives fast accessing of data. So if it is a read operation, how fast the data can be accessed from the file. Okay, so these are all the disk scheduling algorithms. We'll see one by one how these disk scheduling algorithms works from our next session. So in our next session, we'll see these two algorithms, FCFS and SSTF. Okay, first come first serve and shortest seek time first. So disk scheduling algorithms. So the first one is of FCFS. So which is called first come first serve. Okay, so here the name itself indicates, so whatever the order the request gets, in the same order the request will be processed. So the request will be processed in the same order they requested. Okay, so there will be one request queue, so where all IO requests will be stored in that particular queue. So initially the head position will be pointing towards a one position, and from that position, based upon the request, based upon the orders they requested, so in the same order the processes or the request will be processed. Okay, so here one advantage of using this FCFS is easy to implement, easy to implement, easy to implement. And second one is there will be no starvation. So no starvation, because in the same order the request will be processed, there will be no process will be remains or waits for completing its process, I mean completing its execution, right? So there will be no chance of a starvation. Okay, but only one disadvantage is, so seek time, high seek time. That means moving the head position from one position to another position based upon the request, so that will be more. Okay, the position will be more, the head will be moving faster, as well as that may be more, the seek time will be more. Okay, so let us see an example. So we will consider the number of tracks as well as the head position and the requests and how it will be processed in first come first serve. See, let us take this example, and here the first one, disk tracks are 0 to 199, so totally 200 tracks for example, and current head position is at 100. The current head position is at 100, and see the request queue is 55, so that means the read write head should be pointing towards 55, then 58, then 39, then 18. So in the same way the data should be accessed from the disk, right? So these are the track numbers, let it be the track numbers, and this is a position. Now let us take first initial position is 100. So here I have taken a graph. Okay, so x-axis all the requests. So how many requests? 1 2 3 4 5 6 7 8 9, and initial position 100. So let us take this as a request 1, request 2, request 3, request 4, request 5 6 7 8 9 10. 10 requests are there. So I have taken all the 10 requests in the x-axis, and y-axis are the track numbers. So what is the first come first serve? The name itself indicates which request appears first, that will be get processed, right? So initially the position is at 100. So here it is. Okay, then the second request is 55. This is the order. Okay, this is the order of request. So 55, immediately the head moves towards 55 for request to 2. So what is the request to 2? 55, which is in between 40 and 60. I'll take here. So it is not I mean it is not perfect, but it's an approximate, right? Next to 58, request 3 is at 58, a little bit more, this one. And request 4 39, again it drops down. Request 4, it's at 39. Next 18, still down, close to 20. Next 90, moves up, it moves up to here. Request 6 and close to 90, which is 90, right? Next 160, request 7 moves to 160. So here it moves this way. And then 150, request 8 is with 150. Then 38, again it drops to 38. So it comes here. And 184, again it moves R10, request 10 moves to 184. So it moves till here. So if you join this one, see the request head moves in this way. So this is a graph, how the requests are being completed, okay, processed. So first initial position is at 100, and the next request is at 55, right? So here you can see the first request is at 100, immediately the next request is at 55, so the head should move from 100 to 55. So 100 to 55. So what is the seek time? So which is how much? It's around 45. Now the head position is at 55, right? Now the head position is 55, immediately it moves to 58. So what is the seek time? 55 minus 58 or 58 minus 58. So forget about the negative. Okay, so 55 minus 58, the difference is 3. The head should be moved towards the 3 positions. Okay, so backward. Okay, you need not represent it as a negative or a positive. So the backward 3 positions it should be shifted. Now the head position is at 58, then immediately it moves to 39. So which is a 19. Okay, 19 position should be moved. Now the head position is at 39. Next it moves to 18. What is the thing? 21. Result is 21. Now the head position is at 18 and it moves to 90. So 72 almost. Yes, 72. Now the head position is at 90. Then it moves to 160. So which is 70. Okay, and 160 it moves to 150. So 10 backward. Now 150 to 38, which is almost 112, 112, and 38 to 184. So which is 146. 146. So this is the seek time. Okay, this is the seek time. That means moving the head from one position towards the another position. So, so you can find out the seek time, which is the addition of all these things. So 45 plus 3 plus 19 plus 21 plus 72 plus 70 plus 10 plus 112 plus 146. So it will be 8, 10, 11, 20, 23 and 28, which is 8, 6, so 2 plus 4, 6, 7, 8, 15, 22, 24, 25, 29 and 2 plus 1, 3, 4. So 498 is the seek time. So which is very high. So in order to process the 10 requests, the seek time is 498. So because initially the position of the head is at 100, immediately the next request is 55. So there is no starvation. So whatever the request comes first, that will be get processed. Okay, there is no priority, there is no reordering. Okay, that's most important. No reordering. So it doesn't change the order, right? So whatever the order it gets the request, those requests will be processed. Okay, it doesn't follow any reordering. Okay, no priority also. So that is the main thing. That's one advantage as well as one disadvantage. So here the advantage is, so there will be no process or there will be no request waiting for its execution. Okay, here the execution means accessing the moving the read-write head to the particular track. So no request will be waiting for the read-write head, right? So because whatever the order it is receiving, so in the same order the request will be processed. So what is the drawback? So these many moves, that means the seek time will be more. The seek time will be more. You can observe here. So if the last request, if you can consider the last but one request, the position of the read-write head is at 38. It should move towards 184th track. So it have to move around 146 tracks. Okay, so which gives more time. So time taking is more, but it's a very easy to implement, no starvation. So this is all about the first one, that is the first come, first serve disk scheduling algorithm. The shortest seek time first. So in our previous session, we have seen the introduction to disk scheduling algorithms, and in that we have seen what are the key terms we have to concentrate, and then we have seen one disk scheduling algorithm, that is FCFS, which is a first come first serve. So where we have seen the advantage, there is no starvation, and also there is a disadvantage, so more seek time to move the head from one request to another request. So in order to avoid the disadvantage, so we are moving towards the second one, that is the shortest seek time first. So here we are taking the same example. So disk tracks with 0 to 199, so totally 200 tracks, and the current head position is at 100, and the request queue is also same, 55, 58, 39, 18, 90, 160, 150, 38 and 184. But here, so whatever the order the request is being processed, so we are not following that order, so reordering will be done here. So based upon the current head position, the nearest request will be processed first. So nearest request to current head position will be processed first. And also, okay, so less seek time. Okay, less seek time. And there is a one drawback here in this process. There might be a chance of getting the starvation. Okay, so might have a starvation problem. So that means reordering will be done. So the same order, the request will not be processed. Okay, now let us see the same thing. Graph, we are representing it in a graph. So x-axis we are taking the request, so total 10 requests, including the current head position. So we are considering that as a first request. Okay, and the y-axis, that's the track numbers. So let us see how it can be implemented. So first the current position is at 100, so R1 is at 100. Now instead of getting 55, because 55 is the first request. Okay, so the head position will not be moved towards the 55. So first it will check, so the request which is close to the 100. Okay, it doesn't follow the order, but it will follow the nearest track to the current head position. So now it is at 100. What is the request which is near to 100? So it is 90. So the second request will be 90. And now the third request will be closer to 90. Which one is a closer to 90? So I think it's 90 minus 160 or 90 minus 150, it is around 60, and 90 minus 58, it is around 32. So 58 will be processed first. Okay, so hope you understood. The nearest track to the current head position, is at 90. So which is the nearest track? So here it is a 150, so the difference is 60 positions. And if you consider the second request 58, the difference is around 32. So this will be the nearest to 90. So the next will be 58. So R3, the request 3, the head position will be moving towards the 98. and 58. Now the nearest position to 58. What is the nearest position to 58? So nearest position to 58 is 55. So request 4 is at 55. 55. Now what is the nearest position to 55? So 55, it will be 39 itself, right? So next one is a 39. Request 5 is a 39. So next 38. Obviously the next request will be 38 itself. 38. So next request, that means which is close to 38. So which one is the closest to 38? 38 is at 18, right? So it moves to 18. Now from 18, what is the next request? Obviously 150. Okay, only 3 requests are there, 160, 150 and 184. The nearest request is at 150. So the R80 will be at 150. Right? Next one, 160. Next one is 184. Now you can so this is a graph how the requests are being processed. So only one thing. So here in this case, from the current head position, the next request will be processed which is closer to the current head position. Okay. So here we can observe the seek time. The first one is at 100. So the next closer to 100 is at 90. So the difference is 10. And now the position is at 90. The next request is at here it is, yes, 100, 90, and request 3. Just wait, 100 and it's 90, and from 90 it's around 55 itself. Okay, so 55, so which is around 58. 58. Yes, I think here we have to write down. Okay, this one, not this one. This is a 58. Okay, yes. Imagine. Okay, 58. That is a 32. The difference is 32. And from 58, what is the nearest position? Which is a 55. So which is around only 3 difference. From 55, the next one is 39. So which is around 16. And from 39, 38, which is only 1. And from 38, it is 18, which is a 20. And from 18, 1, 2, 3, 4, 5, 6. 18, it moves to 150. So which is around 132. From 150, it moves to 160, which is only 10. From 160, it moves to 184, which is 24. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes. So this is the seek time. This is the seek time. Now you can see what is the seek time is equal to 10 plus 32 plus 3 plus 16 plus 1 plus 20 plus 132 plus 10 plus 24. So which is around 4 plus 2, 6, 6 plus 1, 7, 7 plus 6, 13, 13 plus 3, 16, 18. So 8, 1 plus 2, 3, 4, 7, 9, 10, 13, 14, 4, 1. 1 plus 1, it's 2. So it is around 248. So if you process the same kind of request in FCFS, in our previous session, you can see the seek time is almost more than 400. But here you can see it is only 248. So automatically the seek time has been reduced. So the movement of read-write head is already reduced. Okay, so don't forget, I mean, don't bother about the graph. So you can observe the movement of read-write heads. Okay, the movement of read-write heads will be less when compared to the first come first. Okay, and see here one problem is a starvation. We are saying the I mean this process may have the starvation problem. For example, if you are processing the request at 90, and if the request, a new request comes with some 85, so obviously the next request process will be the 85. Similarly, if you are processing the request 85, the new request comes with the 80, again it moves to the 80. And if the next process we got which is near to 80, that is 60, then it moves to 60. So what about this 184? When it will be executed? When it will be processed? So in such cases we may have this starvation problem. So if during processing these requests, if the new request comes with which is closer to the current head position, those requests will be get processed, and this request will be keep on waiting for processing. So this is a problem in this shortest seek time first. But so where we are just following the nearest head position to process the request, the seek time will be very less when compared to the first come first serve approach. Okay, so that's why we are saying reordering is done here. Reordering. So this is the not order we are following. So it will be reordered based upon the shortest distance or nearer to the current head positions. Okay. So here the positions we will see first 100 will be processing. The next position will be at 90. The next position will be at 58. And next position will be at 55. Next position will be at 39. Next position will be at 38. Next position will be at 18. Next position will be at 150. Next position it will be at 160, and next to last it is 84. If there is no request occurs during the processing these requests, if any request occurs in between this one, automatically this order will be changing. Okay, so that may lead to the starvation. So 100, 90, 58, 55, 39, 38, and 18, 150, 160, and 184. See, one more disk scheduling algorithm is a scan scheduling algorithm, which is also known as elevator algorithm. So here the read-write head will be keep on moving on one side, and once it reaches to the highest number of track, then again it will just travel to the backward, right, and it will process the request. So it will move in only one direction, so until it reaches to the highest track number. So we know that. So in the disk, okay, there will be a concentric circles which we call it as a tracks, and the track numbers will be starting from inner to the outer. Okay, so that means a center circle towards the outer circle. So the last track is nothing but the last one, outer track, right? So here read-write head moves in one direction, only one direction. Okay, and read-write head move backward once it reaches to the maximum track number. So in this example we are taking some 0 to 199. So 199 is the last track. So whenever the read-write head moves towards this 199, then only the read-write head will be it starts from backward to the forward, right? Then read-write head processes the request during its path towards inner track, or simply we can say towards least track number. Okay, so once the read-write head reaches to 199, it will start moving backward. So during the backward, again it will start processing the request during its path. Okay, now let us take this example. So first current head position is at 100. So I'll start with the 100 itself. So what it means? So it will start in a forward direction until it reaches to the maximum point. So here after 100, what is the next possible request? So 150. So just request 2 will be 150. Request 2 will be 150, and then 160. So it doesn't start with the 55. Okay, now the read-write head is at 100, so it will only move forward, right? So 100, 100 to 150, 150 to 160. So the third request is at 160. Okay, 160. Then 184 forward. So request 4 will be 184. Okay, then it will reach us to 199. So it will reach us to 199. So once it reaches to the maximum number, so that is the last track. Okay, so for example, you can consider this is a cylinder. This is a platter. So inside this platter there will be a concentric circles. Okay, so we are saying all these concentric circles are tracks. So the number of this track will be 0, and the number of this track will be 199, for example, in this case. So read-write head, whenever it touches the last track, so again it will start towards this forward direction. So what is the next possible thing among this one? So 90, which is nearer. Okay, so the next request R5 is at 90. Okay, then after 90, 58. So R6 is at 58. Next 55, R7 will be again 55, example. Okay, and then it moves towards 39. R8 is at 39. So here it is 39. The next request is at 38 itself. It's like 38, and finally it's at 18. R10 is at 18. So now you can see it start here. So it moves forward. Whenever it touches, it go backward. This one. So this is how the requests will be processed in scan algorithm. So only it will start in a forward direction. So now in this case, the current head position is at 100. So the next possible request to be processed is obviously 150. So if the current head position is at 50, then the next position, I mean the next request which is being processed is 55, then 58, then 90, then 150, then 160, 184, then it reaches 199, and again it comes back to 0. Okay, once it hits the largest number, it comes back to 0. So during coming back, it will process the request of the remaining thing. Okay, so hope you understood this one. And now we will write whatever the request being processed. First 100, from 100 the next request processed is 150. Okay, so the difference is a 50, the seek time. Okay, next 150, from 150 the next one is a 160, which is a 10, and from 160 the next one is 184, so which is a 24. Okay, so 100 to 150, 150 to 160, 160 to 184, and then 184 to 199, so the next one is a 199. Okay, it moves towards a 199, then 199 to, what's the next possibility? It's a 90, which is a 109. From 90 it moves to, 58, so which is 32. From 58 the next position is, I mean the next request is a 55, which is a 3 seek time, and from 55 the next sequence is at 39, so which is around 16. From 39 the next one is a 38, which is a 1. From 38 the next one is a 18, 38, and the next one is a 18, which is a 20. Okay, now the seek time. What is the seek time? The time taken to move the read-write head, okay, to the desired location or desired track. So seek time can be the addition of all these things. Okay, so we can write it as 50 plus 10 plus 24 plus 109 plus 32 plus 3 plus 16 plus 1 plus 20. So which becomes 0, 1, 7, 10, 12, 21, 25. So it will be 5, 2, 2 plus 2, 4, 5, 8, 10, 11, 16. 6, 1, 1 plus 1, it is 2. So you can see the seek time is also less when compared to the FCFS. When compared to the first come first serve, this is less. Okay, and here also there is no starvation. So reordering is there. So here also we are just following the reordering, and low seek time compared to FCFS. Okay, FCFS. So and no starvation. Starvation is very less possibility of having the starvation. Okay, so hope you understood this scan algorithm, which is also called as elevator algorithm. So because we are, I mean the read-write head has been moving forward and backward based upon the request. So one thing just remember, it moves in a single direction. Whenever it reaches to the maximum track, it will again start backward towards the 0th track. So during its traversal, it will process all the requests in that particular path. So in today's session, we'll say one more algorithm, that is a C-scan. So the working of C-scan is similar to the scan with a little bit different. So here, the first point is similar to our scan algorithm. Here also the read-write head will be keep on moving in a single direction. Okay, so read-write head will be moving on single direction. Okay, that is a forward. Usually it is a forward direction. Okay, usually towards a forward direction. So whenever it reaches the maximum track number, then it will again come back to the 0 directly. Okay, it will come back to the lower track number directly, and again it will start processing the request in a single direction itself. So during the backward, it doesn't process any request. So that is the difference among C-scan and a scan one. Okay, scan algorithm. So the read-write head, once reached to maximum track number, then it directly move towards lowest track number, particularly it is 0. Okay, and during move towards track 0, it doesn't process the request, any request. Okay, so for example, let us take, these are the different tracks. So whenever the read-write head reaches to 199 in this example, okay, maximum, immediately it will directly move towards the 0. Okay, during this particular direction, so that means a backward direction. So whenever the read-write head moves from track 199 to track 0, it doesn't process any kind of request. Okay, only once it reaches to 0, then only it will again start moving forward by processing all the requests. So let us see an example. So the first request here it is 100. So initially the position is at 100. Then what is the next one? So it will move only towards the forward direction. So 100 means only it will process the requests which are above 100 until it reaches to 199. So the next request processed is 150. So the next request processed is 150. Okay, and the next request process is 160. Only forward. Okay, 160. And the next request processed is 184, R4, 184. It processed at 184. Now, whenever it reaches to 199, so whenever it reaches to 199, again immediately it moves from 0. Okay, it will just start with 0. From 0, again it will start processing the request. So now it is at 0. So I'll write here. Okay, so I'll write here so that you can understand. See, it starts with 100. The next request processed is 150. The next request it is processed is 160. Next request it processes 184. And next it just moves with the 199. So 199 is not a request, but it reaches the maximum one. So immediately what happens means it will directly comes towards 0. 0 is not any request. So directly it comes to 0. The read write head directly moves towards 0. So during this movement, it doesn't process any request. From here, it will start processing the request. From 0, what is the next one? 18. Okay, so here the next request R5 is at 18. 18. From 18, it moves to 38. 18, it moves to 38. From 38, it moves to 39. So which is almost equal. And from 39, it moves to 58. 58. So which is almost here. From 58, it moves to 55. 55. So this is not around here. And the next one is 58. So the next one is a 58, which is slight upward, and then it is a 90. Then R10 is at 90. This one. So it will start towards forward direction. Whenever it reaches, again directly it moves to 0, and again it processes the request. Okay. So in scan algorithm, what happens? Whenever it reaches to maximum track number, it will start processing the requests which are backwards. I mean, while returning to 0, whatever the requests are there, all those requests will be processed. But here, directly the read write head will be moving from the higher maximum track to the minimum track without processing any request. So that's why we call it as a C-scan algorithm. C-scan means a circular scan algorithm. So which is called as a circular scan algorithm. Right? So this is the process. 100 to 150, 150 to 160, 160 to 184, 184 to 199, which is the maximum track. Immediately the read write head comes to the initial tracks. That means a 0. So from 0 again it starts processing the request. Okay, so that is the only difference between the scan and C-scan algorithm. So now we can calculate the seek time. See, 100. What is the next one? 100 to 150. So which is a 50, and 150 to 160, which is 10. 160 to the next one is 184, which is a 24, and 184 to 199, and again 199 to 0, directly 0. So 184 to 199, 199 to 0, then 0 to what's the next one? 18. So you can directly go with the 18, and from 18 to 38, so which is a 20, and 38 to 39, which is 1, 39 to 55, which is around 16, 55 to 58, so which is 3, and 58 to 90, which is around 32. Okay, it stops here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes. So here you can see what is the seek time. Seek time 50 plus 10 plus 24 plus 18 plus 20 plus 1 plus 16 plus 3 plus 32. So sometimes you can also calculate this particular thing, which is around 15 and which is around again 199. So you can I'm skipping this one. So directly I'm calculating only the movements from one request to another request. So 2 plus 3 5, 5 plus 6 11, 12, 20, 24. So which is 4, 2, 2 plus 3 5, 6, 8, 9, 10, 11, 12, and 2, 5, 11, 12, 20, 24, 4, 2, 2 plus 3, 5, 6, 8, 9, 10, 12, and 17. So it is a 174. So if you add these also, then automatically the seek time will be more. So here also there will be reordering. Reordering will be there, and seek time. So low seek time compared to FCFS compared to FCFS, and also there might be very low chance of having the starvation. So starvation possibility is also very low. So this is a C-scan algorithm, which is a circular scan algorithm. Today's session we'll see one more concept in disk scheduling algorithms, that is look disk scheduling algorithm. So in our previous session we have seen what are the key concepts of scheduling algorithms, particularly disk scheduling algorithms, and in that we have covered a few disk scheduling algorithms like scan FCFS, SSTF, and scan and C-scan. So in today's session we'll see the one more thing, that is a look disk scheduling algorithm. So the working of this look disk scheduling algorithm is similar to the scan scheduling algorithm with a little bit of difference. So here also, so similar to the first point is, it is similar to scan algorithm, but there is a simple difference. So the processing of requests will start from the head position and it will keep on moving in one direction, okay, processing all the requests. For example, here the head position is 100, so it will process the request from 100 towards 199, okay. So whenever it processes the last request in the same direction, it stops and automatically it will reverse, and again it will process all the requests until it goes to the lowest request in that direction. So previously in scan algorithm, so whenever it processes the last request, immediately it will move on with the end of the track, okay. For example, here end of the track is 199, so whenever it executes or it processes 184 requests, automatically the read write head will be moving towards 199 and then it will be reversing. But here, after processing this 184, directly the read write head will be reversed without reaching to the last track of a platter. Hope you understood, right? So that is a small difference among scan and look. So starts at current head position. The first step is it starts at current head position and processes the request in one direction. So usually it will be forward direction, okay, one direction. And whenever the last request in that direction is processed, what happens? Then it reverses the direction and start processing in the reverse direction until it reaches lowest request, okay, lowest request, until it reaches to the lowest request. For example, here you can see the current head position is at 100, excuse me. So current head position is 100, so let us start from here, and what happens? It moves towards one direction, so next immediate request will be 150 and then 160. This is 150, this is 160, this is 160, and then 184, so it moves here, 184, and then it doesn't move to the 199. So because 184 is the last request in the forward direction, immediately it will return back and it will start processing from the reverse order, right? So immediately after returning, what's the next one? Which is a 90. So the request 5 will be executed, processed with a 90, okay, track 90, and after 90 it moves to 58, so it moves to 58, then it's a 55, then it's a 55, and then it's 39, and then 38 is also similar, 38, and finally 18. So it will start from here, it process and it reverse. See, so what happens? This is a look disk scheduling algorithm, whereas in scan scheduling algorithm, what we have seen, whenever it reaches to 188, that means the last request, automatically it will reach till the end of the platter, the last track of the platter. So the last track here is 199, so it will be moving from 184 to 199, and then the process will be reversed. I mean the processing of request will be reversed, okay. So here I'll show you. First it will start with 100, after that it will process towards 150, afterwards 160, after 184, and immediately it will return back, so it will be 90 and 58 and then 55, and then 39, then 38, then 18. So this is the way the request will be processed. Okay, and see here the advantage of using this one is, so it will avoid unnecessary movement of read write head. So why we are saying unnecessary movement of read write head means it doesn't move towards the last track. Okay, so immediately it will be reversed, and automatically low seek time when compared to scan, when compared to the scan algorithm, so very low seek time. So we can also calculate the seek time. We can calculate the seek time here. Hope you understood how to calculate the seek time, right? So seek time. So first 100 to 150, the difference will be 50. 150 to 160, difference will be 10. 160 to 184, the difference will be 24. 184 to 90, which is 94. 90 to 58, so which is 32. 58 to 55, so which is a 3. 55 to 39, so which is 16. 39 to 38, which is 1. 38 to 18, which is 20. So these are the read write head movements, okay, on between the tracks. And if you add all these things, we will be getting the seek time. So I'm not adding, so you can check it out. But when compared to the scan, automatically we'll get the less seek time because there is an unnecessary movement is avoided. So immediately after reaching towards the last request, it will be reversed. Last request, okay, not the last track. So scan means it goes towards the last track, but here it moves towards the last request. Then immediately it will be returned. Right. In today's session, we'll see one more disk scheduling algorithm, that is a C-look disk scheduling algorithm. So in our previous session, we have seen many disk scheduling algorithms like FCFS, SSTF, scan, C-scan, and look scheduling. And now we'll see the C-lookup, C-look disk scheduling. So here the C-look scheduling means circular look scheduling algorithm. Circular look scheduling algorithm. So this works similar to the C-scan. So works similar to C-scan, which is a circular scan. So here also it will start from the current head position. It will be moving towards one direction, processing all the requests. Whenever it reaches to the last request, not the last track, whenever it reaches to the last request in that direction, immediately it will be moving towards the lowest request in another direction. Okay, so previously look, automatically whenever it reaches to the last request, it will start reversing and it will process all the requests during the reversing to the lowest track or lowest request. But here directly whenever it reaches to the highest request or highest track, okay, the highest track, immediately it will again start from the lowest track, processing all the requests towards that one direction. So that means it will also process the request in one direction first. So initially it starts with current head position. Okay, it will start from the current head position and it processes the request in one direction. So usually it will be in the forward direction. Okay, so whenever it processes the last request, then it moves back and starts processing from lowest request. So during the reversal process, it doesn't process any request. Okay, so once it reaches to the maximum track, immediately it will start from the lowest track again. So the read write head comes to the lowest track immediately. So during this movement, it doesn't process any request. So to the lowest track. So here let me explain you this one. So current head position is 100. So from 100 it moves towards a single direction, that is a forward, usually a forward process. So 160. So from 160 it moves towards, sorry, it is 150. 150 it moves towards a 160 and it moves towards 160 to 184. And immediately after going to 184, what happens? Directly it will go to the lowest request. Okay, so in look disk scheduling, it immediately start processing the request in the reverse direction, but it doesn't process the request in the reverse direction. Again, it will start from the lowest request. What is the lowest request here? 18. So immediately it will move towards 18. After 18, again it moves to the forward direction. After 18, it will be 38. After 38, it will be 39. After 39, it will be 55. And after 55, it will be 58. After 58, it will be 90. So this is the process how the request will be processed in C-look disk scheduling algorithm, which is a circular look disk scheduling algorithm. Okay, so let us draw this one. So it will start from 100. So the first position will be 100, and then immediately 150. The request 2 will be 150. So it will start with 150, and then 160. Immediately the third request will be 160. So it was moving in one direction, right? So request 3, and then 184. R4 will be 184. So here it will be 184. Immediately after coming to the 184, it doesn't reverse the process, but it will come from the lowest. It will start from the lowest. So then immediately it comes with the 18. So R5 will be 18 itself. So directly the read-write head will be from this position 18, and then 38, and then 39, then 55, 58, and 90. So 90 means it goes to here 90. So how it starts? So it will be starting in one direction, and immediately it will start from the lowest request. So this is how the request will be processed. Okay, coming to the C scan, what happens? See, in the C scan, after reaching to the last request, it will move towards the last track. Okay, so that means after 184, the read-write head will be moved to 199, and after 199, it will come back to 0, and again it will start processing the request. But here also the unnecessary movement of read-write head will be avoided. So whenever the read-write head reaches to 184, immediately it will come back to the lowest request. Okay, lowest request, which is a 18. Right. So this is how the disk scheduling algorithm works. That means circular loop disk scheduling algorithm. So here also you can find the seek time. So what is the seek time here? So obviously the seek time will be somewhat more than loop scheduling algorithm, and automatically that will be efficient than FCFS algorithm. So seek time, I'll write so that you can calculate and you can check or compare. Seek time. So first position is 100 to 2. The read-write head moves with 150. So the difference is a 50, and that means here 50 means the read-write head moves 50 tracks. Okay. So the next one 150 to 160. So it moves 10 tracks, and 160 to 184. That means it moves around 24 tracks, and 184 to almost 18. So that means 166. It moves 166 tracks back. Okay. Then 18 to how much? 18 to 38. So 20 tracks. 38 to 39. So one track. 39 to 55. 16 tracks. 55 to 58. 3 tracks. 58 to 90. 32 tracks. So if you add all these things, we'll be getting the seek time, and you can compare. So seek time will be less when compared to FCFS. Okay, and the advantage is reducing the read-write head movement, unnecessary of read-write head movement. So similar to look disk scheduling algorithm. Okay, so here among all these things, what we have seen: FCFS, STTF, seek time, shortest to seek time, SSTF, scan, C scan, look, C look. So all these are the disk scheduling algorithms. So among that, so which one is having less seek time and no starvation? So starvation means the request will be keep on waiting to complete its process. Okay, so less seek time and no starvation will be the efficient algorithm, efficient disk scheduling algorithm, efficient disk scheduling algorithm. So less seek time, it should be having the less seek time, and as well as there should be no starvation, right? So if anything is here in this way, automatically that we are calling it as a efficient disk scheduling algorithms. Management. So here the name itself indicates it is a process of managing. Here disk means a storage devices. Okay, managing the storage device. So what are the storage device? We know. So the storage devices are the hard disk or flash drive or anything else. Okay, the memory. Okay, the memory, right? So managing the storage device. So what will be doing that in that memory? So it will also be responsible on allocating the space. That means efficient usage of space and file systems, etc. So whatever the things we can done on storage device, everything will be responsible by the disk management. Okay, so mainly this is managing the storage devices. So we have studied about the disk structure, right? So the disk structure, there will be cylindrical parts, we call them as a platters, and each platter will be having the centric circles, which we call them as a tracks, and every track is further divided into sectors, right? So the storage device and everything will be comes under with the disk management. Now we'll see the key features. What are the key features or key functions? These are main important key functions of disk management. So the first one is a partitioning. Many of you know about this partitioning, I think. So partitioning means dividing the complete hard disk into different sections, different parts. So if you are using any computer, so if you open this PC, you will be seeing the C drive, D drive, E drive, etc. So all these drives comes under the partitions. We can call them as a partitions. So partitioning means dividing storage into partitions, and each partition will be a different section. Okay, and the next one, formatting. So formatting means, so once a partition is divided, so we can't directly use that partition until it was formatted or it was kept ready with some file system. So the formatting means making partition to get ready with the file system. With the file system. Okay, so we have seen different kinds of file systems also, right? So whatever the concepts we have discussed in last 10 classes, everything comes under this disk management. Okay, then file system. The next one, the next function is a file system. So we have studied that. So every operating system will be having a different file systems. Okay, so here also there will be different file systems which will be managing the files in order to manage the files. So during partition itself, during formatting itself, the partition will be formatted with a particular file systems. So we have seen a different file systems like FAT32, okay, and NTFS and ext3, etc., etc. Different file system we have seen. So every partition will be get ready with a different file systems based upon the requirements. And the next one, free space management. So it will deal with available storage space. So available storage space. So based upon this available storage space, it will allocate or deallocate memory blocks to the files. So because we have studied that files will be stored in the memory blocks, so in order to store the files, we require some memory to be get allocated. So based upon the free space, the allocation will be done, and based upon the usage or a completion, the deallocation of memory blocks will be done. So everything will be comes under this free space management, which will be done under the disk management. Next, disk storage, or we can simply call it as a disk performance and optimization. Disk performance and optimization. So we have studied different key terms in disk scheduling algorithms, like access time, okay, next throughput, latency. So like that we have studied different key concepts. So always if you want to get the optimized disk performance, then it should have a less access time. So that means within a less time we need to get the file, right? So less access time as well as less latency also. So by using this one, if you achieve this less access time and less latency, automatically it will give the optimized disk performance. Next, hope you understood partitioning, formatting, file system, free space, and disk performance. Now the next one, disk scheduling. So this also we have studied in our previous session. So whenever we want to access the files from the disk, so based upon the access time, right? So based upon the different constraints, so the request will be processed. So we have studied a different algorithms in order to process the request on the disk. So like we have seen FCFS, first come first serve, SSTF, shortest seek time, and similarly scan, cscan, look, clook, circular look. So these are different kinds of scheduling algorithms we are using in order to process the request. And then disk caching. So it stores frequently accessed files. frequently accessed files, just similar to cache memory. Okay, just similar to cache memory. So it will store all the files which are being frequently accessed. So in order to get the fast access. The next one is a defragmentation. So obviously we know that in order to, allocation of a space or allocating the files to the memory, so we face a few problems like a fragmentation. One problem is a fragmentation. So internal fragmentation and external fragmentation. So collection of all fragments which are available to make a memory is called the defragmentation, right? So arranging all fragments, that means unused blocks of memory, okay, to make continuous blocks, right? So that is a defragmentation. So fragmentation and defragmentation will be done here. Next, error detection and recovery. So what happens in this error detection and recovery? So the name itself indicates here. So it will detect. So here error means the bad sectors. So we have studied that the data will be stored in a sectors, right? So it detects bad sectors. It detects in bad sectors, and also it recovers the data from the bad sectors. Okay, then space allocation. So here space allocation, the name itself indicates allocating the memory to the files. So we have seen three different styles of this space allocation methods, file allocation methods. We have studied that in another way, that is a file allocation method. So which is contiguous. We have studied all these things: contiguous, linked allocation, as well as indexed. So contiguous means the file will be stored in a contiguous memory blocks, and linked means so the end of one memory will be pointing towards the another block, and indexed means there will be one more block which will be having the pointer towards all the locations of that particular file. So in such way the space allocation will be done. And security and access control. So security means preventing from unauthorized access, preventing from unauthorized access. So data protection, we can say data protection by using different encryption mechanisms, by using encryption, so we can protect our data. So all these things come under the security and access. And similarly there is one more thing called mounting and unmounting. Mounting and unmounting. So here mounting means mounting and unmounting means making the disk available. So making the file or partition available. Okay. So unmounting means so disconnection. Okay. And unmounting means it is a disconnection in a smooth way. The example, so you can consider a pen drive. So if you insert that pen drive in a USB slot, automatically that we call it as a mounting will happens. Mounting. So it will be ready to use. That will be ready to use. And unmounting means you can safely remove that particular storage device. Okay, eject. You will be having one option called eject. So safely we can remove that pen drive or any flash drive, so without losing any data. So that is called as an unmounting. So mounting and unmounting. So making the partition or a file available to the user, and unmounting means disconnecting the partition safely without losing any kind of data. So these are all key functions. These are all different key functions of this disk management. And now we'll see the goals. What are the goals of disk management? One is efficient use of space. Efficient use of disk space. So allocation and deallocation of space to the files. Fast accessing of data. That is most important. Fast accessing of data from files. And we have seen the data recovery and protection. So protecting the data, right? So data reliability and protection. Data reliability and protection. Okay, and also it supports multi-user and multitasking systems. Multitasking systems. So these are all different goals of disk management. So simply we can say, so the storage and whatever the things we are doing on that storage, everything comes under this disk management. Okay, so in Windows you may find the option called disk management utility. Okay, there will be an option. So there you can find all the partitions which are available in your drive. So there you can compress or deallocate the memory, or you can allocate a new memory. Okay, you can expand the new allocation, or you can expand the partitions also, right? So once you check it that control panel, you go with the disk management, so you can find all the details of disk storage and everything, right? The file system and everything you'll be finding. So this is how these are the concept of disk management, the key functions as well as the goals of disk management. So let's stop here, and if you are having any queries regarding this one, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. And if you really enjoyed the session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.